Welcome to Quantum Mechanics. My name is Brent Carlson. Since this is the first lecture on quantum mechanics, we ought to have some sort of an introduction. And what I want to do to introduce quantum mechanics is to explain, first of all, why it's necessary, and second of all, to put it in historical context to, I'll show one of the most famous photographs in all of physics that really gives you a feel for the brain power that went into the construction of this theory. And hopefully we'll put it in some historical context as well, so you can understand where it fits in the broader philosophy of science. But the main goal of this lecture is about the need for quantum mechanics, which I really ought to just have called, Why Do We Need Quantum Mechanics? This subject has a reputation for being a little bit annoying, so why do we bother with it? Well, first off, for some historical context, imagine yourself back in 1900. Turn of the century, science has really advanced a lot. We have electricity, we have all this fabulous stuff that electricity can do, and even almost 100 years before that, physicists thought they had things figured out. There's a famous quote from Laplace: "Given for one instant an intelligence which could comprehend all the forces by which nature is animated, and the respective position of the beings which compose it, nothing would be uncertain, and the future, as the past, would be present to its eyes." Now, maybe you think intelligence which can comprehend all the forces of nature is a bit of a stretch. And maybe such a being which can know all the respective positions of everything in the universe is a bit of a stretch as well. But the feeling at the time was that if you could do that, you would know everything. If you had perfect knowledge of the present, you could predict the future. And of course you can infer what happened in the past. And everything is connected by one unbroken chain of causality. Now, in 1903, Albert Michelson, another famous quote from that time period, said, "The more important fundamental laws and facts of physical science have all been discovered. Our future discoveries must be looked for in the 6th place of decimals." Now, this sounds rather audacious. This is 1903, and he thought that the only thing that we had left to nail down was the part-in-a-million level precision. Well, to be fair to him, he wasn't talking about never discovering new fundamental laws of physics. He was talking about really astonishing discoveries like the discovery of Uranus on the basis of orbital perturbations of Neptune. Never having seen the planet Uranus before, they figured out that it had to exist just by looking at things that they had seen. That's pretty impressive. And Michelson was really onto something. Precision measurements are really, really useful, especially today. But back in 1903, it wasn't quite so simple, and Michelson probably regretted that remark for the rest of his life. The attitude that I want you guys to take when you approach quantum mechanics, though, is not this sort of 1900s notion that everything is predicted. It comes from Shakespeare. Horatio says, "Oh, day and night, but this is wondrous strange." To which Hamlet replies, one of the most famous lines in all of Shakespeare, "And therefore as a stranger give it welcome. There are more things in heaven and earth, Horatio, than are dreamt of in your philosophy." So that's the attitude I want you guys to take when you approach quantum mechanics. It is wondrous strange, and we should give it welcome. There are some things in quantum mechanics that are deeply non-intuitive, but if you approach them with an open mind, quantum mechanics is a fascinating subject, and there's a lot of really fun stuff that goes on. Now, to move on to the necessity for quantum mechanics, there were some dark clouds on the horizon, even at the early 20th century. Michelson wasn't quite having a big enough picture in his mind when he said that everything was down to the 6th place of decimals. The dark clouds on the horizon, at least according to Kelvin here, were a couple of unexplainable experiments. One, the black body spectrum. Now, a black body you can just think of as a hot object. And a hot object, like, for example, the coils on an electrical stove, when they get hot, will glow. And the question is, what color do they glow? Do they glow red? Do they glow blue? What is the distribution of radiation that is emitted by a hot object? Another difficult to explain experiment is the photoelectric effect. If you have some light, and it strikes a material, electrons will be ejected from the surface. And as we'll discuss in a minute, the properties of this experiment do not fit what we think we know about, or at least what physicists thought they knew about the physics of light and the physics of electrons at the turn of the 20th century. The final difficult experiment to explain is bright line spectra. For example, if I have a flame coming from, say, a Bunsen burner, and I put a chunk of something, perhaps sodium, in that flame, it will emit a very particular set of frequencies that looks absolutely nothing like a black body. We'll talk about all of these experiments in general, or in a little bit more detail in a minute or two, but just looking at these experiments now, these are all experiments that are very difficult to explain, knowing what we knew at the turn of the 20th century about classical physics. And they're also experiments that involve light and matter. So we're really getting down to the details of what stuff is really made of and how it interacts with the things around it. So these are some pretty fundamental notions, and that's where quantum mechanics really got its start. So let's pick apart these experiments in a little more detail. The black body spectrum, as I mentioned, you can think of as the light that's emitted just by a hot object. And while hot objects have some temperature associated with them, let's call that T. The plot here on the right is showing very qualitatively, I'll just call it the intensity of the light emitted as a function of the wavelength of that light. So short wavelengths, high energy, long wavelengths, low energy. Now if you look at T equals 3500 Kelvin curve here, it has a long tail to long wavelengths, and it cuts off pretty quickly as you go to short wavelengths, so it doesn't emit very much high energy light. Whereas if you have a much hotter object, 5500 Kelvin, it emits a lot more high energy light. The red curve here is much higher than the black curve. Now if you try to explain this, knowing what early 20th century physicists knew about radiation and about electrons and about atoms and how they could possibly emit light, you get a prediction. And it works wonderfully well up until about here, at which point it blows up to infinity. Infinities are bad in physics. This is the Rayleigh-Jeans law, and it works wonderfully well for long wavelengths, but does not work at all for short wavelengths. That's called the ultraviolet catastrophe, if you've heard that term. On the other end of things, if you look at what happens down here, well, it's not so much a prediction but an observation, but there's a nice formula that fits here. So on one side we have a prediction that works well on one end but doesn't work on the other. And on the other hand we have a sort of empirical formula called Wien's law that works really well at the short wavelengths, but, well, also blows up to infinity at the long wavelengths. Both of these blowing up things are a problem. The question is, how do you get something that explains both of them? This is the essence of the blackbody spectrum and how it was difficult to interpret in the context of classical physics. The next experiment I mentioned is the photoelectric effect. This is sort of the opposite problem. It's not how a material emits light, it's how light interacts with the material. So you have light coming in, and the experiment is usually done like this. You have your chunk of material, typically a metal, and when light hits it, electrons are ejected from the surface, hence the electric part of the photoelectric effect. And you do all this in a vacuum, and the electrons are then allowed to go across a gap to some other material, another chunk of metal, where they strike this metal. And the experiment is usually done like this. You connect it up to a battery. So you have your material on one side and your material on the other, and you have light hitting one of these materials and ejecting electrons. And you tune the voltage on this battery such that your electrons, when they're ejected, never quite make it. So the electric field produced by this voltage is opposing the motion of the electrons. When that voltage is just high enough to stop the motion of the electrons, keep them from completely making it all the way across, we'll call that the stopping voltage. Now, it turns out that what classical E&M predicts, as I mentioned, doesn't match what actually happens in reality. But let's think about what does classical E&M predict here. Well, classical electricity and magnetism says that electromagnetic waves here have electric fields and magnetic fields associated with them, and these are propagating waves. If I increase the intensity of the electromagnetic wave, that means the magnitude of the electric field involved in the electromagnetic wave is going to increase. And if I'm an electron sitting in that electric field, the energy I acquire is going to increase. That means V stop is going to increase, because I'll have to have more voltage to stop a higher energy electron, as would be produced by a higher intensity beam of light. The other parameter of this incoming light is its frequency. So we can think about varying the frequency. If I increase the frequency, I have more intense light. Now, that doesn't say anything about the string, if I increase the frequency, I don't necessarily have more intense light. The electric field magnitude is going to be the same, which means the energy and the stopping voltage will also be the same. Now, it turns out what actually happens in reality does not match this at all. In reality, when the intensity increases, the energy, which I should really write as V stop, the stopping voltage necessary, doesn't change. And when I increase the frequency, the voltage necessary to stop those electrons increases. So this is sort of exactly the opposite. What's going on here? That's the puzzle in explaining the photoelectric effect. Just to briefly check your understanding, consider these plots of stopping voltage as a function of the parameters of the incident light, and check off which you think shows the classical prediction for the photoelectric effect. The third experiment that I mentioned is bright line spectra. And as I mentioned, this is what happens if you take a flame or some other means of heating a material, like the bar of sodium I mentioned earlier. This will emit light, and in this case, the spectrum of light from red to blue of sodium looks like this. Oh, actually, I'm sorry, that's not sodium, that's mercury. These are four different elements: hydrogen, mercury, neon, and xenon. And instead of getting a broad, continuous distribution, like you would from a black body, under these circumstances where you're talking about gases, you get these very bright regions. It's the spectrum, instead of looking like a smooth curve like this, looks like spikes. Those bright lines are extraordinarily difficult to explain with classical physics, and this is really the straw that broke the camel's back, broke classical physics' back, that really kicked off quantum mechanics. How do you explain this? This is that famous photograph that I mentioned. This is really the group of people who first built quantum mechanics. Now, I mentioned three key experiments. The black body spectrum. This guy figured that out. This is Planck. The photoelectric effect. This guy, who I hope needs no introduction, this is Einstein, figured that out. This is the paper that won Einstein the Nobel Prize. And as far as the bright line spectra of atoms, it took a much longer time to figure out how all of that fit together. And it took a much larger group of people. But they all happen to be present in this photograph. There's this guy, and this guy, and these two guys, and this guy. This photograph is famous because these guys worked out quantum mechanics. But that's not the only, these aren't the only famous people in this photograph. You know this lady as well. This is Marie Curie. This is Lorentz, which if you studied special relativity, you know Einstein used the Lorentz transformations. Pretty much everyone in this photograph is a name that you know. I went through and looked up who these people were, these were all of the names that I recognized, which doesn't mean that the people whose names I didn't recognize weren't also excellent scientists. For example, C.T.R. Wilson here, one of my personal favorites, inventor of the cloud chamber. This is the brain trust that gave birth to quantum mechanics, and it was quite a brain trust. You had some of the most brilliant minds of the century working on some of the most difficult problems of the century. And what's astonishing is they didn't really like what they found. They discovered explanations that made astonishingly accurate predictions, but throughout the history you keep seeing them disagreeing, like, no, that can't possibly be right. Not necessarily because the predictions were wrong or they thought there was a mistake somewhere, but because they just disliked the nature of what they were doing. They were upending their view of reality. Einstein, in particular, really disliked quantum mechanics to the day that he died, just because it was so counterintuitive. And so with that introduction to a counterintuitive subject, I'd like to remind you again of that Shakespeare quote, "There are more things in heaven and earth, Horatio, than are dreamt of in your philosophy." Try to keep an open mind, and hopefully we'll have some fun at this. Knowing that quantum mechanics has something to do with explaining the interactions of light and matter, for instance in the context of the photoelectric effect, or blackbody radiation, or bright line spectra of atoms and molecules, one might be led to the question of when is quantum mechanics actually relevant? The domain of quantum mechanics is unfortunately not a particularly simple question. When does it apply? Well, on the one hand, you have classical physics, and on the other hand, you have quantum physics. And the boundary between them is not really all that clear. On the classical side, you have things that are certain, whereas on the quantum side, you have things that are uncertain. What that means in the context of physics is that on the classical side, things are predictable. They may be chaotic and difficult to predict, but in principle they can be predicted. Well, on the quantum side, things are predictable too, but with a caveat. In the classical side, you determine everything. Basically, every property of the system can be known with perfect precision, whereas in quantum mechanics what you predict are probabilities. And learning to work with probabilities is going to be the first step to getting comfortable with quantum mechanics. The boundary between these two realms, when the uncertain and probabilistic effects of quantum mechanics start to become relevant, is really a dividing line between things that are large and things that are small. And that's not a particularly precise way of stating things. Doing things more mathematically, quantum mechanics applies, for instance, when angular momentum L is on the scale of Planck's constant, or the reduced Planck's constant, h bar. Now, h bar is the fundamental scale of quantum mechanics, and it appears not only in the context of angular momentum. Planck's constant has units of angular momentum, so if your angular momentum is of order Planck's constant or smaller, you're in the domain of quantum mechanics. We'll learn more about uncertainty principles later as well, but uncertainties in this context have to do with products of uncertainties. For instance, the uncertainty in the momentum of a particle times the uncertainty in the position of the particle. This, if it's comparable to Planck's constant, is also going to give you the realm of quantum mechanics. Energy and time also have an uncertainty relation, again, approximately equal to Planck's constant. Most fundamentally, the classical action, when you get into more advanced studies of classical mechanics, you'll learn about a quantity called the action, which has to do with the path a system takes as it evolves in space and time. If the action of the system is of order Planck's constant, then you're in the quantum mechanical domain. Now, Planck's constant is a really small number. It's 1.05 times 10 to the negative 34 kilogram meters squared per second. times 10 to the negative 34 is a small number. So if we have really small numbers, then we're in the domain of quantum mechanics. In practice, these guys are the most useful, whereas this is the most fundamental. But we're more interested in useful things than we are in fundamental things, after all. For example, the electron in the hydrogen atom. Now, you know from looking at the bright line spectra that this should be in the domain of quantum mechanics. But how can we tell? Well, to use one of the uncertainty principles as a calculation, consider the energy. The energy of an electron in a hydrogen atom is, let's say about 10 electron volts. If we say that's p squared over 2m, using the classical kinetic energy relation between momentum and kinetic energy, that tells us that the momentum, p, is going to be about 1.7 times 10 to the minus 24th kilogram meter kilogram, where'd it go? Where's my eraser? Kilogram meters per second. Now, this suggests that the momentum of the electron is, non-zero. But if the hydrogen atom itself is not moving, we know the average momentum of the electron is 0. So if the momentum of the electron is going to be 0 with still some momentum being given to the electron, this is more the uncertainty in the electron momentum than the electron momentum itself. The next quantity, if we're looking at the uncertainty relation between momentum and position, is we need to know the size of, or the uncertainty in the position of the electron, which has to do with the size of the atom. Now, the size of the atom, that's about 0.1 nanometers, which, if you don't remember the conversion from nanometers, is 10 to the minus 10th meters. So let's treat this as delta x, our uncertainty in position, because we don't really know where the electron is within the atom, so this is a reasonable guess at the uncertainty. Now, if we calculate these two things together, delta p, delta x, you get something, and I should say this is approximate because this is very approximate, 1.7 times 10 to the negative 34th, and if you plug through the units, it's kilogram meter squared per second. This is about equal to h bar. So this tells us that quantum mechanics is definitely important here. We have to do some quantum in order to understand this system. As an example of another small object that might have quantum mechanics relevant to it, this is one that we would actually have to do a calculation. I don't know intuitively whether a speck of dust in a light breeze is in the realm of quantum mechanics or classical physics. Now, I went online and looked up some numbers. For a speck of dust, let's say the mass is about 10 to the minus 6th kilograms, a microgram. It has a velocity in this light breeze of, let's say, 1 meter per second. And let me make myself some more space here. The size of this speck of dust is going to be about 10 to the minus 5 meters. So these are the basic parameters of this speck of dust in a light breeze. Now we can do some calculations with this. For instance, momentum. Well, in order to understand quantum mechanics, there's some basic vocabulary that I need to go over. So let's talk about the key concepts in quantum mechanics. Thankfully, there are only a few. There's really only 3, and the first is the wave function. The wave function is, and always has been, written as psi, the Greek letter. My handwriting gets a little lazy sometimes, and it'll end up just looking like this, but technically, it's supposed to look something like that. Details are important, provided you recognize the symbol. Psi is a function of position, potentially in 3 dimensions, x, y, and z, and time. And the key facts here is that psi is a complex function, which means that while x, y, z, and t here are real numbers, psi, evaluated at a particular point in space, will potentially be a complex number with both a real and imaginary part. What is subtle about the wave function, and we'll talk about this in great detail later, is that while it represents the state of the system, it doesn't tell you with any certainty what the observable properties of the system are. It really only gives you probabilities. So for instance, if I have a coordinate system, something like this, where say this is position in the x direction, psi, with both real and imaginary parts, might look something like this. This could be the real part of psi, and this could be, say, the complex or the imaginary part of psi. What is physically meaningful is the squared magnitude of psi, which might look something like this in this particular case. And that is related to the probability of finding the particle at a particular point in space. As I said, we'll talk about this later, but the key facts that you need to know about the wave function is that it's complex and it describes the state of the system, but not with certainty. The next key concept in quantum mechanics is that of an operator. Now, operators are what connect psi to observable quantities. That is one thing operators can do. Just a bit of notation, usually we use hats for operators. For instance, x hat or p hat are operators that you'll encounter shortly. Operators act on psi. So if you want to apply, for instance, the x hat operator to psi, you would write x hat psi. As if this were something that as it appears on the left of psi, the assumption is that x acts on psi. If I write psi x hat, doesn't necessarily mean that x hat acts on psi. You assume operators act on whatever lies to the right. Likewise, of course, p hat psi. Now, we'll talk about this in more detail later, but x hat, the operator, can be thought of as just multiplying by x. So if I have psi as a function of x, x hat psi is just going to be x times psi of x. So if psi was a polynomial, you could multiply x by that polynomial. The p operator, p hat, is another example, is a little bit more complicated. This is just an example now, and technically this is the momentum operator, but we'll talk more about that later. It's equal to minus h bar times the derivative with respect to x. So this is again something that needs a function, needs the wave function to actually give you anything meaningful. Now the important thing to note about the operators is that they don't give you the observable quantities either. But in quantum mechanics, you can't really say the momentum of the wave function. For instance, p hat psi is not, and I'll put this in quotes because you won't hear this phrase very often, the momentum of psi. It's the momentum operator acting on psi, and that's not the same thing as the momentum of psi. The final key concept in quantum mechanics is the Schrodinger equation. And this is really the big equation. So I'll write it big. I, h bar, partial derivative of psi with respect to time is equal to h hat, that's an operator, acting on psi. Now h hat here is the Hamiltonian, which you can think of as the energy operator. So the property of the physical system that H is associated with is the energy of the system. And the energy of the system can be thought of as a kinetic energy. So we can write a kinetic energy operator plus a potential energy operator together acting on psi. And it turns out the kinetic energy operator can be written down. This is going to end up looking like minus h bar squared over 2m partial derivative of psi with respect to, second partial derivative of psi with respect to position, plus, and then the potential energy operator is going to look like the potential energy as a function of position, just multiplied by psi. So this is the Schrodinger equation. Typically, you'll be working with it in this form. So I h bar times the partial derivative with respect to time is related to the partial derivative with respect to space, and then multiplied by some function. The basic quantum mechanics that we're going to learn in this course mostly revolves around solving this function and interpreting the results. So to put these in a bit of a roadmap, we have operators. We have the Schrodinger equation. And we have the wave function. Now operators act on the wave function, and operators are used in the Schrodinger equation. Now the wave function that actually describes the state of the system is going to be the solution to the Schrodinger equation. Now I mentioned operators acting on the wave function. What they give you when they act on the wave function is some property of the system, some observable perhaps. And the other key fact that I mentioned so far is that the wave function doesn't describe the system perfectly, it only gives you probabilities. So that's our overall concept map. To put this in the context of the course outline, the probabilities are really the key feature of quantum mechanics, and we're going to start this course with a discussion of probabilities. We'll talk about the wave function after that and how the wave function is related to those probabilities, and we'll end up talking about operators and how those operators and the wave functions together give you probabilities associated with observable quantities. That will lead us into a discussion of the Schrodinger equation, which will be most of the course, really. The bulk of the material before the first exam will be concerned with various examples. Solution to the Schrodinger equation under various circumstances. This is really the main meat of quantum mechanics in the beginning. After that, we'll do some formalism. And what that means is we'll learn about some advanced mathematical tools that make keeping track of all the details of how all of this fits together a lot more straightforward. And then we'll finish up the course by doing some applications. So those are our key concepts and a general roadmap through the course. Hopefully now you have the basic vocabulary necessary to understand phrases like the momentum operator acts on the wave function, or the solution to the Schrodinger equation describes the state of the system, and that sort of thing. Don't worry too much if these concepts haven't quite clicked. In order to really understand quantum mechanics, you have to get experience with them. These are not things that you really have any intuition for based on anything you've seen in physics so far. So bear with me, and this will all make sense in the end, I promise. Complex numbers, or numbers involving, conceptually you can think about it as the square root of -1, I, are essential to understanding quantum mechanics, since some of the most fundamental concepts in quantum mechanics, for instance the wave function, are expressed in terms of complex numbers. Complex analysis is also one of the most beautiful subjects in all of mathematics, but unfortunately in this course I don't have the time to go into the details. Lucky you, perhaps. Here's what I think you absolutely need to know to understand quantum mechanics from the perspective of complex analysis. First of all, there's the basic definition. I squared is equal to -1, which you can think of also as I equals the square root of -1. In general, a complex number, z, then, can be written as the sum of a purely real part, x, and a purely imaginary part, I times y. Note in this expression, z is complex, x and y are real, where I times y is purely imaginary. The terms purely real or purely imaginary in the context of this expression like this, x plus iy, something is purely real if y is 0, something is purely imaginary if x is 0. As far as some notation for extracting the real and imaginary parts, typically mathematicians will use this funny calligraphic font to indicate the real part of x plus iy or the imaginary part of x plus iy, and that just pulls out x and y. Note that both of these are real numbers. When you pull out the imaginary part, you get x and y. You don't get iy, for instance. Another one of the most beautiful results in mathematics is e to the I pi plus 1 equals 0. This formula kind of astonished me when I first encountered it, but it is a logical extension of this more general formula that e raised to a purely imaginary power iy is equal to the cosine of y plus I times the sine of y. This can be shown in a variety of ways, in particular involving the Taylor series. If you know the Taylor series for the exponential, the Taylor series for cosine of y, and the Taylor series for sine of y, you can show quite readily that the Taylor series for complex exponential is the Taylor series of cosine plus the Taylor series of sine. And while that might not necessarily constitute a rigorous proof, it's really quite fun if you get the chance to go through it. At any rate, the trigonometric functions here, cosine and sine, should be suggestive, and there is a geometric interpretation of complex numbers that we'll come back to in a minute. But for now, know that while we have rectangular forms like this, x plus iy, where x and y, the nomenclature there is chosen on purpose, you can also express this in terms of r e to the I theta, where you have now a radius and an angle. The angle here, by the way, is going to be the arctangent of y over x. And we'll see why that is in a moment when we talk about the geometric interpretation. But given these rectangular and polar forms of complex numbers, what do the basic operations look like? How do we manipulate these things? Well, addition and subtraction in rectangular form is straightforward. If we have two complex numbers, a plus ib plus, and we want to add to that a second complex number, c plus id, we just add the real parts, a and c, and we add the imaginary parts, b and d. This is just like adding in any other sort of algebraic expression. Multiplication is a little bit more complicated. You have to distribute, and you distribute in the usual sort of draw a smiley face kind of way. A times c and b times d are going to end up together in the real part. And the reason for that is, well, a times c, a and c both being real numbers, a times c will be real. Whereas ib times id, both being purely complex numbers, you'll end up with b times d times I squared, and I squared is minus 1. So you just end up with minus bd, which is what we see here. Otherwise, the complex part is perhaps a little more easy to understand. You have I times b times c, and you have a times I times d, both of which end up with plus signs in the complex part. Division, in this case, is like rationalizing the denominator, except instead of involving radicals, you have complex numbers. If I have some number a plus ib divided by c plus id, I can simplify this by both multiplying and dividing by c minus id. Note the sign change in the denominator here. C plus id is then prompting me to multiply by c minus id over c minus id. Now, when you do the distribution there, for instance, let's just do it in the denominator, c plus id times c minus id, my top eyebrows here of the smiley face, c squared times id, or c squared plus, now, id times minus id, which is, well, I'll just write it out, I times minus id, which is going to be d squared times I times minus I. So I squared times minus 1, and I squared is minus 1. So I have minus 1 times minus 1, which is just 1, so I can ignore that. I've just got d squared. So what I end up with in the denominator is just c squared plus d squared. What I end up with in the numerator, well, that's the same sort of multiplication thing that we just discussed. So the simplified form of this has no complex part in the denominator, which helps keep things a little simple and a little easier to interpret. Now in polar form, addition and subtraction, well, they're complicated. Under most circumstances, if you have two complex numbers given in polar form, it's easiest just to convert to rectangular form and add them together there. Multiplication and division, though, in polar form have very nice expressions. Q e to the I theta times R e to the I phi. Well, these are just all real numbers multiplying together, and then I can use the rules regarding multiplication of exponentials, meaning if I have two things like e to the I theta and e to the I phi, I can just add the exponents together. It's like taking x squared times x to the fourth and getting x to the sixth. But QR e to the I theta plus phi. So that was easy. We didn't have to do any distribution at all. The key fact here is that you add the angles together. In the case of division, it's also quite easy. You simply divide the radii, q over r, and instead of adding, you subtract the angles. So polar complex numbers expressed in polar form are much easier to manipulate in multiplication and division, while complex numbers represented in rectangular form are much easier to manipulate for addition and subtraction. Taking the magnitude of a complex number, usually we'll write that as something like z, if z is a complex number, just using the same notation for absolute value of a real number. Usually is expressed in terms of the complex conjugate. Now, the complex conjugate, notationally speaking, is usually written by whatever complex number you have, here in this case x plus iy, with a star after it. And what that signifies is you flip the sign on the complex part, on the imaginary part. X plus iy becomes x minus iy. The squared magnitude then, which is always going to be a real and positive number, this absolute value squared notation, is what you get for multiplying a number by its complex conjugate. And that's what we saw earlier with c plus id. Say I take the complex conjugate of c plus id and multiply it by c plus id. Well, the complex conjugate of c plus id is c minus id times c plus id. And doing the distribution, like we did when we calculated the denominator, when we were simplifying the division of complex numbers in rectangular form, just gave us c squared plus d squared. This should be suggestive if you have something like x plus iy, that's really messy, x plus iy, and I want to know the squared absolute magnitude. Thinking about this as a position in Cartesian space should make this formula, c squared plus d squared in this case, just make a little more sense. You can also, of course, write that in terms of real and imaginary parts. But let's do an example. If w is 3 plus 4i, and z is minus 1 plus 2i, first of all, let's find w plus z. Well, w plus z is 3 plus 4i plus minus 1 plus 2i. That's straightforward. If you can keep track of your terms, 3 minus 1 is going to be our real part, so that's 2. And 4i plus 2i, which is plus 6i, is going to be our complex part. Sorry, our imaginary part. Now, w times z, 3 plus 4i times minus 1 plus 2i. For this, we have to distribute, like usual. So from our top eyebrow terms here, we've got 3 times minus 1, which is minus 3, and 4i times 2i, both positive. So I have 4 times 2, which is 8, and I times I, which is minus 1, minus 8. Then, for my imaginary part, I guess the mouth and the chin, if you want to think about it that way, I have 4i times minus 1, minus 4 with the I out front, will just be minus 4 inside the parentheses here. And 3 times 2i is going to give me 6i plus 6 inside. The end result you get here is 8, or minus 8 minus 3 is minus 11, and minus 4 plus 6 is going to be 2. So I get minus 11 plus 2i for my multiplication here. I guess if I'm going to circle that answer, I should circle this answer as well. Now, slightly more complicatedly, w over z. W is 3 plus 4i, and z is minus 1 plus 2i. And you know when you want to simplify an expression like this, you multiply by the complex conjugate of the denominator divided by the complex conjugate of the denominator. So minus 1 minus 2i divided by minus 1 minus 2i. And if we continue the same sort of distribution, we'll do the numerator first. Same sort of multiplication we just did here, only the signs will be flipped a little bit. We'll end up with minus 3 plus 8 instead of minus 3 minus 8. And for the imaginary part, we'll end up with minus 4 minus 6 instead of minus 4 plus 6. And you can work out the details of that distribution on your own if you want. The denominator is not terribly complicated. Since we know we're taking the absolute magnitude of a complex number by multiplying a complex number by its complex conjugate, we can just write this out as the square of the real part, 1, plus the square of the imaginary part, minus 2, which squared is 4. So if I continue this final step, this is going to be 5. This is going to be minus 10i, and our denominator here is just going to be 5. So in the end, what I'll end up with is going to be 1 minus 2i. So it actually ended up being pretty simple in this case. Now for the absolute magnitude of w, 3 plus 4i, you can think of this as w times w star square root. You can think of this as the square root of the real part of w plus the imaginary part of w. Sorry, square root of the squared of the real part plus the square of the imaginary part, which is perhaps a little easier to work with in this case, so you don't have to distribute out complex numbers in that way. Real part is 3, imaginary part is 4, so we end up with the square root of 3 squared plus 4 squared, which is 5. Now this was all in rectangular form. Let me move this stuff out of the way a little bit. And let's do it again, at least a subset of it, in polar form. In polar form, w, 3 plus 4i, we know the magnitude of w, that's 5. So that's going to be our radius, 5. And our e to the I theta, where theta is, like I said, the arctan. Since complex numbers are so important to quantum mechanics, let's do a few more examples. In this case, I'm going to demonstrate how to manipulate complex numbers in a more general way, not so much just doing examples with numbers. First example, simplify this expression. You have two complex numbers multiplied in the numerator, and then a division. First of all, the first thing to simplify is this multiplication. You have x plus iy times ic. This is pretty easy. It's a simple sort of distribution. We're going to have x times ic, that's going to be a complex part. So I'm going to write that down a little bit to the right, ixc. And then we're going to have iy times ic, which is going to be minus yc. That's going to be real. We also have a real part in the numerator from the d here, so I'm going to write this as d minus yc plus ic. That's the result of multiplying this out. That's then going to be divided by f plus ig. Now, in order to simplify this, we have a complex number in the denominator. You know you need to multiply by the complex conjugate and divide by the complex conjugate. So f minus ig divided by f minus ig. Now, expanding this out is a little bit messier, but fundamentally you've seen this sort of thing before. You have real part, and imaginary part in the numerator, and then you're going to have imaginary part, and real part, imaginary part. And what you're going to end up with from this first term, you get f times d minus yc. From the second term, you have minus ig times ixc, which is going to give you xcg. We have a minus I times an I, which is going to give us a plus. Incidentally, if you're having trouble figuring out something like minus I times I, think about it in the geometric interpretation. This is I in the complex plane. This is minus I in the complex plane. So I have one angle going up, one angle going down. If I'm multiplying them together, I'm adding the angles together. So I essentially go up and back down, and I just end up with 1 equals I times minus I. Otherwise, you can keep track of I squareds equals minus 1s and just count up your minus signs. This, then, is the real part. Suppose I should write that in green, lest my fonts get too confusing. Excuse me. So that's the real part. The imaginary part, then, is what you get from these terms here. I'm going to write an I out front, and now we have xc times f, so xcf with an I from here. And then we have d minus yc times ig, which I'll just write as g d minus yc. In the denominator, we're now multiplying a number by its complex conjugate. You know what to do there. F squared plus g squared. This is just the magnitude of this complex number. Sorry, squared magnitude. Now, this doesn't necessarily look more simple than what we started with, but this is effectively fully simplified. You could further distribute this and distribute this, but it's not really going to help you very much. The thing to notice about this is that the denominator is purely real. We've also separated out the real part of the numerator and the imaginary part of the numerator. Yeesh. My handwriting is getting messier as I go. Imaginary part of the numerator. So we can look at this numerator now and say, this is the complex number, real part, imaginary part, and then it's just divided by this real number, which effectively is just a scaling. It's a relatively simple thing to do, to divide by a real number. As a second example, consider solving this equation for x. Now this is the same expression that we had in the last problem, only now we're solving it for it equal to 0. So from the last page, I'm going to borrow that first simplification step we did, distributing this through. We had d minus yc for the real part, plus ixc for the imaginary part, and that was divided by f plus ig. If we're setting this equal to 0, the nice part about dealing with complex expressions like this is that 0, treated as a complex number, is 0 plus 0i. It has a real part and an imaginary part as well. It's just kind of trivial. And in order for this complex number to be equal to 0, the real part must be 0 and the imaginary part must be 0. So we can think of this as d minus yc plus ixc. This has to equal 0 and this has to equal 0 separately. So we effectively have two equations here, not just one, which is nice. We have d minus yc equals 0 and xc equals 0, which, unless c equals 0, just means x equals 0. That's the only way that this equation can hold, is if x equals 0. The key fact here is to keep in mind that in order for two complex numbers to be equal, both the real parts and the imaginary parts have to be equal. As a slightly more involved example, consider finding the cubed roots of 1. Now, you know 1 cubed is 1. That's a good place to start. We'll see that fall out of the algebra pretty quickly. What we're trying to do is solve the equation z cubed equals 1, which you can think of as x plus I y, where x and y are real numbers, cubed, equals 1. Now if we expand out this cubic, you get x cubed plus 3x squared times iy plus 3x times iy squared plus iy cubed. And this is going to have to equal 1. Excuse me. Equal 1. Now, looking at these expressions, here we have an iy, here we have an iy squared. This is going to give me an I squared, which is going to be a minus sign. And here I have an iy cubed. This is going to give me an I cubed, which is going to be minus I. So I have two complex parts and two real parts. So I'm going to rewrite that. X cubed, and then now a minus sign from the I squared, 3xy squared, plus, pulling an I out front, the imaginary part then is going to come from this 3x squared y and this y cubed. So I've got a 3x squared y here, and then a minus y cubed, minus coming from the I squared. And this is also going to have to equal 1. Now, in order for this complex number to equal this complex number, both the real parts and the imaginary parts have to be equal. So let's write those two separate equations. X cubed minus 3xy squared equals the real part of, this is the real part of the left-hand side, has to equal the real part of the right-hand side, 1. And the imaginary part of the left-hand side, 3x squared y minus y cubed, has to equal the imaginary part of the right-hand side, 0. So those are our two equations. This one in particular is pretty easy to work with. We can simplify this. This is, we can factor a y out. This is y times 3x squared minus y squared equals 0. One possible solution then is going to come from this. You have a product like this is equal to 0. Either this is equal to 0 or this is equal to 0. And saying y equals to 0 is rather straightforward. So let's say y equals 0. And let's substitute that into this expression. That's going to give us x cubed equals 1, which might look a lot like the equation we started with, z cubed equals 1, but it's subtly different because z is a general complex number, whereas our assumption in starting the problem this way is that x is a purely real number. So a purely real number, which when cubed gives you 1, that means x equals 1. So x equals 1, y equals 0, that's one of our solutions. Z equals 1 plus 0i, or just z equals 1. Now, we could have told me that right off the bat, z cubed equals 1. Well, one possible solution is that z equals 1, since 1 cubed is 1. The other thing we can do here is we can say 3x squared minus y squared is equal to 0. This means that, I'll just cheat a little bit and simplify this, 3x squared equals y squared. Now I can substitute this y squared, into this expression as well. And what you end up with is x cubed minus 3x, and then y squared was equal to 3x squared. So 3x squared is going to go in there. That has to equal 1. Now let's move up here. What does that leave us with? That says x cubed minus 9x cubed equals 1. So minus 8x cubed equals 1. This means x, again, being a purely real number, is equal to minus 1/2. Minus 1/2 times minus 1/2 times minus 1/2 times 8 times minus 1 is equal to 1. You can check that pretty easily. Now, where does that leave us? Where did I go? That leaves us substituting this back into this expression, which tells us that 3x squared equals y squared. X equals minus 1/2, so 3 minus 1/2 squared equals y squared, which tells you that y equals plus or minus the square root of 3/4 if you finish your solution. So now we have two solutions for y here coming from one value for x, and that gives us our other two solutions to this cubic. We have a cubic equation. We would expect there to be three solutions, especially when we're working with complex numbers like this. And this is our other solution. Z equals minus 1/2 plus or minus the square root of 3/4 I. So those are our three solutions. Now, finding the cubed roots of 1 to be these complex numbers is not necessarily particularly instructive. However, there's a nice geometric interpretation. The cubed roots of unity like this, the nth roots of unity, doesn't have to be a cubed root. All lie on a circle of radius 1 in the complex plane. And if you check the complex magnitude of this number and the complex magnitude of this number, you will find that it is indeed unity. To check your understanding of this, a slightly simpler problem is to find the square roots of I. Put another way, you've got z, some generic complex number here, equals to x squared x plus iy. Quantity squared, if that's going to equal y, we'll expand this out, solve for x and y in the two equations that will result from setting real and imaginary parts equal to each other. And same as with the cubed roots of 1, the square roots of I will also fall on a circle of radius 1 in the complex plane. So those are a few examples of how complex numbers can actually be manipulated. In particular, finding the roots of unity, there are better formulas for that than the approach that we took here, but I feel this was hopefully instructive.
If probability is at the heart of quantum mechanics, what does that actually mean? Well, the fundamental source of probability in quantum mechanics is the wave function psi. Psi tells you everything that you can in principle know about the state of the system, but it doesn't tell you everything with perfect precision. How that actually gives rise to probability distributions in observable quantities like position or energy or momentum is something that we'll talk more about later, but from the most basic perspective, psi can be thought of as related to a probability distribution. But let's take a step back and talk about probabilistic measurements in general first. If I have some space, let's say it's position space. Say this is the floor of a lab, and I have a ball that is somewhere on the floor. I can measure the position of that ball. Maybe I measure the ball to be there on the floor. If I prepare the experiment in exactly the same way, attempting to put the ball in the same position on the floor and measure the position of the ball again, I won't always get the same answer because of perhaps some imprecision in my measurements or some imprecision in how I'm reproducing the system. So I might make a second measurement there, or a third measurement there. If I repeat this experiment many times, I'll get a variety of measurements at a variety of locations. And maybe they cluster in certain regions, or maybe they're very unlikely in other regions. But this distribution of measurements, we can describe that mathematically with a probability distribution. A probability distribution, for instance, I could plot P of x here, and P of x tells you roughly how many, or how likely you are to make a measurement. So I would expect P of x as a function to be larger here, where there's a lot of measurements, and 0 here where there's no measurements, and relatively small here where there's few measurements. So P of x might look something like this. So the height of P of x here tells us how likely we are to make a measurement in a given location. This concept of a probability distribution is intimately related to the wave function. So the most simple way that you can think of probability in quantum mechanics is to think of the wave function psi of x. Now psi of x, you know, is a complex function, and a complex number can never really be observable. What would it mean, for example, to measure a position of, say, 2 plus 3i meters? This isn't something that's going to occur in the physical universe. But the fundamental interpretation of quantum mechanics that this book in particular, that most physicists think of is the interpretation that psi, in the context of a probability distribution, the absolute magnitude of psi squared is related to the probability of finding the particle described by psi. So if the squared magnitude of psi is large at a particular location, that means it is likely that the particle will be found at that location. Now the squared magnitude here means that we have to take the squared magnitude of psi. We can't just take psi itself. So for instance, in the context of the plot that I just made on the last page, if this is x and our y-axis here is psi, psi has real and imaginary parts. So the real part of psi might look something like this, and the imaginary part might look something like this. And the squared magnitude would look something like, well, what you can imagine the squared magnitude of that function looking like. And you can think of the squared magnitude of psi as the probability distribution. Let me move this up a little bit, give myself some more space. The squared magnitude of psi then can be thought of as a probability distribution in the likelihood of finding the particle at a particular location, like I said. Now, what does that mean mathematically? Mathematically, suppose you had two positions, A and B, and you wanted to know what the probability of finding the particle between A and B was. Given a probability distribution, you can find that by integrating the probability distribution. So the probability that the particle is between A and B is given by the integral from A to B of the squared absolute magnitude of psi dx. You can think of this as a definition. You can think of this as an interpretation. But fundamentally, this is what the physical meaning of the wave function is. It is related to the probability distribution of position associated with this particular state of the system. Now, what does that actually mean? And that's a bit of a complicated question. It's very difficult to answer. Suppose I have a wave function, which I'm just going to write as plot as the squared magnitude of psi now. Suppose it looks something like this. Now that means I'm perhaps likely to measure the position of the particle somewhere in the middle here. So suppose, wrong color. So suppose I do that. Suppose I measure the position of the particle here. So I've made a measurement now. Messy handwriting. I've made a measurement, and I've observed the particle to be here. What does that mean in the context of the wave function? Now, everything that I can possibly know about the particle has to be encapsulated in the wave function, so after the measurement, when I know the particle is here, you can think of the wave function as looking something like this. It's not going to be infinitely narrow because there might be some uncertainty. The width of this is related to the precision of the measurement. But the wave function before the measurement was broad, like this, and the wave function after the measurement is narrow. What actually happened here? What about the measurement caused this to happen? This is one of the deep issues in quantum mechanics that is quite difficult to interpret. So what do we make of this? Well, one thing that you could think, just intuitively, is that, well, this probability distribution wasn't really all the information that was there. Really, the particle was there. Let's say this is point C. One interpretation is that the particle really was at C all along. That means that this distribution reflects ignorance on our part as physicists, not fundamental uncertainty in the physical system. This turns out to not be true, and you can show mathematically and in experiments that this is not the case. The main interpretation that physicists use is to say that this wave function psi here, also shown here, collapses. Now that's a strange term. Collapses. But it's hard to think of it any other way. Suppose you were concerned with the wave function's value here. Before the measurement, it's non-zero, whereas after the measurement, it's 0. So this decrease in the wave function out here is reasonable to call that a collapse. What that wave function collapse means is subject to some debate, and there are other interpretations. One interpretation that I'll mention very briefly, but we won't really discuss very much, is the many worlds interpretation, and that's that when you make a measurement like this, the universe splits. So it's not that the wave function all of a sudden decreases here, it's that for us, in our tiny little chunk of the universe, the wave function is now this, and there's another universe somewhere else where the wave function is this, because the particle was observed to be here. Don't worry too much about that, but the interpretation issues in quantum mechanics are really fascinating once you start to get into them. You can think about this as the universe splitting into, splits. The universe, you can think about this as the universe splitting into many little sub-universes where the probability of where the particle is observed at a variety of locations. One location per universe, really. This question of how measurements take place is really fundamental, but hopefully this explains a little bit of where probability comes from in quantum mechanics. The wave function itself can be thought of as a probability distribution for position measurements. And unfortunately, the measurement process is not something that's particularly easy to understand, but that's the fundamental origin of probability in quantum mechanics. To check your understanding, here is a simple question about probability distributions and how to interpret them. Variance and standard deviation are properties of a probability distribution that are related to the uncertainty. Since uncertainty is such an important concept in quantum mechanics, we need to know how to quantify how uncertainty results from probability distributions. So let's talk about the variance and the standard deviation. These questions are related to the shape of a probability distribution. So if I have a set of coordinates, let's say this is the x-axis, and I'm going to be plotting then the probability density function as a function of x. Probability distributions come in lots of shapes and sizes. You can have probability distributions that look like this, probability distributions that look like this. You can even have probability distributions that look like this, or probability distributions that look like this. And these are all different. The narrow peak here versus the broad distribution here. The distribution with multiple peaks, or multiple modes. In this case it has 2 modes, so we call this distribution bimodal, or multimodal. And then this distribution, which is asymmetric, has a long tail in the positive direction and a short tail in the negative direction. We would say this distribution is skewed. So distributions have lots of different shapes, and if what we're interested in is the uncertainty, you can think about that roughly as the width of the distribution. For instance, if I'm drawing random numbers from the orange distribution, the narrow one here, they'll come over roughly this range. Whereas if I'm drawing from the blue distribution, they'll come over roughly this range. So if this were, say, the probability density for position, say this is the squared magnitude of the wave function for a particle, I know where the particle represented by the orange distribution is much more accurately than the particle represented by the blue distribution. So this concept of width of a distribution and the uncertainty in the position, for instance, are closely related. The broadness is related to the uncertainty. This is fundamental to quantum mechanics, so how do we quantify it? In statistics, the broadness of a distribution is
called the variance. The variance is a way of measuring the broadness of a distribution, for example. So suppose this is my distribution. The mean of my distribution is going to fall roughly in the middle here. Let's say that's the expected value of x, if this is the x-axis. Now, if I draw a random number from this distribution, I won't always get the expected value. Suppose I get a value here. If I'm interested in the typical deviation of this value from the mean, that will tell me something about how broad this distribution is. So let's define this displacement here to be delta x. Delta x is going to be equal to x minus the expected value of x. And first of all, you might think, well, if I'm looking for the typical values of delta x, let's just try the expected value of delta x. Well, what is that? Unfortunately, the expected value of x doesn't really work for this purpose because delta x is positive if you're on this side of the mean and negative if you're on this side of the mean. So the expected value of delta x is 0. Sometimes it's positive, sometimes it's negative, and they end up canceling out. Now, if you're interested in only positive numbers, the next guess you might come up with is let's use not delta x, but let's use the absolute value of delta x. What is that? Well, absolute values are difficult to work with since you have to keep track of whether a number is positive or negative and keep flipping signs if it's negative. So this turns out to just be kind of painful. What statisticians and physicists do in the end then is instead of taking the absolute value of a number to make it positive, we square it. So you calculate the expected value of the squared deviation, sort of the mean squared deviation. This has a name in statistics. It's written as sigma squared, and it's called the variance. To do an example, let's do a discrete example. Suppose I have two probability distributions, all with equally likely outcomes. Say the outcomes of one distribution are 1, 2, and 3, while the outcomes for the second distribution are 0, 2, and 4. Put it graphically, these numbers are more closely spaced than these numbers. So I would expect the broadness of this distribution to be larger than the broadness of this distribution. You can calculate this out by calculating the mean squared deviation. So first of all, we need to know the mean. The expected value of x is 2 in this case, and also in this case. Knowing the expected value of x, you can calculate the deviations. So let's say delta x here is going to be -1, 0, and 1 are the possible deviations from the mean for this probability distribution, whereas in this case it's -2, 0, and 2. Then we can calculate the delta x squareds that are possible, and you get 1, 0, and 1 for this distribution, and 4, 0, and 4 for this distribution. Now when you calculate the mean of these squared deviations, in this case, the expected value of the squared deviation is 2/3, whereas in this case, the expected value of the squared deviation is 8/3. So indeed, we did get a larger number for the variance in this distribution. So you can think of that as the definition. This is not the easiest way of calculating the variance, though. It's actually much easier to calculate the variance as an expected value of a squared quantity and minus the square of the expected value of the quantity itself. So the mean of the square minus the square of the mean, if that helps you to remember it. You can see how this results fairly easily by plugging through some basic algebra. So given our definition, the expected value of delta x squared, we're calculating an expected value. So suppose we have a continuous distribution now. The continuous distribution expected value has an integral in it, so we're going to have the integral of delta x squared times rho of x dx. Now delta x squared, we know what delta x is.
delta x is x minus the expected value of x. So we can plug that in here, and we're going to get the integral of x minus expected value of x squared times rho of x dx. I can expand this out, and I'll get integral of x squared minus 2x expected value of x plus expected value of x quantity squared rho of x dx. And now I'm going to split this integral up into three separate pieces. First piece, integral of x squared rho of x dx. Second piece, integral of 2x expected value of x rho of x dx. And the third piece, integral of expected value of x squared rho of x dx. Now this integral you recognize right away. This is the expected value of x squared. This integral, I can pull this out front since this is a constant. This is just a number. This is the expected value. So this integral is going to become 2, I can pull the 2 out of course as well, 2 times the expected value of x, and then what's left is the integral of x, rho of x dx, which is just the expected value of x. This integral, again this is a constant, so I can pull it out front, and when I do that, I end up with just the integral of rho of x dx. And we know the integral of rho of x dx over the entire domain. I should specify that this is the integral from minus infinity to infinity now. All of these are integrals from minus infinity to infinity. The integral of minus infinity to infinity of rho of x dx is 1. So this, after I pull the expected value of x quantity squared out, is just going to be the expected value of x quantity squared. So this is expected value of x squared. This is, well, I can simplify this as well. This is the expected value of x quantity squared as well. So I'm going to erase that and say squared there. So I have this minus TISE this plus this. And in the end, that gives you expected value of x squared minus the expected value of x squared. So mean of the square minus the square of the mean. To check your understanding of how to use this formula, I'd like you to complete the following table. Now I'll give you a head start on this. If your probability distribution is given by 1, 2, 4, 5, and 8, all equally likely, you can calculate the mean. Now once you know the mean, you can calculate the deviations, x minus the mean, which I'd like you to fill in here. Then square that quantity and fill it in here, and take the mean of that squared deviation. Same as what we did when we talked about the variance as the mean squared deviation. Then, taking the other approach, I'd like you to calculate the squares of all of the x's and calculate the mean square. You know the mean, you know the mean square. You can calculate this quantity, mean of the square minus the square of the mean, and you should get something that equals the mean squared deviation. That's about it for variance, but just to say a little bit more about this, variance is not the end of the story. It turns out there's more. I mentioned the distributions that we were talking about earlier on the first slide here. Keep forgetting to turn my ruler off. The distributions that look like this versus distributions that look like this. This is a question of symmetry, and the mathematical name for this is skew, or skewness. There's also distributions that look like this versus distributions that look like this. And this is what, mathematically, this is called kurtosis, which kind of sounds like a disease or perhaps a villain from a comic book. Kurtosis has to do with the relative weights of
things near the peak versus things in the tails. Now, mathematically speaking, you know the variance, sorry, let me go back a little further. You know the mean, that was related to the integral of x, rho of x, dx. We also just learned about the variance, which was related to the integral of x squared, rho of x, dx. It turns out the skewness is related to the integral of x cubed, rho of x, dx, and the kurtosis is related to the integral of x to the fourth, rho of x, dx. At least those are common ways of measuring skewness and kurtosis. These are not exact formulas for skewness and kurtosis, nor is this an exact formula for the variance, of course, so I'm taking some liberties with the math. But you can imagine, well, what happens if you take the integral of x to the fifth, rho of x dx? You could keep going, and you would keep getting properties of the probability distribution that are relevant to its shape. Now, you won't hear very much about skewness and kurtosis in physics, but I thought you should know that this field does sort of continue on. For the purposes of quantum mechanics, what you need to know is that variance is related to the uncertainty, and we will be doing lots of calculations of variance on the basis of probability distributions derived from wave functions in this class. We talked a little bit about the probabilistic interpretation of the wave function psi. That's one of the really remarkable aspects of quantum mechanics, that there are probabilities rolled up in your description of the physical state. We also talked a fair amount about probability itself, and one of the things we learned was that probabilities had to be normalized, meaning the total sum of all of the probable outcomes, the probabilities of all of the outcomes in a probability distribution has to equal 1. That has some implications for the wave function, especially in the context of the Schrodinger equation, so let's talk about that in a little more detail. Normalization in the context of a probability distribution just means that the integral from minus infinity to infinity of rho of x dx is equal to 1. You can think about that as the sort of extreme case of the probability that, say, x is between a and b, being given by the integral from a to b of rho of x dx. In the context of the wave function, that statement becomes the probability that the particle is between a and b is given by the integral from a to b of the squared magnitude of psi of x integrated between a and b. So this is the same sort of statement. You're integrating from a to b, and in the case of the probability density, you have just the probability density. In the case of the wave function, you have the squared absolute magnitude of the wave function. This is our probabilistic interpretation. We're sort of making an analogy between psi, squared magnitude, and a probability density. This normalization condition, then, has to also hold for psi, if the squared magnitude of psi is going to be treated as a probability density. So, integral from minus infinity to infinity of squared absolute magnitude of psi dx has to equal 1. This is necessary for our statistical interpretation of the wave function. This brings up an interesting question, though, because not just any function can be a probability distribution. Therefore, this normalization condition, treating psi as a probability density, means there are some conditions on what sorts of functions are allowed to be wave functions. This is the question of normalizability. Suppose, for instance, I had a couple of functions that I was interested in. Say one of those functions looks sort of like this, keeps on rising as it goes to infinity. If I wanted to consider the squared magnitude of this function, this is our possible psi, this is our possible psi squared, sorry about the messy there. This function, since it's going to, it's continuing to increase as x increases, both in the negative direction and in the positive direction, its squared magnitude is going to look something like this. I can do a little better there, sorry. If I tried to, say, calculate the integral from minus infinity to infinity of this function, I've got a lot of area out here from, say, 3 to infinity, where the wave function is positive. This would go to infinity, therefore. What that means is that this function is not normalizable. Not all functions can be normalized. If I drew a different function, for example, something that looked maybe something like this, its squared magnitude might look something like this. There is a finite amount of area here, so if I integrated the squared magnitude of the blue curve, I would get something finite. What that means is that whatever this function is, I could multiply or divide it by a constant such that this area was equal to 1. I could take this function and convert it into something such that the integral from minus infinity to infinity of the squared magnitude of psi equaled 1, and it obeyed our sort of statistical constraint on the probability distribution. In order for this to be possible, psi has to have this property, and the mathematical way of stating it is that psi must be square integrable. And all this means is that the integral from minus infinity to infinity of the squared magnitude of psi is finite. You don't get 0, you don't get infinity. In order for this square integrability to hold, for example, though, you need a slightly weaker condition that psi goes to 0 as x goes to either plus or minus infinity. It's not possible to have a function that stays non-zero or goes to infinity itself as x goes to infinity and still have things be integrable. Like I said, if this holds, if this integral here is finite, you can convert any function into something that is normalized by just multiplying or dividing by a constant. Is that possible, though? In the Schrodinger equation, does multiplying or dividing by a constant do anything? Well, the Schrodinger equation here you can just glance at it and see that multiplying and dividing by a constant doesn't do anything. The Schrodinger equation is I h bar partial derivative with respect to time of psi equals minus h bar squared over 2m second derivative of psi with respect to position plus the potential times psi. Now, if I made the substitution psi went to some multiple or some constant a multiplied by psi, you can see what would happen. Here I would have psi times a, here I would have psi times a, and here I would have psi times a. So I would have an a here, an a here, and an a here. So I could divide through this entire equation by a, and all of those a's would disappear, and I would just get the original Schrodinger equation back. What that means is that if psi solves the Schrodinger equation, a psi does too. I'll just say a psi works. Now this is only if a is a constant. Does not depend on time, does not depend on space. If a depended on time, I would not be able to divide it out of this partial derivative because the partial derivative would act on that a. Same goes for if a was a function of space. If a was a function of space, I wouldn't be able to divide it out of this partial derivative with respect to x. So this only holds if a is a constant. That means that I might run into some problems with time evolution. I can choose a constant and I can multiply psi by that constant such that psi is properly normalized at, say, time t equals 0, but will that hold for future times? It's a question of normalization and time evolution. What we're really interested in here is the integral from minus infinity to infinity of psi of x and time squared dx. if this is going to always be equal to 1, supposing it's equal to 1 at some initial time, what we really want to know is what the time derivative of this is. If the time derivative of this is equal to 0, then we'll know that whatever the normalization of this is, it will hold throughout the evolution of the wave function. Now I'm going to make a little bit of simplifying notation here, and I'm going to drop the integral limits since it takes a while to write. And we're going to manipulate this expression a little bit. We're going to use the Schrodinger equation. We're going to use the rules of complex numbers. We're going to use the rules of differential calculus. And we're going to get something that will show that indeed this does hold. So let's step through that. Manipulations of the Schrodinger equation like this are a little tricky to follow, so I'm going to go slowly, and if it seems like I'm being extra pedantic, please bear with me. Some of the details are important. So the first thing that we're going to do, pretty much the only thing that we can do with this equation, is we're going to exchange the order of integration and differentiation. Instead of differentiating with respect to time the integral with respect to x, we're going to integrate with respect to x of the time derivative of this psi of x and t quantity squared. Basically, I've just pushed the derivative inside the integral. Now, notationally speaking, I'm going to move some stuff around here, give myself a little more room. Notationally, oops, didn't mean to change the colors. Notationally speaking here, the d dt became a partial derivative with respect to time. The total derivative, d by dt, is now a partial. What the notation is keeping track of here is just the fact that this is a function only of time, since you've integrated over x and you've substituted in limits. Whereas this is a function of both space and time. So whereas this derivative is acting on something that's only a function of time, I can write it as a simple d by dt, the total derivative. In this case, since what the derivative is acting on is a function of both position and time, I have to treat this as a partial derivative now. So the next thing that we're going to do, aside from after pushing this derivative inside and converting it to a partial derivative, is rewrite this squared absolute magnitude of psi as psi star times psi. Now the squared absolute magnitude of a complex number is equal to the complex number times its complex conjugate. It's just simple complex analysis rules there. So what we've got is the integral of the partial derivative with respect to time of psi star times psi, integral dx. Now we have a time derivative applied to a product. We can apply the product rule from differential calculus. And what we end up with is the integral of the partial derivative with respect to time of psi star times psi plus psi star partial derivative of psi with respect to time. That's integrated dx. Now what I'm going to do is I'm going to notice these partial derivatives with respect to time. And I'm going to ask you to bear with me for a minute while I make a little more space. It's probably a bad sign if I'm running out of space on a computer where I have effectively infinite space. But bear with me. The partial derivatives with respect to time appear in the Schrodinger equation. I h bar d by dt of psi equals minus h bar squared over 2m partial derivative, second partial derivative of psi with respect to position plus potential times psi. These are the time derivatives that I'm interested in. I can use the Schrodinger equation to substitute in, say, the right-hand side for these time derivatives, both for psi star and for psi. So first I'm going to manipulate this by dividing through by I h bar, which gives me d partial psi partial time equals I h bar over 2m, second partial of psi with respect to x, minus, where did it go? I v over h bar psi. So that can be substituted in here. I also need to know something for the complex conjugate of psi, so I'm going to take the complex conjugate of this entire equation. What that looks like is partial derivative of psi star with respect to time. Now I'm taking the complex conjugate of this, so I have a complex part here. The sign of that needs to be flipped. And I have a complex number here that needs to be complex conjugated, since the complex conjugate of a product is the product of the complex conjugates. What that means is this is going to become minus I h bar over 2m d squared psi star dx squared, sorry, I forgot the squared there, plus I v over h bar psi. So I've just gone through and changed the signs on all of the imaginary parts of all these numbers. Psi became psi star, I became minus I became I. And this can be substituted in for that. And what you get when you make that substitution, this equation isn't really getting simpler, is it? It's getting longer. What you get is the integral of something. I'll put an open square brackets at the beginning here. I've got this equation, minus I h bar over 2m, second partial derivative of psi star partial x squared, plus I v over h bar psi star, that's multiplied by psi from here. So I've just substituted in this expression for this. Now the next part I have plus psi star and whatever I'm going to substitute in from this, which is what I get from this version of the Schrodinger equation here. I h bar over 2m, second partial derivative of psi with respect to x, minus I v over h bar psi. Close parentheses, close square brackets, and I'm integrating dx. Now, this doesn't look particularly simple, but if you notice what we've got here, this term, if I distributed this psi in, would have I v over h bar psi star times psi. This term, if I distributed this psi star in, would have an I v over h bar psi star and psi. This term has a plus sign, this term has a minus sign. So these terms actually cancel out. What we're left with, then, to rewrite things, both of the terms that remain have this minus I h bar over 2m out front. So we're going to have equals to I h bar over 2m. And here I have a minus second partial derivative of psi star with respect to x times psi. And here I have plus psi star times the corresponding second partial of psi with respect to x. And this is integrated dx. Is that all right? Yes. Now, what I'd like you to notice here is that we've got d by dx and we've got an integral dx. We don't have any time anymore. So we're making progress. And we're actually almost done. Where did we get so far? We started with the time derivative of this effective total probability, which should have been equal to 1, which would be equal to 1 if this were a proper probability distribution, but we're just considered with the time evolution, since we know that whatever psi is, we can multiply it by some constant to make it properly normalized at a particular time. Now we're interested in the time evolution. We're looking at the time derivative of this, and we've gone to this expression, which has complex conjugates of psi and second partial derivatives with respect to x. Now, what I'd like you to do, and this is a check your understanding question, is think about why this statement is true. This is the partial derivative with respect to x of psi star d psi dx minus d psi star dx. So, sorry, I'm saying d, I should be saying partial. These are partial derivatives. This is true, and it's up to you to figure out why. But since this is true, what we're left with is we have our I h bar over 2m, and an integral over minus infinity to infinity of this expression, partial with respect to x of psi star partial psi partial x minus partial psi star partial x psi. We're integrating dx now. And this is nice because we're integrating dx of a derivative of something with respect to x. So that's easy. Fundamental theorem of calculus. We end up with I h bar over 2m psi star partial psi partial x minus partial psi star partial x psi, evaluated at the limits of our integral, which are minus infinity to infinity. Now, if psi is going to be normalizable, we know something about the value of psi at negative and positive infinity. If psi is normalizable, psi has to go to 0 as x goes to negative and positive infinity. What that means is that when I plug in the infinity here, psi star, d psi dx, and psi, everything here is going to be 0. So when I enter in my limits, I'm just going to get 0 and 0. So the bottom line here, after all of this manipulation, is that this is equal to 0. What that means is that the integral from negative infinity to infinity of the squared absolute magnitude of psi as a function of both x and time is equal to a constant. Put another way, time evolution does not affect normalization. What that means is that I can take my candidate wave function, not normalized, integrate it, find out what I would have to multiply or divide it by to make it normalized, and if I'm successful, I have my normalized wave function. I don't need to worry about how the system evolves in time. The Schrodinger equation does not affect the normalization. So this is that check your understanding question I mentioned. The following statement was that crucial step in the derivation, and I want you to show that this is true, explain why in your own words. Now, to do an example here, normalize this wave function. What that means is that we're going to have to find a constant, and I've already put the constant in the wave function, a, such that the integral from minus infinity to infinity of the squared absolute magnitude of psi of x, in this case I've left the time dependence out, is equal to 1. And same as in the last problem, the first thing we're going to do is substitute the squared absolute magnitude of psi for psi star times psi. The other thing I'm going to do before I get started is notice that my wave function is 0 if the absolute value of x is greater than 1, meaning for x above 1 or below negative 1. So instead of integrating from minus infinity to infinity here, I'm just going to focus on the part where psi is non-zero and integrate from minus 1 to 1. Integral from minus 1 to 1 of psi star, which is going to be a, e to the ix is going to become e to the minus ix, and 1 minus x squared is still going to be 1 minus x squared. Now, I haven't complex conjugated a because part of the assumption about normalization constants like this is usually that you can choose them to be purely real. So I'm not going to worry about taking the complex conjugate of a just to make my life a little easier. Psi, well, that's just right here, a e to the ix 1 minus x squared. And I'm integrating dx. This is psi star, this is psi, integral dx from minus 1 to 1, should be equal to 1. So let's do this. We end up with a squared times the integral from minus 1 to 1 of e to the minus ix and e to the ix. What's e to the minus ix times e to the ix? Well, thinking about this in terms of the geometric interpretation, we have e to the ix, which is cosine theta plus I sine theta. You can think about that as being somewhere on the unit circle at an angle theta. Minus I theta would just be in the exact opposite direction. So when I multiply them together, I'm going to get something that has the product of the magnitudes. The magnitudes are both 1, and it's purely real. You can see that also by looking at just the rules for multiplying exponentials like this. E to the minus ix times e to the plus ix is e to the minus ix plus ix, or e to the 0, which is 1. So I can cancel these out. And what I'm left with is 1 minus x squared, quantity squared, dx. Plugging through the algebra a little further, a squared, integral minus 1 to 1, of 1 minus 2x squared plus x to the 4th dx. You can do this integral equals a squared x minus 2/3 x cubed plus x to the 5th over 5. We know in quantum mechanics that all of the information about the physical system is encapsulated in the wave function psi. Psi then ought to be related to physical quantities for for example, position, velocity, and momentum of the particle. We know a little bit about the position. We know how to calculate things like the expected value of the position, and we know how to calculate the probability that the particle is within a particular range of positions. But what about other dynamical variables like velocity or momentum? The connection with velocity and momentum brings us to the point where we really have to talk about operators. Operators are one of our fundamental concepts in quantum mechanics, and they connect the wave function with physical quantities. But let's take a step back first and think about what it means for a quantum system to move. The position of the particle, we know, say, the integral from a to b of the squared magnitude of the wave function dx gives us the probability that the particle is between a and b. And we know that the expected position is given by a similar expression, the integral from minus infinity to infinity of psi star of x times psi of x dx. Now these expressions are related, by the fact that the squared magnitude of psi is the probability density function describing position, and this is really just the calculation of the expected value of x given that probability density function. Now what if I want to know what the motion of the particle is? One way to consider this is, suppose I have a box, and if I know the particle is, say, here at time t equals 0, what can quantum mechanics tell me about where the particle is later? Physically speaking, you could wait until, say, t equals 1 second, and then measure the position of the particle. And maybe it would be here. You could then wait a little longer and measure the particle again. Maybe at that point it would be here. That's, say, t equals 2 seconds. Or if I wait a little bit longer and measure the particle yet again at, say, t equals 3 seconds, maybe the particle would be up here. Now, does that mean that the particle followed a path that looked something like this? No. We know that the position of the particle is not something that we can observe at any given time with impunity because of the way the observation process affects the wave function. Back when we talked about measurement, we talked about having a wave function that looks something like this, a probability density that looks something like that,
And then after we measure the position of the particle, the probability density has changed. If we say measure the particle to be here, the new wave function has to accommodate that new probability density function. The fact that measurement affects the system like this means that we really can't imagine repeatedly measuring the position of a particle in the same system. What we really need is an ensemble. That's the technical term for what we need. What an ensemble means in this context is that you have many identically prepared systems. Now, if I had many identically prepared systems, I could measure the position over and over and over and over again, once per system. If I have, 100 systems, I could measure the position 100 times, and that would give me a pretty good feel for what the probability density for position measurements is at the particular time when I'm making those measurements. If I wanted to know about the motion of the particle, I could do that again, except instead of taking my 100 measurements all at the same time, I would take them at slightly different times. So instead of this being the same system, these would all be different systems that have been allowed to evolve for different amounts of time. And as such, the motion of the particle isn't going to end up looking something like that. It's going to end up looking like some sort of probabilistic motion of the wave function in space. What we're really interested in here, oh, sorry, I should make a note of that. Single measurement per system. This notion of averaging over many identically prepared systems is important in quantum mechanics because of this effect that measurement has on the system. So what we're interested in now, in the context of something like motion, is, well, can we predict this? Can we predict where the particle is likely to be as a function of time? And yes, we can. And what I'd like to do to talk about that is to consider a quantum mechanical calculation that we can actually do, the time derivative of the expected value of position. This time derivative tells us how the center of the probability distribution, if you want to think about it that way, how the center of the wave function moves with time. So this time derivative, d by dt of the expected value of x, that's d by dt of, let's just write out the expected value of x, integral from minus infinity to infinity of x times psi star of x, psi of x, where this is the probability density function that described or given by the wave function, and this is x. We're integrating dx. Now, if you remember when we talked about normalization and whether the normalization of the wave function changed as the wave function evolved in time, we're going to do the same sort of calculation with this. We're going to do some calculus with this expression. We're going to apply the Schrodinger equation. But as before, the first thing we're going to do is move this derivative inside the equation. This is a total time derivative of something that's a function of, in principle, position and time. I should write these as functions of x and t. And what you get when you push that in is, as before, the integral, or the total derivative becomes a partial derivative. Since x is just the coordinate x in these contexts of functions of both space and time, the total time derivative will not affect the coordinate x, even when it becomes a partial derivative. So what we'll end up with is x times the partial time derivative of psi star psi, integral dx. I'm not going to write the integral from minus infinity to infinity here, just to save myself some time. Now, if you remember this expression, the integral, or sorry, not the full integral, just the partial time derivative of psi star psi, that was what we worked with in the lecture on normalization.
So if we apply the result from the electron normalization, and it's equation 126, yes, in the book, if we apply that, you can simplify this down a lot right off the bat. And what you end up with is I h bar over 2m times this integral x, and then what we substitute in. The equation 126 gives an expression for this highlighted part here in orange. And what you get is the partial derivative with respect to x of psi star partial of psi with respect to x minus partial of psi star with respect to x times psi. Integral still with respect to dx, of course. Now, if we look at this equation, we're making the same sort of progress we made when we did the normalization derivation. We had time derivatives here. Now we have only space derivatives. And we have only space derivatives in an integral over space. So this is definitely progress. Now we can start thinking about what we can do with integration by parts. The first integration by parts I'm going to do has the non-differential part just being x, and the differential part being dv is equal to, I'm not going to have space to write this here. I got to move stuff around a little bit. So the differential part is dv is the partial derivative, well, what's left of this equation, the partial derivative with respect to x of psi star d psi dx minus d psi dx psi, d psi star dx psi. And then there's the dx from the integral. Sorry, I'm running out of space. This differential part here is just this part of the equation. Now I can take this derivative, du dx, in my integration by parts procedure, du equals dx, and dv here is easy to integrate because this is a derivative. So when I integrate the derivative there, I'll just end up with v equals psi star d psi dx minus d psi star dx psi. Now when I actually apply those, that integration by parts, the boundary term here without the integral in it is going to involve these two. So I'm going to have x times psi star partial psi partial x minus partial psi star partial x psi. And that's going to be evaluated between minus infinity and infinity, the limits on my integral. And the integral part, which comes in with a minus sign, is going to be composed of these bottom two terms. Integral of psi star partial psi partial x minus partial psi star partial x psi, and it's the integral dx from minus infinity to infinity. Now what's nice, I forgot something here. What did I forget? My leading constants. I still have this IH bar over 2m out there. IH bar over 2m is multiplied by this entire expression. Now, the boundary terms here vanish. The boundary terms in integration by parts in quantum mechanics will often vanish because if you're evaluating something at, say, infinity, psi has to go to 0 at infinity, so this term is going to vanish. Psi star has to go to 0 at infinity, so this is going to vanish. So even though x is going to infinity, psi is going to 0. And if you dig into the mathematics of quantum mechanics, you can show convincingly that the limit as x times psi goes to infinity is going to be 0. So this boundary term vanishes, both at infinity and at minus infinity. And all we're left with is this. Yes. All you're left with is that. So I'll write that over. IH bar over 2m times the integral of psi star partial psi partial x minus partial psi star partial x psi integral dx. I'm actually going to split that up into two separate integrals. So I'll stick another integral sign in here, and I'll put a dx there, and I'll put parentheses around everything so my leading constant gets multiplied in properly. And now I'm going to apply integration by parts again, but this time just to the second integral here. So here, we're going to say u is equal to psi, and dv is equal to, again, using the fact that when we do this integral, if we can integrate a derivative, that potentially simplifies things. So this is going to be partial psi star partial x dx. So when we take the derivative of this, we're going to get du is equal to partial psi partial x. And when we integrate this, we're going to get v equals psi star. Now, when we do the integration, when we write down the answer from this integration by parts, the boundary term here, psi star times psi, is going to vanish, again, because we're evaluating it at a region where both psi star and psi, vanish. So the boundary term vanishes. And you notice I have a minus sign here. When we do the integration by parts, the integral term has a minus sign in it here. So we're going to have the partial psi with respect to x and psi star, with a minus sign coming from the integration by parts and a minus sign coming from the leading term here. So we're going to end up with a plus sign there. So we get a minus from the integral part. What that means, though, is that I have psi star and partial psi partial x. In my integration by parts, I end up with partial psi partial x and psi star. It's the same. And the fact that I had a minus and another minus means I get a plus. So I have two identical terms here. The result of this, then, is I h bar over m. I'm adding a half and a half and getting 1, basically, times the integral of psi star partial psi partial x dx. And this is going to be something that I'm going to call now the expectation of the velocity vector, the velocity operator. This is the sort of thing that you get out of operators in quantum mechanics. You end up with expressions like this. And this I'm sort of equating just by analogy with the expectation of a velocity operator. This is not really a probability distribution anymore, at least not obviously. We started with the probability distribution due to psi, the absolute magnitude of psi squared, and we end up with the partial derivative on one of the psi's. So it's not obvious that this is a probability distribution anymore, and well, it's the probability distribution in velocity, and it's giving you the expected velocity in some sense, in a quantum mechanical sense. So this is really a more general sort of thing. We have the velocity operator, the expectation of the velocity operator. Oh, and operator-wise, I will try to put hats on things. I will probably forget. I don't have that much attention to detail when I'm making lectures like this. The hat notation means operator. If you see something that you're really sure is an operator but it doesn't have a hat, that's probably just because I made a mistake. But this expression for the expectation of the velocity operator is the one we just derived, minus I h bar over m times the integral of psi star partial derivative of psi with respect to x integral dx. Now it's customary to talk about momentum instead of velocity. Momentum has more meaning because it's a conserved quantity under most physics. So we can talk about the momentum operator, the expectation of the momentum operator. And I'm going to write this momentum operator expression in a slightly more suggestive way. The integral of psi star times something in parentheses here, which is minus I h bar, partial derivative with respect to x. And I'm going to close the parentheses there, put a psi after it, and a dx for the integral. You have the same sort of expression for the position operator. We were just writing that as the expected value of position without the hat earlier. But that's going to be the integral of psi star. What goes in the parentheses now is just x psi dx. So this you recognize as the expectation of the variable x, subject to the probability distribution given by psi star times psi. This is slightly more subtle. You have psi star and psi, which looks like a probability distribution, but what you have in the parentheses now is very obviously an operator that does something. It does more than just multiply by x. It multiplies by minus I h bar and takes the derivative of psi. Operators in general do that. we can write them as, say, x hat equals x times, where there's very obviously something that has to go after the x in order for it to be considered an operator. Or we can say the same for v hat. It's minus I h bar over m times the partial derivative with respect to x, where there obviously has to be something that goes here. Likewise for momentum, minus I h bar partial derivative with respect to x. Something has to go there. Another example of an operator is the kinetic energy operator. Usually that's written as T, and that's minus h bar squared over 2m. You can think of it as the momentum operator squared. It's got a second derivative with respect to x. And again, there very obviously has to be something that goes there. The operator acts on the wave function. That's what I said back when I talked about the fundamental concepts of quantum mechanics, and this is what it means for the operator to act on the wave function. The operator itself is not meaningful. It's only meaningful in the context when it's acting on a wave function. In general, wrong color. In general, the expectation value of some...
As an introduction to the uncertainty principle, we're going to talk about waves and how waves are related to each other. We'll get into a little bit of the context of Fourier analysis, which is something we'll come back to later. But the overall context of this lecture is the uncertainty principle. And the uncertainty principle is one of the key results from quantum mechanics, and it's related to what we discussed earlier in the context of the boundary between classical physics and quantum physics. Quantum mechanics has these inherent uncertainties that are built into the equations, built into the state, built into the nature of reality that we really can't surmount. And the uncertainty principle is one way in which those, or is the mathematical description. It's those relationships that I gave you earlier. Delta p, delta x is greater than about equal to h bar over 2. I think I just said greater than about equal to h bar earlier. We'll do things a little more mathematically here, and it turns out there's a factor of 2 there. To start off, though, conceptually think about position and wavelength. And this really is now in the context of a wave. So say I had a coordinate system here, something like this. And if I had some wave with a very specific wavelength, you can just think about it as a sinusoid. If I asked you to measure the wavelength of this wave, you could take a ruler and you could plop it down there and say, okay, well, how many inches are there from peak to peak? Or from zero crossing to zero crossing, or if you really wanted to, you could get a tape measure and measure many wavelengths, 1, 2, 3, 4 wavelengths in this case. That would allow you to very accurately determine what the wavelength was. If, on the other hand, the wave looked more like this, give you another coordinate system here, the wave looked something like this, you wouldn't be able to measure the wavelength very accurately. You could, as usual, put your ruler down on top of the wave, for instance, and count up the number of inches or centimeters from one side to the other, but that's just one wavelength. It's not nearly as accurate as, say, measuring 4 wavelengths, or 10 wavelengths, or 100 wavelengths. You can think of some limiting cases. Suppose you had a wave with many oscillations. It looks like I'm crossing out the wave underneath there, so I'm going to erase this in a moment. But if you had a wave with many wavelengths, and you could measure the total length of many wavelengths, you would have a very precise measurement of the wavelength of the wave. The opposite is the case here. You only have one wavelength, you can't really measure the wavelength very accurately. What you can do, however, is measure the position very accurately. Here, I can say pretty certainly the wave is there, plus or minus a very short spread in position. The other hand, here, I cannot measure the position of this wave accurately at all. If this thing continues, I can't really say where the wave is. It's not really a sensical question to ask, where is this wave? This wave is everywhere. These are the sorts of built-in uncertainties that you get out of quantum mechanics. Where is the wave? The wave is everywhere. It's a wave. It doesn't have a local position. It turns out, if you get into the mathematics of Fourier analysis, that there is a relationship between the spread of wavelengths and the spread of positions. If you have a series of waves of all different wavelengths and they're added up, the spread in the wavelength is related to the spread in positions of the sum. And we'll talk more about Fourier analysis later, but for now just realize that this product is always going to be greater than or equal to about 1. Wavelength is something with units of inverse length, and the position, of course, is something with units of length. So the dimensions of this equation are sort of a guideline. Wavelength and position have this sort of relationship, and this comes from Fourier analysis. So how do these waves come into quantum mechanics? Well, waves in quantum mechanics really first got their start with Louis de Broglie. I always thought his name was pronounced de Broglie, but it's, well, he's French, so there's all sorts of weird pronunciations in French. De Broglie is my best guess at how it would probably be pronounced. De Broglie proposed that matter could travel in waves as well. And he did this with an interesting argument on the basis of 3 fundamental equations that had just recently been discovered when he was doing his analysis. This was in his PhD thesis, by the way. E equals mc squared. You all know that equation. You all hopefully also know this equation, E equals hf. Planck's constant times the frequency of a beam of light is the energy associated with a quanta of light. This was another one of Einstein's contributions, and it has to do with his explanation of the photoelectric effect. The final equation that de Broglie was working with was C equals f lambda. The speed of light is equal to the frequency of the light times the wavelength of the light. And this is really not true just for light. This is true for any wave phenomenon. The speed, the frequency, and the wavelength are related. Now, if these expressions are both equal to waves, or are both equal to energy, then I ought to be able to say mc squared equals hf. And this expression tells me something about f. It tells me that f equals c over lambda. So I can substitute this expression in here and get mc squared equals hc over lambda. Now I can cancel out one of the c's, and I'm left with mc equals h over lambda. Now what de Broglie said was this is like momentum. So I'm going to write this equation as p equals h over lambda. And then I'm going to wave my hands extraordinarily vigorously and say, while this equation is only true for light, and this equation is only true for waves, this is also true for matter. How actually this happened in the context of quantum mechanics, in the early historical development of quantum mechanics, is de Broglie noticed that the spectrum of the hydrogen atom, these bright line spectra that we were talking about, where a hydrogen atom emits light of only very specific wavelengths. Intensity as a function of wavelength looks something like this. That could be explained if he assumed that the electrons were traveling around the nucleus of the hydrogen atom as waves, and that only an integer number of waves would fit. The one that I just drew here didn't end up back where it started, so that wouldn't work. If you had a wavelength that looked something like this, going around, say, 3 full times in a circle, that would potentially account for these allowed emission energies. That was quite a deep insight, and it was one of the things that really kicked off quantum mechanics at the beginning. The bottom line here, for our purposes, is that we're talking about waves, and we're talking about matter waves. So that uncertainty relation, or the relationship between the spreads of wavelengths and the spreads in positions that I mentioned in the context of Fourier analysis, will also potentially hold for matter. And that gets us into the position-momentum uncertainty relation. The wave-momentum relationship we just derived on the last slide was p equals h over lambda. This tells you that the momentum and the wavelength are related. From 2 slides ago, when we were talking about waves and whether or not you could say exactly where a wave was, we had a relationship that was something like delta lambda, the spread in wavelengths, times the spread in positions of the wave, is always greater than about equal to 1. Combining these relationships together in quantum mechanics, and this is not something that I'm doing rigorously now, I'm just waving my hands, gives you delta p, delta x is always greater than about equal to h bar over 2. And this is the correct mathematical expression of the Heisenberg uncertainty principle that we'll talk more about and derive more formally in Chapter 3. But for now, just realize that the position of a wave, the position of a particle, are uncertain quantities, and the uncertainties are related by this, which in one perspective results from consideration of adding many waves together in the context of Fourier analysis, which is something we'll talk about later as well, extended through the use of, or the interpretation of, matter as also a wave phenomenon. To check your understanding, here are 4 possible wave packets, and I would like you to rank them in 2 different ways. 1, according to the uncertainties in their positions, and 2, according to the uncertainties in their momenta. So if you consider, say, wave B to have a very certain position, you would rank that one highest in terms of the certainty of its position. Perhaps you think wave B has a very low uncertainty in position, you would put it on the other end of the scale. I'm looking for something like the uncertainty of B is greater than the uncertainty of A is greater than the uncertainty of D is greater than the uncertainty of C for both position and momentum. The last comment I want to make in this lecture is on energy-time uncertainty. This was the other equation I gave you when I was talking about the boundary between classical physics and quantum physics. We had delta P delta X is greater than or equal to h bar over 2, and now we also had excuse me for a moment here, delta E, delta T greater than about equal to h bar over 2. Same sort of uncertainty relation, except now we're talking about spreads in energy and spreads in time. And I'd like to make an analogy between these 2 equations. Delta P and delta X. Delta P, according to Dirac, is related to the wavelength, which is sort of a spatial frequency. It's the frequency of the wave in space. Delta X, of course, is just, well, I'll just say that's a space. And these are related, according to this equation. In the context of energy and time, we have the same sort of thing. Delta T, well, that's pretty clear, that's time. And delta E, well, that then, therefore, by analogy here, has to have something to do with the frequency of the wave now in time. And that's simple, that's just the frequency. The fact that these are also related by an uncertainty principle tells you that there's something about energy and frequency in time. And this is something that we'll talk about in more detail in the next lecture when we start digging into the Schrodinger equation. The time-dependent Schrodinger equation and deriving the time-independent Schrodinger equation, which will give us the relationship exactly. But for now, position and momentum, energy and time, are both talking about sort of wave phenomenon, except in the context of position and momentum, you're talking about wave length, frequency of the wave in space, whereas energy and time, you're talking about the frequency of the wave in time, how quickly it oscillates. That's about all. The uncertainty principle, as I've said, is something that we'll treat in much more detail in Chapter 3. But for now, the uncertainty principle is important because you have these equations, and these are fundamental properties of the universe, if you want to think of them that way. And they're something that we're going to be working with as a way of checking the validity of quantum mechanics throughout the rest of throughout Chapter 2. That's all for now. You just need to conceptually understand how these wave lengths and positions or frequencies and times are interrelated. The last few lectures have been all about the wave function, psi. And since psi is such an important concept in quantum mechanics, really the first entire chapter of the textbook is devoted to the wave function and all of its various properties. Since we've reached the end of chapter 1 now is a good opportunity to go and review the key concepts of quantum mechanics, in particular the wave function and how it is related to the rest of quantum mechanics. The key concepts, as I stated them earlier, were operators, the Schrodinger equation, and the wave function. Operators are used in the Schrodinger equation and act on the wave function. Your friend and mine, psi. What we haven't really talked about a lot yet is how to determine the wave function, and the wave function is determined as solutions to the Schrodinger equation. That's what Chapter 2 is all about, solving the Schrodinger equation for various circumstances. The key concepts that we've talked about so far, operators and the wave function, conspire together to give you observable quantities. Things like position or momentum, or say the kinetic energy of a particle. But they don't give us these properties with certainty. In particular, the wave function really only gives us probabilities. And these probabilities don't give us really any certainty about what will happen. Uncertainty is one of the key concepts that we have to work with in quantum mechanics. So let's take each of these concepts in turn and talk about them in a little more detail, since now we have some actual results that we can use, some mathematics. We can put more meat on this concept map than just simply the concept map. First, the wave function. The wave function psi does not tell us anything with certainty, and it's a good thing too, because psi, as a function of position and time, is complex. It's not a real number, and it's hard to imagine what it would mean to actually observe a real number. So the wave function is already on somewhat suspect ground here. But it has a meaningful connection to probability distributions if we more or less define the squared modulus, the absolute magnitude of the wave function, to be equal to a probability distribution. And this is the probability distribution for what? Well, it's the probability distribution for outcomes of measurements of position, for instance. You can think about this as a probability distribution for where you're likely to find the particle should you go looking for it. This interpretation as a probability distribution requires the wave function to be normalized. Namely, that if I integrate the squared magnitude of the wave function over the entire space that I'm interested in, I have to get 1. This means that if I look hard enough for the particle everywhere, I have to find it somewhere. The probability distributions, as I mentioned earlier, don't tell you anything with certainty. In particular, there is a good deal of uncertainty, which we express as a standard deviation or a variance. For instance, if I'm interested in the standard deviation of the uncertainty, or standard deviation of the position, it's most easy to express as the variance, which is the square of the standard deviation. And the square of this standard deviation, or the variance, is equal to the expectation value of the square of the position minus the square of the expectation value of the position. And we'll talk about expectation values in a moment. Expectation values are calculated using expressions with operators that look a lot like these sorts of integrals. In fact, I can re-express this as the expectation of the square in terms of a probability distribution is just the x squared times multiplied by the probability distribution with respect to x, integrated over all space. This is the expectation of x squared. I can add to that, or subtract from that, the square of the expectation of x, which has a very similar form. And that gives us our variance. So our wave function, which is complex, gives us probability distributions. which can be used to calculate expectation values and uncertainties. This probabilistic interpretation of quantum mechanics gets us into some trouble pretty quickly. I'm going to move this up now, give myself some more space. Namely with the concept of wave function collapse. Now, collapse bothers a lot of people, and it should. This is really a philosophical problem with quantum mechanics, that we don't really have a good interpretation of what quantum mechanics really means for the nature of reality. But the collapse of the wave function is more or less a necessary consequence of the interpretation of the wave function as a probability distribution. If I have some states, some space, some coordinate system, and I plot on this coordinate system the squared magnitude of psi. This is related to our probability distribution with respect to position. If I then measure the position of the particle, what I'm going to get is, say I measure the particle to be here. Now, if I measure the position of the particle again immediately, I should get a number that's not too different than the number that I just got. And this is just sort of to make sure that if I repeat a measurement, it's consistent with itself, that I don't have particles jumping around truly randomly. If I know the position, I know the position. That's a reasonable assumption. What that means is that the new probability distribution for the position of the particle after the measurement is very sharply peaked about the position of the measurement. If this transition from a wave function, for instance, that has support here to a wave function that has no support here did not happen instantaneously, it's imaginable that if I tried to measure the particle's position twice in very rapid succession, that I would have one particle measured here and another particle measured here. Does that really mean I have one particle, or do I have two particles? These particles could be separated by quite a large distance in space, and my measurements could be not separated by very much in time, so I might be getting into problems with special relativity and the speed of light. And these sorts of considerations are what leads to the Copenhagen interpretation of quantum mechanics, which centers on this idea of wave functions as probability distributions and wave function collapse as part of the measurement process. Now, I mentioned operators in the context of expectation values. Operators are our second major concept in quantum mechanics. What about operators in the wave function? Well, operators, let's just write a general operator as q hat. Hats usually signify operators. Operators always act on something. You can never really have an operator in isolation. And what the operators act on is usually the wave function. We have a couple of operators that we've encountered, namely the position operator, x hat, which is defined as x times. And what's it multiplied by? Well, it's multiplied by the wave function. We also have the momentum operator, p hat, and that's equal to minus I h bar times the partial derivative with respect to x of what? Well, of the wave function. We also have the kinetic energy, which I'll write as ke hat. You could also write it as t hat. That operator is equal to minus h bar squared over 2m times the second derivative with respect to position of what? Well, of the wave function. And finally, we have h hat, the Hamiltonian, which is an expression of the total energy in the wave function. It's a combination of the kinetic energy operator here, which you can see, first of all, as p squared. We have a second derivative with respect to position and minus h bar squared. This is just p squared divided by 2m. P squared over 2m is a classical kinetic energy. The analogy is reasonably clear there. You add a potential energy term in here, and you get the Hamiltonian. Now, expectation values of operators like this are calculated as integrals. The expectation value of q, for instance, is the integral of psi star times q acting on psi over all space. This bears a striking resemblance to our expression, for instance, for the expectation of the position, which was the integral of just x times rho of x, where rho of x is now given by the absolute magnitude of psi squared, which is given by psi star times psi. Now, basically, the pattern here is you take your operator and you sandwich it between psi star and psi. And you can think about this position as being sandwiched between psi star and psi as well, because we're just multiplying by it. It doesn't really matter where I put it in the expression. The sandwich between psi star and psi of the operator is more significant when you have operators with derivatives in them. But I'm getting a little long-winded about this. Perhaps suffice it to say that operators in the wave function allow us to calculate meaningful physical quantities, like x, the expectation of position. This is more or less where we would expect to find the particle. Or the expectation of p, and I should be putting hats on these since technically they're operators. The expectation of p is more or less the expected value of the momentum, the sorts of momenta that the system can have. Or the expectation value of h, the typical energy the system has. And all of these are tied together in the context of uncertainty. For instance, if I wanted to calculate the uncertainty in the momentum, I can do that with the same sort of machinery we used when we were talking about probability, that I calculate the expectation of p squared and I subtract the expectation of p squared. So the expectation of the square minus the square of the expectations is directly related to the uncertainty. So that's a little bit about operators and a little bit about the wave function and a little bit about how they're used. Operators acting on the wave function calculating expectations in the context of the wave function being treated as a probability distribution. Now, where are we all going with this? We're going towards the Schrodinger equation. And the Schrodinger equation, to write it out, is I h bar partial derivative with respect to time of the wave function, and that's equal to minus h bar squared over 2m second partial derivative with respect to position of the wave function, plus some potential function of x, times the wave function. Now the wave function psi here, I've left it off as a function of position and time. So this is really the granddaddy of them all. This is the equation that we will be working with throughout Chapter 2. We will be writing this equation for various scenarios and solving it, and describing the properties of the solutions. So hopefully now you have a reasonable understanding of the wave function and enough understanding of operators to understand what to do with the wave function. The sorts of questions you can ask of the wave function are things like, what sorts of energy does this system have? How big is this spread in momenta? Where am I likely to find the particle if I went looking for it? But all of that relies on having the wave function, and you get the wave function by solving the Schrodinger equation. So that's where we're going with this. And that's all of the material for Chapter 1. And without further ado, moving on to the next lecture, we'll start solving the Schrodinger equation. We're going to move now into actually solving the Schrodinger equation. This is really the main meat of quantum mechanics. And in order to start tackling the Schrodinger equation, we need to know a little bit about how equations like the Schrodinger equation are solved in general. One of those solution techniques is separation of variables, and that's the solution technique that we're going to be applying repeatedly to the Schrodinger equation. First of all, though, let's talk a little bit about ordinary and partial differential equations. The Schrodinger equation is a partial differential equation, which means it's a good deal more difficult than an ordinary differential equation. But what does that actually mean? First of all, let's talk about ordinary differential equations. What an ordinary differential equation tells you is how specific coordinates change with time. At least that's most applications. So you have something like x as a function of time, y as a function of time, sorry, not y as a function of x, y as a function of time, z as a function of time. For example, the position of a projectile moving through the air could be determined by three functions, x, y, and z. If you're only working in 2 dimensions, for instance, let me drop the z, but we might have a velocity as well, say vx of t and vy of t. These 4 coordinates, position in 2 dimensions and velocity in 2 dimensions, fully specifies the state of a projectile moving in 2 dimensions. What an ordinary differential equation might look like to govern the motion of this projectile would be something like the following. dx dt is vx dy dt is Vy. Nothing terribly shocking there. The position coordinates change at a rate of change given by the velocity. While the velocities change, dvx dt is given by, let's say, minus kvx, and dvy dt is minus kv subscript y now, kvy minus g. This tells you that, where I got these equations, this is effectively damped frictional motion in the plane xy, where gravity is pulling you down. So in the absence of any velocity, gravity leads to an acceleration in the negative y direction, and the rest of this system evolves accordingly. What that tells you, though, in the end, is the trajectory of the particle. If you launch it as a function of time, tick, 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 as the projectile moves through the air in, say, x, y space. Partial differential equations, on the other hand, PDEs, you have several independent variables. So where in an ordinary differential equation we only had time, and everything was a function of time, in a partial differential equation, what you're trying to solve for will have several independent variables. For example, the electric field, the vector electric field in particular, as a function of x, y, and z. The electric field has a value, both a magnitude and a direction, at every point in space, so x, y, and z potentially vary over the entire universe. Now you know how, excuse me, you know a few equations that pertain to the electric field that maybe you could use to solve to determine what the electric field is. One of these is Gauss's law, which we usually give an integral form. The integral of the electric field dotted with an area vector over a closed surface is equal to the charge enclosed by that surface over epsilon naught. Now hopefully you also know there is a differential form for Gauss's law, and it usually is written like this. This upside down delta is read as del, so you could say this is del dot E, and this is a vector differential operator. I'm going to skip the details of this because this is all electromagnetism, and if you go on to take advanced electromagnetism courses, you will learn about this in excruciating detail. Perhaps suffice to say here that most of the time when we're trying to solve equations like this, we don't work with the electric field, we work with the potential, let's call that V, and this system of equations here, if you treat the electric field as minus the gradient of the potential, gives you this equation gives you the Laplace equation. Del squared V equals rho over epsilon naught. What that actually writes out to, if you go through all of the vector algebra, is the second derivative of V with respect to x plus the second derivative of V with respect to y plus the second derivative of V with respect to z, and I've left off all my squareds in the denominator here, is equal to rho over epsilon naught. This is a partial differential equation, and if we had some machinery for solving partial differential equations, we would be able to determine the potential at every point in space. And that would then allow us to determine the electric field at every point in space. This is just an example. Hopefully you're familiar with some of the terms I'm using here. The main solution technique that is used for partial differential equations is separation of variables. And separation of variables is fundamentally a guess. Suppose we want to find some function. In the case of electromagnetism, it's the potential x, y, and z. The potential is a function of x, y, and z. Let's make a guess that v of x, y, and z can be written as x of x times y of y times z of z. So instead of having one function of three variables, we have the product of three functions of one variable each. Does this guess work? Well, it's astonishing how often this guess actually does work. This is a very restrictive sort of thing, but under many realistic circumstances, this actually tells you a lot about the solution. For example, the wave equation. The wave equation is what you get mathematically if you think about, say, having a string stretched between two solid objects. Now, under those circumstances, if you zoom in on, if you say, pluck the string, you know it's going to vibrate up and down. Mathematically speaking, if you zoom in on a portion of that string, say it looks like this, you know the center of this string is going to be accelerating downwards. And the reason it's going to accelerate downwards is because there is tension in the string, and the tension force pulls that direction on that side and that direction on that side. So it's being pulled to the right and pulled to the left, and the net force then ends up being in the downward direction. If the string curved the other direction, you would have effectively a net force pulling up and to the right, and a net force pulling up into, or a force pulling up into the right, a force pulling up into the left, and your net force would be up. This tells you about forces in terms of curvatures, and that thought leads directly to the wave equation. The acceleration, as a result of the force, is related to the curvature of the string. And how we express that mathematically is with derivatives. The acceleration is the second derivative of the position. So if we have the position of this string is u as a function of position and time, then the acceleration of the string at a given point and at a given time is going to be equal to some constant, traditionally written c squared, times the curvature, which is the second derivative of u with respect to x. Again, u being a function of position and time. So this is the wave equation. I should probably put a box around this because the wave equation shows up a lot in physics. This is an important one to know. But let's proceed with separation of variables. U, as a function of position and time, is going to be x, a function of, not time, x a function of position, and t a function of time. So capital X and capital T are functions of a single variable each, and their product is what we're guessing will reproduce the behavior of u. So if I substitute this u into this equation, what I end up with is the second derivative of x, t of t, with respect to time, equals c squared times the second derivative of x, t of t, with respect to position. So this hasn't really gotten us anywhere yet, but what you notice here is we have derivatives with respect to time, and then we have this function of position. Since these are partial derivatives, they're derivatives taken with everything else other than the variable that you're concerned with held constant, which means this part here, which is only a function of position, can be treated as a constant and taken outside of the derivative. The same sort of thing happens here. We have second derivatives, partial second derivatives with respect to position, and here we have only a function of time, effectively a constant for this partial derivative. Which means we can pull things out, and what we've got then is capital X. I'm going to drop the parentheses x, because you know capital X is a function of lowercase x. So you've got big X, second partial derivative with respect to time of big T, equals c squared, big T, second partial derivative of big X with respect to x. That's nice, because you can see we're starting to actually be able to pull x and t out here. And the next step is to divide both sides of this equation by xt, by basically dividing through by u. In order for this to work, we need to know that our solution is non-trivial, meaning if x and t are everywhere 0, dividing through by this will do bad things to this equation. But what you're left with after you divide by this is 1 over t, second partial of t, big T with respect to little t, and c squared 1 over big X, second partial of big X with respect to little x. This is fully separated. What that means is that the left-hand side here is a function only of t. And the right-hand side is a function only of x. That's very interesting. Suppose I write this function of t as, say, f of t. This part, let's call that g of x. I have two different functions of t and x. Normally you would say, oh, I have f of t and I have g of x, and I know what those forms are. I could, in principle, solve for t as a function of x. But that isn't what you're going to do, and the reason that's not the case is that this is a partial differential equation. Both x and t are independent variables. All of this analysis, in order for separation of variables to work, must hold at every point in space, at every x and at every time. So suppose this relationship held for a certain value of t and for a certain value of x. I ought to be able to change x and have the relationship still hold. So if I change x without changing t, the left-hand side of the equation isn't changing. If changing x led to a change in g of x, then my relationship wouldn't hold anymore. So effectively what this means is that g of x is a constant. In order for this relationship to hold, both f of t and g of x have to be constant. Essentially, what this is saying in the context of the partial differential equation is that if we look at the x part here, when I change the position, any change in the second derivative of the position function is mimicked by this 1 over x, such that the overall function ends up being a constant. That's nice, because that means I actually have two separate equations. F of t is a constant and g of x is a constant. What these equations actually look like. This was my f of x, and this was my f of t, and this was my g of x. That constant, which I've called a here, and the notation is arbitrary, though you can in principle save yourself some time by thinking ahead and figuring out what might be a reasonable value for a. What's especially nice about these is that this equation is now only an ordinary differential equation. Since big T is only a function of little t, we just have a function of a single variable. We only have a single variable here. We don't need to worry about what variables are being held constant and what variables aren't being held constant. So we can write this as total derivative with d instead of partial derivative with the partial derivative symbol. So we've reduced our partial differential equation into two ordinary differential equations. This is wonderful. And we can rearrange these things to make them a little more recognizable. You get d squared t dt squared equals a t, and c squared d squared big X d little x squared equals a times big X, multiplying through by big T in this equation and big X in this equation. And these are equations that you should know how to solve. If not, you can go back to your ordinary differential equations books, and solution to ordinary differential equations like this are very commonly studied. In this case, we're taking the second derivative of something and we're getting the something back with a constant out front. Anytime you take the derivative of something and get itself, or itself times a constant, you should think exponentials. And in this case, the solution is t equals e to the square root of a times time. If you take the second derivative of this, you'll get two square roots of a factors that come down, e times e to the root at, which is just big T. You can in principle also have a normalization constant out front, and you end up with the same sort of thing for x. Big X is going to be e to the square root of a over c x, with, again, in principle, a normalization constant out front. What that means is, if I move things up a little bit, and get myself some space, u of x and t, what we originally wanted to find, is now going to be the product of these two functions. So I have a normalization constant in front, then I have e times root a t, and e times root a over c x. Now, if this doesn't look like a wave, and that surprises you because I told you this was the wave equation, it's because we have, in principle, some freedom for what we want to choose for our normalization constant and for what we want to choose for our separation constant, this constant a. And the value of that constant will, in principle, be determined by the boundary conditions. A and a are determined by boundary conditions. The consideration of boundary conditions and initial conditions in partial differential equations is subtle, and I don't have a lot of time to fully explain it here. But if what you're concerned with is why this doesn't look like a wave equation, what actually happens when you plug in to your initial conditions and your boundary conditions to find your normalization constants and your actual value for the separation constant, you'll find that a is complex. And when you substitute in the complex value for a into these expressions, you'll end up with e to the I omega t sort of behavior, which is going to give you effectively cosine of omega t, up to some phase shifts as determined by your normalization constant and your initial conditions. So this is how we actually solve a partial differential equation. The wave equation in particular separates easily into these two ordinary differential equations, which have solutions that you can go and look up pretty much anywhere you want. Finding the actual value of the constants that match this general solution to the specific circumstances you're concerned with can be a little tricky, but in the case of the wave equation, if what you want is, say, a traveling wave solution, you can find it. There are appropriate constants that produce traveling waves in this expression. So, to check your understanding, what I'd like you to do is go through that exercise again, performing separation of variables to convert this equation into, again, two ordinary differential equations. This equation is called the heat equation, and it's related to the diffusion of heat throughout a material. If you have, say, a hot spot and you want to know how that hot spot will spread out with time. Since this is a quantum mechanics course, let's move on to the time-dependent Schrodinger equation. This is the full Schrodinger equation in all of its glory, except I've just written it in terms of the Hamiltonian operator now. H hat is the Hamiltonian. The Hamiltonian is related to the total energy. I evidently can't spell total energy of the system. Meaning it's, kinetic energy plus potential. And we have a kinetic energy operator, and we have, well, we will soon have a potential energy operator. What H hat actually looks like is it's the kinetic energy operator, which, if you recall correctly, is minus h bar squared over 2m times the second derivative with respect to position. And the potential energy operator is just it looks a lot like the position operator. It's just multiplying by some potential function, which here I'll consider to be a function of x. Now this is an operator, which means it acts on something, so I need to substitute in a wave function here. And when you do that in the context of the Schrodinger equation, you end up with the form that we've seen before. I h bar d psi dt equals minus h bar squared over 2m d squared psi dx squared plus v of x psi. So that's our Schrodinger equation. How can we apply separation of variables to this? Well, we make the same sort of guess as we made before. Namely, psi is going to be xt, where big X is a function of position and big T is a function of time. If I substitute psi equals xt into this equation, you get pretty much what you would expect. I h bar. Now when I substitute xt in here, big X, big T, big X is a function only of position, so I don't need to worry about the time derivative acting on big X. So I can pull big X out. And what I'm left with then is a time derivative of big T. This is then going to be equal to minus h bar squared over 2m times the same thing. When I substitute xt in here, the second derivative with respect to position is not going to act on the time part. So I can pull the time part out. T, second derivative of big X with respect to position. And substituting an xt here doesn't really do anything. There's no derivatives here, so this is not a particularly interesting term. So we're getting vxt. All right. Now the next step in separation of variables is to divide through by your solution, xt, assuming it's not 0, that's okay. And you end up with I h bar 1 over big T, canceling out the x, and you're just left with big T. 1 over T, partial of T dt. And then on the right-hand side, we have minus h bar over 2m, h bar squared over 2m, 1 over big X, second partial of x with respect to position, plus v. X and t are fully canceled out in this term. Now, as before, this is a function of time only, and this is a function of space only. Which means both of these functions have to be constant. And in this case, the constant we're going to use is E. And you'll see why once we get into talking about the energy in the context of the wave function. So we have our two equations. One, I h bar over t, first partial derivative of big T with respect to time, is equal to E. And on the right-hand side, from the right-hand side, we get minus h bar squared over 2m, 1 over big X, second partial of big X with respect to position, plus V is equal to the energy. So these are our two equations. Now I've written these with partial derivatives, but since, as I said before, these functions, big T and big X, are only functions of a single variable, there's effectively no reason to use partial derivative symbols. I could use d's instead of partials. Essentially, there's no difference if you only have a function of a single variable, whether you take the partial derivative or the total derivative. So, let's take these equations one by one. The first one, the time part. This we can simplify by multiplying through by big T, as before, and you end up with I h bar d big T dt equals E times t. Taking the derivative of something and getting it back, multiplied by a constant, again should suggest two exponentials. Let me move this I h bar to the other side. So we would have divided by I h bar, and 1 divided by I is minus I. So I'm going to erase this from here and say minus I in the numerator. So first derivative with respect to time of our function gives us our function back with this out front. Immediately this suggests exponentials, and indeed our general solution to this equation is some normalization constant times e to the minus I e over h bar times time. So if we know what this separation constant, capital E, is, we know the time part of the evolution of our wave function. This is good. What this tells us is that our time evolution is actually quite simple. It's in principle a complex number. T is, in principle, a complex number. It has constant magnitude. Time evolving this doesn't change the absolute value of capital T. And essentially it's just rotating about the origin in the complex plane. So if this is my complex plane, real axis, imaginary axis, wherever capital T starts, as time evolves, it just rotates around and around and around and around in the complex plane. So the time evolution that we'll be working with, for the most part, in quantum mechanics is quite simple. The space part of this equation is a little more complicated. All I'm going to be able to do now is rearrange it a little bit by multiplying through by capital X, just to get things on top, and change the order of terms a little bit to make it a little more recognizable. Minus h bar squared over 2m, second derivative of capital X with respect to position, plus v times capital X is equal to e times capital X. And this is all the better we can do. We can't solve this equation because we don't know what v is yet. V is where the physics enters this equation and where the wave function from one scenario differs from the wave function for another scenario. Essentially, the potential is where you encode the environment into the Schrodinger equation. Now, if you remember back a ways, when we were talking about the Schrodinger equation on the very first slide of this lecture, what we had was the Hamiltonian operator acting on the wave function. And this is that same Hamiltonian. This is h hat, not acting on psi now, just acting on x. So you can also express the Schrodinger equation as h times x equals e times x. The Hamiltonian operator acting on your spatial part is the energy of, is the separation constant E, which is related to the energy, times the spatial part. So this is another expression of the Schrodinger equation. This equation itself is called the time-independent Schrodinger equation, or TISE if I ever use that abbreviation. And this is really the hard part of any quantum mechanics problem. To summarize what we've said so far, starting with the Schrodinger equation, which is this: time derivatives with complex parts in terms of Hamiltonians and wave functions gives you this, substituting in the actual definition of the Hamiltonian, including a potential V. And applying separation of variables gets us this pair of ordinary differential equations. The time part here gave us numbers that just basically spun around in the complex plane. Not the imaginary part. This is traditionally the real part, and this is the imaginary part. So the time evolution is basically rotation in the complex plane. And the spatial part, well, we have to solve this equation being the time-independent Schrodinger equation. We have to solve this for a given potential. The last comment I want to make in this lecture is a comment about notation. My notation is admittedly sloppy, and if you read through the chapter, Griffiths calls my notation sloppy. In Griffiths, since it has the luxury of being a book and not the handicap of having my messy handwriting, they use capital psi to denote the function of x and time. And when they do separation of variables, they re-express this as lowercase psi as a function of position and lowercase phi as a function of time. So for this, I used capital X. Sorry, I should put things in the same order. I used capital T of t and capital X of x, because I have a better time distinguishing my capital letters from my lowercase letters than trying to, well, you saw how long it took me to write that symbol. I'm not very good at writing capital psis. There is a lot of sloppiness in the notation in quantum mechanics, namely because, oops, geez, I have two functions of time. This is Griffiths' function of position. Sorry about that. This here and this here, these are really the interesting parts, the functions of position, the solutions to the time-independent Schrodinger equation. What that gives us, well, what that means is that a lot of people are sloppy with what they call the wave function. This is the wave function. This is the spatial part, or the solution to the time-independent Schrodinger equation. This is not the wave function. But, I mean, I've already made this sloppy mistake a couple of times in problems that I've given to you guys in class. Namely, I'll ignore the time domain part and just focus on the spatial part, since that's the only interesting part. So, perhaps that's my mistake. Perhaps I need to relearn my handwriting. But, at any rate, be aware that Sometimes I, or perhaps even Griffiths, or whoever you are talking to, will use the term the wave function when they don't actually intend to include the time dependence. And the time dependence is, in some sense, easy to add on because it's just this rotation in complex number space. But hopefully things will be clear from the context what is actually meant by the wave function. So we're still moving toward solutions to the Schrodinger equation. And the topic of this lecture is what you get from separation of variables and the sorts of properties it has. To recap what we talked about last time, the Schrodinger equation, I h bar partial derivative of psi with respect to time is equal to minus h bar squared over 2m second partial derivative of psi with respect to position plus v times psi, where this is essentially the kinetic energy and this is the potential energy as part of the Hamiltonian operator. We were able to make some progress towards solving this equation by writing psi, which is in principle a function of position and time, as some function of position multiplied by some function of time. Why did we do this? Well, it makes things easier. We can make some sort of progress, but haven't we restricted our solution a lot by writing it this way? Well, really we have, but it does make things easier, and it turns out that these solutions that are written as products that result from solving the ordinary differential equations you get from separation of variables with the Schrodinger equation can actually be used to construct everything that you could possibly want to know. So let's take a look at the properties of these separated solutions. First of all, these solutions are called stationary states. What we've got is psi as a function of position and time is equal to some function of position multiplied by some function of time. And I wrote that as capital T on the last slide, but if you remember from the previous lecture, the time evolution equation was solvable, and what it gave us was a simple exponential, e to the, minus I times e times t divided by h bar. So this is our time evolution part, and this is our spatial part. What does it mean for these states to be stationary? Well, consider, for instance, the probability density for the outcome of position measurements. Hopefully you remember this is equal to the squared absolute magnitude of psi, which is equal to the complex conjugate of psi times psi. Now if I plug this in for psi and its complex conjugate, I end up with the complex conjugate of big X as a function of position times the complex conjugate of this. And the only part that's complex about this is the I here in the exponent, so we need to flip the sign on that. And we'll have e to the I, positive I now, e t over h bar. That's for the complex conjugate of psi. And for the psi itself, well, x of x e to the minus I e t over h bar. Now, multiplying these things together, there's nothing special about the multiplication here, and this are complex conjugates of each other, so they multiply together to give the magnitude of, the squared magnitude of each of these numbers together, which, since these are just complex exponentials, is magnitude 1. So what we end up with here is x star x. Essentially the squared magnitude of just the spatial part of the wave function. There's now no time dependence here, which means the probability density here does not change as time evolves. So that's one interpretation of these, or one meaning of these things being called stationary states. The fact that I can write a wave function as a product like this, and the only time dependence here comes in a simple complex exponential, means that that time dependence drops out when I find the probability distribution. Another interpretation of these things as stationary states comes from considering expectation values. Suppose I want to calculate the expectation value of some generic operator, capital Q. The expression for the expectation of an operator is an integral of the wave function times the operator acting on the wave function. So complex conjugate wave function, operator, wave function. Now I'm going to go straight to the wave function as expressed in terms of x and t parts. So complex conjugate of the spatial part times the complex conjugate of the time part, which from the last slide is e to the plus I e t over h bar. Our operator gets sandwiched in between the complex conjugate of the wave function and the wave function itself. So this is again, no stars anymore, come on Brent, just x and then e to the minus I e t over h bar. And this is all integrated dx. So this is psi star, and this is psi. And this is our operator sandwiched between them, as in the expression for the expectation. Now, provided this operator does not act on time, it doesn't have anything to do with the time coordinate, and that will be true for basically all of the operators we will encounter in this course. Now, we talked about how the Schrodinger equation can be split by separation of variables into a time-independent Schrodinger equation and a relatively simple time-dependent part. What that gave us is, provided we have solutions to that time-independent Schrodinger equation, we have something called a stationary state. And it's called a stationary state because nothing ever changes. The probability densities are constant, the expectation values are constant, and the state effectively, since it has a precise, exact, no uncertainty energy, has to live for an infinite amount of time. That doesn't sound particularly useful. From the perspective of physics, we're often interested in how things interact and how things change with time. So how do we get things that actually change with time in a non-trivial way? Well, it turns out that these stationary states, while their time dependence is trivial, the interaction of their time dependence when added together in a superposition is not trivial. And that's where the interesting time dynamics of quantum mechanics comes from. Superpositions of stationary states. Now we can make superpositions of stationary states because of one fundamental fact, and that fact is the linearity of the Schrodinger equation. So the Schrodinger equation, as you hopefully remember it by now, is I h bar partial derivative of psi with respect to time is equal to minus h bar squared over 2m second derivative of psi with respect to x, and that's a really ugly psi. Must fix. Second derivative of psi with respect to position plus v times psi. So this is our Hamiltonian operator applied to the wave function, and this is our time dependence part. Now, in order for an equation to be linear, what that means is that if psi solves the equation, psi plus some other psi that also solves the equation will solve the equation. So if, say, let's call it A, solves the Schrodinger equation, and B solves the Schrodinger equation, and let me write this out in a little more detail. First of all, I'm talking about A is a function of position and time, as is B. If A and B both solve the Schrodinger equation, then A plus B must also solve the Schrodinger equation. And we can see that pretty easily. Let's substitute psi equals A plus B into this equation. The first step, I h bar partial derivative with respect to time of A plus B is equal to minus h bar squared over 2m second partial derivative with respect to space of A plus B plus the potential V times A plus B. Now the partial derivative of the sum is the sum of the partial derivatives. That goes for the second partial derivative as well. And well, this is just the product of the potential with the sum is the sum of the product of the potential with whatever you're multiplying out. I'm going to squeeze things a little bit more here. So I can write that out. I h bar d by dt of A plus I h bar dB dt equals minus h bar squared over 2m second derivative of A with respect to space, forgot my squared on the second derivative, minus h bar squared over 2m second derivative of B with respect to position, plus v times a plus v times b. That's just following those fundamental rules. Now, you can probably see where this is going. This, and this. These three terms together make up the Schrodinger equation, the time-dependent Schrodinger equation for A. For A. For A. And this, and this altogether, that's the time-dependent Schrodinger equation for B. So if A satisfies the time-dependent Schrodinger equation, which is what we supposed when we got started here, then this term, and this term will cancel out. They will obey the equality. Likewise, for the parts with B in them. So essentially, if A solves the Schrodinger equation and B solves the Schrodinger equation, A plus B also solves the Schrodinger equation. And the reason for that is the partial derivatives here. The partial derivative of the sum is the sum of the partials, and the product with the sum is the sum with the products. These are linear operations, so we have a linear partial differential equation, and the linearity of the partial differential equation means, well, essentially that if A solves and B solves, then A plus B will also solve it. That allows us to construct solutions that are surprisingly complicated. And actually, the general solution to the Schrodinger equation is psi of position and time is equal to the sum, and I'm going to be vague about the sum here. You're summing over some index j, x sub j, as a function of position. These are solutions now to the time-independent Schrodinger equation, the spatial part of the Schrodinger equation, times your time part. And we know the time part from the, well, from back from when we discussed separation of variables, is minus I, e, now this is going to be e sub j, t, over h bar. So this is a general expression that says we're summing up a whole bunch of stationary state solutions to the time-independent Schrodinger equation. And we're getting psi. No, oh, I've left something out, and what I've left out is quite important here. We need some constant, c sub j, that tells us how much of each of these stationary states to add in. So this is actually, well, it's going to be a solution to the Schrodinger equation since it's constructed from solutions to the Schrodinger equation. And this is completely general. That's a little surprising. What that means is that this can be used to express not just a subset of solutions to the Schrodinger equation, but all possible solutions to the Schrodinger equation. All the solutions to the Schrodinger equation can be written like this. That's a remarkable fact. And it's certainly not guaranteed. You can't just write down any old partial differential equation, apply separation of variables, and expect the solutions that you get to be completely general and superposable to make any solution you could possibly want. The reason this works for the Schrodinger equation is because the Schrodinger equation is, well, just to drop some mathematical terms if you're interested in looking up information later on, the Schrodinger equation is an instance of what's called a Sturm-Liouville problem. Sturm-Liouville problems are a class of linear operator equations, for instance, partial differential equations or ordinary differential equations, that have a lot of really nice properties. And this is one of them. So the fact that the Schrodinger equation is a Sturm-Liouville equation, or the fact that the time-independent Schrodinger equation is a Sturm-Liouville equation, means that this will work. So if you go on to study, advanced mathematical analysis methods in physics, you'll learn about this. But for now, you just need to sort of take it on faith that general solutions to the Schrodinger equation look like this. superpositions of stationary states. So if we can superpose stationary states, what does that actually get us? One example I would like to do here is, and this is just an example of the sorts of analysis you can do given superpositions of stationary states, is to consider the energy. Suppose I have two solutions to the time-independent Schrodinger equation, which I'm just going to write as h hat x1 equals E1 x1, and h hat x2 equals E2 x2. So x1 and x2 are solutions to the time-independent Schrodinger equation, and they're distinct solutions. E1 not equal to E2. I'm going to use these to construct a wave function, let's say psi, of x, and at time t equals 0, let's say it looks like this. C1 times x1 as a function of position plus. Quantum mechanics is really all about solving the Schrodinger equation. That's a bit of an oversimplification, though, because if there was only one Schrodinger equation, we could just solve it and be done with it, and that would be it for quantum mechanics. The reason this is difficult is that the Schrodinger equation isn't just the Schrodinger equation. There are many Schrodinger equations. Each physical scenario for which you want to apply quantum mechanics has its own Schrodinger equation. They're all slightly different, and they all require slightly different solution techniques. And the reason there are many different Schrodinger equations is that the situation under which you want to solve the Schrodinger equation enters the Schrodinger equation as a potential function. So let's talk about potential functions and how they influence, well, the physics of quantum mechanics. First of all, where does potential appear in the Schrodinger equation? This is the time-dependent Schrodinger equation, and the right-hand side here, you know, is giving the Hamiltonian operator acting on the wave function. Now the Hamiltonian is related to the total energy of the system, and you can see that by looking at the parts. This is the kinetic energy, which you can think of as the momentum operator squared over 2m, sort of a quantum mechanical analog of p squared over 2m in classical mechanics. And the second piece here is, in some sense, the potential energy. This v of x is the potential energy as a function of position. As if this were a purely classical system. For instance, if the particle was found at a particular position, what would be its potential energy? That's what this function v of x encodes. Now we know in quantum mechanics we don't have classical particles that can be found at particular positions. Everything is probabilistic and uncertain, but you can see how this is related. This is the time-dependent Schrodinger equation, which is a little bit unnecessarily complicated. Most of the time, we work with the time-independent Schrodinger equation, which looks very similar. Again, we have a left-hand side given by the Hamiltonian. We have a kinetic energy here, and we have a potential energy here. If we're going to solve this time-independent equation, note now that the wave functions here are expressed only as functions of position, not as functions of time. This operator gives you the wave function itself back multiplied by e, which is just a number. This came from the separation of variables. It's just a constant, and we know from considering the expectation value of the Hamiltonian operator, which is related to the energy, for solutions to this time-independent Schrodinger equation, that we know this is essentially the energy of the state. Now, what does it mean here in this context, or in this potential context? Well, you have a potential function of position, and you have psi, the wave function. So this v of x psi of x, if that varies as a function of position, and it will, if the wave function has a large value, a large magnitude in a certain region, and the potential has a large value in a certain region, that means that there is some significant probability the particle will be found in a region with high potential energy. That will tend to make the potential energy of the state higher. Now, if psi is 0 in some region where the potential energy is high, that means the particle will never be found in a region where the potential energy is high. That means the state likely has a lower potential energy. This is all a very sort of heuristic qualitative argument, and we can only really do better once we know what these solutions are and what these actual potential functions look like. What I'd like to do here before we move on is to rearrange this a little bit to show you what effect the potential energy related to the energy and how it's related to the energy of the state, what effect that has on the wave function. And in order to do that, I'm going to multiply through by this h bar squared over 2m and rearrange terms a little bit. What you get when you do that is the second derivative of psi with respect to x. There's my eraser. With respect to x being equal to 2m over h bar squared times v of x minus e psi. So this quantity here relates the second derivative of psi to psi itself. For instance, if the potential is larger than the energy of the state, you'll get one overall sign relating the second derivative in psi, whereas if energy is larger than potential, then you'll end up with a negative quantity here relating the second derivatives of psi with itself. So keep this in the back of your mind, and let's talk about some example potential functions. This is what we're going to be doing, or this is what the textbook does in all of Chapter 2. Write different potential functions and solve the Schrodinger equation. The first example potential we do, and this is section 2.2, is what I like to call the particle in a box. The textbook calls it an infinite square well. The particle in a hard box, for instance, you can think of as a potential function that looks like this. Get myself some coordinate systems here. You have a potential function v of x, oops, turn off my ruler, that looks something like this. This is v of x as a function of x. The potential goes to infinity for x larger than some size. Let's call this, minus a to a. If you're inside minus a to a, you have zero potential energy. If you're outside of a, you have infinite potential energy. It's a very simple potential function. It's a little bit non-physical, though, because, well, infinite potential energy, what does that really mean? It means it would require infinite energy to force the particle beyond A. If you had some infinitely dense material that just would not tolerate the electron ever being found inside that material, and you made a box out of that material, this is the sort of potential function you would get. Much more realistically, we have the harmonic oscillator potential. The harmonic oscillator potential is the same as what you would get in classical physics. It's a parabola. This is something, proportional to x squared. V of x being proportional to x squared is what I mean. This is what you would get if you had a particle attached to a spring connected to the origin. If you move the particle to the right, you stretch the spring. Put quantum mechanically, if you happen to find the particle at a large displacement from the origin, the spring would be stretched quite a large amount and would have a large amount of potential energy associated with it. From a more physical, down-to-earth sort of perspective, this is what happens when you have any sort of equilibrium position for a particle to be in. The particle is sitting here near the origin where there is a flat potential, but any displacement from the origin makes the potential tend to increase in either direction. This is like an electron in a particle trap, or an atom in a particle trap. Harmonic oscillator potentials show up all over the place, and we'll spend a good amount of time talking about them. The next potential that we consider is the delta function potential. And what that looks like, now I'm going to start at 0 and draw it going negative, but it's effectively an infinitely sharp, infinitely deep version of this particle in a box potential. Instead of going to infinity outside of your realm, it's at 0, and instead of being at 0 inside your realm, it goes to minus infinity there. This now continues downwards. It doesn't bottom out here. The overall behavior will be different now because the particle is no longer disallowed from being outside of the domain. There is no longer an infinite potential energy here. And we'll talk about that as well. These are all sort of weird, non-physical potentials. The particle in a soft box potential is a little bit more physical. If I have my coordinate system here, A particle in a soft box potential looks something like this. To keep things simple, it still changes instantaneously at, say, minus A and A, but the potential energy is no longer infinity. This is, for instance, a box made out of a material that has some pores in it, and the electron, or whatever particle you're considering to be in the box, doesn't like being in those pores. So there's some energy you have to add in order to push the particle in. Once it's in, it doesn't really matter where it is, you've sort of made that energy investment to push the particle into the box. And we'll talk about the quantum mechanical states that are allowed by this potential as well. Finally, we will consider what happens when there's no potential at all. Essentially, your potential function is constant. That actually has some interesting implications for the form of the solutions of the Schrodinger equation. And we'll talk about that in more detail. To map this onto textbook sections, this is section 2.2. The harmonic oscillator is section 2.3. The delta function potential is section 2.5. The particle in a box is section 2.6. Particle in a soft box is 2.6. And particle with no potential, or an overall constant potential everywhere in space, is section 2.4. So these are some example potentials that we'll be talking about in this chapter. What do these potentials actually mean, though? How do they influence the Schrodinger equation and its solutions? Well, the way I wrote the Schrodinger equation a few slides ago, second derivative of psi with respect to x is equal to 2m over h bar squared, just a constant, times v of x minus e psi. This is now the time-independent Schrodinger equation, so we're just talking about functions of position here. And E, keep in mind, is the energy of the state. If we're going to have a solution to the time-independent Schrodinger equation, this E exists, and it's just a number. So what does that actually mean? Let's think about it this way. We have a left-hand side determined by the right-hand side of this equation. And the left-hand side is just the second derivative with respect to position of the wave function. This is related to the curvature of the wave function. I could actually write this as a total derivative, since this is just psi is only a function of position now. So there's no magic going on with this partial derivatives. It's going to behave same as the ordinary derivative that you're used to from calculus class. The second derivative is related to the concavity of a function, whether something's concave up or concave down. So let's think about what this means. If you have a potential v of x that's greater than your energy, if v of x is greater than e, what does that mean? That means v of x minus e is a positive quantity. That means the right-hand side here will have whatever sign psi has. And I'm being a little sloppy since psi here is in general a complex function. But if we consider it to just be, say, positive, which isn't as meaningful for a complex number as it is for a real number, you would have psi of x. If psi of x is positive and this number is positive, then the second derivative is positive. Which means that if psi is, say, here, psi is positive, when it's multiplied by is positive, then the second derivative is positive. It curves like this. Whereas if psi is down here, psi is negative, this is positive, second derivative of psi is negative. It curves like this. What this means is that psi curves away from our axis, away from this psi equals 0 line. On the other hand, if v of x is less than the energy, this quantity will be negative, and we get the opposite behavior. If psi is up here, positive, it's multiplied by a negative number, and the second derivative is negative, you get something that curves downwards. If psi is on the other side of the axis, it curves upwards. Psi curves toward the axis. So this helps us understand a little bit about the shape of the wave function. For instance, let me do an example here in a little bit more detail. Suppose I have, I'll do it over here, coordinate system. If I have a potential function, let's do the sort of soft particle in a box. I can do better than that. Soft particle in a box. So v of x is constant outside your central region and constant inside your central region and has a step change at the boundaries of your region. Let's think about what our wave function might look like under these circumstances. So we have our boundaries of our region here. The other thing that we need to know to figure out what the wave function might look like is a hypothetical energy. And I'm just going to set an energy here. I'm going to do the interesting case. Let's say this is the energy. And I'm plotting energy on the same axis as the potential, which is fine. This is the energy of the state. This is the potential energy as a function of position, so they have the same units. What this energy hypothetically means is that outside here, the potential energy is greater than the energy of the state, and inside here, the potential energy is less than the energy of the state. So we'll get different signed sort of behaviors, different curvatures of the wave function. So, do my wave function in blue here. If I say, start my wave function, this is all hypothetical now, this may not work. If I start my wave function here, at some point on the positive side of the axis, at the origin, we know the energy of the state is larger than the energy of, or than the potential energy. So this quantity is negative, and psi curves towards the axis. So since psi is positive here, I'm looking at this sort of curvature. So I could draw my wave function out sort of like this. Maybe that's reasonable, maybe that's not. This is obviously not a quantitative calculation. This is just sort of the sort of curvature that you would expect. Now, I only continued these curving lines out to the boundaries, since at the boundaries, things change. Outside our central region here, the potential energy is larger than the energy of the state, and you get curvature away from the axis. What might that look like? Well, something curving away from the axis. It's going to look sort of like that. But where do I start it? Do I start it going like that? Do I start it going like that? What does this actually look like? Well, if you think about this, we can say a little bit more about what happens to our wave function when it passes a boundary like this. And the key fact is that if v of x is finite, then while we might have the second derivative of psi with respect to x being discontinuous, maybe, might not be. In this case, the second derivative of psi is just set by this difference. So when we have a discontinuity in the potential, we have a discontinuity in the second derivative. The first derivative of psi will be continuous. Think about integrating a function that looks like this. I integrate it once, I get something maybe with large positive slope going to slightly smaller positive slope. There will be no discontinuity in the first derivative. What this means for psi is that it's effectively smooth. And that by that I just sort of mean no corners. The first derivative of psi won't ever show a corner like this. It will be something like that, for example. No sharp corners to it. What that means in the context of a boundary like this is that if I have psi going downwards at some angle here, I have to keep that angle as I cross the boundary. Now once I'm on the other side of the boundary here, I have to curve. And I have to curve according to the rules that we had here. So depending on what I actually chose for my initial point here and what the actual value of the energy was and what the actual value of the potential is outside in this region, I may get differing degrees of curvature. I may get something that happens like this, curves up very rapidly, or I may get something that doesn't curve very rapidly at all. Perhaps it's curving upwards very slowly, but it crosses the axis. Now, as it crosses the axis, the sign on psi here changes. The curvature is also determined by psi. As psi gets smaller and smaller, the curvature gets smaller and smaller, the curvature becoming 0 as psi crosses the axis. Then when psi becomes negative, the sign of the curvature changes, so this would start curving the other direction, curving downwards. It turns out that there is actually a state right in the middle, sort of a happy medium state, where psi curves, and just kisses the axis. Comes towards the axis, and when it comes towards the axis and reaches the axis with 0 slope and 0 curvature, it's stuck. It will never leave the axis again. And these are the sorts of states that you might actually associate with probability distributions. You know, if psi is blowing up like this, going to positive infinity or to negative infinity, that your wave function will not be normalizable. But the wave function here, denoted by these green curves, has finite area, therefore is sort of normalizable. So these are the sorts of things that the potential function tells you about the wave function. In general, what direction it curves, how much it curves, and how quickly. And of course, doing this quantitatively requires a good deal of mathematics. But I wanted to introduce the math, or before I introduce the math, I wanted to give you some conceptual framework with which to understand what exactly this potential means. If the potential is larger than the energy, you expect things that curve upwards. And when you get things that curve upwards, you'll have, or curve away from the axis, you tend to have things blow up unless they just sort of go down and kiss the axis like this. So there will be a lot of things approaching the axis and never leaving, so that we have normalizable wave functions. On the other hand, if the potential energy is less than the energy of the state, you get things that curve towards. And well, if you have something that curves towards, it tends to do this. Always curving towards, always curving towards, always curving towards the axis. You get these sort of wave-like states. So that's a very hand-waving discussion of the sorts of behavior you get from, in this case, step discontinuous potential. And we'll see this sort of behavior throughout this chapter. To check your understanding, take this step discontinuous potential and tell me which of these hypothetical wave functions is consistent with the Schrodinger equation. Now, I did not actually go through and solve the Schrodinger equation here to make sure these things are quantitatively accurate. They're probably all not quantitatively accurate. What I'm asking you to do here is identify the sort of qualitative behavior of these systems. Is the curvature right? And let's see. Yeah, are the boundary conditions right? In particular, does the wave function behave as you would expect as it passes from the sort of interior region to the exterior region? We've been talking about solving the Schrodinger equation and how the potential function encodes the scenario under which we're solving the Schrodinger equation. The first real example of a solution to the Schrodinger equation and a realistic wave function that we will get comes from this example, the infinite square well, which I like to think of as a particle in a box. The infinite square well is called that because its potential is infinite and, well, square. What the potential ends up looking like is, if I plot this, going from 0 to A, the potential is infinity if you're outside the region between 0 and A, and at 0 if you're in between the region, if you're in between 0 and A. So what does this look like when it comes to the Schrodinger equation? Well, what we'll be working with now is the time-independent Schrodinger equation, the TISE, which reads minus h bar squared over 2m times the second derivative of, I'm getting ahead of myself, the second derivative of psi with respect to x plus potential as a function of x times psi is equal to the energy of the stationary state that results from the solution of this equation times psi. Now, this equation doesn't quite look right if we're outside the region. Bad things happen. You end up with an infinity here for v of x if x is not between 0 and a. The only way this equation can still make sense under those circumstances is if psi of x is equal to 0, if x is less than 0 or x is greater than a. So outside this region, we already know what our wave function is going to be. It's going to be 0, and that's just a requirement on the basis of infinite potential energy. Can't really exist in the real world. Now, what if we're inside? Then v of x is 0, and we can cancel this entire term out of our equation. What we're left with then is minus h bar squared over 2m, second partial derivative of psi, with respect to x, is equal to e times psi, just dropping that term entirely. So this is the time-independent Schrodinger equation that we want to solve. So how do we solve it? Well, we had minus h bar squared over 2m times the second derivative of psi with respect to x being equal to e times psi. We can simplify that just by rearranging some constants. What we get, minus second derivative of psi with respect to x equal to minus k squared psi. And this is the sort of little trick that people solving differential equations employ all the time. Knowing what the solution is, you can define a constant that makes a little more sense, in this case using a square for k instead of just some constant k. But in this circumstance, k is equal to root 2m times e over h bar. So this is our constant, which you just get from rearranging this equation. This equation you should recognize. This is the equation for a simple harmonic oscillator, a mass on a spring, for instance. Now, as I said before, the partial derivatives here don't really matter. We're only talking about one dimension, and we're talking about the time-independent Schrodinger equation, so the wave function here, psi, is just a function of x, not a function of x in time. So this is the ordinary differential equation that you're familiar with for things like masses on springs. And what you get is oscillation. Psi, as a function of x, is going to be a sine kx plus b cosine kx. And that's a general solution. A and b here are constants, to be determined by the actual scenario under which you're trying to solve this equation. This equation now, not the original Schrodinger equation. So these are our solutions. Sines and cosines. Sines and cosines. That's all well and good, but that doesn't actually tell us what the wave function is because, well, we don't know what a is, we don't know what b is, and we don't know what k is either. We know k in terms of the mass of the particle that we're concerned with, Planck's constant, and the E separation constant we got from deriving the time-independent Schrodinger equation. While that might be related to the energy, we don't know anything about these things. These are free parameters still. But we haven't used everything we know about the situation yet. In particular, we haven't used the boundary conditions. And one thing the boundary conditions here will determine is the form of our solution. Now, what do I mean by boundary conditions? Well, the boundary conditions are what you get from considering the actual domain of your solution and what you know about it, in particular at the edges. Now, we have a wave function that can only be non-zero between 0 and a. Outside that, it has to be 0. So we know right away our wave function is 0 here and 0 here. So whatever we get for those unknown constants, a, b, and k, it has to somehow obey this. We know a couple of things about the general form of the wave function. In particular, just from consideration of things like the Hamiltonian operator or the momentum operator, we know that the wave function itself, psi, must be continuous. We can't have wave functions that look like this. And the reason for that is this discontinuity here would do very strange things to any sort of physical operator that you could think of. For example, the momentum operator is defined as minus I h bar partial derivative with respect to x. The derivative with respect to x here would blow up and we would get a very strange value for the momentum. That can cause problems. By sort of contradiction then, the wave function itself must be continuous. We'll come back to talking about the boundary conditions on the wave function later on in this chapter, but for now, all we need to know is that the wave function is continuous. What that means is that since we're 0 here, we must go through 0 there, and we must go through 0 there, since we're 0 here. So, what that means, wrong color, means psi of 0 is equal to 0, and psi of a is equal to 0. What does that mean for our hypothetical solution psi of x equals a sine kx plus b cosine kx? Well, first of all, consider this one. The wave function at 0 equals 0. When I plug 0 into this, the sine of 0, k times 0 is going to be 0. The sine of 0 is 0, but the cosine of 0 is 1. So what I'll get if I plug in 0 for psi is 1 times b. So I'll get b. Now if I'm going to get 0 here, that means b must be equal to 0. So we have no cosine solutions. No cosine part to our solutions. So everything here is going to start like sines. It's going to start going up like that. That's not the whole story, though, because we also have to go through 0 when we go through a. So if I plug a into this, what I'm left with is psi of a is equal to capital A times the sine of ka. If this is going to be equal to 0, then I know something about ka. In particular, the sine function goes through 0 for particular values of particular values of its argument. Sine of x is 0 for x equals integer multiples of pi. What that actually looks like on our plot here is things like this. Our wave functions are going to end up looking like this. So let me spell that out in a little more detail. Our psi of a wave function is a times the sine of k times a. And if this is going to be equal to 0, ka has to be either 0, plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, etc. This is just coming from all of the places where the sine of something crosses 0, crosses the axis. Now it turns out this is not interesting. This means psi is 0 everywhere, since the sine of 0 is, well, sine k times a. If ka is going to be 0, then everything. If ka is 0, k is 0. So the sine of k times x is going to be 0 everywhere. So that's not interesting. This is not a wave function that we can work with. Another fact here is that these plus or minuses, the sine of minus x is equal to minus the sine of x. Sine is an odd function. Since what we're looking at here has a normalization constant out front, we don't necessarily care whether there's a plus or a minus sign coming from the sine itself. We can absorb that into the normalization constant. So essentially what we're working with then is that Ka equals pi, 2 pi, 3 pi, etc., which I'll just write as n times pi. Now if k times a is going to equal n times pi, we can figure out what, well, let's just substitute in for k, which we had a few slides ago was root 2m capital E over h bar. So that's k. K times a is equal to n pi. This is interesting. We now have integers coming from n here as part of our solution. So we're no longer completely free. We in fact have a discrete set of values. Now a, that's a property of the system. We're not going to solve for that. M, that's a property of the system. H bar, that's a physical constant. The only thing we can really solve for here is E. So let's figure out what that tells us about E. And if you solve this for E, you end up with n squared pi squared h bar squared over 2m a squared. This is a discrete set of allowed energies. I keep talking about solutions to the time-independent Schrodinger equation and how they have nice mathematical properties. What that actually means is, well, what I'm referring to are the orthogonality and completeness of solutions to the time-independent Schrodinger equation. What that actually means is the topic of this lecture. To recap, first of all, these are what our stationary states look like for the infinite square well potential. This is the potential such that v of x is infinity if x is less than 0 or x is greater than a, and 0 for x in between 0 and a. So if this is our potential, you express the time-independent Schrodinger equation, you solve it, you get sine functions for your solutions. You properly apply the boundary conditions, namely that psi has to go to 0 at the ends of the interval because the potential goes to infinity there. And you get n pi over a times x as your argument to the sine functions. And you normalize them properly, you get a square root of 2 over a out front. The energies associated with these wave functions, and this energy now is the separation constant in the conversion from the time-dependent Schrodinger equation to the time-independent Schrodinger equation, are proportional to n, that index. The wave functions themselves look like sine functions, and they have an integer number of half wavelengths, or half cycles, in between 0 and a. So this orange curve, this is n equals 1. The blue curve is n equals 2. The purple curve is n equals 3. And the green curve is n equals 4. If you calculate the squared magnitude of the wave functions, they look like this. 1 hump for n equals 1. 2 humps for the blue curve, n equals 2. 3 humps for the purple curve, n equals 3. And 4 humps for the green curve, n equals 4. So you can see just by looking at these wave functions that there's a lot of symmetry. One thing we talked about in class is that these wave functions are either even or odd about the middle of the box, and this is a consequence of the potential being an even function about the middle of the box. If I draw a coordinate system here, going between 0 and a, either the wave functions have a maximum or they have a 0 at the middle of the box. So for n equals 1 we have a maximum, for n equals 2 we have a 0. And this pattern continues. The number of nodes is another property that we can think about. And this is the number of points where the wave function goes to 0. For instance, the blue curve here for n equals 2 has 1 node. This trend continues as well if I have a wave function that, for instance, let me draw it in some absurd color, has 1, 2, 3, 4, 5, 6, 7 nodes. You know this would be for n equals 8. This would be sort of like the wave function for n equals 8. These symmetry properties are nice. They help you understand what the wave function looks like, but they don't really help you calculate. what helps you calculate are the orthogonality and completeness of these wave functions. So what does it mean for two functions to be orthogonal? Let's reason at this from a perspective which you're more familiar, the orthogonality of vectors. We say two vectors are orthogonal if they're at 90 degrees to each other, for instance. So if I had a two-dimensional coordinate system, and one vector pointing in this direction, let's call that A, and another vector pointing in this direction, let's call that B, I would say those two vectors are orthogonal if they have a 90-degree angle separating them. Now that's all well and good in 2 dimensions. It gets a little harder to visualize in 3 dimensions, and, well, what does it mean for two vectors to be separated by 90 degrees if you're talking about a 17-dimensional space? In higher dimensions like that, it's more convenient to define orthogonality in terms of the dot product. And we say two vectors are orthogonal in that case if the dot product of those two vectors is 0. Now in 2 dimensions, you know the dot product is given by the x components of both vectors, ax times bx, plus the y component of those two vectors multiplied together, ay times by. If this is 0, we say these two vectors are orthogonal. In 3 dimensions, we can say plus az times bz. And if this is equal to 0, we say the vectors are orthogonal. And you can continue this multiplying together like components, or same dimension of the components of vectors in each dimension, multiplying them together. a1, b1, a2, b2, a3, b3, a4, b4, all added up together. And if this number is 0, we say the vectors are orthogonal. We can extend this notion to functions. But what does it mean to multiply two functions like this? In the case of vectors, we were multiplying like components, both x components, both y components, both z components. In the case of functions, we can multiply both functions' values at particular x coordinates and add all those up. And what that ends up looking like is an integral. Say the integral of f of x, g of x, dx. So I'm scanning over all values of x instead of scanning over all dimensions, and I'm multiplying the function values at each individual point, at each individual x, together, and adding them all up, instead of multiplying the components of each vector together at each individual dimension and adding them all up. The overall concept is the same, and you can think about this as, in some sense, a dot product of two functions. Now in quantum mechanics, since we're working with complex functions, it turns out that we need to put a complex conjugate here on f in order for things to make sense. This should start to look familiar now. You've seen expressions like the integral of psi star of x times psi of x dx is equal to 1, our normalization condition. This is essentially the dot product of psi with itself. Psi, of course, is not orthogonal to itself, but it is possible to make a pair of functions that are orthogonal. And we say functions are orthogonal if orthogonal. So, we've been working with solutions to the time-independent Schrodinger equation for the infinite square well potential, the particle in a box case. How do these things actually work, though? In order to give you guys a better feel for what the solutions actually look like and how they behave, I'd like to do some examples and use a simulation tool to show you what the time evolution of the Schrodinger equation in this potential actually looks like. So, the general procedure that we've followed or will be following in this lecture is, once we've solved the time-independent Schrodinger equation, we get the form of the stationary states. Knowing the boundary conditions, we get the actual stationary states, the stationary state wave functions and their energies. These can then be normalized to get true stationary state wave functions that we can actually use. These stationary state wave functions will, for the most part, form an orthonormal set, psi sub n of x. We can add the time part, knowing the time-dependent Schrodinger equation, or the time part that we got when we separated variables in the time-dependent Schrodinger equation. We can then express our initial conditions as a sum of these stationary state wave functions and use this sum then to determine the behavior of the system. So what does that actually look like in the real world? Not like very much, unfortunately, because the infinite square well potential is not very realistic, but a lot of the features that we'll see in this sort of potential will appear in more realistic potentials as well. So this is our example. These are our stationary state wave functions. This is what we got from the solution to the time-independent Schrodinger equation. This was the form of the stationary states, these were the energies, and then this was the normalized solution with the time dependence added back on, since the time dependence is basically trivial. The initial conditions that I'd like to consider in this lecture are the wave function evaluated at 0 is either 0 if you're outside the, this should be A. If you're outside the domain, you're 0. If you're inside the domain, you have this properly normalized wave function. We have an absolute value in this, which means this is a little difficult to work with. But what the plot actually looks like, if I draw a coordinate system here, going from 0 to A, is this. It's just a tent, a properly built tent with straight walls going up to a nice peak in the middle. Our general procedure suggests that we express this initial condition in terms of these stationary states with their time dependence, and that will tell us everything we need to know. One thing that will make this a little easier to work with is getting rid of the absolute values we have here. So let's express psi of x time t equals 0 as a three-part function. First, we have root 3 over a 1 minus. Now what we should substitute in here is what we get if, say, 0 is less than x is less than a over 2. Sort of the first half interval going out to a over 2 here. In this case, we have something sloping upwards, which is going to end up, in this context, being 1 minus a over 2 minus x over a over 2. So, to say another word or two about that, if x is less than a over 2, this quantity here will be negative. So I can get rid of the absolute value if I know that this quantity in the numerator is positive. So I multiply the quantity in the numerator by a minus sign, which I can express more easily just by writing it as a over 2 minus x. A over 2 minus x. That will then ensure that this term here is positive for x's in this range. 1 minus that is then this term in our wave function. For the other half of the range, root 3 over a 1 minus something, and this is now from a over 2 is less than x is less than a, the second half of the interval. For the second half of the interval, x is larger than a over 2, so x minus a over 2 is positive. So I can take care of this absolute value just by leaving it as x minus a over 2. I don't need to worry about the absolute value in this range. So this is x minus a over 2 all over a over 2. And of course, if we're outside that, we get 0. This technique of splitting up absolute values into separate ranges makes the integrals a little easier to express and a little easier to think about. So that is our initial conditions. How can we express these initial conditions as a sum of stationary state wave functions evaluated at time t equals 0? This is where Fourier's trick comes in. If I want to express my initial conditions as a sum of stationary state wave functions, I know I can use this sort of an expression. This is now my initial conditions, and my stationary state wave functions are being left multiplied, complex conjugated, integrated over the domain, and that gives us our constants, C sub n, that go in this expression for the initial conditions in terms of the stationary state wave functions. The notation here is that if psi appears without a subscript, that's our initial condition. That's our actual wave function. and if psi appears with a subscript, it's a stationary state wave function. So what does this actually look like? Well, we know what these functions are. First of all, we know that this function, which has an absolute value in it, is best expressed if we split it up in two. So we're going to split this integral up into one going from 0 to a over 2 and one going from 0 to a. So let's do that. We have c sub n equals the integral from 0 to a over 2 of our normalized stationary state wave function, which is root 2 over a times the sine of n pi x over a. That's this psi sub n star, evaluated at time t equals 0. I'm ignoring time for now, so even if I had my time parts in there, I would be evaluating e to the 0, where time is 0. So I would get 1 from those parts. Then you have psi, our initial conditions, and our initial conditions for the first half of our interval was root 3 over a, 1 minus a over 2 minus x over a over 2. And I'm integrating that dx. The second half of my integral from a over 2 to a, looks much the same. Root 2 over a sine n pi x over a. That part doesn't change. The only part that changes is the fact that we're dealing with the second half of the interval, so the absolute value gives me a minus sign up here, more or less. Root 3 over a, 1 minus x minus a over 2 over a over 2 dx. So, substitute in for n and do the integrals. This, as you can imagine, is kind of a pain in the butt. So what I'd like to do at this point is give you a demonstration of one way that you can do these integrals without really having to think all that hard. And that's doing them on the computer. You can of course use Wolfram Alpha to do these. You can of course use Mathematica. But the tool that I would like to demonstrate is called Sage. Sage is different than Wolfram Alpha and Mathematica in that Sage is entirely open source and it's entirely freely available. You can download a copy, install it on your computer, and work with it whenever you want. It's a very powerful piece of software. Unfortunately, it's not as good as the commercial alternatives, of course, but it can potentially save you a couple $100. The interface to this software that I'm using is their notebook webpage. So you can use your Google account to log into this notebook page, and then you have access to this sort of an interface. So, if I scroll down a little bit here, I'm going to start defining the problem. A, here, that's our domain. Our domain goes from 0 to a. H bar, I'm defining to be equal to 1, since that number is a whole lot more convenient than 10 to the minus 31st. N, x, and t, those are just variables, and I'm defining them as variables given by these strings, n, x, and t. Now we get into the physics. The energy, that's a function of what index you have, what your which particular stationary state you're talking about. This would be psi sub n, this would be E sub n. E sub n is equal to n squared pi squared h bar squared over 2ma squared. That's an equation that we've derived. Psi of x and t, psi sub n of x and t in particular, is given by this. It's square root of 2 over a times this sine function times this complex exponential, which now uses the energy, which I just defined here. Psi star is the complex conjugate of psi, which I've just done by hand by removing the minus sign here. More or less just a copy-paste. G of x is what I've defined the initial conditions to be, which is square root of 3 over a times this 1 minus absolute value expression. And c sub n here, that's the integral of g of x times psi from 0 to a over 2 plus g of x times psi going from a over 2 to a. That's all well and good. Now I've left off the psi stars, but since I'm evaluating at time t equals 0, it doesn't matter. Psi is equal to psi star at t equals 0. I did have to split up the integral from 0 to a over 2 and a over 2 to a, because otherwise Sage got a little too complicated in terms of what it thought the integral should be. But given all this, I can plot, for instance, g, and if I click evaluate here, momentarily a plot appears. This is the plot of g of x. as a function of x. Now I defined a to be equal to 1, so we're just going from 0 to 1. This is that tent function I mentioned. If I scroll down a little bit, we can evaluate c of n. This is what you would get if you plugged into that integral that I just wrote on the last slide. You can make a list evaluating c of n for x going from 1 to 10, and this is what you get. You get these sorts of expressions: 4 times square root of 6 over pi squared, or minus 4 root 6 over pi squared divided by 9, 4 root 6 over pi squared over 25, 4 root 6 over pi squared over 49. You can see the sort of pattern that we're working with. Some number divided by an odd number raised to the nth power, or squared. We can approximate these things just to get a feel for what the numbers are actually like. And we have 0.99 minus 0.11 plus 0.039, etc. Moving on down. So that's the sort of thing that we can do relatively easily with Sage. Get these types of integral expressions and their values. You can see I've done more with this Sage notebook, and we'll come back to it in a moment. But for now, these are the sorts of expressions that you get for c sub n. So our demo with Sage tells us c sub n equals some messy expression. And it can evaluate that messy expression and tell us what we need to know. Now, the actual form of the evaluated c sub n was not actually all that complicated. And if we truncate our sum, instead of summing from, now this is expressing psi of x t, our wave function, as an infinite sum, n equals 1 to infinity, of c sub n psi sub n of x and t. If I truncate this sum at, say, n equals 3, I'll just have a term from psi 1 and psi 3. Recall back from the Sage results that psi 2, the coefficient of psi 2, c sub 2, was equal to 0. So let's find the expectation of x squared. Knowing the form of these functions, and now knowing the values of these c sub n from Sage, you can write out what x squared should be. This is the expected value of x squared, and it's going to be an integral of these numbers, 4 root 6 over pi squared times psi 1, which was root 2 over a sine, not n, since we're just dealing with psi 1 now, we have pi x over a. We have to include the time dependence now, since I'm looking for the expected value of x squared as a function of time now. And we have e to the, where'd it go, minus I times pi squared h bar squared t over 2ma squared, all divided by h bar, or I could just cancel out one of the h bars here. That's our first term, in our first term of our expression. The next term, we have 4 root 6 over 9 pi squared from this coefficient. Now psi 3 is root 2 over a sine of 3 pi x over a times, again, complex exponential, e to the minus I pi squared h bar squared t over 9 pi squared h bar squared t over 2ma squared, all divided by h bar. Now, what is this? This whole thing needs to be complex conjugated, because this is psi star. What's next? Well, I need to multiply this by x squared, and I need to multiply that by the same sort of thing, e to the plus this minus same sort of thing, e to the plus this. So this is the term in orange brackets here is psi star. This is our x. The term in blue brackets here is our psi. So we're just using the same sort of expression, only you can only see just how messy it is. This is the integral of psi star x squared psi. This is psi star this is x squared, and this stuff is psi. We have to integrate all of this dx from 0 to a. This is pretty messy as well. Messy, but doable. Now, since I was working with Sage anyway, I thought, let's see how the time dependence in this expression plays out in Sage. So, going back to Sage, we know these c sub n's. These are the c sub n's that I chose for c sub 1 and c sub 3. And c sub n of x gives me some digits. Or, sorry, c sub n evaluated gave me these numbers in just in decimal form. Now I can use these c sub n's to express that test function where I truncated my sum at psi sub 3. So this is our test function. If you evaluate it, it's a lot more simple when you plug in the numbers, sine 3 pi x and sine pi x. When h bar is 1 and a is 1, these expressions are a lot easier to work with, which gives you a feeling for why quantum mechanics often we assign h bar equal to 1. The expected value of x squared here is then the integral of the conjugate of my test function times x squared times my test function, integrated from 0 to a. And Sage can do that integral. It just gives you this. Sage can also plot what you get as a result. Now you notice Sage has left complex exponentials in here. If you take this expression and manually simplify it, you can turn this into something with just a cosine. There is no complex part to this expression. But Sage isn't smart enough to do that numerically, so I have to take the absolute value of this expression to make the complex parts, the tiny, tiny complex parts, go away. And if I plot it over some reasonable range, this is what it looks like. It's a sinusoid, or a cosinusoid actually. And what we're looking at here on the y-axis is the expected value of x squared. This is related to the variance in x. So it's a measure of more or less the uncertainty in position. So our uncertainty in position is oscillating with time. What does this actually look like in the context of the wave function? Well, the wave function itself is going to be a sum, c sub 1 times psi 1, c sub 3 times psi 3, c sub 5 times psi 5, c sub 7 times psi 7, etc. I can do that in general by making this definition of a function, where I just add up all of the c sub n's and all the psi sub n's for n in some range. F of x, if I go out to 7, looks like this. You can get a feel for what it would look like if I added more terms as well. Now the plot that I'm showing you here is a combination of 4 things. First, it's the initial conditions shown in red. That's the curve that's underneath here, the tent. And I'm also showing you this approximate wave function when I truncate the sum at 2, just the first term. That's this poor approximation here, smooth curve. The function, if I truncate the approximation at 4, that will include psi 1 and psi 3. That's this slightly better approximation here, this one. And if I continue all the way up to 20, that's this quite good approximation, the blue curve here, that comes almost all the way up to the peak of the tent. So that's what our approximate wave functions look like, but these are all evaluated at t equals 0. What does that look like, for instance, in terms of the probability density and as a function of time? So let's define the probability density, rho of xt, as the absolute value of our approximate function, and I'll carry the approximation all the way to n equals 20, absolute value squared. And I'm getting the approximate form with this dot n at the end. So this is our approximate form of the probability density calculated with the first 20 stationary state wave functions. This plot then shows you what that time dependence looks like. I'm plotting the probability density at time t equals 0, probability density at time t is 0.04, 0.08, 0.12, 0.16. We start with blue, dark blue. That's this sort of peaked curve, which should be more or less what you expect, because we did a problem like this for this sort of wave function in class. Then you go to dark green, which is under here, underneath the yellow. It seems to have lost the peak, and it's spread out slightly. Red is at time 0.08, and if I scroll back up to our uncertainty as a function of time plot, 0.08 is here. So it's pretty close to the maximum uncertainty. You expect the uncertainty, the width, to start decreasing thereafter. If I scroll back down here, this red curve then is more or less as wide as this distribution will ever get. And if we continue on in time, now going to 0.12, that was the orange curve here. And the orange curve is back on top of the green curve. The wave function has effectively gotten narrower again. And if you keep going all the way up to 0.16, you get the cyan curve, the light blue curve, which is more or less back on top of the dark blue curve. So the wave function sort of spilled outwards and then sloshed back inwards. You can sort of imagine this as ripples in a tank of water radiating out and then coming back to the center. This is what the time evolution would look like as calculated in SAGE. You can make definitions of functions like this, you can evaluate them, you can plot them, and you can do all of that relatively easily. Now I'll give you all a handout of this worksheet so that you get a feel for the syntax. If you're interested in learning more about SAGE, please ask me some questions. I think SAGE is a great tool, and I think it has a promising future, especially in education like this. For students, the fact that this is free is a big deal. So that's what the time variability looks like. We had our wave function, which started out sort of sharply peaked, our probability density, rho of x, which I should actually write as rho of x and t, which sort of got wider and then sloshed back in. So we sort of had this outwards motion followed by inwards motion, where our expectation of x squared, related to our uncertainty, oscillated. Oh, sorry. It didn't oscillate about x equals 0. It oscillated about some larger value. Sorry, it didn't oscillate about 0. It oscillated about some larger value. So there's some sort of mean uncertainty here. Sometimes you have less uncertainty, sometimes you have more uncertainty. That's the sort of time dependence you get from quantum mechanical systems. To get an even better feel for what the time variability looks like, there's a simulation that I'd like to show you. And this comes from Falstad.com, which, as far as I can tell, is a guy who was sick of not being able to visualize these things, so he wrote a lot of software to help him visualize them. So here's the simulation, and I've simplified the display a little bit to make things easier to understand. These circles on the bottom here, each circle represents a stationary state wave function. And he has gone all the way up to stationary state wave functions that oscillate very rapidly, in this case. But this is our ground state. This is our first excited state, second excited state, third excited state, etc. N equals 1, 2, 3, 4, 5, 6, 7, etc. Now, in each of these circles, there may or may not be a line. The length of the line represents the magnitude of the time part of the evolution of that particular stationary state. And the angle going around the circle here represents the phase as that evolution proceeds. So if I unstop this simulation, you can see this slowly rotating around. You're also probably noticing the color here changing. The color of this represents the phase. The vertical size of this represents the probability density, and the color represents the phase. So it's a representation of where you're likely to find it, and a sort of color-based representation of how quickly it's evolving. The vertical red line here in the center tells you what the expectation value for position is. And in this case, it's right down the middle. If I freeze the simulation and add a second wave function, this is now adding some component of the first excited state. And by moving my mice around here, I can add varying amounts, either adding none or a lot, and I can add it at various phases. I'm going to add a lot of it, an equal amount as the ground state, and I'm going to do it at the same phase. And I'm going to release and let that evolve. So you can see now the probability density is sort of sloshing to the left and sloshing back to the right. And if you look at our amplitude and phases, you can see the ground state is still rotating. The first excited state is rotating, but the first excited state is rotating 4 times faster. So when they align, you have something on the right. When they anti-align, something on the left. They're aligned, they're anti-aligned. And this sloshing back and forth is one way where we can actually get motion out of stationary states. You notice the phase is no longer constant. You have some red parts, some purple parts, and things are sort of moving around in an awkward way. The colors are hard to read, but you know now that the phase of your wave function is no longer going to be constant as a function of position. So those exponential time parts may be giving you a wave function that's purely real here and purely imaginary here, or some combination of purely real and imaginary, some general complex number. And that complex number is not simply e to the I omega t. It's e to the I omega something that's a function of position as well as time. It's complicated. I can, of course, add some more wave functions here, and you get even more complicated sorts of evolution. Our expected value of x is now bouncing around fairly erratically. Our phase is bouncing around even more erratically. But what we're looking at here is just the sum of the first 1, 2, 3, 4, 5, 6 stationary states, each evolving with the same amplitude and different phases. Now I'm going to stop the simulation and clear it now. Another thing I can do with this simulation tool is put a Gaussian into the system. So I'm going to put a Gaussian in here. So this is sort of our initial conditions, and the simulation has automatically figured out, well, I want this much, I want a lot of the first of the ground state, psi 1, a lot of psi 3, a lot of psi 5, a lot of psi 7, a little bit of psi 9, a little bit of psi 11, etc. And if I play this, I'm going to slow this down a little bit first. If I play this, you see the wave function gets wide, becomes 2, gets narrower again, and sloshes back where it started. If you watch these arrows down here, you can tell when it comes back together, the arrows are all pointing in the same direction, and when it's dispersed, the arrows are sort of pointing in opposite directions. Since our initial conditions were symmetric, there's no reason to expect the expected value to ever be non-zero, ever move away from the center of this well. But as your, say, psi 1, psi 3, psi 5, psi 7, etc., oscillate at their own rates in time, the superposition results in a relatively complicated dynamics for the overall probability density. And of course I can make some ridiculously wacky excited initial conditions that just sort of oscillate all over the place in a very complicated way. There are a lot of contributions to this wave function now, and no one contribution is particularly winning, but you can occasionally see little flashes of order in the wave function. I highly encourage you to play with these simulations just to get a feel for how time evolution in the Schrodinger equation works. There are a lot more than just the square well here. There's a finite well, harmonic oscillator, a pair of wells. There are lots of things to play with, so you can get a reasonably good feel with how the Schrodinger equation behaves in a variety of physical circumstances. So that's our simulation, and hopefully you have a better feel now for what solutions to the Schrodinger equation actually look like. To check your understanding, explain how these two facts are related. Time variability in quantum mechanics happens at frequencies given by differences of energies, whereas in classical physics, you could set the reference level for potential energy to whatever you want, sort of equivalent to saying I'm measuring gravitational potential from ground level versus from the bottom of this well. The system we're considering in this lecture is the quantum harmonic oscillator. There are a few ways to solve the Schrodinger equation for the quantum harmonic oscillator, but what we're going to do in this lecture is a solution more or less by pure cleverness. The solution is called the solution by ladder operators, and we'll see what that means in a few minutes. Just to set the stage, the potential that we're working with here is the potential of a harmonic oscillator. The amount of energy, essentially, that you get if you displace a particle attached to a spring from equilibrium. If you remember spring potential energy, the potential as a function of x is 1/2 the spring constant times the displacement x squared. But it's traditional to write this instead in terms of the angular frequency. The angular frequency of the oscillations that result when a mass m is on a spring with spring constant k is the square root of the spring constant divided by the mass of the particle. And if you substitute this in here and mess around with the simplification a little bit, you end up with 1/2 m omega squared x squared. So this is the form of the potential that we'll be using. What this looks like, if I plot it, is a parabola. Not the world's prettiest parabola, but you get the idea. And we know a little bit about what solutions to the Schrodinger equation should look like under circumstances like this. Let me draw this a little lower so I have room. If I have some energy E in this combined energy wave function axis, making a diagram of what the wave function looks like, if I start my wave function here, you know in this region the energy is above the potential, so the Schrodinger equation solutions have to curve downwards. And what they end up looking like is, well, something like this, say. Now, in the regions outside here, where the potential is above the energy, the Schrodinger equation solutions curve upwards. In the case of the harmonic oscillator solutions, they curve just down to kiss the axis. And you end up with a nice sort of hump-shaped wave function. If you have a higher energy, say up here, it's entirely possible to get solutions that look different. Suppose I started my wave function here, pointed at some angle. The energy now is higher relative to the potential, so the wave function is going to curve more, and it's possible to make it curve down to the point where when it reaches this point now where the potential is higher than the energy and it starts curving back upward, you again get a wave function that just smoothly joins in with the axis, giving you a sort of nice normalizable wave function. So these are the sorts of solutions that we expect to get. If you want to get these solutions just by, well, like drawing them, like I just did, you can conceptually understand what they look like, but quantitatively you'll have to do a lot of fine-tuning to get these energy levels exactly right and to get the initial conditions here. I just started my wave function. How high up should I start my wave function? Or in this case, should I start it at the middle? Should I displace it? What should this angle here be? Fine-tuning like that is hard, and we'll see how to do that in the next lecture. But in this case, we're going to make a solution by cleverness instead of fine-tuning. To set that up, let's go back to the time-independent Schrodinger equation. This is the general time-independent Schrodinger equation, where now we're going to be substituting in the harmonic oscillator potential, 1/2 m omega squared x squared. That means the harmonic oscillator time-independent Schrodinger equation that we actually have to work with minus h bar squared over 2m times partial derivative of psi with respect to x squared plus 1/2 m omega squared x squared psi is equal to E psi. So this here is the Hamiltonian operator. The time-independent Schrodinger equation is also often just written as H psi equals E psi, and that's fine. Let's take a closer look at this Hamiltonian operator. Maybe we can do something with it. The cleverness comes in this step. Consider factoring the Hamiltonian. Well, I can simplify this a little bit by pulling out for instance, a 2m here, and writing this as the momentum operator squared. This is essentially p squared over 2m, the kinetic energy part. This is the potential energy part. If I pull out 1 over 2m, what I get, 1 over 2m p hat squared plus m omega x quantity squared. This is suggestive. If we had numbers, and I had something like a squared plus b squared, I could factor that over the complex numbers as ia plus b times minus ia plus b. If you expand this out, you'll end up getting a plus a squared from multiplying these, a plus b from multiplying these, and similar to the cross terms in, say, a minus b times a plus b, the cross terms end up canceling out, and we would end up with what we started. Now, this is suggestive. You can't actually factor operators like this because they're not numbers, they're operators, and operators don't necessarily behave the same way numbers behave. We'll see what that means in a minute, but for now, let's just suggest looking at things like this. Plus or minus I times the momentum operator plus m omega x, where x now is the position operator. Now x, the position operator, just entails multiplying by x, so perhaps I should put a hat here, perhaps I shouldn't. Doesn't really matter. This is what we're considering now. I haven't justified this in any way beyond saying it kind of looks like maybe it would factor. Well, does it factor? These things are called ladder operators, and they're traditionally defined, just to make the notation a little bit simpler, a hat, and there's either a plus or a minus on this. Let me draw this a little bigger. A hat, plus or minus in the subscript, and these are defined to be 1 over the square root of 2 h bar m omega. The constant just makes things more nice overall, times minus or plus I p hat plus m omega x. This is now the position operator x hat. So this is the traditional definition. Let's see. If we have something that properly factors, what we should have is that a hat minus times a hat plus is our Hamiltonian. Is this true? This is an operator algebra problem, and operator algebra problems are tricky to do without test functions, but initially we can just write this out. We have two a's being multiplied together, so we're going to have a 1 over 2 h bar m omega out front. And then we're going to have I p hat plus m omega x times minus I p hat plus m omega x. Once again, hats on the x's if you prefer. So far, we've just written down our operators in order. Now, if I actually tried to expand these out, 1 over 2 h bar m omega. Now, this term, I times minus I, that's just plus 1. So we would get p hat squared. So far, so good. For this term, this is okay as well, plus m squared omega squared x hat squared. That's still okay. We're still on track. This was more or less what our Hamiltonian looked like. The cross terms get a little more interesting, though. We have a term like this, which gives us, let's see, we're going to end up with a minus I from this, minus I m omega, and we have x hat p hat. We're going to end up with something very similar from this term. We're going to have an I, we're going to have an m, we're going to have an omega, except in this case we're going to have p hat x hat, not x hat p hat, as we had here. So I'm going to factor the constants out and do that in the right color. That means we're going to have minus p hat x hat here. So this is what we get when we expand this out. This part here looks a lot like the Hamiltonian. So we're on the right track. It's actually like 1 over h bar omega times the Hamiltonian. This part, though, this is a little more difficult to work with. And it turns out that this piece right here, this sort of thing appears a lot in quantum mechanics, and we have a name for it and a notation for it. And the notation is x hat comma p hat in square brackets. This is called a commutator. And fundamentally, the fact that I can't just subtract these two things from each other and get 0 is one of the most fundamental parts of quantum mechanics, one of the most fundamental features of quantum mechanics. So, let's talk about commutators in a little more detail. The commutator in general is defined for two operators A and B to be what you just saw on the last page. First, I have A, B, and then I subtract the opposite order, B, A. So if I acted on this, or if I used this operator, this combined operator, to act on a wave function, I would first let A act and then let B act. And I would subtract that from what I get if I let B act and then A act. Just to make that a little more explicit, if I had A, B minus B, A acting on some wave function, I would say that's A, B, psi minus B, A, psi. You don't necessarily get the same answer for both of these things because the order in which operators act is important. So let's look then at our commutator. The commutator we had in the last slide was x and p. The commutator of x and p is x hat p hat minus p hat x hat. And let's allow this to act on some wave function psi. In order to make my notation correct, I ought to have the same sort of psi here. So if I allow this to act on psi, first we're going to have x hat p hat psi minus p hat x hat psi. And what this means is x hat is acting on p hat acting on psi, and this is p hat acting on x hat acting on psi. We have definitions for these things. X hat is just x multiplied by something, and p hat is minus I h bar times the derivative of something, in this case psi. Our second term here is minus I h bar times the derivative of, with respect to x, of x times psi. When I apply the derivative here, I have to use the product rule since I have a product of two terms. I'll have to hit x in one term and psi in the other term. So, on the leftmost term here is easy to deal with, though. It's just minus I h bar x d psi dx. Actually, let's factor out a minus h bar, I h bar, from both terms, since they both have it. So x d psi dx is my first term here. Then I have minus, if I use the derivative on the x, derivative of x with respect to x is just 1. So all I'll be left with is the psi remaining untouched in the product rule. And if I let the derivative hit the psi, I'll leave the x untouched, and I'll have the derivative of psi with respect to x. This is good because here I have an x d psi dx minus x d psi dx. So I can let these terms subtract out and cancel. And what I'm left with, I have a minus I h bar times minus psi, which is just going to be I h bar psi. So I started with the commutator acting on the wave function, and I just got constant multiplied by the wave function. So I can drop my hypothetical wave function now and just write an equation involving the operators again. The commutator of x and p is I h bar. It's a weird looking equation, but you can see, if you recall from the last slide, what we're going to end up with. when we evaluated a minus hat, a plus hat, we ended up with 1 over h bar omega times the Hamiltonian, plus some constants. And if you flip back a slide, the IH bars end up actually canceling out, and we just end up with plus a half for our constant. So while we did not succeed in fully factoring the Hamiltonian, we did get the Hamiltonian back, plus a constant. And if you reverse the order and repeat the algebra, a hat plus a hat minus, you end up with the same sort of thing. It looks very similar. You get 1 over h bar omega times the Hamiltonian minus a half instead. What this means is we can express the Hamiltonian in terms of these ladder operators and these constants. What we get for the Hamiltonian, h hat, is h bar omega times a minus a plus operators minus a half. Or alternatively, the Hamiltonian is equal to h bar omega a plus a minus plus a half. So these are the sorts of things that we got from our operator algebra after attempting to factor the Hamiltonian. That was pretty clever, but it didn't actually get us a solution. It just got us a different expression of the problem. The cleverness really comes in considering ladder operators and energy. The time-independent Schrodinger equation here is h hat psi equals e psi. So suppose we have some solution psi to the Schrodinger equation. We can then express the Hamiltonian in terms of these ladder operators, h bar omega times a plus a minus operators plus 1/2 acting on the wave function should be equal to e times the wave function. The clever part is this. What if I consider h hat times a plus psi? What happens to the wave function if I allow a plus to act on it before I allow the Hamiltonian to act on it? Now, assuming this is the case, maybe we can manipulate our expressions here involving the Hamiltonian and the ladder operators to get something with which we can apply our solution. Let's see what happens. Expressing the Hamiltonian now as ladder operators, h bar omega a hat plus a hat minus plus 1/2, now acting on a plus hat psi. Forgot my hat there, sorry. Looking at this, you can take a plus psi and distribute it in to the expression in parentheses here. H bar omega a plus hat a minus hat a plus hat psi plus 1/2 psi. Put another way, I'm really just distributing the operator in. And that's actually a more convenient way to look at it. So I'm going to erase my psi's here, and I'm going to leave my psi outside the expression. Oops, and I forgot an a plus hat here. Sorry about that. Just distributing the a plus in here, you'll end up with plus minus plus, and just plus on the 1/2. Now, you notice I have an a plus here, and an a plus here. If you think about factoring this out to the left, that's actually allowed as well. I can rewrite this as h bar omega a plus hat in front of the expression a minus hat a plus hat plus 1/2, all acting on psi. That's okay. What's nice about this is if you look, we have here now an h bar omega and an a minus a plus. If I had the appropriate constant here, which would turn out to be minus 1/2, I would have the Hamiltonian back. And getting the Hamiltonian back means we might be able to apply our Schrodinger equation. So let's rewrite this as h bar omega a plus hat times a minus a plus minus 1/2 plus 1. I haven't changed anything now, except this piece, this, is my Hamiltonian. I had two expressions for the Hamiltonian that I got from calculating the product of ladder operators. One if I did A plus first and then A minus, one if I did A minus first and then A plus, and they were different by the sign that appeared here. So the fact that this is the Hamiltonian allows me to rewrite things a little bit. It turns out I can rewrite this whole expression as A plus hat acting on the Hamiltonian, and you have to distribute the h bar omega in, Hamiltonian operator plus h bar omega acting on psi. So I'm starting to lose my ladder operators, which is a good sign because I don't actually want expressions with lots of ladder operators in them. I'd like expressions with things that I know in them. And it turns out you know what happens when the Hamiltonian acts on psi. So if I distribute psi in here, I'll just have psi times h bar omega and the Hamiltonian acting on psi. But you know the Hamiltonian acting on psi is E times psi. So we're definitely making progress now. This is going to become A plus hat times E plus h bar omega psi. This now is all constant. So it doesn't matter if I put it in between the ladder operator and the wave function or not. So I can pull that out and make this E plus h bar omega times ladder operator A plus acting on the wave function psi. If I rewrite my entire equation then, I end up with h hat acting on ladder operator psi, A plus psi, is equal to E plus h bar omega ladder operator acting on psi, A plus acting on psi. This looks a lot like the Schrodinger equation for a wave function given by A plus psi. So, if psi is a solution to the time-independent Schrodinger equation, A plus psi is also a solution to the time-independent Schrodinger equation with this new energy. That's really the clever part. If psi is a solution, A plus psi is also a solution. That's really quite interesting. What that means is if I have one solution psi, I can apply the ladder operator, which I've just been writing as A plus hat here, but we know what the ladder operator A plus is. It's a combination of the momentum operator and multiplication by x with appropriate constants thrown in. We know about A plus psi. If we knew the wave function, we could actually do this. It would involve taking some derivatives and multiplying by some constants. We can do that. So this gives us some machinery for constructing solutions from other existing solutions. We haven't actually solved the system yet. There's a little bit of cleverness left. And this has to do with ladder operators and the ground state. What we showed on the last slide was that if psi was a solution, then A plus hat psi was a solution with energy E plus h bar omega. It turns out A minus hat psi, you can follow through the same algebra, is also a solution, but it has energy E minus h bar omega. So suppose we have some solution, psi, and I'll call it psi sub n now. If we apply the ladder operator, A plus psi, we'll end up with some wave function psi n plus 1. It's another solution to the Schrodinger equation. It has a slightly higher energy. The energy has been increased by the amount h bar omega here. I can repeat that process, and I'll get, say, something I would call psi n plus 2. And you can keep applying the ladder operator over and over and over, and you'll generate an infinite number of solutions with higher and higher and higher energies. We can also apply the ladder operator A minus hat, and you'll get something I'll call psi sub n minus 1 with slightly lower energy. The energy has been lowered by an amount h bar omega. You can apply the ladder operator A minus hat as many times as you want, of course, as well, and you'll get psi sub n minus 2, or psi sub n minus 3, or psi sub n minus 4, or psi sub n minus 5. Every time you apply the lowering operator, the ladder operator A minus hat, you get another solution with lower and lower and lower energy. But we know if we have a wave function with very, very low energy, it's going to behave very strangely. If your potential, for instance, is your harmonic oscillator potential, it looks like this, and your energy, E, is below your potential V of x, then if I start my wave function, say, anywhere, really, let's start it here. The fact that the energy is below the potential for the entire domain of the potential means that over the entire domain of the wave function is going to be curving away from the axis. The wave function is going to be blowing up. That's a problem. I cannot have solutions with arbitrarily low energy. What that means, cannot have solutions with very low energy. What that means is that if I apply this lowering operator over and over and over again, sooner or later I have to get something that I can no longer apply the lowering operator to. Something will no longer give me a meaningful solution. And it turns out the best way of thinking about that is there is some wave function such that A minus acting on that wave function is equal to 0. If we have a state like this, this will be our lowest energy state, and I'll call it psi sub 0. This is a necessary condition for getting a normalizable wave function. If we did not have this condition, we'd be able to keep applying the lowering operator, and we would sooner or later get solutions that were not allowed. That's a problem. So let's figure out what this actually implies. We know what the lowering operator is. We know what 0 is. We ought to be able to solve this. This is going to be an ordinary differential equation just given by the definition of the ladder operator. 1 over 2m h bar omega in a square root times the momentum operator h bar d by dx plus m omega x acting on psi sub 0 is equal to 0. This we can solve. This is a relatively easy ordinary differential equation to solve, in fact, because it's actually separable. If you mess around with the constants, you can convert this into the differential equation d psi dx is equal to minus m omega over h bar x psi. And these are now psi zeros, sorry. This can be directly integrated. I can rewrite this as d psi over psi is equal to minus m omega over h bar x dx. And if I do this integral, integrating both sides of this equation, what you end up with, after you simplify, is that psi sub 0 is equal to e to the minus m omega over 2 h bar x squared. E to the minus x squared for our ground state, for our lowest energy psi sub 0, for our lowest energy solution. There's a normalization constant here, and I'll save you the trouble of calculating the normalization constant out. It's m omega over pi h bar to the 1/4 power. So this is our ground state. Now it's off to the races. By consideration of the Hamiltonian, and attempting to factor it, and defining ladder operators, and exploring the consequences of these ladder operators, in particular that we ended up with any single solution giving us an infinite number of solutions by repeatedly applying a plus and a minus, the necessity of a normalizable wave function, the necessity of having a lowest energy state, meant that we got an equation that was simple enough that we could solve it with just simple ordinary differential equations. Now, there's really no such thing as a simple ordinary differential equation, but this was a lot easier to solve than some ordinary differential equations. What that ended up giving us in the end was psi 0, our lowest energy state. We can then apply the raising operator, a plus, over and over and over again to construct an infinite number of states. To summarize, here's a slide with all of the definitions. The raising and lowering operators, the ladder operators, a plus and a minus, the expressions that you get from simplifying the Hamiltonian in terms of the ladder operators. I want to highlight these two expressions because I have not completely derived them. I have argued that the ladder operator a plus applied to some wave function psi sub n gives you psi sub n plus 1, but I haven't told you anything about the normalization. You could apply this operator over and over again and renormalize all of the wave functions you get as a result, but it turns out there's a pattern to them, and that pattern is that what you get by applying the ladder operator a plus to psi n is not psi n plus 1, but psi n plus 1 times this square root of n plus 1. Likewise for the lowering operator. There's a nice explanation in the textbook of how you can use still more cleverness to derive what these normalization multiplicative factors are. Our ground state we got from applying the lowering operator to some hypothetical wave function, which when we solve it, we ended up with this, our psi sub 0, our lowest energy wave function. Putting all of this together, you can come up with an expression for the nth wave function, psi sub n, in terms of psi sub 0. You have to apply a plus n times. This superscript n here means to apply a plus n times. For instance, a plus hat cubed would be a plus, a plus, a plus, all acting on, say, if there's a psi in here, all acting on the psi, just one after the other. And if you calculate the energies that we get, applying the Hamiltonian to our lowest energy wave function, and then knowing that the raising the operator a plus gives you a new solution with an energy that's increased by the amount h bar omega, you end up with the energies. So we actually know everything about the solutions now. We know the lowest energy solution, we have a procedure for calculating higher energy solutions, and we know the energies of all of these solutions. So that's wonderfully good. To give an example of how these things are actually used, let's calculate psi 1. We know psi 1, buying black a little easier to read, psi 1 is going to be equal to a plus acting on psi 0, and there's that normalization constant, the square root of n plus 1, except in this case n is 0, so this is just going to be 1. If I substitute in the definition of the operator a plus, that's 1 over that square root of 2 h bar m omega minus I p hat plus m omega x, where p hat now is minus I h bar d by dx. This is my raising operator. That's all acting on psi sub 0. And we know psi sub 0, given in normalized form, m omega over pi h bar to the 1/4 power e to the minus m omega over 2 h bar x squared. We just have to evaluate this, taking derivatives of this exponential and multiplying it by x. So let's continue with that. Moving our normalization constant out front, m omega over pi h bar to the 1/4 power over this square root factor, 2 h bar m omega. Simplifying this expression out, we end up with minus h bar d by dx plus m omega x, all acting on e to the minus m omega over 2 h bar x squared. Now, this term with the m omega x, that's going to be easy. The derivative here is going to be relatively straightforward as well. And what we end up with is the constants we had out front, and taking the derivative of an exponential, we're just going to get the exponential back. So we're going to have an h bar e to the minus m omega over 2 h bar x squared times the inner derivative, the derivative of what's in the exponent itself, which is minus 2 x, sorry, let me actually write this out, minus m omega over 2 h bar times 2x. That's okay. The minus sign here and the minus sign I had out front will end up canceling out. I can simplify, I can cancel out my 2's, I can cancel out an h bar. That's all I'm going to do with that term for now. The other term is easy. M omega x e to the minus m omega over 2 h bar x squared. So that's our result. We have an e to the m minus m omega, etc., over x squared in both of these terms. So I'm going to pull that out to the right. And if I pull my constants out to the left, I have an m omega and an m omega in both of these terms, so I can factor that out. And what you end up with at the end, after all is said and done, the only step I'm skipping now is to simplify the constants. What you end up with is m omega over pi h bar to the 1/4 power. There isn't much we can do about that. Square root of 2m omega over h bar x e to the minus m omega over 2 h bar x squared. Both of these terms had x and x in them. So these terms just add up, and this is what we end up with at the end. This is your expression for psi 1. The algebra here gets a little bit complicated, but fundamentally what we're doing is calculus, taking derivatives, multiplying, manipulating functions, applying the chain rule, and turning the crank, more or less. The formula we started with here does give us machinery that we can use to calculate any wave function that we might want as a solution to the time-independent Schrodinger equation for the quantum harmonic oscillator. To check your understanding, here is an operator algebra problem. Given that x hat is the position operator and t hat is the kinetic energy operator, essentially p squared over 2m, calculate the commutator of x and t. That's just defined as this. The one tip I have for you here is to be sure to include a test function when you expand out these terms, and when you take second derivatives, do it as a sequence of 2 steps. Don't just try and take the second derivative twice in one step. You may have to apply the product rule. We've heard about the solution to the harmonic oscillator time-independent Schrodinger equation by cleverness with ladder operators. This is the differential equation we have to work with is something that can be solved by other techniques. In particular, it can be solved by power series. Power series is a common solution technique for ordinary differential equations, so it's useful to see how it applies to the time-independent Schrodinger equation. The equation we have to solve is this. Essentially, H operator psi equals E psi, where we're now only talking about psi as a function of x. We have a second partial derivative with respect to x that comes from the kinetic energy part of the Hamiltonian operator, and we have a potential energy part here, where the potential function we're now working with, v of x, is the potential in a harmonic oscillator, 1/2 m omega squared x squared, basically proportional to the square of the displacement of a particle from some equilibrium position. Often, the first step in solving an ordinary differential equation like this is to make some change of variables to simplify the structure of the equation. Basically, what we're looking to do is get rid of some of these constants. And it turns out the change of variables that we want to use here, and you can determine this with a little bit of trial and error, knowing how change of variables works, is we want to, instead of x, we want to use x is the square root of h bar over m omega times some new coordinate c. Now, what happens when we substitute in new coordinates here? Well, we have to worry about psi of x here, and here, and here. Psi is going to have to, in some sense, change a little bit in order to be represented as a function of c instead of x. We also very clearly have an x here, and we have to worry about the second partial derivative with respect to x. So let's work through this step by step, and you'll see how these substitutions can be made. First of all, we can pretty easily handle these psi as a function of x because we know what x is. X is the square root of h bar over m omega times c. So we'll have minus h bar squared over 2m. Don't have to worry about the constants. Second derivative of psi, now square root of h bar over m omega c is the argument for psi, but we're still second differentiating with respect to x. Dx squared, pardon me, plus 1/2 m omega squared. Now, substituting in for x, this is relatively easy. We're going to get this squared, h bar, over m omega c squared, times psi, and the argument of psi is again going to be this root h bar over m omega c, equals e times psi, where again the argument of psi is this function of c. You can see there's going to be some cancellation here. I can get rid of some m's and some omegas, but I'll leave that until later. The only difficult term to deal with here is the second partial derivative with respect to x of psi, which is now a function of c. Now, when you're taking the derivative of something with respect to a function of something else, you have to use the product rule. Sorry, not the product rule, the chain rule. So I'm going to apply the chain rule to this derivative term, and I'm going to split it up into two steps, two first derivatives instead of one second derivative, just to see how each of those steps applies. So first of all, minus h bar squared over 2m times the derivative with respect to x of the derivative with respect to x of psi of c. Now, I can take the derivative of psi with respect to c. That I know how to do. That's just d psi dx, because psi is a function of c. But in order to turn this into a partial derivative with respect to x, I have to multiply by the derivative of c with respect to x. So this is the chain rule at work here. And I know how to take the derivative of c with respect to x, because I know c is a function of x. This is just going to give me square root of m omega over h bar. What I get if I solve for c and then just differentiate with respect to x. This can then be pulled out front. It's a constant, doesn't contribute anything. Minus h bar, oops, don't want to be an orange. Minus h bar squared over 2m times our constant, root m omega over h bar, times partial derivative again with respect to x. But now I'm taking the partial derivative of psi with respect to c. So again, I have to apply the chain rule. What I'm going to get differentiating psi with respect to c is a second derivative of psi with respect to c now, times again a partial derivative of c with respect to x. You can do this all in one step if you know that the partial derivative of c with respect to x is simple. If the partial derivative of c with respect to x had some problems in it, some dependence, you would have two separate functions here. You wouldn't be able to factor it out as a constant, and you'd have to apply the product rule to this term. So be careful when you're doing this. Don't just assume that you can take a second partial derivative with the chain rule in one step. But the second step here, again, partial derivative of c with respect to x gives me the square root of m omega over h bar, which as a constant I can pull out front and combine. What I'm left with for this term then is minus h bar squared over 2m times m omega over h bar, again giving me some nice cancellations, times the second derivative of psi with respect to c. So this converts my derivative with respect to x into a derivative with respect to c. I've converted my x into c, and all of my other x's into c's just by changing the arguments of psi. So the overall equation I get now, minus h bar squared over 2m, m omega over h bar, second partial of psi with respect to c, plus 1/2 m omega squared h bar over m omega, c squared psi, equals e psi. And this is good because we can do some cancellations. We can, for instance, cancel one of the omegas here, and we can cancel the m. We can also cancel an m here and one of the h bars. What's nice about this is I have h bar omega over 2 here and h bar omega over 2 here. So I have the same constant, and I'm going to move both of these constants, factor them out, move them over with the e to lump all of my constants together. I'm also going to change the ordering of the terms to get my two psi's together and mess with the signs a little bit, but the final equation you get is the second derivative of psi with respect to c is equal to c squared minus some constant k psi,
where k is what we got when we aggregated all these constants together. It's, need an equal sign there, k is equal to 2e over h bar omega. So this is a differential equation that's substantially simpler than the differential equation we had here. Just by rearranging constants, we haven't actually changed the structure of the solution any. This differential equation isn't something that we want to just go ahead and try and solve with power series, though, and you'll see why in a moment. Solutions that are most easily represented by power series are solutions that are only interesting near the origin. And this equation tends to be difficult to represent with power series because of what happens for large values of xi. So let's look for something called an asymptotic solution. Let's look for a solution for large xi. Xi much, much greater than 1. What happens when xi is much, much greater than 1? Well, if xi is much, much greater than 1, I don't care about k here. It's going to be about equal to xi squared. Xi squared minus k is about xi squared. That means the actual differential equation we have to solve is second derivative of psi with respect to xi is xi squared psi. Oh, and I've unintentionally changed notation here. This is a derivative of psi, not a partial derivative of psi. That doesn't really matter. The partial derivative and the total derivative are the same because psi now is only a function of x. Likewise, I should also probably write capital psi here instead of lowercase psi. That's just an error. Apologies. This approximate equation has solutions. In the case of an asymptotic solution, we don't really care about the exact solution. An approximate solution is good enough if we can still use this approximation in our solution. So our approximate solution, and you can check this, is that the wave function is approximately equal to a times e to the minus xi squared over 2 plus b e to the xi squared over 2. Rewrite that, or make it more look like a c. So this equation is an approximate solution to this equation. And you can see that by taking the second partial derivative of psi. I'll just look at this term, for instance. The second partial derivative of this term, d squared dxi squared of e to the minus xi squared over 2 is, and you can plug this into whatever computational algebra tool you want, xi squared minus 2 times e to the minus xi squared over 2. So this, again, approximately for large values of xi, is going to be about equal to xi squared. So second derivative of this effectively pulled down a xi squared and gave us our function back. And that's what our approximate differential equation is. Now if you had a minus sign in front of the xi and the exponent here, you'd end up with much the same sort of expression. So you can see this is effectively an approximate solution to our approximate differential equation. This is useful in a couple of ways. First of all, there will be large values of xi. Unlike the case of the infinite square well, there's no sound reason for believing that the wave function will go to 0 for large values of xi. It's certainly not required by the laws of physics. It is, however, required by the laws of mathematics. In order to have a normalizable wave function, this asymptotic behavior can't have any of this in it. So if we want our wave function to be normalizable, then b must equal 0. That's a requirement. What that tells us then, if we have something that's going to be a solution to the time-independent Schrodinger equation, its asymptotic behavior will be given by this. So psi is approximately equal for large xi to some constant e to the minus xi squared over 2. That's an approximate solution.
This is the story all about how the Schrodinger equation applies to the free particle. What do we mean by a free particle? Imagine an electron, for instance, floating in the vacuum of space. It never encounters anything. It never runs into anything. How that enters the Schrodinger equation is that there is effectively no potential anywhere. So the time-independent Schrodinger equation, we're back to one dimension now, so don't think about a particle floating around in the vacuum of three-dimensional space. It's floating around in the vacuum of one-dimensional space. The left-hand side of our time-independent Schrodinger equation is the Hamiltonian operator applied to the wave function. This is in some sense the total energy, which breaks down into a kinetic energy component here with the momentum of the particle squared divided by twice the mass, and a potential energy part here, where V of x is the potential energy that the particle would have to be found at a particular location. In the context of the free particle, where there is no potential, what that means is that V of x is equal to 0 everywhere. That means we can just cross out this term entirely. We don't have to worry about it. What we're left with then for our time-independent Schrodinger equation is minus h bar squared over 2m times the second partial derivative of psi with respect to x equal to e psi. Now we have some constants here and we have a constant here, so let's lump them all together. And I'm going to shift the signs around a little bit as well, so that what we've got is the second derivative of psi with respect to x is equal to minus 2me over h bar squared times the wave function. So I've just lumped all our constants together and multiplied through by a minus sign. Now, you notice the second derivative here of the wave function, giving you the wave function back. The fact that we're taking a second derivative suggests that the constant here perhaps is squared. So what I'm actually going to write this as is the second derivative of psi with respect to x is equal to minus some constant k squared times the wave function, where k, our constant, is the square root of 2me over Planck's constant. So this is the differential equation, and we ought to be able to solve this. This is relatively simple compared to the structure of the differential equations we got from the harmonic oscillator. So how do we solve this? Well, what we have, second partial of psi with respect to x, is minus some constant squared times the wave function. Taking the second derivative gives you a constant squared. That immediately suggests we look for exponential solutions. And it turns out the general solution to this equation is some constant times e to the minus I k x plus b e to the plus I k x. If I take the second derivative of this exponential term, I'll get a minus I k squared, which you know is just minus k squared, applying the rules of complex numbers, which is what we get here. So when I take the second derivative of this term, I'll end up with minus k squared times this term. And I get the same sort of thing here. If I take plus I k squared from the second derivative, that again gives me a minus k squared. So we're okay. This is our general solution. When we include time in this, since you know this is a solution to the time-independent Schrodinger equation, it's going to have time dependence given by the time part, the time equation that we got when we did separation of variables. What you end up with is psi of x and time now is equal to a e to the minus I k x times e to the I energy t over h bar plus b times e to the I k x e to the I energy time over h bar. And I've left off my minus signs here in the energy dependence, just conventional to include minus signs there. We can rewrite this a little bit as a e to the I k. Now, what I'm doing here is substituting in the definition of k, which if you remember was the square root of 2me all over h bar, expressing energy in terms of this k. And when I do that, what I end up with is this term ends up looking like h bar k squared over 2m. Substituting that in here is what we get from manipulating our constants here. If I do that manipulation, the first term here, instead of having this product of two exponentials, I'm going to write it as a sum in the exponent, x minus h bar k over 2m t plus b times something that looks very similar, e to the minus I k x plus h bar k over 2m t. So these are our general solutions to the full Schrodinger equation, our full wave function as a function of both position and time. And these solutions are traveling waves. You can think about this as a traveling wave in the context of looking at this as a complex number. If I look at e to the ikx, for instance, as a function of x, you know what that does in the complex plane. It just rotates around in the complex plane. If I look at this as e to the ikx, let me redo that a little. Ik times x minus h bar k over 2m t. And I treat this as a function of time. Again, we just get rotation in the complex plane. We get rotation in the other.
I promised in the last lecture that the solutions we got to the time-independent Schrodinger equation for the free particle, though they are not themselves normalizable and therefore cannot represent physically realizable states, could be used to construct physically realizable states. What that means is that we can take those solutions which themselves are not real and can add them up in a way that we can make something that is real. This is a little subtle. We're constructing something called a wave packet, and basically what that amounts to is adding up a bunch of infinities and getting something finite. Taking these traveling wave solutions to the time-independent Schrodinger equation for the free particle, which extend from minus infinity to infinity in the spatial domain, and from minus infinity to infinity in the temporal domain, and summing them up somehow to get something that is localized in the spatial domain. What that means is that we're making a wave packet. A wave packet, the features that we care about is that it's going to be 0 for, say, large negative values of x, 0 for large positive values of x, and only non-zero over some domain. What it might look like is, well, 0, some wave activity over a relatively limited region, and then going back to 0. We will see wave packets that look like this later on. I'll give a more concrete example and show some animations. But for now, let's think about the math. How would we go about constructing something like this? What we did in the case of the particle in a box, the infinite square well potential, was when we solved the Schrodinger equation, we got solutions. If our potential looks like this, going to infinity at regions outside of a box, our solutions looked like this. We got sinusoids with an integer number of half wavelengths fitting in our box. That was nice because it allowed us to construct our overall solution to the Schrodinger equation, psi of x and t, as an infinite sum of these stationary state wave functions. The integer number of half wavelengths fitting in the box plus the essentially trivial time dependence that you get from the time equation when you do separation of variables with the general Schrodinger equation. This isn't going to work for the case of the free particle for a couple of reasons. First of all, instead of having a discrete sum over, states which have an index n, for instance, this is our psi sub n, where n goes from 1 to infinity, we now have wave functions psi that are continuous. We did not have quantized states. So our stationary states now are going to have to look like our traveling waves. They're going to have to look like e to the I, k, and then x minus, where did it go? h bar k over 2m t. This was our traveling wave solution from the last lecture. So instead of having our discrete set of states indexed by n, we have our continuous set where the parameter is k. K is a completely free parameter, not fixed to be an integer. The second reason our machinery for the particle in a box won't quite work is this coefficient c sub n. C sub n is also going to have to somehow become a function of k. K now being unrestricted, we can't just treat it as a set of discrete entities. We have to have some function, and that function is conventionally written as phi of k. And finally, this sum out front. Again, we can't do a sum if we have a continuous set of functions that we're working with that we want to add up. We have to do an integral. The integral now is going to be an integral over k. So our sum over n became an integral over k. Our coefficient, subscript n, became a function of k. And our discrete set of functions, psi sub n, became these traveling wave solutions with the parameter k in them. Our integral dk goes over all the possible values of k from minus infinity to infinity. And this is what the expression is overall going to look like. We have an integral, we have this continuous function, and we have our traveling wave states. The main problem with this expression is this guy. How do we know? How do we find phi of k? Phi of k is a general function. What we had done to find the analog of this was at c sub n in the case of the particle in a box. What we did for the case of the particle in a box was use Fourier's trick to collapse the sum. Instead of a sum now we have an integral, and it's not immediately clear from looking at this what it means for an integral to collapse. We'll see what that means in a second. But first of all, let's go back to what we did in the case of the particle in a box and spell out some of the details so that we can make an analogy. On the left-hand side here now we have the results for the particle in a box, whereas on the right-hand side we have the results as I have outlined what they might look like for the free particle. So the first thing we did for our particle in a box was to express the initial conditions as an infinite sum of the time t equals 0 form of our stationary state wave functions. The second thing we did in manipulating this expression to attempt to find a formula for the c sub n was to multiply on the left by a particular stationary state wave function. Not n, m. So we multiplied by root 2 over a sine m pi over a x psi of x 0. This is now looking at the left-hand side. So we multiplied by this, and we integrated from 0 to a. This integral is taken dx. It's important to note now that this is not the wave function psi, this is the complex conjugate of the wave function psi, and we'll come back to that in a moment. This integral, this is our left-hand side. If we do the same thing to the right-hand side, you end up with an integral dx that you can push inside the sum. You can pull out some constants, and all you're left with then, the only x dependence comes from the sine function here and the sine function you're multiplying in. So we ended up with a sum from n equals 1 to infinity of c sub n, our two root 2 over a factors from our two wave functions multiply together, just give us 2 over a. And what we're left with inside the integral is sine of m pi over a x sine of n pi over a x dx. So that was our expression, and the nice feature about this is that the sine functions had an orthogonality condition on them that allowed us to take this integral from 0 to a and express it as delta mn. The sine functions, if m is not equal to n, will integrate to 0 over this interval. And if m is equal to n, you just end up with 1. I should be including this factor out front in the expression for the orthogonality. What that means is that the sum collapses. The only remaining term is the term from Cm. So our right-hand side just becomes Cm. This gave us our formula for Cm being equal to the integral from 0 to a of essentially root 2 over a sine m pi over a x times our initial conditions, psi of x 0. This was a very brief overview of what we did back when we were talking about the particle in a box. Now, continuing this analogy into our free particle case, again, the first thing we're going to do is left multiply by the complex conjugate of the wave function. Now, the wave functions that we're working with now are stationary state solutions to the time-independent Schrodinger equation for the free particle. And what those look like, if I evaluate them at t equals 0, is e to the minus I kx. Now, I'm leaving off normalization constants because I don't know what they are at this point, but while I have a k in this integral, I shouldn't use k here. This is the same as saying I have an n in this sum, so I shouldn't use n in the function that I'm multiplying through. Things will just get confusing. So I'm going to call this k prime. So I've left multiplied by k prime. I have my wave function, my initial conditions, and again I'm integrating. Now I'm integrating from minus infinity to infinity, and I'm integrating dx. This is what I get for the left-hand side, just following by analogy from what we did for particle in a box. The right-hand side, in this case, now instead of having a sum over n, I have an integral over k. What I'm multiplying by from the left is again the e to the minus I k prime x, but this integral that I'm doing, that's an integral dx. So I can exchange the order of integration by k and integration by x. So I'm going to write this right-hand side now a little differently. We have the integral of minus infinity to infinity dk. Then we have phi of k, which is not a function of x, so I can pull it out of my integral over x, same as I could pull my c sub n out of this integral dx. Sorry, phi of k, not phi of x. What I'm left with then is the integral from minus infinity to infinity dx e to the minus I k prime x e to the I k x. Now, in order for this term to be meaningfully, in order for this integral to collapse, like the sum collapsed here, we have to have some sort of orthogonality condition. The orthogonality condition for the sine functions from 0 to a was fairly straightforward. The orthogonality condition that applies here for this, where we are integrating over an infinite domain of something with a continuous parameter, k prime and k are continuous parameters that can take on any value, is not a simple Kronecker delta. It's a little different, but it looks very much the same. What you end up with here is called a Dirac delta function, and we will meet these Dirac delta functions in more detail later. If you're interested, there is a video lecture posted on the Dirac delta function and what its properties are. But for our purposes here, this expression evaluates to a Dirac delta function. A Dirac delta function is defined essentially as an infinitely narrow distribution. If you treat this as a distribution that only is non-zero at a particular value, the delta function by default is defined to be non-zero only for its argument equal to 0. This is effectively a distribution that only has non-zero values, only has support for k equal to k prime. If you treat this as a distribution, and you examine the expression integral from minus infinity to infinity dk of phi of k delta of k minus k prime, if this is a distribution, we're integrating a distribution times a function. This is the expected value of phi of k, subject to the distribution given by the delta function. The delta function, acting like an infinitely narrow distribution, then simply pulls out the value that phi of k has when k equals k prime. Since this is infinitely narrow, phi of k is effectively a constant over the non-zero domain of the delta function. So it's just effectively averaging a constant over this domain. So this whole integral here is equal to phi of k prime. That's what it means for an integral to collapse. And like I said, if you're not entirely clear on how the delta function works, there's another video lecture on how to go about, or how to understand what the delta function can do for you. For now, notice that we can re-express this phi of k prime then in terms of our left-hand side. Phi of k prime is equal to the integral from minus infinity to infinity of e to the minus I k prime x psi of x0 integral dx. This completely determines phi of k. This is the real genius behind what's called Fourier analysis. What we were talking about in the case of the particle in a box was really Fourier series, and now we're talking about Fourier analysis. The way the math behind this is usually defined is in terms of something called the Fourier transform. The top two equations here are essentially definitions of the Fourier transform. We have some function of x. This is like our wave function as a function of time, and it's being expressed as an integral of some function of k multiplied by e to the ikx, integral dk. This function f, capital F of k, can be determined by essentially what we did in the previous slide, an integral from minus infinity to infinity dx of the function lowercase f of x times e to the minus ikx. The 1 over root 2 pi factors here are customary. Some authors use them, some authors define them slightly differently. It depends on the specific definition of the Fourier transform that you're using. But you can see the nice symmetry between these two equations. You have your 1 over root 2 pi in both equations. You have an integral from minus infinity to infinity in both equations. You have e to the ikx here, positive, and e to the minus ikx here, negative. That's the only difference. Then you have a function of k, integral dk, function of x, integral dx. Up to labeling x and k differently, the only difference between these two equations is the sign in the exponent. There's a lot of really nice math that comes from using Fourier transforms. Just to give a very brief example, if you're interested in processing astronomical images, for example, or any images really, treating the image as a function of this k parameter, which is a spatial frequency parameter, instead of treating the image as a function of x, as a function of which pixel you're looking at, you can do some very powerful analysis to identify features, for instance. High spatial frequency features versus low spatial frequency features. Smoothly varying backgrounds versus the boundaries between objects where the image varies rapidly will have different behavior when expressed in terms of this function of the spatial frequency. From the perspective of quantum mechanics, what we're interested in is how to express our wave function as a function of position and time. Well, using the Fourier transform definition here, we can find this phi of k by the same sort of equation. Phi of k is determined by an integral dx of our initial conditions times a complex exponential. Knowing what phi of k is, we can then determine what phi of x and t is. So again, our initial conditions determine our constant multiples essentially of our stationary states, these complex exponentials, which then gives us our overall wave function and how it behaves. To check your understanding, here is a simple example problem that requires you to apply the formulas on the previous page to go from a particular initial condition. In this case, it's a constant. Our initial wave function looks something like this. 0 everywhere except for a region between minus a and a. Your task, find the phi of k that goes with this particular function. That's about it, but before we finish talking about how to superpose these solutions, I want to look at the solutions themselves in a little more detail. Let's talk about the wave velocity in particular. This is our traveling wave solution, and we can figure out what its velocity is by looking at this argument. Which direction is this wave going? Well, if we look at a particular point on this spiral, on this e to the ikx, as time evolves, we can figure out where that point on the spiral is by setting this argument equals to a constant. Since I don't really care about what that constant is, I'm just going to set that equal to 0. So let's say kx minus h bar k squared over 2m t is equal to 0. If I continue along these lines, it's clear that in this case, if t increases, this part of this expression is getting more negative. This part of the expression has to get more positive. So that means x has to increase as well. So as t increases, x increases. That means this wave is moving to the right. The next question I can ask is how fast? How fast is it moving? And if you look at this again as setting this expression equal to 0, I can solve this and say x is equal to h bar k over 2m t. And in this case, the velocity is pretty clear. We have this constant, x equals some constant times time. Position equals something times time. This is our velocity. What this actually is, in terms of the energy of the particle, requires knowing what the definition of k is. So we have h bar over 2m, and the definition of our k was root 2me over h bar. So our h bars cancel out, and if we finish this expression, moving the 2m effectively under the square root, we get the square root of e over 2m t. So the velocity we get here is square root of e over 2m. Now, classically, what we get, we have a particle moving at some velocity and it has some energy. We know the relationship between those. It's the kinetic energy, 1/2 mv squared, gives me E. And if I solve this, I get v squared equals 2e over m, or v equals root 2e over m. These expressions are not equal to each other. That's a little strange. The velocity that we got from quantum mechanics, looking at how fast features on this wave function move, is not equal to the classical velocity. Will this hold true regardless? Do quantum mechanical particles have a different propagation behavior? That doesn't really make a lot of sense. This is actually not a problem, because what we're measuring here is the velocity of a feature on this wave. It's not actually the velocity of a wave packet. And since wave packets are the only real states that we can get, that we expect to observe in the physical universe, what we need to figure out is the wave packet velocity. In order to figure out the wave packet velocity, consider this wave packet. This is just a sum of two traveling waves with different k's, which I've now indexed k1 and k2. What I'd like you to do is think about expressing k1 and k2 as if they were near each other. So k1 is slightly less than k2, for example, or k1 is slightly greater than k2. Under these circumstances, it makes sense to rewrite these things. I'm going to define alpha as k1 plus k2 over 2, the average, times x, minus h bar k1 squared plus k2 squared over 2m t. Essentially, the sum of the argument of this and the argument of this. I'm also going to define a parameter delta, which is k1 minus k2 over 2x minus h bar k1 squared minus k2 squared over 2m t. Actually, sorry, I don't mean 2m's here. I mean 4m's here. Because I have a factor of 2 from the over 2m, and I have a 1/2 essentially from the way I'm combining the two terms. So given these definitions, you can express this as, not writing it there, as e to the I alpha plus delta plus e to the I alpha minus delta. So you see what I've done here? I've just re-expressed the arguments here as sums and differences. This is getting into the idea behind sum and difference and product identities in trig functions, except I'm doing this with complex exponentials instead. If I write this function as alpha plus delta, when I add alpha and delta, for instance, this first term gets me k1 plus k2 plus k1 minus k2. The k2's drop out, and I end up with 2k1 over 2, which is just k1 times x. Just k1x, essentially. What you want to get from this, if I express these exponentials in that way, you can factor out the alpha part. You get an e to the I alpha times an e to the I delta plus e to the minus I delta. If you're familiar with the complex exponential form of trig functions, you can probably see where I'm going with this. This is going to end up equal to e to the I alpha times cosine, actually not just cosine, 2 cosine of delta. What this looks like in the context of our discussion of wave packets is if we have an axis there, we have this cosine factor, and it's the cosine of delta. If k1 and k2 are near each other, this will be a small number. This will also be a relatively small number. So delta evolves much more slowly with space and time than alpha. So if I was going to draw this wave function, I would have some slowly varying envelope like this, and superposed on top of that, multiplied by that slowly varying envelope, is e to the I alpha, which is the sum. So if k1 is close to k2, this is going to evolve much more rapidly. So my overall wave packet is going to look something like this, where you have zeros and areas with large amplitude, areas with small amplitude, areas with large amplitude, areas with small amplitude. As time evolves, this wave packet will propagate. And if what we're interested in is the velocity with which the overall packet propagates, you can consider a point on delta, not a point on alpha. If we're interested in the velocity with which these rapidly moving peaks, rapidly oscillating peaks evolve, then we would look at alpha. But since what we're interested in now is the wave packet, we want to look at delta. We want to look at the slowly varying envelope, how quickly the slowly varying envelope moves. Now, I haven't actually constructed a fully formed, physically realizable wave packet here because I have this cosine term, which again extends all the way from minus infinity to infinity. But hopefully, conceptually, you can think about this as a sort of rudimentary wave packet. The question then is, how fast does the rudimentary wave packet move? Well, if I look at delta, and if I assume that k1 is near k2, we can see how that works out. So what I'm looking at here is delta is equal to 0, say. The same sort of argument that I was using to determine how fast a feature on a single wave moved, setting this delta equal to a constant, not caring what the constant was, and setting it equal to 0. What I get then is k1 minus k2 over 2x being equal to h bar over 4m, and then k1 squared minus k2 squared, I'm going to look at this as the difference of two squares, which I can factor, k1 plus k2 times k1 minus k2. I can then cancel out this and this, and what I'm left with is just x over 2 equals to h over 4m k1 plus k2. If I assume that k1 is about equal to k2 then, I can pretend that this is some effective average k bar. If I write that out, sorry, this is 2 k bar, twice k bar, since I have k1 and k2, and they're added together. I can then look at this, I have a 1 over 2 here, a 1 over 4 here, and a 2 here. What I end up with at the end is just going to be x equals h bar over m times k bar. This is different than the expression we got before. K bar now is going to be our average k, h bar over m to copy that over, and our k was root 2 m e bar now for k bar. Instead of k bar, I'll have e bar for my average. And then I have Planck's constant. I can cancel out Planck's constant in the denominator. I can again push my mass into the square root here. And what I'm left with then is root 2e over m times time. I forgot my times time here. All of these have a times time. So x equals something times time. This is our velocity. So here, for the wave packet velocity, we get root 2e over m. This is the classical velocity. So, problem solved. Whereas the features on each individual peak, for instance, in our wave function, traveled at one velocity, the overall wave packet traveled at another velocity. For the case of this particular wave packet, or wave packets in general, the wave packet itself travels at the velocity you would expect, except I have to be clear here now. Let me rewrite this. The velocity we get for a wave packet now, this is only approximate, so I should write it as approximately equals, and it's not twice the energy, it's twice the average energy divided by mass in the square root. So this is not exactly the classical formula because now we don't necessarily have a single energy. If we had a single energy, we would be stuck with one of those solutions to the time-independent Schrodinger equation, which have definite energy. In the case of this free particle, those definite energy solutions extended throughout all space, and that was a problem. So we don't actually have a definite energy, so we'll have some spread in energies here. And if you have a large spread in energies, you'll effectively get a large spread in velocities. And what starts off as a wave packet will not stay a wave packet very long. It will propagate at different speeds. Different parts of the wave packet will propagate faster than others. But at any rate, what this actually looks like, to make some visuals here, and I couldn't hope to draw this accurately, but if we have some wave packet at time t equals 0, delta t, 2 delta t, and 3 delta t, it's going to propagate gradually. You can see the disturbance of this wave moving to the right. Now I've drawn solid, thick lines here behind it to designate the motion of the overall wave packet. The overall packet is moving at a speed more or less determined by the slope of these thick black lines. The thin gray lines identify features. For instance, this peak becomes this peak, becomes this peak, becomes this peak. This peak is traveling at a more slow rate than the overall wave packet and is essentially sort of falling off the back of the packet. It's decreasing in amplitude as it goes. The slopes of these lines are different, meaning the features on the waves are propagating at a different speed than the overall wave packet. This is actually a general feature of many waves. It's not something we hear about very often in everyday life because we never really think about whether there might be a difference or not. Plus, most of the common waves that we work with, like sound waves for instance, don't have this property. But if you look closely, for instance, if you drop a rock in a still pond, the small-scale ripples actually behave with this different velocity. In that case, actually, the features on the wave move faster than the overall wave packet. So in that case, you could view this as sort of time reversed, where the features start at the back of the wave packet and propagate forwards. But this is really the question of what's called group velocity and the question of phase velocity. The phase velocity refers to the features in the wave, whereas the group velocity refers to the velocity of the wave packet. This is not a wave mechanics course, but there's a lot of interesting math that can be done with this. The group velocity and the phase velocity being different is one of the more interesting features of, for instance, propagation of electromagnetic waves in plasmas in space. So if you're interested in radio astronomy, for instance, you need to know about this in very high levels of detail. To give you a better feel for what this looks like, here's an animation. What we're looking at now are the real and complex parts, shown in red and blue respectively, of a hypothetical wave packet that might represent a solution to the Schrodinger equation. It doesn't actually represent a solution to the Schrodinger equation, but this is the sort of behavior we're looking at. If I track a particular pulse, say this one, I'm moving my hand to the right as I do so. Here. But I'm not moving my hand to the right nearly as fast as the overall wave packet is propagating. So the overall wave packet is propagating at effectively twice the speed of the individual features on the wave. So this is what wave propagation might actually look like for the Schrodinger equation. You can construct wave packets like this. If you add the time dependence, then you can determine how the wave packet will propagate, how it will spread out, how the individual wave features will move, and you'll know effectively everything you need to. To check your understanding, here are a few true or false questions. Don't think that because they're true or false, they're easy. Think about these in detail.
We've already met the Dirac delta function a couple of times in this course as examples. So it's good at this point since what we're going to be discussing next is the Dirac delta function as a potential, to discuss the general properties of the Dirac delta function, how it works from the mathematical perspective. What I want you guys to think of when you think of the Dirac delta function is the limit of a distribution. The Gaussian distribution, for example, rho of x is given by 1 over the square root of 2 pi as a normalization, sigma, e to the minus, say, x squared over 2 sigma squared. The limit as sigma goes to 0 of this function gives you something that is very much like the delta function. This is not the only way to define the delta function, but if we start with, for instance, this purple curve here at large sigma, and this orange curve here at small sigma, as sigma gets smaller and smaller, the distribution gets narrower and narrower and taller. As sigma gets smaller, for instance, the dependence here in the exponent of e to the minus x squared gets faster and faster, since I'm effectively multiplying the x squared by a larger and larger number. And the normalization constant out front, 1 over root 2 pi times sigma, gets larger and larger as sigma gets smaller and smaller. So thinking about this as the limit, in the limit, we have a distribution that is infinitely narrow and infinitely tall. It has absolutely no support for any values of x other than, say, x equals 0 here. So this would be, say, delta of x as a distribution. You often see delta functions written as, in terms of more conventional function notation, delta of x is equal to 0 for x not equal to 0, and infinity for x equals to 0. But this isn't a sufficiently accurate description because it doesn't tell you this property that the delta function is the limit of a distribution. It has specified integral. So you always have to add an extra condition here for something like, for instance, something like the integral from minus infinity to infinity of delta of x dx is equal to 1. That essentially sets the specific value of the infinity here such that the integral equals 1. But thinking of it as the limit of a distribution is essentially the actual definition of the delta function. Knowing that the delta function acts like a distribution allows us to do things like calculate integrals with delta functions. This is where delta functions really shine. If you have an integral of minus infinity to infinity of any function, f of x, multiplied by the delta function, if we think of this as a distribution, this is effectively the expectation of x, of f of x, the expected value of f of x, subject to this distribution given by the delta function. Now, since the delta function has absolutely no support over any values of x other than x equals 0, essentially what this is telling you is the expected value of f of x where the only region that we care about is the area very near 0. So this just gives us f of 0. Thinking about this in the context of a distribution, if we had a distribution with some very narrow width, if this width gets extraordinarily narrow, then no matter what f of x does out here, we don't care. And as the distribution becomes extraordinarily narrow, we're just zeroing in on the behavior of x over this region, which makes f of x basically look like a constant. And you know, the expected value of a constant, like if I wrote this as the expected value of f of 0, it wouldn't matter what the distribution was, it would just give you f of 0. So this is the same sort of concept. The infinitely narrow distribution effectively just pulls out the value of f of x at that point. So this is our first really useful formula with delta functions. If we integrate, it doesn't really matter what we integrate over, minus infinity to infinity will work. Delta of x times any function f of x integrating dx, we just get f of 0. We don't have to do the integral. Delta functions effectively make integrals go away. We can do this not just for the delta function of x, we can do it for delta functions of x minus anything, for instance x minus a. If we plotted this distribution, delta of x minus a, it's going to be 0 except for the point where x equals a. So at x equals a, the argument is delta function goes to 0. So effectively, we've just translated our delta function over by some distance a. It's not the most clear notation. This is the x-axis, and this is a. So what this is going to do, and you can think about doing a change of variables, some sort of u substitution where u equals x minus a, it's just going to give you the value of f at the point where the delta function has support. So this is going to give us f of a. So if we have some way of expressing the delta function, or if we're just using the delta function itself translated, we can pull out the value of f at any point. We can do more with this, though. Instead of just subtracting values in the delta function, we can evaluate the delta function of a function. Again, what we're working with here is integrals multiplied by some other function, since that's how delta functions most often appear in this context. So, if I have coordinates, and what I'm interested in now is g of x plotted as a function of x, suppose g of x looks something like this. I have some places where g of x crosses the x-axis, where g of x equals 0. I know the delta function is going to be 0 for any argument that's non-zero. So essentially what this is going to do is home in on these regions where g of x is equal to 0. And I drew 5 of them here. It doesn't really matter how many there are. As we consider a broader variety of potentials when we solve the time-independent Schrodinger equation, we get a broader variety of solutions. The potentials that we're considering next have a couple of unique conceptual features that I'd like to talk about in a little more detail. Essentially, when you're trying to solve the time-independent Schrodinger equation for a complicated potential, for instance, a potential v of x that's defined as a function of one region and then another region having a separate function, you may end up with a well-defined solution in region 1 and a well-defined solution in region 2. For instance, if we had, say, a psi of x that was wave-like in region 1 and behaved differently in region 2, for instance, just smoothly curving down to join with the axis, it's useful to be able to combine these two solutions. And the question then is, how do they match up at the boundary? This is the question of boundary conditions, which is the subject of this lecture. The boundary conditions that you need to match two solutions of the Schrodinger equation, the time-independent Schrodinger equation now, can be determined more or less from consideration of the time-independent Schrodinger equation. What is the allowed behavior of a solution? We've discussed the time-independent Schrodinger equation in detail. You know now that this is the kinetic energy operator, and this is in some sense the potential energy operator. But let's focus on the kinetic energy operator, since it has this second derivative of psi. That's where we're going to get a good notion for what's allowed of psi and what's not allowed of psi. Suppose we had a step discontinuity. Is that allowed? What our psi would look like under those circumstances is something like this. Maybe we have a psi that comes in on one side and goes out on the other. If this happens in an infinitely narrow region, we say psi is step discontinuous here. If we wanted to look at, for instance, the kinetic energy associated with a step discontinuity like this, we're going to need to take a second derivative of psi. So if I take the first derivative of psi, the first derivative of a step function is a delta function. If it's not obvious why that's the case, think about what you would get if you integrated from one side of the delta function to the other side of the delta function. If you integrate from, say, a point here to a point here, you'll get 0. If you integrate from a point here to a point here, you'll get 1. Or you'll get some multiple of 1, depending on if you're, say, multiplying by a delta function, like 3 times a delta function or 5 times a delta function. You get 3 or you get 5. So as a function of integrating from this point to this point, you would get 0, 0, 0, 0, 0, some constant, and then increasing your upper limit on your integration doesn't change your final answer. So integrating a delta function from some point on one side of the delta to some variable point gets you a step. And that's more or less, if you go back to the fundamental theorem of calculus, what you expect if you say integrate the derivative as a function of the upper limit of the integral. So the first derivative of our wave function psi here gives us a delta function. If I take then a further derivative, the second derivative with respect to x of my wave function psi, what I'm going to get is going to be the derivative of a delta function. It's going to be 0 away from... Over the past few lectures, we've developed the machinery necessary to solve the time-independent Schrodinger equation with a potential given by a delta function. We've talked about bound and scattering states, and the delta function potential will actually have both solutions, or both types of solution. And we've talked about boundary conditions, which will help us match solutions in the areas away from the delta function, where we can easily express the solutions, we'll be able to make those solutions match at the delta function itself. So, what we're working with is a delta function potential, v of x, and v of x under these circumstances looks something like this. It's 0 everywhere except at a specific point. So we're looking now at v of x as a function of x. It's 0 everywhere except at the origin here, x equals 0. And there, it goes to negative infinity. I'm defining v of x to be minus a times delta of x because we don't necessarily know exactly what the strength of this delta function potential is. You can have different strengths of delta function. If you treat a delta function as a distribution, of course, it has to be normalized. But in this case, we're treating it as a representation of a potential. So we need some constant here which determines the strength of the potential relative to sort of a unit normalized potential. What our solutions will look like under these circumstances depend on the energy of the solution. For instance, if we have an energy up here, E greater than 0, we know we have, in these regions away from x equals 0, we know we have sort of traveling wave solutions. We don't know exactly what happens at x equals 0 here, but we know these are going to look like solutions to our free particle potential, which we discussed a few lectures ago. On the other hand, if we have an energy below 0, then we know what the solutions have to look like. When our energy is below our potential, our solutions have to curve away from the axis. And if we're going to have something normalizable, we need to have the solutions eventually, as they curve away from the axis, instead of curving up to infinity or curving down to minus infinity, they have to just sort of smoothly join in with the axis itself. And we have to have that on both sides of the boundary. But we still don't know what exactly happens at the boundary. That's where our boundary condition matching comes in. But first of all, let's consider what the solution looks like away from the boundary. And in this lecture, I'm going to focus on the bound state, the state where the energy of the state is less than 0. For the bound states, energy less than 0, if what we're looking at is away from x equals 0, then we know v of x is equal to 0. So our time-independent Schrodinger equation becomes minus h bar squared over 2m times the second derivative of psi with respect to x is going to be equal to E times psi. We know the energy now is negative, so we're going to have a negative quantity on the left and a negative quantity on the right. In order to consolidate some constants, let's consider moving the 2m over h bar squared over to the right-hand side here by multiplying through 2m over h bar squared. We'll end up then with d squared dx squared of psi is equal to k squared psi, where I'm defining k to be equal to something that looks a little strange.
square root of minus 2me all over h bar. To make the signs clear here, energy is negative. So what we're actually looking at here is the square root of a positive number. We've got a negative energy, positive mass, and negative from the minus sign, negative from the energy. So we're taking the square root of a negative quantity here. So our k constant here is going to be real. Looking at our equation here, you can look at this and think second derivative is giving me something squared times my wave function back. Well, I know what the solution to that sort of differential equation is. It's psi of x is equal to a e to the minus kx plus b e to the kx. This is our general solution, and as is typical in quantum mechanics, if what we're going to have is normalizable, then we can set some conditions on this. Our actual space looks like this. We have, as a function of x, our potential is blowing up at x equals 0. So we know we have a solution away from x equals 0. That's what we're trying to find here. If we want a solution on the right here for x greater than 0, and we want our wave function to be normalizable, we know we have to have b equals to 0. Because if we have a non-zero b, integrating, say, the squared modulus of the wave function from 0 to infinity will give us infinity, because we have something growing exponentially here. So for x greater than 0, we know b must be equal to 0. Similarly, for x less than 0, we have to have a equal to 0, because otherwise we have something growing exponentially as x goes to minus infinity. What our overall solution then will look like is in region 1 here, let's say psi 1 of x is going to be equal to a times e to the minus k, or to the e to the kx, whereas in region 2 we're going to have our solution psi 2 is equal to b e to the kx with the minus sign. So e to the minus kx over here, e to the kx over here. What our solution then is going to look like overall is something like this and something like this, and we still don't know exactly what happens at the boundary. So let's figure out what actually happens at the boundary. Our boundary conditions, and we had two of them, was first of all that psi was continuous, and second of all that the first derivative of psi was continuous unless the potential went to infinity. Let's consider the first of those boundary conditions here. Psi continuous. In order to have psi continuous, what this means is that in our regions here we have psi 1 on the left and psi 2 on the right of x equals 0 here. If we're going to match these two conditions continuously, we have to have psi 1 of x equals 0 equal to psi 2 of x equals 0. If I evaluate my solution on the left at the boundary and my solution on the right at the boundary, I have to get continuity, I have to get equality. So if we go back to our general solution, we had our psi 1 was, flipping back a slide a moment to get my a's and b's straight, our psi 1 was a times an exponential growing with x, and psi 2 was b times an exponential decaying with x. So going forwards a slide, our solution in region 1 is a e to the kx. If I'm evaluating that at x equals 0, I have to get something that's equal to b times e to the minus kx evaluated at x equals 0. Now when I evaluate the exponential parts here at x equals 0, I'm substituting in 0 in the exponent. Anything to the 0 is 0, or is 1. So both of these terms become 1, and I'm just left with a equals b. That helps a lot, but it doesn't tell us everything. Our second boundary condition was that the first derivative of the wave function, d psi dx, was continuous. But it's actually not continuous in this case. We had a condition on this boundary condition. We can only apply this boundary condition when the potential remains finite. And in this case, we have a delta function potential at the origin, so we're going to actually break this boundary condition in this case. We're not going to break it beyond all hope of recovery, though. The question is, what does d psi dx do at the boundary? The way to solve this problem is to go back to the Schrodinger equation, the time-independent Schrodinger equation, and keep in mind that our potential now is delta of x. It's a delta function. We actually had a minus sign and an a in front of that. So if we go back and think about what happens with delta functions. Delta functions are only really meaningful when you treat them as distributions and integrate. The trick here, then, is to think about integrating the Schrodinger equation. Where does it make sense to integrate the Schrodinger equation? Well, I don't know anything about the solution. Well, I know everything about the solution away from the boundary, but I don't know what happens at the boundary. So let's just integrate over the boundary. Let's integrate from, say, minus epsilon to epsilon, just integrating over the boundary. To rewrite that, what we've got is minus h bar squared over 2m times the integral from minus epsilon to epsilon of second derivative of psi with respect to x squared. That's our first term. Then substituting in for our delta function, we have minus a integral from minus epsilon to epsilon of delta of x, psi of x. And then on the right-hand side, we have an integral from minus epsilon to epsilon of energy, which is a constant and can come out, psi of x. All of these integrals, and I've left them off all over the place, are taken with respect to x. So we have three separate integrals here, and we can figure out what each of these terms look like. Our left-hand term, we have the integral with respect to x of a second derivative. So that's easy. We're just going to get the first derivative. Minus h bar squared over 2m times d psi dx evaluated at the endpoints, epsilon and minus epsilon. So far, so good. The second term here, we have minus a, and now we just have a delta function in an integral. Delta functions just pull out the value of whatever else is in the integral wherever the delta function, or wherever the argument of the delta function goes to 0. In this case, delta of x is going to pull out the x equals 0 value of psi. So this is just going to give me psi of 0. On the right-hand side here, I'm going to get something. But the key point about this integral is that we're only integrating over the boundary. We're going from minus epsilon to epsilon. You can probably see where I'm going with this. I'm going to let epsilon be a very small number. As minus epsilon goes to epsilon, or as epsilon goes to 0, I'm essentially integrating this function psi from 0 to 0. So I'm not going to get anything meaningful here. I'm just going to get 0. So this is actually all right. What we've gotten from consideration of integrating the time-independent Schrodinger equation over the boundary with the delta function potential is a condition that tells us how much our first derivative changes at the boundary. If I rearrange this expression here, I'm getting derivative of psi with respect to x evaluated at epsilon minus what I get if I evaluate it at minus epsilon. That's just equal to, rearranging my constants, what is it going to be equal to? Minus 2ma over h bar squared times psi of 0. So that's actually pretty nice to work with. Let me try and move this over a little bit to give myself more space to work. And what we're left with then is substituting our general expression for our solutions for psi, now away from the boundary, into this expression. So we had d psi dx, evaluating this at positive values of epsilon, means I'm in region 2, I'm on the right, which means I'm working with psi 2, evaluating that at x equals 0 on the boundary, subtracting d psi 1 dx, evaluated at x equals 0. So for now I'm letting epsilon go to 0, and I'm looking at just the values of the first derivatives. This is our left-hand side over here. We can substitute in values for that because we know what these expressions are, and furthermore, we know that a is equal to b
in our expressions for the general solution. So if you refer back to our definitions earlier, what you get here, you're taking the derivative of an exponential, which brings down the k, and we get minus bk e to the minus kx, and we're evaluating this e to the minus kx at x equals 0. So this e to the minus kx is just going to go to 1. So I'm not going to bother writing it. I just get minus bk for the first derivative of psi in region 2 at the boundary. For the first derivative of psi in region 1 at the boundary, now I'm subtracting it because this is the second endpoint. I get a very similar expression. Again, bk e to the now plus kx. And again, evaluating this at 0 means my e to the kx is just going to be 1. The right-hand side now, we had constants minus 2ma over h bar squared, and then the value of psi at 0, is just going to be b e to the plus or minus kx. Again, substituting in x equals 0. It doesn't matter if I'm considering the plus or the minus, region 1 or region 2. This is still going to be just 1. So far so good. I can cancel out all of my b's. And what I'm left with, when I simplify a little bit, is minus 2k being equal to minus 2ma over h bar squared. This is the sort of condition we got when we were looking at how the boundary conditions affected the solution to the particle in a box potential, the infinite square well potential. When we actually looked at what the boundary conditions required, and in the case of the particle in a box, it was that the wave function went to 0 at the endpoints of the box, we got quantization. We have quantization again here, except we have a strict equality. There are really no more unknowns in this expression. If you manipulate this further, k equals ma over h bar squared, keeping in mind that k is equal to the square root of minus 2me, where e is a negative number, over h bar, you can solve for the energy. And what you get is that energy is equal to minus ma squared over 2 h bar squared. We have quantized energies. What our wave function then looks like, so far, what we know is that psi of x is equal to, on the left, e, and now substituting back in to the definition for k, e to the ma(x) over h bar squared, if x is less than 0, and e minus ma(x) over h bar squared, if x is greater than 0. Now, all of this had a b multiplying it out front, which I canceled out here. So my first derivative boundary condition did not help me find b. But there's one more fact that we know about wave functions like this, and that is that the wave function has to be normalized. So if you want to normalize this, you calculate the normalization integral, which you all should know by now. Integral of psi star psi dx has to be equal to 1. You can substitute in this definition for psi, set it equal to 1, do the integral, and find out what b is. This was one of our activities on day 4, so refer back to day 4 if you want to see a little bit about how to normalize a wave function like this. To summarize our results, this is what our normalized bound state solution actually looks like. What you find for the normalization constant is the square root of ma over h bar out front. And now instead of writing it as a piecewise function for positive and negative x, I'm expressing this as an absolute value of x in the exponent. The energy associated with this was minus ma squared over 2 h bar squared. We are quantized, but we only have one bound state solution, singular, and this is what it looks like. For a delta function potential, you get these two exponentials decaying as x moves away from the origin. To check your understanding, consider the following two questions. Why is there only a single bound state? And can any initial condition be expressed as a superposition of bound state solutions in this case? We've developed the machinery to solve the time-independent Schrodinger equation for the delta function potential by connecting solutions covering the regions away from the delta function and matching them together with boundary conditions at the delta function itself. The last lecture discussed the bound state solution. This lecture discusses the scattering state solutions. To put this in context, what we're talking about is a potential v of x given in terms of a Dirac delta function. A now is just a constant that defines how strong the delta function actually is. So our potential is everywhere 0, except at some point where it goes to negative infinity. This is a plot now of v of x as a function of x. What we discussed in the last lecture was the bound state solution. What happens if we have an energy E of our state that's less than the potential, less than 0, less than the potential away from the delta function? And what we got was a wave function psi of x that looked something like this. Going down towards 0, away from the actual position of the delta function. I haven't done a very good job drawing this, but I think you get the idea. The scattering state solutions, by contrast, have energy greater than 0. So we're talking about solutions with energy E up here. At regions away from the delta function, we have basically the behavior of a free particle. We get traveling waves at regions away from the delta function, away from x equals 0. We don't really know what happens at the origin, but we know what our solutions should look like, and we should be able to use our boundary condition matching to figure out what happens at the origin. So what do our scattering states look like? Well, away from x equals 0, we have v of x is equal to 0. That means our Schrodinger equation, the time-independent Schrodinger equation, looks like minus h bar squared over 2m times the second derivative of psi with respect to x. No potential now is just equal to E times psi, where energy now is strictly greater than 0. We can manipulate our constants, much how we did when we were talking about the bound state, and express this as d squared psi dx squared equals minus k squared psi. Now I'm defining a slightly different k than when I was talking about the bound state solution because we have a different sign for the energy. Instead of having k be a negative or imaginary now, I'm going to again have k be positive and real by saying k is equal to the square root of 2me over h bar. If you recall when I was talking about the bound state, I had e less than 0 and I had a minus sign inside this expression. Looking at this ordinary differential equation, we can write down the solution. And the solution is, let's say psi is equal to a e to the I kx plus b e to the minus I kx. When we take the second derivative of this exponential, we'll bring down an ik quantity squared, which will give us a minus k squared. Since we're talking only about regions away from the delta function, we really actually have two general solutions here. We have psi1 for regions for, say, x less than 0, and we have psi2 for x greater than 0. Psi2 now, to the right of the delta function, is going to look very similar, and it's going to be f e to the ikx plus g e to the minus ikx. I should write this as a capital G, sorry. Instead of saying C and D, I've jumped ahead to F and G to eliminate any possible ambiguity if we have to assign future constants, for example, E. So, we have our two general solutions covering regions for negative x and for positive x. What happens at the boundary? How do we match these solutions up? Our boundary condition matching, in terms of these two general solutions, is a two-stage process. We have two distinct boundary conditions, and the first is that psi is continuous. What that means is that psi1 of 0, our solution for negative x, evaluated at the boundary at x equals 0, must be equal to psi2 of 0, our solution for positive x's evaluated at the boundary. If I substitute 0 in for these exponentials, for x in these exponentials, what I end up with here is reasonably straightforward. A plus b equals f plus g. That's the result of our continuity boundary condition. And it helps, but it doesn't help all that much. We only get a single equation out of this, so we need to do more. The first derivative boundary condition is that the first derivative of psi is continuous, provided that the potential is finite. However, in this case, our potential is given by delta of x, which does not remain finite at x equals 0. The trick that we used when we were discussing the bound state solution was to effectively integrate the Schrodinger equation dx from one side of the boundary, minus epsilon, to the other side of the boundary, plus epsilon. When we integrate this, we should still have an equality, integrating the terms on the left-hand side and integrating the terms on the right-hand side. And knowing the properties of the delta function, we can simplify this integral greatly. I refer you back to the notes for the last lecture to see what this actually works out to be. What it tells you is that d psi dx, the first derivative of psi, which we get from integrating the second derivative of psi, evaluated at epsilon, and then subtracting the value evaluated at minus epsilon, essentially the change in the first derivative as we go from one side of the boundary to the other, is equal to minus 2 times m times a, the strength of our potential, over h bar squared, times psi evaluated at 0. The right-hand side here we actually got from the integral of our delta function times psi. So this is our boundary condition here, appropriate for use with delta function potentials. This tells us about the behavior of the first derivative of psi as we cross the boundary. So we're going to need to know what our first derivatives actually are. Well, psi1 was equal to a e to the ikx plus b e to the minus ikx. So if I take the first derivative of this and evaluate it at effectively 0, some very small quantity, what I'm going to get for d psi1 dx evaluated at 0, essentially, plus or minus epsilon. I'm looking at psi1 now, so I'm talking about the negative half plane, negative x's. What I get is ik is going to come down from both of these, and I'm going to get an a minus b. I can do the same sort of thing for psi2, which was equal to f e to the ikx plus g e to the minus ikx. When I take the first derivative of this, d psi2 dx, and evaluate it at the boundary, I'll end up with ik times f minus g, by similar reasoning. That means the left-hand side here, which I can calculate by looking at the derivative of psi for positive values of x, as x goes to 0, this expression, and subtracting the first derivative of psi for negative values of x as x goes to 0, this expression, what I end up with is ik times f minus g minus ik times a minus b. That's the left-hand side now of our expression up here. Our right-hand side is minus 2ma over h bar squared times the value of psi at x equals 0. Now, if you look at either one of these definitions, you can see what happens when we substitute in x equals 0. We get a plus b for this one, or f plus g for this one, and I have a bit of a choice as to which one I want to use. In this case, I'm going to use a plus b, and you'll see why in a moment. What we end up with now, if you manipulate this expression a little bit and define a useful constant, in this case the constant is going to be beta, just to save some writing. Beta is defined to be ma over h bar squared k. What we end up with is f minus g is equal to a 1 plus 2i beta minus b 1 minus 2i beta. And this is the result of our first derivative boundary condition. There's effectively no restriction on these solutions so far. We have something similar to what we had for the free particle. There were no boundaries that were terribly restrictive. We did not end up with a quantization condition. We did not end up with enough of a restriction on our solutions that we ended up with something straight normalizable. But we have our two equations now involving a, b, f, and g. That, unfortunately, is two equations to go with four unknowns. We have our definitions of psi in terms of a, b, f, and g, and these e to the I kx, e to the I minus kx, e to the minus I kx. And then we have our two equations relating a and b and f and g. It seems like we're not going to be able to come up with a very rigorous solution here. But we can actually do a little better if we start thinking about what the initial conditions might actually be. First of all, note that these solutions are the spatial part, and if we add a temporal part to come up with an overall solution for an overall wave function, we'll end up with the same sort of traveling wave states that we had for the free particle. The time dependence for those states was essentially e to the minus I e t over h bar. If you look at each of these terms, you can see this is a plus I kx going with a minus I e t. As time increases, space must increase here in order to maintain a constant phase. So, as in our discussion of traveling waves, the plus I kx here, for positive values of k, is associated with the wave propagating to the right. So if you think about our boundary here at x equals 0, in the space to the left of the boundary, where we're considering psi 1, we have a wave coming in from the left, whose amplitude is given by a. Conversely, the term with b in it here is associated with e to the minus I kx. That represents a wave traveling away from our boundary with amplitude b. The bound states for the finite square well potential are discussed in another lecture. The subject of this lecture is the scattering states for the finite square well, which can be derived in a very similar way. The overall context is our finite square well potential, a potential v of x that's defined to be 0 for x less than minus a, 0 for x greater than a, and a constant minus v naught for x is in between minus a and a. So this is an even potential, and we exploited that fact when we were discussing the bound states where the energy is negative, to figure out what those states look like. And the lowest energy bound state that we found ended up looking something like this. Smoothly joining the axis as x becomes large and negative, smoothly joining the axis for x becomes large and positive, and a smooth curve in between minus a and a inside the well. We found this by examining the general solution for regions less than minus a, between minus a, and greater than a, and smoothly matching those piecewise defined solutions together with the boundary conditions for the Schrodinger equation. We're going to take a very similar approach here, except instead, this time, we seek scattering state solutions, where the energy E is everywhere above the potential, and as a result, our solution can extend all the way from minus infinity to plus infinity. The solutions that we get will end up looking a little something like this, but we'll see what they look like momentarily. Given this potential, we're looking at three distinct regions, and we're trying to solve our Schrodinger equation over those regions. Our Schrodinger equation, as always, is minus h bar squared over 2m, second derivative of psi, with respect to x, plus v of x psi is equal to e times psi. Now we know away from our discontinuities, v of x is going to be a constant, so we expect the overall properties of this solution to be relatively straightforward. And indeed they are. Our three regions are divided by x equals minus a and x equals a. For x's less than minus a, our potential here is going to be defined to be 0, and our Schrodinger equation then simplifies to something of the form second partial derivative of psi with respect to x is equal to minus k squared psi, where k is defined as, for instance, in the case of the free particle, as 2me over h bar squared. K squared is 2me over h bar squared. We know the solution to this case for the free particle gave us traveling waves, and we're going to reuse that form of our solution here. We'll have psi being equal to a e to the I kx plus b e to the minus I kx. Traveling waves moving to the right and traveling waves moving to the left. Of course, nothing is traveling about this now, since we're just looking at solutions to the time-independent Schrodinger equation. But if you, as before, add the time dependence to these solutions, you find that they are indeed traveling waves. That was for the region where x is less than minus a. The region where x is greater than minus a is going to give us something very similar. It's going to give us an exactly identical Schrodinger equation, and it's going to give us exactly identical solutions, except we'll be working with slightly different constants. Our wave function psi is going to be given by, in this case I'll call it f e to the I kx plus g e to the minus I kx. Now I've used different constants for f and g, but the same constant for k, since overall we're trying to solve the same Schrodinger equation, so we have effectively the same value for e, and therefore the same value for k, as defined in terms of 2me over h bar squared. For the region in between minus a and plus a, we're going to have a slightly different Schrodinger equation. It's going to give us essentially the same sorts of solution, though, but I'm going to write them slightly differently. Our overall Schrodinger equation will become, as before, the second derivative of psi is equal to minus some constant times psi, but the constant is going to be different. The constant, instead of being 2me over h bar, is going to be 2m over h bar squared times e minus v. E minus v naught, but since, e minus v of x, let me step this out a little bit, e minus v of x, since v of x in the region between minus a and a is minus v naught, this is effectively e plus v naught. So we have our constants here, and in the case of these solutions, we could easily write them in terms of traveling waves with L instead of K, but it's actually slightly easier here to write them instead in terms of sines and cosines. This is just as general a solution, but let's write psi in this regime as c times the sine of Lx plus d times the cosine of Lx. Apologies for being messy here. These are then our three general solutions. We can call them psi 1, psi 2, and psi 3, if you like. But these are general solutions to the Schrodinger equation, the time-independent Schrodinger equation, for these three regions. The next step is to mesh these solutions together with our boundary conditions. And we had two boundary conditions, and if you're unfamiliar with the boundary conditions that we'll be using under these circumstances, I suggest you go back and examine the lecture on boundary conditions. The first of our boundary conditions was that the wave function is continuous, and the second was that the first derivative of the wave function is continuous. And there are sound physical reasons that that has to be the case. For instance, if the wave function itself is discontinuous, the expectation value for the kinetic energy of the wave function diverges to infinity and cannot be a physical state. But, considering the boundary at x equals minus a, ensuring that the boundary condition holds means meshing the value of this wave function at minus a and the value of this wave function at minus a. Excuse me. So, let's go ahead and plug that in. Our boundary condition at minus a here is going to give us a e to the minus I kx plus b e to the I kx, oh, sorry, not x, we're plugging in for x, minus I ka, and then b e to the I ka, since I'm substituting in minus a for x. That's what I get for this region. That has to be equal to what I get for this region, which in this case I will write as minus c sine La plus d cosine La. Now if I substitute in minus a for x here, I would actually get the sign of minus La, but since sine is an odd function, I'm pulling the minus sign out front and writing this as minus c times the sine of La, just to keep the arguments inside all of the trig functions consistent. So this is our boundary condition for the continuity of psi. We have another boundary condition for the first derivative of psi, and you can write that down more or less just as easily by noting that in either of these cases, taking the first derivative with respect to x is going to bring down an ik. So we'll end up with ik times the quantity a e to the minus I ka plus b e to the ika, and I've screwed up the minus signs already. Since the sign here is going to bring down a minus ik, when I factor out the ik, I'll still be left with the minus sign. So that's our first derivative of the wave function in this region. And if we're going to ensure continuity of the first derivative, we must also equal the first derivative of this wave function evaluated at the boundary. Taking the first derivative of sine and of cosine is going to pull out an L, so I'm going to have something that looks similar. I'm going to have L times a quantity, then the derivative of sine is cosine, C cosine, LA, and the derivative of cosine is minus sine, so I'm going to have minus D sine, and I'm evaluating it at minus LA again, which I'm going to use to cancel out this minus sign. Sine of minus an argument is minus the sign of the argument, so I have two minus signs, and I end up with a plus overall. So these are our boundary conditions at x equals minus a. We get very similar expressions for our boundary conditions at plus a, but before I write them down, I'm going to make an additional simplification. Since what we're considering here are scattering states, for instance, in our consideration of the scattering of scattering states off of a delta function potential, we had a wave incident from the left, a wave bouncing back to the left, and we had a wave that was transmitted through. That was for a single potential. If we have some potential well, we're still probably interested in the same sort of process. A wave incident from the left, a wave scattering back to the left, and a wave transmitted through to the right. We're probably not so concerned with the wave coming in from the right, so I'm going to get rid of that one, and that amounts to setting g equal to 0 for our general solution in this regime. So we're no longer working with a fully general solution, but we have one fewer unknown to work with since we've gotten rid of g, which simplifies the algebra quite a lot. Makes it solvable, in fact. So, going through the same procedure we did at minus a, instead evaluating the wave function and its first derivative at a, the expressions we get are c sine LA plus d cosine LA is equal to f e to the I k a. That's from just continuity, plugging in x equals a into this expression and setting it equal to plugging x equals a into this expression. Our first derivative, again, by taking the first derivative and repeating the process, gives you L times c times the cosine of LA minus now d times the sine of LA. We have a minus sign here because now we get the minus sign from taking the derivative of cosine, and we're substituting in plus a, so what I did to get a plus sign here no longer works. I can't factor a minus sign out. That's our left-hand side, and it's going to be equal to, first derivative of this brings down an ik, as before, ik f e to the I k a. So those are our general boundary conditions, and we have essentially 5 equations and 4 unknowns here. We have a, b, c, d, f, and k, all being unknown. K is determined entirely by the energy, and since what we're working with here are scattering states, linear algebra is very useful for quantum mechanics. We've already used a lot of the notation and terminology of linear algebra when we say, for instance, that two wave functions are orthogonal to each other. But quantum mechanics puts its own spin on things. In part, for instance, because we're not dealing with, say, three-dimensional Cartesian coordinates. We're dealing with a complex vector space that describes the state of a physical system. So dealing with complex numbers and dealing with vector spaces in a more general way is very useful, especially as we move away from simply solving the Schrodinger equation, but to manipulating solutions to the Schrodinger equation to infer the properties of physical systems. So linear algebra will be useful in the coming chapters. To justify why this is useful, I'm going to make a couple of analogies. There are some things that we can say on the basis of vectors. We have vectors, A. We can make dot products between two vectors. We can express a vector A in, say, Cartesian coordinates,
axx hat plus ayy hat plus az z hat. We can also express some vector A in a different coordinate system. I'll call it a sub alpha, not x hat, excuse me, alpha hat plus a beta hat plus a gamma hat, where now the hatted vectors here are unit vectors, and the numbers ax, ay, az, a alpha, a beta, and a gamma are simply coordinate, or simply components. They're simply numbers. If these x, y, and z, alpha, beta, and gamma represent different coordinate systems, we can still say that this is the same geometrical object, A. The vector A is not changed by expressing it in different coordinate systems. It exists independent of any coordinate system. And of course, we can also take dot products of unit vectors with themselves and get 1. Quantum mechanically speaking, each of these expressions in terms of vectors has an analog. The vector A, that's what we've been talking about so far as, say, psi of x. That's the state of the physical system, the wave function. Taking the dot product of two vectors, that's our integral from minus infinity of, say, psi sub a star of x times psi sub b star of x integral dx. Expressing a vector in terms of one coordinate system versus in terms of another coordinate system is essentially the difference between looking at the state of the system as the wave function psi of x versus the wave function in momentum space, the wave function phi of k, which we got by taking Fourier transforms back when we considered the free particle. Our whirlwind tour of linear algebra continues with linear transformations. Here, we'll write linear transformations with hats. For instance, t with a hat, capital letters especially, will be considered to be transformations. A linear transformation, quite simply, is a transformation that's linear. What it means for something to be linear is if I apply the transformation to A times the vector alpha plus B times the vector beta, I get A times the transformation t applied to the vector alpha plus B times t applied to the vector beta. If this sort of identity holds, the transformation you're working with is linear. It's difficult to work with transformations in general, so it's useful to consider what a transformation looks like if we have a vector in a particular basis. So suppose I have a set of basis vectors, x sub I. I'm not telling you how big this set of basis vectors is, but if we have our transformation applied to the basis vector x sub I, let's say x sub 1 in particular, that transformation applied to a basis vector will be given by another vector, which is in general going to be expressed as a sum of basis vectors. So x1 will be transformed into some number, which I'll write as t11 x1, vector x1, not xi, excuse me, tx1, plus some other number, t21 times the vector x2, plus t31 times the vector x3, etc., up to xn. If I have, say, x2, I get a similar expression, except I'm going to number things slightly differently. I'll say this is the t12 number, is the x1 component of the transformation applied to x2, plus, etc., t22 x2 plus t32 x3 plus, etc. So if I have some vector then, alpha, being expressed as a1 x1 plus a2 x2 plus a3.
The mathematics of quantum mechanics is, technically speaking, linear algebra in an infinite dimensional vector space. Now, if that seems a little bit unfamiliar, don't worry, we will work through it step by step. It does turn out, however, to be an immensely powerful mathematical structure. There's a lot more going on behind the scenes to quantum mechanics than simply the wave function. What we're really talking about, in terms of the formalism of quantum mechanics, is attempting to represent the quantum mechanical state of the system. Now, what is the state of the system? Well, quantum mechanically speaking, it's everything that we can possibly know about the physical system that we're working with. There is no further level of information than knowledge of the state. And we've been working with states in a couple of different ways. The first way we worked with state was this notion of a wave function. Let's say psi of x and t. And to some extent, you can write down sort of closed form mathematical expressions for psi. Let's say psi is equal to some sort of, maybe it's a Gaussian, or a sinusoid, or a complex exponential. We also thought about representing the state of the system as a superposition, a sum over n of some coefficient a sub n, multiplied by some psi sub n of x and t, where these psi sub n's come from solutions to the time-independent Schrodinger equation. We're talking about, say, particle in a box, or the quantum harmonic oscillator. Gives you sets of wave functions that you can superpose together to represent an arbitrary state of a quantum mechanical system. We also talked about representing the wave function as some sort of an integral. Perhaps we're integrating from minus infinity to infinity. Instead of summing, we're computing an integral. We're integrating perhaps decay, if we're working with the free particle, for instance. And we have some sort of a phi of k, some sort of a coefficient that tells you how much each of the stationary states for the free particle that we have to work with. And those free particle states look something like e to the I kx minus h bar k squared over 2m t. And there was a normalization divided by the square root of 2 pi, if I recall correctly. Now these expressions bear a certain similarity. Instead of a sum, we have an integral. Instead of a discrete list of coefficients, we have a function, phi of k. And instead of a stationary state, we have a stationary state. We also talked above and beyond these sorts of representations, hinting at some sort of a deeper mathematical structure. We wrote down expressions like psi sub n is equal to a plus the operator acting on psi sub n minus 1, all divided by the square root of n. This sort of expression came from a consideration of an operator algebra that actually had no knowledge whatsoever of the states. So while you can think of representing the states as sort of a closed form mathematical function, some sort of a list of coefficients, some sort of a function, there's actually more going on behind the scenes. We also have this notion of operators relating different states to each other, and these expressions are going to be true regardless of the nature of psi 1 or psi n and psi n minus 1. That expression has to hold. Why? Well, there is a deep mathematical structure going on behind the scenes here. So let's explore that mathematical structure. That's what this chapter is all about. So, what we're working with here, like I said at the beginning, technically speaking, is linear algebra in Hilbert space. Now, if you've studied linear algebra, you know it deals a lot with vectors, and you can gain a lot of intuition about the behavior of physical systems in terms of vectors. So, say we have some sort of a vector A pointing in that direction, some sort of a vector B pointing in that direction. You can do basic vector operations on these things. We can, for instance, take the dot product of A and B. And I've drawn these things as approximately perpendicular to each other, so you would expect the dot product to maybe be 0. We can also write perhaps the vector B as some sort of linear transformation acting on a vector A. And in the language of three-dimensional vectors, it's easy to write down linear transformations as matrices, in this case 3 by 3 matrices. So if you've studied linear algebra, these sorts of concepts are familiar to you. In particular, there are a lot of linear algebra concepts, things like the inner product or normalization or orthogonality and the notion of a basis that we can express. Now, the nuance in quantum mechanics is that we're working with a Hilbert space. And a Hilbert space, technically speaking, is an infinite dimensional vector space. So the infinite dimensionality here, I think I've actually written infinite, but you get the idea. Instead of working in 3 dimensions, we're working in infinite dimensions. Instead of lists of 3 numbers, we need lists of infinitely many numbers. And that makes life a little bit more difficult. The basic structure ends up being the same, though, so much of your linear algebra experience is still going to hold here. To give you some basic vocabulary and some basic intuition, we're dealing with vectors, first of all. And the notation that we'll use for a vector in the notion of a vectors in this Hilbert space is going to be something like this. So, vertical bar, name of vector, and then angle bracket. We'll expand on this notation much more later on in the chapter, but for now, just think of this vector as somehow representing the state of the system. As a proxy, think something like psi of x, if you need a more concrete representation of the state. You don't want to just think in general. Now, I contend that when we're talking about linear algebra and Hilbert space as applied to quantum mechanics, this representation is actually more useful than the wave function. And we'll see why that's the case later on. Oftentimes, we don't need to know anything about the wave function to still make useful conclusions on the basis of the vectors themselves. So what else can we do in terms of linear algebra? Well, we can do inner products. The way we'll write that in this notation is BA, or beta alpha here, angle bracket beta, vertical bar, alpha, angle bracket. In the language of states and wave functions, you can represent inner products like this as integrals, minus infinity to infinity, of, in this case, let's say psi beta star as a function of x times psi alpha of x, all integrated to dx. This is that same sort of normalization and orthogonality integral that we've been dealing with a lot in the context of wave functions, but expressed in a more compact notation, in a more general mathematical form, that of linear algebra. With this notion for an inner product, we can also think about normalization. Something like the vector alpha inner product with the vector alpha would translate into wave function language as an integral from minus infinity to infinity of psi sub alpha of x, psi sub alpha of x, need to complex conjugate this one, sorry about that, dx. And in terms of normalization, this had better equal 1, and this had better equal 1. So the inner product of a vector in this Hilbert space with itself had better give you 1 if this is going to represent a valid quantum mechanical state, same as the wave function has to integrate in this squared modulus context to give you 1. We can also talk about orthogonality. Orthogonality, in the language of linear algebra, refers to the vectors being perpendicular to each other, if you're just thinking in 3 dimensions. Now, in infinite dimensions, it's a little bit harder to express, a little bit harder to think about, but it's just as easy to write down. I can say alpha and beta equals 0. That means these vectors are orthogonal to each other. In the language of integrals here, integral from minus infinity to infinity of psi alpha of x, complex conjugate, psi beta of x, is going to give you 0. If these come from, for instance, a solution to the time-independent Schrodinger equation, perhaps we have a set of wave functions to work with. I'll write that as a set of states, say psi sub n. I may be guaranteed that psi sub n inner product with psi sub m gives me a Kronecker delta. This would express orthonormality, that this set is every element in this set is orthogonal with every other element, and that each element of the set is properly normalized. We can also talk about the completeness of a basis. So, working with this sort of set psi n, suppose it comes from solving the Schrodinger equation in the language of the wave function, I can express some arbitrary psi, arbitrary quantum mechanical state, as a sum of, let's say, n equals 1 to infinity potentially, of a sub n, psi sub n. If this sort of expression is possible, these psi sub n's form a complete basis. And if you think about invoking the orthogonality and applying Fourier's trick to this sort of expression, that works out just as well. You can figure out that in this case a sub n is going to be what you get if you take the inner product of psi sub n with this arbitrary wave function that we're starting with. Now these expressions have corresponding versions in terms of the wave function as well, but since I'm running out of space on the slide, I'm not going to go into the details. This one is going to be an inner product, same sort of integral as we're working with here. Likewise, this is your infinite sum. I think I had that expression on the last slide. Now, within the language of linear algebra and Hilbert space, we have this sort of notation, these sorts of representations for what these states really are as they exist in the vector space, or in the Hilbert space. What can we do with these states? Well, the fundamental question in quantum mechanics generally has to do with the observable properties of a system. So what do we have in the language of observables? Well, observables, we know, are going to be real numbers, and they have some sort of statistical properties in quantum mechanics. For instance, we talked about the expectation value. Say I have some sort of observable Q, I can write the expectation value as Q inside a pair of angle brackets. And the angle brackets here are not exactly the same as the angle brackets in the earlier expressions that we've been working with, but the connection is, there is a connection. We'll come back to that later. If you want to think about the expectation value, for example, in terms of some sort of quantum mechanical system, we're dealing with an operator. So the observable isn't just going to be the expectation value of some q, some quantity q. We've got some sort of an operator, which I'll write as capital Q with a hat. So what would our expectation value q look like in this language of angle brackets? Well, we know what it looks like in terms of inner products, or in terms of integrals of wave functions, for example. It's going to be an integral of the wave function, the state of the system, then the operator, then the wave function of the state of the system. And we have that same sort of notation in context of inner products in our vector space. So we would have the state of our system, psi, and we have our operator acting on psi. So the operator acting on psi gives you, in some sense, another state of the system. It's not really another state of the system, though. It's more a vector in this Hilbert space. Operators here, if I think about this Q operator acting on the state of the system, is going to give you some new vector in your Hilbert space. Now, we know that this sort of expectation value quantity or concept has to result in some sort of a real number. So you can think about this as, what happens if I take the complex conjugate of this? Well, if you're thinking about psi, q hat psi, complex conjugated, in the language of the integrals that we've been working with, this is going to be taking the complex conjugate of q hat psi. So instead of being a psi star q hat psi, it's going to be a q hat psi star multiplied by psi inside the integral. And the same notation sort of holds here. Whenever you take the complex conjugate of an inner product like this in our Hilbert space, you swap the order of these things. Instead of the psi being on the left, the psi is on the right. And the q hat psi on the right is on the left. So this notion of what appears on the left and what appears on the right is a useful way of keeping track of what's been complex conjugated. So q hat psi psi in our revised notation here. Now, this sort of substitution here, if this is going to be equal to the original expectation value of q, right? The complex conjugate of the expectation value has to be equal to the expectation value itself if this is going to be a real number. This expression has to be equal to this expression. And the equality of two operator expressions in the language of linear algebra like this, essentially the operator can act on the left or the operator can act on the right. The operator behaves the same when acting on a complex conjugate of the state as it does on the state itself. Complex conjugate of state with operator gives you the same result. That is only going to be true if the operator here is Hermitian. And there's lots more that can be said about the notion of Hermitian operators, and we'll come back to that in further lectures. But for now, know that there's a lot of mathematical formalism that goes along with linear transformations, such as vectors to new vectors in the space, especially associated with Hermitian linear transformations. So as an example of the notion of a Hermitian operator and how that manifests itself in this context, think about the momentum operator. Is the momentum operator Hermitian? Well, if the momentum operator is Hermitian, we know that if I have some sort of a wave function f, the momentum operator acting on the wave function g has to be equal to the momentum operator acting on f, inner product with the wave function g. Sorry, I shouldn't say wave function, I should say state. State f, momentum operator g, momentum operator f, state g. These things should be equal to each other. So let's do some manipulations of the one on the left. And just since we have a large amount of machinery for working with the notion of states in terms of wave functions, let's express this in terms of wave functions. So our inner product in the terms of the wave functions is going to be the integral from minus infinity to infinity of some wave function f, complex conjugated, as a function of x, multiplied by the momentum operator applied to our wave function g. And our momentum operator is minus I h bar, partial derivative, with respect to x. So this is acting on the function g of x, and we're integrating dx. Now this is an expression that looks a little bit difficult to work with. We have partial derivatives inside an integral, but whenever you see a derivative inside an integral, think integration by parts. So let's say I do integration by parts. I can define my variable u to be some sort of f complex conjugate, recognizing the part that I would like to differentiate. And the part that I would like to integrate would be, well, the part that's already been differentiated. So let's say dv is equal to partial g partial x with the dx tacked on. So identifying this part as my v and this part as my u. You can pull the constants out front if you want. So this is going to give me du would be the partial derivative of f star partial x, and my v when I integrate it, now it's the integral of a derivative, so fundamental theorem of calculus just gives me g. Integration by parts then says this whole thing is going to be equal to f star of x, g of x, evaluated at my boundary, minus infinity to infinity, minus the integral from minus infinity to infinity of these two guys, v du. So I have my partial f, partial x, and I have my g, and I'm integrating dx. Oops, forgot to, technically I should put a dx there in my integration by parts notation. So, as usual in quantum mechanics, we require these functions to be square integrable, meaning normalizable, meaning they have to go to 0 at infinity. So 0 at plus infinity, 0 at minus infinity, this term all by itself drops out. Oh, and I've got this coefficient overall that I should pull out front. So minus I h bar multiplies all of this. So I've got a minus I h bar and a minus. The minus I h bar and the minus are going to cancel out if you want to simplify this, and I'll have I h bar. Let me put that inside the integral. I h bar, I have a partial derivative of f star, partial x, and g, and I'm integrating dx. So we're almost there. This looks a lot like the momentum operator applied to the function f. So we've almost sort of closed the loop here. We've almost shown that p is Hermitian. What's missing here? Well, what's missing is the notion of this minus sign on the IH bar. This here itself is not exactly the momentum operator applied to f. But what we want actually isn't exactly the momentum operator applied to f. It's the momentum operator applied to f, but then acting on the left in this inner product notation, which means we have to take the complex conjugate. So if I really wanted to write this out, I would have to say this is the integral, put some limits on here, minus infinity to infinity of minus I h bar partial f partial x, all complex conjugated, multiplied by g integrated to dx. And now we've actually gotten back to this original expression. This here is the operator p acting on f, complex conjugated, inner product with the function g. So that's the end result. We have sort of demonstrated that our definition of minus I h bar partial g partial x here is indeed a Hermitian operator. And perhaps this goes a little bit of the way towards explaining why exactly you had a minus I h bar, or minus I, in the definition of the momentum operator. That minus I is a little bit perplexing at first, but it is required essentially by the notion that the momentum operator be Hermitian, by the notion that the expectation value of the momentum is always going to be a real number. As a further example of how we can manipulate these sorts of things in the language of formal linear algebra, let's think about a state with no uncertainty. What sort of quantum mechanical state would have no uncertainty? These things are also called determinate states, meaning you have some operator or some observable, let's say the observable q as represented by the operator q hat, and it has absolutely no uncertainty associated with it. There is a quantum mechanical state that has a definite value of some variable, some observable. Now, if you're thinking about something like position or momentum, you might be thinking along the lines of the uncertainty principle, and well, is that really possible? And the answer is probably not. The states of determinate position and determinate momentum tend to be a little bit poorly behaved, mathematically speaking. But in terms of energy, perhaps, you know states of determinate energy. They are the solutions to the time-independent Schrodinger equation. So there's certainly nothing wrong with that. In particular, I can write something like sigma q, the variance, sigma q squared, the uncertainty in a measurement of quantity q squared. And I can write that this quantity was, back when we were talking about variance and probability distributions, defined as the expectation value of the operator q minus the expectation of q. So the deviation of some observable from its mean squared. So the expected mean squared deviation, the mean squared deviation from the expected value. Now, in our language of linear algebra here, we can write this out as psi on the left, and then q hat minus the expected value of q acting on psi on the right. Oh, and this is squared, of course. So I can expand out the square, let's say psi on the left, and then q hat minus expected value of q hat minus expected value of q twice, acting on psi. And this operator, if this is going to represent an observable, has to be Hermitian. So if q hat, the operator, is Hermitian, q, multiplication by a number here, the expected value of q, this is just going to be a number. It's also, of course, going to be Hermitian. Multiplication by a number is going to be a Hermitian operator. Doesn't matter if you do it on the wave function on the right or the wave function on the left. I can take this whole thing and apply it on the left, since this is a Hermitian operator. So if you make that sort of manipulation, you end up with, now on the left, I have q hat minus expectation of q acting on psi, and on the right, q hat minus expectation of q acting on psi. And if this whole thing is going to have zero uncertainty, what exactly does that mean? Well, if this whole inner product is going to turn out to be zero, then either psi equals zero, meaning my wave function is in some sense trivial. That's not terribly useful. If psi is not zero, then each individual piece here, this has to in some sense be equal to zero. Or this piece on the left has to be equal to zero. What that means, well, either left and right, these are very similar expressions. It means q hat minus the expected value of q. In terms of that as an operator acting on my state, that has to equal zero. And that's easily rearranged into q hat acting on the state equals the expected value of q multiplied by the state. This is just a number, it's not an operator. This here, this is an eigenvalue problem. And there is yet another massive set of linear algebra machinery dedicated to solving eigenvalue problems. We've already done some of them. For example, the Hamiltonian operator acting on the state of the system is the energy times the state of the system. This is our time-independent Schrodinger equation. This gave us the states of definite energies, and that's the same sort of framework as you got in here. So that's a taste of the sorts of things that we can represent and think about in the language of linear algebra as applied to quantum mechanics. We can express generalized states with no uncertainty and derive that they are going to be the states that are eigenstates of the linear operators that represent the observables. Now, we haven't really written down any linear operators in detail in the notation of linear algebra, or really in quantum mechanics. We've only really got a few operators that we can work with, like Hamiltonian and position and momentum and whatnot. But this is hopefully I have at least convinced you that there's more to quantum mechanics than just dealing with the wave function, that we can do some interesting things with the linear algebra structure. So, to check your understanding here, let's consider a set of states that you get, stationary states from the quantum harmonic oscillator. That means the solutions to the time-independent Schrodinger equation, which if you wanted to write it out in terms of operators and linear algebra, is h bar psi sub I, let's say psi n actually, is equal to en psi n. So that would give us this set of solutions here. So in terms of the language of linear algebra, some basic notational questions. And in terms of whether or not observable operators are Hermitian or not, think about why the operator x hat, the position operator, would be Hermitian. Let's continue our discussion of the mathematical formalism of quantum mechanics by considering Hermitian operators and the eigenvalue and eigenvector problems that result from their consideration. What we're talking about here is a Hermitian operator in general. So for a Hermitian operator, I'll just write q with some hat on it. And you can consider just this general operator to be Hermitian if the following condition holds. The inner product of some arbitrary function, arbitrary state in the Hilbert space, f, inner product with the operator acting on some arbitrary state in the Hilbert space, g, is going to be equal to the operator acting on the state F inner product with the state G. So if this inner product and this inner product are equal to each other for all F and G, then the operator is Hermitian. These sorts of operators show up a lot in quantum mechanics because Hermitian operators are what we are considering if we're talking about observable quantities in quantum mechanics. Now, in terms of eigenvalue problems, the general statement of an eigenvalue problem looks like the operator applied to some general state is equal to some eigenvalue, which I'll write as lowercase q, in the case of the operator uppercase q, multiplied by that state. So applying the operator to the state doesn't really do anything, it only changes the overall scaling factor by some amount q. So these sorts of eigenvalue problems show up in quantum mechanics all over the place. For example, the time-independent Schrodinger equation is such an equation. We have the Hamiltonian operator acting on a state, giving you the energy multiplying the state. H psi equals E psi. Now, solving the eigenvalue problem gives you one of two general kinds of solution. First of all, what we're going to get are going to be eigenstates. Those are going to be our psi's that solve this sort of equation. Generally, we're going to get a lot of them. And we'll get some sort of eigenvalues. Those are going to be the values of q that result from application of this operator to a particular solution to the eigenvalue problem. And we're going to get many q's as well. Each solution to this problem, and there will be many, generally has its own distinct value of q in this sort of expression. And the sets of psi's and the sets of q's that solve these problems generally come in two discrete classes. We have discrete and we have continuous. The discrete case means that we have some explicit set of, let's say, psi sub n. There are a potentially infinite number of these psi sub n's, but we can write them down in a list. Psi 1, psi 2, psi 3, etc. We're also going to get some set of q sub n's, where q sub n goes with psi sub n. As an example of where this has occurred already that you've seen, talking about the particle in a box, solving the time-independent Schrodinger equation gave us a set of stationary states and the associated energies. For the continuous case, things are a little bit more complicated. For an example of this that you've seen before, consider something like the momentum operator applied to the wave function, giving you the momentum, the value, multiplied by the wave function. This sort of eigenvalue expression came up in our consideration of the free particle. And under those circumstances, we didn't get a real nice set of solutions. We got wave functions that looked something like, well, there was some free parameter k. And our wave function as a function of x looked something like a complex exponential. We had e to the I kx minus h bar k squared over 2m t for the time dependence. Probably we were dividing this by root 2 pi, if I remember correctly, to effectively normalize it within the language of the Fourier transform, at least. So there's no way of writing down psi 1, psi 2, psi 3, psi 4. There is only psi k, and k can take on essentially any value. The eigenvalue that we got was, well, in the case of the momentum operator, h bar k. Given the definition of k that we came up with in this consideration of the free particle, we have an infinite set of continuously variable solutions. This k value can be anything, as opposed to indexed by just an integer 1, 2, or 3 sort of setup. Now, the mathematics that results from a discrete spectrum, a discrete set of eigenvalues, versus a continuous spectrum, a continuous set of eigenvalues, are going to be a little bit different. But it's a little easier to understand the discrete case. It's a lot easier to write down mathematical expressions, so let's consider that case first. Most of the results will still hold, and we'll come back to the continuous case later on in lecture. So, the first thing that you probably want to know about the eigenvalues that result from these eigenvalue problems is whether or not they can possibly represent observables. And in this case, the eigenvalues of Hermitian operators are real. You can see that by fairly straightforward application of the eigenvalue equation itself, looking at q hat, the operator, applied to some arbitrary wave function psi, giving you the eigenvalue q, multiplied by the wave function psi. You can take the complex conjugate of that expression, And complex conjugating the left-hand side merely converts this into, well, the result of complex conjugating the operator acting on the wave, or acting on the state, which we're writing in our vector notation as angle bracket on the left instead of angle bracket on the right. Complex conjugating the right-hand side of this expression gives you, well, the complex conjugate of the eigenvalue, q star, multiplied by the result of complex conjugating this wave function, or this state, psi. So again, angle bracket on the left. The other ingredient to understanding why the eigenvalues of Hermitian operators are real is the definition of a Hermitian operator, which says that q acting on some state f, inner product with the same state f perhaps, is going to give you the same result as if you take the inner product of the state f itself with the operator acting on the state f on the right. Operator on the left, operator on the right gives you the same result. Now if I apply this sort of expression over here, and this sort of expression over here, you can see what's going to happen. Applying the operator on the left turns this into q complex conjugate f, inner product with f, and applying this expression on the right turns this part into q, the number, multiplying f. Now a number inside an inner product like this is just going to factor out. So we're left with q, the number, times f, inner product with f. And the inner product of a state with itself is always going to be non-zero. So I can effectively divide both sides of the equation by this, and thereby show that q star is equal to q. Therefore, our eigenvalues of the eigenvalue problem for a Hermitian operator is going to be a real number. Real numbers means that these are potentially feasible representations of observable quantities. So that's a step in the right direction. Now, we talked about a lot of other facets of solutions for the time-independent Schrodinger equation, for example. What about orthogonality and normalization and whatnot? We can talk about those within the language of eigenvectors and eigenvalues, eigenstates of a Hermitian operator. It turns out the eigenstates of a Hermitian operator are orthogonal to each other. Now, that's not a completely rigorous mathematical statement. I'll point out some of the difficulties with it later on. But in the context of orthogonality, we're talking about an inner product of two different states. So suppose I have q hat, and I'll say the state f gives me some eigenvalue qf, multiplying the state. And then I have a distinct state q, let's call it g, gives me the eigenvalue qg, multiplying the state g. These two eigenvalue problems are solved for the state f and for the state g. So in principle, I know f, I know g, or qf, I know g, I know qg. Now, if you consider the definition of a Hermitian operator in the context of the states f and g, I have f acting on q times g, and that has to be equal to q acting on f, inner product with g. This is our definition of a Hermitian operator. And we know, considering eigenvalues and our eigenvalue problems here, qg, I can write down that. That's just going to give me q sub g times the state g. So this is going to give me qg times the inner product of f and g. And qf on the left, we've talked about how to do that sort of thing on the last slide. This is just the complex conjugate of this sort of thing. So this is going to give me qf, complex conjugated, times the inner product of f and g. Now this looks a lot like the sort of expression we were talking about before, but in the case of showing that the eigenvalues were purely real, we were working with the state f and itself, not the state f and some other state g. So, we have some potential problems with this expression. If qg and qf are not equal to each other, and f and g, the inner product here, is non-zero, then we have the same expression on both sides. It can be divided out. qg is equal to qf, but that's going to cause some problems. The problem that we run into is that we have a failure of our inequality here. And the inequality that fails if I say divide these things out, QG, if QG is different than QF, then I have a contradiction. The contradiction is that F and G don't have non-zero inner product. If F and G has zero inner product, I can't just divide it out because I'm dividing both sides of my equation by zero. So what we can conclude from this expression is that either FG is equal to 0 or QG is equal to QF. And I'll just say QG is equal to QF. Since we've just shown that the eigenvalues are real, QF star is equal to QF. So we've shown that if the eigenvalues are different from each other, then the inner product must be 0. If the eigenvalues are the same, we are not guaranteed that the eigenstates, F and G, will be orthogonal to each other. In the case that QF equals QG, we describe the eigenvalue as degenerate. And we have to go through some extra procedures in order to ensure that we have a well-behaved set of eigenstates. In particular, what we want to do is something called Gram-Schmidt orthogonalization. And aside from having a lot of letters in it, orthogonalization is simply the process of taking these two states, F and G, and converting them into two new states, F prime and G prime, that are constructed as superpositions of F and G, such that they are actually orthogonal. I won't go into the details here, but it has to do essentially with finding the component of the vector F that is not orthogonal to the vector G and subtracting it off of the original vector F, so that I only have the part of F that is orthogonal to G left over when I've computed F prime. So that's a little bit about the eigenfunctions in terms of their orthogonality. The other thing that we needed to be able to compute meaningfully in quantum mechanics is completeness. We needed to represent states, arbitrary states, as superpositions of, for instance, stationary states, solutions to the time-independent Schrodinger equation for, say, the quantum harmonic oscillator. In the language of linear algebra, the mathematical formalism of quantum mechanics, that's an eigenvalue problem with the Hamiltonian operator. And it turns out that we have the same sort of mathematical formalism there. The eigenstates of Hermitian operators are indeed complete. And I can't really say much more here than just give you a definition. In terms of the completeness, we're talking about our eigenvalue problem as before, giving us a spectrum of eigenstates, let's say psi sub n, and the resulting set of eigenvalues. And it turns out that this is indeed a complete basis. Within the language of linear algebra, the set of vectors here spans the complete space that you're working with. And what that means is that any arbitrary state, let me call it F, can be written as a superposition. Let's say n equals 1 to infinity here, of some coefficient n multiplying psi n. So I can express any vector in my vector space as a superposition of this set of vectors. It forms a complete basis that spans any desired function that you would be interested in. You can, given the orthogonality of these states, as shown in the last slide, apply Fourier's trick to this sort of expression and determine that this a sub n coefficient is fairly straightforward to calculate. You just multiply from the left by psi sub n, take the inner product with the state that you want to represent. Now, it's important to note that this sort of statement is not on as solid a mathematical footing as the earlier states regarding orthogonality. The completeness is often not easily proven. It is typically going to be something that we assume, and while in the case of consideration of the wave function, we can write down the time-independent Schrodinger equation as a partial differential equation and apply the language of Sturm-Liouville theory and apply the results of Sturm-Liouville theory, in particular to show that the results are complete, or that the set of solutions to the time-independent Schrodinger equation forms a complete set of basis functions. The same sorts of results are typically going to apply here. So while we can't always prove it, we are generally going to assume it, certainly at the level of mathematical sophistication of a course like this. So that's about it for the results. One thing I did want to say before we close here is that all of what I've been stating so far are for discrete spectra. So what about continuous spectra? What if instead of getting a discrete set of eigenstates and eigenvalues, I get a continuous set of eigenstates and eigenvalues? The example I gave earlier was a consideration of the momentum operator as an eigenvalue problem. If I have some arbitrary function, apply the momentum operator, and get that same function back, the solutions that we got looked something like e to the I kx minus h bar k squared over 2mt, with eigenvalues that look like h bar k. Now, first problem. This is not normalizable. So within the language of linear algebra, writing down something like, if I call this psi sub k, in the language of linear algebra, writing down something like psi k, what exactly sense does that make? Can I really say this is normalized? Well, if I have two different values of k, let me say, express this in terms of momentum instead. So I'll write this as a psi sub p. If you consider, say, psi p1 inner product with psi p2, what does the orthogonality actually look like? Orthogonality or normalization? Well, if you write this out in the language that we know, that we've been working with so far, that of wave functions, this is going to be the integral from minus infinity to infinity of, well, this sort of expression. First of all, I've got psi sub p1 complex conjugated, so that's going to be e to the minus I k1x minus h bar k1 squared over 2mt, multiplied by e to the plus I k2x minus h bar k2 squared over 2mt. This is all going to be integrated dx from minus infinity to infinity. So in the case that p1 equals p2, meaning this is really the same state, then the exponential argument here is the same, but has opposite sign. So I've got e to the plus something times e to the minus something, which is just going to give me 1. I'm going to get the integral of minus infinity from minus infinity to infinity of 1 dx. What now? That's going to be infinity, surely, right? It's not a very meaningful expression, but it's going to give me something very large. Now, what if, let me move this over a little bit to the left, what if I consider p1 not equal to p2 then? Well, in that case, my integral here is going to have some function of x. k1, k2 are going to be different. In the subtraction here that I get, if I combine these two things, I'm going to get some function of x. It's going to be like the integral of minus infinity to infinity of e to the I something x. There's going to be other stuff up here as well. But I've got this sort of oscillatory behavior. You can think of this as cosine plus I sine, in other words. Now, as far as formally defining this mathematically, what this limit says, you've got an oscillatory function, you're integrating it all the way to infinity. It's not going to go to infinity, it's going to oscillate, right? And it's going to oscillate about 0. It's going to average out to 0. So in some sense, we can say this sort of goes to 0. And I should really put this in quotes so that I don't make my inner mathematician too angry. We do know, however, from working with these in the past, that these do form a complete basis. These sorts of things can be used to express any arbitrary initial conditions. We talked about that in the context of the free particle when we wrote expressions like that the wave function psi of x, say, can be written as an integral from minus infinity to infinity of dk, some coefficient, phi of k, multiplied by, say, e to the I kx. These sorts of expressions, this is like the inverse Fourier transform of psi sub k. So given some suitable definition of psi sub k, these e to the I kx, these sorts of functions can actually represent pretty much anything that you might want. Now, if we substitute in our definition for phi of k back from when we were talking about these sorts of things, it looks like this. It's the integral from minus infinity to infinity, dk, from before, and our phi of k was itself an integral from minus infinity to infinity. This time it was an integral dx, and it was, let's not leave it as an integral dx, because I've got x in this expression as well. Let's use a dummy variable, my usual squiggle, xi. Integral dxi of psi of xi e to the minus I k xi. So this sort of expression, that was our definition of phi sub k. If I multiply this by e to the I kx, continuing my expression over here, you end up with something that makes a certain amount of sense. In particular, I can manipulate this. Let's consider exchanging the order of integration here and manipulating these such that my exponentials multiply together. You can think of this as the integral from minus infinity to infinity dxi first, and then the integral from minus infinity to infinity dk. E to the I, combining these two things together, I'm going to get something like kx minus kc. And all of this is going to be multiplied by psi of xi. Now, if this whole thing is going to be equal to psi of x, this expression right here should look familiar. What function gives me psi of x when multiplied by psi of a dummy variable and integrated over the dummy variable? This function here, this guy. We have a name for it. It's delta of x minus xi, or xi minus x. So this is sort of delta function. This is what I'm really going to get out of these sorts of normalization conditions. The infinity that it goes to when p1 equals p2 is like the infinity that the delta function goes to when x equals 0, or x minus xi, or x equals xi. The 0 that it goes to is like the 0 of the delta function when its argument is non-zero. So subject to this version of orthonormalization, that if p1 is not equal to p2, you get 0, and if p1 is equal to p2, you get, well, infinity, but infinity in a useful way, such that in the context of integration, I can get functions out that as I would expect. You can prove the same sorts of results for an eigenvalue problem with a continuous sort of spectrum. That's about all that I want to say about these sorts of topics. To check your understanding, let's consider the position operator x hat. Is it Hermitian? What is the spectrum like? Is it continuous or discrete? What are the eigenfunctions of x, the operator? And do those eigenfunctions form a complete basis? So think along those lines, and hopefully that will help solidify this notion of the mathematical formalism that we've been working with in the language of context of Hermitian. The formal mathematical structure of quantum mechanics can also, of course, be applied to determine the statistics, perhaps, of measurements made of quantum mechanical systems. These notions of statistics appear a lot in the context of uncertainty, for example, variance, and the overall average outcome, the expectation value. So let's consider how the formal mathematical structure of states in a Hilbert space can be used to determine statistical properties of quantum mechanical systems. What we're talking about here is some observation. So consider just some generalized observation, meaning I'm talking about some observable Q as represented quantum mechanically as an operator, Q hat. We've talked about, over the last couple of lectures, eigenvalue problems. Q hat applied to some state gives me Q, the eigenvalue, multiplied by that state. And we've talked about the results of these eigenvalue problems. Either we have a discrete spectrum, we get some sort of set of psi sub n's associated with some q sub n eigenvalues, from which we can construct, for instance, any arbitrary state f, for example, as a superposition of a bunch of stationary states, or a bunch of states here, a bunch of psi sub n's multiplied by some sort of a coefficient, and we can determine that coefficient with Fourier's trick, left multiplying this overall expression by a particular psi sub I. So a sub I is going to be given by psi sub I f, coming from the left-hand side. The sum on the right-hand side collapses, etc. The usual Fourier's trick reasoning applies involving the orthogonality of the psi sub n's. We have this nice set of mathematical tools that we can use. We have a set of vectors that forms a complete basis for arbitrary functions. These are orthonormal basis vectors, basis states, and they can be used to construct anything. We also talked a little bit about what happens if you get a continuous set of solutions, not a discrete set. So let me just write this as some arbitrary psi of q, I'll write this as a state. It looks sort of like a function and a state. Think of this as a state that depends on some continuous parameter q. So each value of q plugged into some general structure gives me a distinct state, and I can think about the eigenvalue as q. Under those circumstances, the completeness of the basis states can be expressed as an integral. So I'm constructing the same sort of general quantum mechanical state as an integral over q of some sort of coefficient. Let me write it as f of q, multiplying this state psi of q. So I have some general function multiplied by some general coefficient, and I'm integrating up if I have some sort of continuous spectrum of eigenstates and eigenvalues. This f of q is determined by Fourier's trick using the Dirac orthonormalization of these sorts of states in much the same way. It's again going to be an inner product of psi of q with the state that we're trying to find, or with the state that we're trying to represent, excuse me. Now, given this sort of mathematical structure, can we discuss the notion of measurement, or some sort of an observation? What happens when we measure q? We've got some sort of device, we've put our quantum mechanical system into it, and it spits out a number. What numbers is it likely to spit out? Well, in the discrete case here, it's actually quite straightforward. You are going to get one of these eigenvalues. This is the generalized statistical interpretation of quantum mechanics. You're going to receive one of the q sub n's in that set of q sub n's. I should probably use a different index here. One particular value from that set, and you're going to get it with probability given by, well, if I get value q sub n, I'm going to get it with probability a sub n squared. So the coefficients that appear in this expansion, this representation of the state in terms of these basis vectors, is really the, well, square root, in some sense, of the probability of receiving each particular eigenvalue. So this is actually quite an interesting statement. When we measure q in a system with a discrete quantum mechanical spectrum, we always get one of the eigenvalues of the operator corresponding to the observable that we measure. And we get that value with probability given by this very simple sort of formula. You can take the squared magnitude of, essentially what you're looking at here is the part of f that is in the psi sub I direction, if you want to think about it. There is, of course, a continuous counterpart to this, but measurements of a continuous spectrum are a little bit more subtle. You have to think about what it means to observe something, and you're never going to, if you're trying to compute the probability of getting, say, exactly 6 out of a continuous distribution, exactly 6 will never happen. You will only get ever numbers very, very close to 6. But you can think about what's the probability that I get some value q in between q0 and q0 plus some dq. So I've got some sort of interval here between q0 and q0 plus dq. If the value that I get falls in that range, then we can represent the probability here. And you'll get it with probability given by the magnitude of f of q squared multiplied by dq. So this f of q, this coefficient that we determine as the result of an inner product with our sort of basis and the function that or state that we're trying to represent, can be used as a probability. This is the sort of thing that we're talking about when we talk about the squared modulus of the wave function as a probability density. The wave function psi of x is really the result of some sort of inner product between eigenfunctions of position operator, which are Dirac delta functions, as applied to the state that we're trying to represent. So that's where the probability density comes from. Now, this is not so much a mathematical result that can be proven. These sorts of, you'll always get an eigenvalue and you get some sort of a probability, or you'll always get some sort of a continuous value, some sort of a value with this sort of probability. Those aren't mathematical results as much as they are sort of axioms of quantum mechanics. This is a generalized statistical interpretation that takes us beyond the notion of the wave function as something that gives you the probability density of position measurements, meaning the probability density of where you're likely to find the particle if you observe the particle, meaning observe its position. So these sorts of probabilities are, of course, going to be useful in the context of computing probabilities. But in order for them to be useful in computation of probabilities, we first of all have to have some sort of normalization. Now, you can think about normalization of a wave function or of a state in the context of these vectors in the Hilbert space as the inner product of the state with itself must equal 1. Now, if you think about that in the case of a discrete spectrum, this state f can be written as the sum of some a sub n times some psi sub n, meaning if I'm working with some set of psi sub n functions, some sort of a basis, I can figure out the overall, I can figure out these coefficients and determine the overall state that I'm trying to represent. If you look at this inner product in this context, you're going to have, well, it's an infinite sum and an infinite sum. So I've got some sort of a sum over n of a sub n star, psi sub n on the left, and some sort of an infinite sum over n, or sorry, I should use m, different index, of a sub m, psi sub m. And if I distribute these two infinite sums together, I'm going to get psi n, psi m terms. And psi n and psi m, those inner products, obey an orthogonality relationship. I'm assuming these psi sub n's come from the eigenstates of a Hermitian operator. So the orthogonality is going to collapse the two sums together, and I'm just going to have one sum left. I'll get, say, a sum over n of a sub n star, a sub n. And the normalization means psi n, inner product is 1. So my wave functions are gone. So this normalization condition here implies that the sum of the squares of those coefficients in the representation of my state is going to be 1. In the language of continuous spectra, what we're talking about here, again, is an inner product. Inner products you can think of as integrals. So we've got some sort of an integral of some sort of f of q squared modulus dq. This is, again, sort of an addition of all probabilities. Well, we've got an addition of probabilities here, a summation of a bunch of probabilities that better add up to 1. This is an integral of a bunch of probabilities that adds up to 1. And this integral comes from the same sort of orthogonality argument as the infinite sums collapsing here. Instead of two infinite sums multiplied together, we would have two integrals, which we could manipulate to get a Dirac delta function in terms of the Dirac orthonormalization of these sorts of basis states. What I wrote as psi of q on the last slide. So these normalization conditions make a fair bit of sense. Probabilities have to sum to 1, and we can make some use of that. Another situation where these probabilities are useful is in the computation of an expectation value. So say I want to compute the expectation value of some arbitrary operator q. That, in the language of these linear operators, is f inner product with q times f, q operator acting on f. So here's my arbitrary state f, again, and q being applied to f. So again, I can make these sorts of infinite sum expansions, sum over n of a sub n star, not f, excuse me, psi sub n, multiplied by an infinite sum over m of a sub m times q acting on f. Sorry, not f. Once again, psi sub m, excuse me. Coming from this same sort of expansion of f and the expansion of qf. So the expansion of qf is going to be q acting on the infinite sum, and I've distributed q into that infinite sum, acting on each individual term. Now, q acting on psi sub m, that was my original eigenvalue equation. Q acting on psi sub m is simply going to give me q multiplying psi sub m. So in the case of calculating the expectation value of some general operator, when you have your general state represented in terms of eigenstates of that operator, is actually quite simple. Again, we're going to get psi n and psi m when I distribute these two sums together. You're going to have a sum over n and a sum over m. I'm going to have an a n, excuse me, that looks a little bit like a w, a n star and an AM, and a Q. This is technically going to be Q sub M, excuse me. Associating psi sub m with Q sub m was part of the definition of these psi sub m's. And I have a psi sub n and a psi sub m, which again, I can say this is some delta n m, which collapses my sum down. And what I'm going to get in the end is a sum just over a single variable, let's say n, times the squared modulus of a sub n times q sub n. So this, if you look at it from the perspective of statistics, this is a weighted average. These are the probabilities associated with each observation, and these are the values that are associated with each of those probabilities. You can do the same sort of thing within the context of a continuous spectrum. Under those circumstances, you're going to have, I'll write it out under these circumstances, the expectation value of q for a continuous case is the integral from minus infinity to infinity. Let's say I've got dq, right, so I'm constructing an integral representation of f. So let's say that's going to be an integral over q1, f of q1. I have to complex conjugate this. So this is my coefficient from the integral, from the representation of f complex conjugated. And then I've got my psi of q1, actual function. And definitely running out of space here. Shift this to the left a little bit. And that whole thing is going to be multiplied by a similar looking integral, except this time I'm going to be representing q applied to f. So this is going to be an integral dq2, to use a different variable. I'm going to have a coefficient f of q2, again appropriate for representation of my state. I'm going to have my operator q multiplying my psi of q2. And close my state and close my parentheses off screen. Hopefully that's reasonably clear in terms of at least my handwriting. This is a representation of this, and this is a representation of q applies to that. You can make the same sort of arguments here. Q applied to my state is going to be q2 in this case times psi of q2. That's my eigenvalue operation. And then I have the same sort of double integral becoming a delta function sort of thing as I had a double sum becoming a Schrodinger delta over here. So this is going to give me, rearranging the order of these integrations a little bit, integral minus infinity to infinity dq1, integral minus infinity to infinity dq2, and then I've got an f star of q1 and an f of q2, and q2, and an inner product of psi of q1 and psi of q2. It's subject to these Dirac orthonormalization constraints that we have to have in order to make continuous spectra really make any sense. This is going to be a Dirac delta function of q1 minus q2. Applying that Dirac delta function in this integration means I can do one of these integrals, and what I'm going to get is the value of the integrand such that, or that occurs where the argument of the delta function is 0. So if I'm doing the integral dq2, I'm going to get the value where q2 has become q1. So all you're going to be left with is a single integral, minus infinity to infinity, dq1, and I've got an f star of q1 as before, and an f of q, not 2 anymore, excuse me, f of q1. This q2 becomes q1 is basically the whole point of applying the delta function. This is the result of doing a delta function integral. I've also got that q1 laying around from before, and that's it. That's all there is to it. So this, getting a little cramped in the right, is the integral from minus infinity to infinity of that squared modulus of f of q dq multiplied by, sorry, not dq, let's say multiplied by q integral dq. So this is the same sort of expression here as you have here. So squared modulus times the value, squared modulus times the value, properly normalized, given the Dirac orthonormalization and the Schrodinger delta sort of orthonormalization of these two sorts of sets. Either we have a discrete spectrum, in which case things are infinite sums, or we have a continuous spectrum, in which case things are integrals. So that's what your expectation values are going to look like. They're going to be sort of weighted averages with sums or weighted averages with probabilities. Or, yeah, with continuous functions as computed in integrals. You've seen expressions like this before in, for example, the computation of the expected value of the position operator. This is going to be an integral over position multiplied by the position multiplied by, sorry, this should be squared, the squared magnitude of the probability density of the wave function f of x. Now, of course, all of this is expressed in terms of some general operator q. So let's do an example. Let's think about measuring the momentum for the quantum harmonic oscillator ground state. Now, measurements of momentum means we're talking about the momentum operator. We know we're always going to get one of the eigenvalues of the momentum operator, so we have to, in principle, solve the eigenvalue problem. Momentum operator applied to some arbitrary state gives me the momentum, the number, multiplied by the state. And solving that eigenvalue problem is something we've done. You end up with something like e to the I px over h bar divided by square root of 2 pi h bar, I think, goes in the denominator as well, associated with eigenvalue p. So these are my eigenstates expressed as wave functions, and these are my eigenvalues of those wave functions. Now, we've talked about these things before. This was e to the I kx over root 2 pi, and this was k h bar. How can we determine, for example, what the probability distribution of momentum measurements is going to be for a particle prepared in the ground state of the quantum harmonic oscillator? Well, we're going to get some value p, and we're going to get it with probability given by the magnitude of some function f of p squared. All right? We're not going to get p, we're actually going to get something between p naught and p naught plus delta p. Running out of space here. But the language sort of makes sense. I have some sort of a probability density multiplied by the size of the interval over which I am accepting values of p from p naught to p naught plus dp. That's my sort of probability density. Now, within the language of the linear algebra that we're working with, this function f of p is going to be that psi of p function. Think about that as the complex conjugate of this, multiplied by psi 0. Psi 0 being the ground state of my quantum harmonic oscillator. And you can write out this inner product in terms of wave functions, if you know what these things are. Minus infinity to infinity. I'm integrating dx. And I have my psi sub p on the left, meaning complex conjugated. So this is going to be e to the minus I px over h bar divided by root 2 pi h bar. And then I have my quantum harmonic oscillator ground state, and we found that in a variety of ways. It looks something like m omega over pi h bar raised to the 1/4 power times e to the minus m omega over 2 h bar x squared. So I have an integral dx of e to the minus x squared and e to the ipx. We've done this problem before. This is computing the Fourier transform, essentially, of your ground state. This Fourier transform is essentially a special case of the sort of transforms that we are making when we compute the sort of coefficients that appear in the expansions or representations of some arbitrary state in some arbitrary basis. In this case, we're working with the eigenstates of the momentum operator. We could also be working with eigenstates of the kinetic energy operator or eigenstates of any other Hermitian operator. They're all going to form a complete orthonormal basis for which these sorts of probability calculations work. So this integral is doable. Not all that difficult. You end up with another Gaussian just as a function of momentum. It's a sort of closed form mathematical expression. So to check your understanding of these sorts of probabilistic interpretations or these probabilistic contexts, the results of, or as they result from the linear algebra in quantum mechanics, suppose you're considering a particle in a box. So we're solving the time-independent Schrodinger equation for the Hamiltonian, which is an eigenvalue problem for the Hamiltonian operator. We get a set of stationary states and a set of eigenvalues. Now suppose I'm telling you that some arbitrary state psi is prepared in this superposition of psi 1 and psi 2. Answer these questions. If you measure the energy, what's the probability of observing one of a couple of different energies? Double check that this shouldn't be F. Sorry, I don't know why I always manage to make typos in these check your understanding questions. This should be psi. Is the inner product of psi with itself what you expect it to be? Does it make sense? And suppose I had some general observable with eigenvalues and eigenvectors, such that I have some eigenstate G7, which gives me eigenvalue Q7. If I observe Q, write down an expression for what I would expect in terms of the probability of getting Q7 as a result of that measurement. So that's a bit on the statistical interpretation of the formal mathematical structure of quantum mechanics. This basis allows us to construct probabilistic interpretations of way more than just position and momentum. And we'll continue on along those lines far more later on in the rest of the course. Given our discussion of the formal mathematical structure of quantum mechanics, let's think about the uncertainty principle. Usually we're talking about something like delta x, delta p is greater than or equal to h bar over 2 under those circumstances, but can we do better? Can we expand this beyond simple position momentum uncertainty? The linear algebra structure of quantum mechanics gives us a way to do that. What we're talking about here basically is the uncertainty in some observable quantity. Now, I'll leave it general and say Q here, meaning we have some sort of a Hermitian operator Q hat that we can use when we're talking about making measurements. The uncertainty in that physical quantity, usually expressed as the variance, sigma sub q squared, is expressed as an expectation value. So this outer pair of angle brackets is our usual notation for expectation value. What we're computing the expectation of is a quantity that's squared. So this is the mean squared deviation from the mean, q hat minus the expectation of q. Now this looks a little bit odd. We have one pair of angle brackets giving us the expectation of q. That's just some sort of a number. We can determine that before we even start computing. And then we have the outer pair of angle brackets that's going to give us the expectation of this overall expression, q minus the expectation of q. Let me simplify the notation a little bit here and write this number as just mu sub q. So this is the mean of q. So this is the deviation from the mean squared. This is the average mean squared deviation. That's our normal definition of the variance. Now you can expand this out using our notation for things like expectation values in the linear algebra structure of quantum mechanics. We have some sort of a wave function, q hat minus mu q squared, acting on the wave function. So this, as an operator, we've got the operator q, we've got the operator mu q. Mu q treated as an operator just multiplies by mu. It's like saying 6 as an operator. It's just going to multiply the wave function by 6. You can expand this out, psi on the left, q hat minus mu q, q hat minus mu q, acting on psi. And at this point, you can look at this and say, well, q, as represented by q hat in quantum mechanics, this q hat is going to be a Hermitian operator since we're talking about an observable q. And Hermitian operators can act either to the left or to the right. So let me take this q hat minus mu q, also of course going to be Hermitian because this is going to be a real number, this is going to be a Hermitian operator. The difference is just going to behave itself as a Hermitian operator. Let's have this one act on the left, leaving this one to act on the right. What I get then is going to be the result of having q hat minus mu q act on the left, inner product with the result of having q hat minus mu q act on the right. So this is just a sort of straightforward manipulation of the expression for the uncertainty in some observable quantity q. Now, you've got the same sort of thing on the left as on the right. Let's look at this and let's say this is some vector f. And this is, well, then it's going to be the same vector f. This overall here is going to act as just an inner product. F inner product with itself. I've got these two variables, or this vector which happens to appear twice. So whatever this vector is, I hesitate to call it the state of the system, but it is a vector in the Hilbert space as a result of applying a Hermitian operator to a state. And you can write that down. Just this is a definition of f. Now, in the context of uncertainty principles, we can always have determinate states. Any of the eigenvalues of q, or eigenstates of this Hermitian operator q, are going to have certain value of q. So it's certainly possible for sigma sub q to be equal to 0. But if we have a second observable, that's where we start talking about uncertainty principles. So suppose I have a second operator, or a second observable quantity, r, as represented by some Hermitian operator r hat. I can use that to construct sigma sub r squared in exactly the same way as this, substituting r for q everywhere in this expression. And when you get down to it, instead of calling that f, let me call that g. So if we have two separate operators, there's nothing to prevent me from making this manipulation for both of them, which means what we're talking about in the language of the uncertainty principle, as motivated by that delta x delta p structure, we're talking about something like sigma q squared, sigma r squared. That's going to be equal to, well, it's this f inner product with itself, g inner product with itself, just multiplied together. This is sigma q squared, this is sigma r squared, this is sigma q squared, this is sigma r squared. That should be fine. So what can we do with this? We've got f and we've got g. This is where things get a little bit subtle, but the overall derivation here is not terribly mathematically complicated. You just have to pay attention as things go past. So we've got this sort of expression. What can we do with it? There are two simplifications that are going to turn this equality into an inequality and convert it into a form that is useful from the perspective of the uncertainty principle. The first of those simplifications, working with this FFGG expression for two general vectors in our Hilbert space f and g, is the Schwarz inequality. Now, the Schwarz inequality is just a relationship between any sort of vectors like this. It says that if I've got the inner product of a vector with itself multiplied by the inner product of another vector with itself, that inner product is always going to be greater than or equal to the absolute magnitude of the inner product of the vectors with each other squared. You can think about this inequality very simply from the perspective of three-dimensional vectors in three-dimensional space. The inner product then is the dot product, and what this tells you is that the dot product of two vectors squared, a dot b quantity squared, is always going to be less than or equal to the magnitude of a squared times the magnitude of b squared. And if you're used to thinking about vectors like a dot b in the normal sort of notation, you've probably seen the formula magnitude of a, magnitude of b times the cosine of the angle between them. Now, since we're working in an infinite dimensional vector space, things like the angle between them is somewhat difficult to define, but this is the same sort of expression. If I dropped the cosine and made this into an inequality, meaning the right-hand side without the cosine is always going to be greater than or equal to the left-hand side, and then I were to say square both sides here, you would end up with the same sort of overall expression. Magnitude of a squared, magnitude of b squared, magnitude of dot product squared. So that's just an analogy. The Schwarz inequality holds in general, though it's somewhat difficult to prove. The textbook doesn't even bother proving it. So this is the first sort of simplification. We're going to pretend that instead of working with magnitude of f and magnitude of g, we're going to work with the magnitude of the inner product. The second simplification is that if we have some sort of complex number z, its squared magnitude is always going to be greater than or equal to the squared magnitude of the imaginary part of z. This is a very silly sort of construction to make if you think about it, but we can rewrite this in the context of that complex number z. So the complex number z then is always going to be at least greater than or equal to the imaginary part of z. Now the imaginary part of z, where the z is this complex number f inner product with g, we can write that as f inner product with g minus g inner product with f. So this is that number z minus its complex conjugate. Now minus the complex conjugate just flips the sign on the imaginary part, leaving the real part unchanged. So this subtraction is going to cancel out the real part and double the imaginary part. Now if I think about this, this is actually twice the complex part of this number, f inner product with g. So I would have to divide it by 2. And the imaginary part is, of course, going to be a purely imaginary number. So if I divide it by 2i, I'll get a purely real number, and I can stop worrying about the absolute magnitude. This is going to be a result. This result is essentially the same as this. So I have 1 over 2i dividing the difference of a number and its complex conjugate to pull out the imaginary part, cancel out the I, And then I'm squaring the result, same as I would be squaring the result here. So this sort of simplification, putting the overall expression up, tells you what we started with, which was sigma q squared, sigma r squared, is going to be greater than or equal to that final result, 1 over 2i times the complex number f inner product, or sorry, complex vector f inner product with complex vector g minus inner product of complex vector g with complex vector f. So, somewhat complicated expression, and unfortunately it's going to get worse before it gets better. Let's take a close look at what these vectors represent. Keep in mind that our vector f here was defined to be q hat minus mu q, acting on our state psi, and complex vector g was defined to be operator r minus mu r, acting on our state psi. Those were our definitions. So writing this out, let's take this first term first. We've got f inner product with g. That's going to be written out in terms of these definitions. So this is q operator minus mu q, acting on state psi, on the left, inner product with g, which is vector operator r minus mu r, acting on state psi. Now these are Hermitian operators, which means I can take the one that's acting on the left and push it back over to the right. Now that seems a little bit strange. Didn't we just do that step in reverse earlier on? Yes, we did. But it's a Hermitian operator. It's a perfectly valid mathematical expression. So that leaves me with just psi on its own on the left, and then we have this product of two operators, q hat minus mu q, r hat minus mu r, acting on psi, all acting on the right. This is now two binomials. It can be expanded out. So psi on the left, all by itself. And then here we've got something that needs to be FOILed. And keep in mind, operators don't commute in principle. While the operators q and r are not going to commute, mu q, r, and q, etc., those are just mu q and mu r, just multiplication by numbers. That commutes with pretty much everything. So what we're left with, we're going to have a q hat, r hat term here. We're going to have a minus mu q r hat term here. We're going to have a minus mu r q hat term from here. And we're going to have a plus mu q mu r term here. So there's our smiley face. We've counted for all of our terms, got all of the signs correct. All of that is acting on psi on the right. Now this is just an operator expression with 4 terms in it, separated by addition. These are linear operators, meaning I can separate this out into 4 separate expressions. What you're going to have then is going to be psi, q hat, r hat, acting on psi, minus mu q can be factored out of this sort of resulting expression, mu q times psi acting on r hat psi, from the r hat acting on the psi, the mu hat being factored out. Likewise, mu r psi q hat psi plus mu q mu r psi psi. So we can simplify some of these terms right away. This guy is just 1. This is the normalization integral. If our state is properly normalized, this inner product is going to be 1. And the rest of these things, these are expectation values. This is the expectation value of q hat r hat. This is the expectation value of r hat. This is the expectation value of q hat. So if I was to pull along the constants, have them all come for the ride, this is q hat r hat minus mu q, expectation of r hat, minus mu r, expectation of q hat, plus mu q mu r. But r hat, that's just mu r, and q hat, that's just mu q. So I've got the expectation value of q hat r hat, whatever it is, minus mu q mu r minus mu r mu q plus mu q mu r. These are just scalar multiplications. They commute, so one of these is going to cancel out. Let's say that one. And what I'm left with is the expectation value of q hat r hat minus mu q mu r. So that's what I got for fg. Now fg, I've also got to work with gf. Gf is going to end up very similarly. If you think about g and f, it's going to look essentially identical to this, except q and r are going to be interchanged. So g and f here is going to give me the expectation value of r hat q hat minus, again, mu q mu r. Same sort of product of uncertainties, or product of means. So that, believe it or not, is all we need to get our main result. We have sigma q and sigma r in terms of these sorts of complex numbers, which are expressed in terms of expectation values of those fundamental operators. So if you substitute all of that back in, we had fg minus gf. That's going to be bracket q hat r hat, so expectation of qr, minus the expectation of r hat q hat. And that's it. The mu q mu r terms are going to cancel out. They were added on regardless whether we're talking qr or rq, so when we subtract, they're just going to cancel out. And you can think about this as being the expectation of q hat r hat minus r hat q hat, which this qr minus rq, you should recognize this is a commutator. So we can write this down instead as the commutator of q hat and r hat. So, our final expression then, putting all of the constants back into it, is that sigma q squared, sigma r squared is always going to be greater than or equal to 1 over 2i times the expectation value of the commutator of the operator q with the operator r. All of that squared. That is our result. That is the generalized uncertainty principle. What this tells you is that any two operators, q and r, are going to have an uncertainty relation if they have non-zero commutator. So if the two operators commute, there's nothing wrong with knowing both of them precisely. They can both have zero uncertainty. But if they have non-zero commutator, meaning the expression qr minus rq does not have zero expectation value, then any two observables then those two observables will have non-zero uncertainty principle. There will be some minimum uncertainty. The obvious example to do here is position and momentum. We talked about the commutator of the operator x hat and the operator p hat before. It's just x hat p hat minus p hat x hat. And if you substitute in the definition of p hat as minus I h bar partial x, and the definition of the operator x hat as just x, multiplied by, and you insert some dummy wave functions on either side, that was an activity that we did earlier on in the course, you find that the commutator here is equal to just a constant, I h bar. It's a complex constant, which seems a little strange, but there's nothing wrong with complex numbers when you're mixing operators like this. It's only when you would make an observation of a single operator, single physical quantity, that you have to get real numbers. What that tells us is that sigma x squared sigma p squared in the generalized uncertainty relation is going to be 1 over 2i times the expectation value of the commutator, which is just I h bar squared. So the expectation value of a constant is just going to be the constant. So this is just going to be I h bar over 2i, quantity squared. I's cancel out, and we've just got h bar squared over 4. H bar over 2 squared. Now the way that uncertainty principle is usually stated is sigma x sigma p is greater than or equal to h bar over 2, and that of course is clearly the same expression that we're working with here. So good. We've got the same sort of uncertainty relation that we introduced earlier on in the course. To check your understanding of this sort of process, here are some questions for you. What would happen in the derivation if instead of throwing out the real part, meaning instead of saying that the absolute magnitude squared of some complex number is always greater than 1 over 2i z minus z star, all squared. What would happen if I instead threw out the real part by adding the number to its complex conjugate instead? Would you still get a commutator, and what extra terms would it introduce? And finally, just in terms of some of the steps in that derivation, why exactly did this step happen? What are the principles that are applied in that equality? What definitions do you need to know? Now, that's about all that there is to the generalized uncertainty principle. It's an amazingly powerful mathematical tool, but well, let's play with it a little more. How strict is this limit, and can we beat it? Now, the limit that we're talking about here is this relationship. I had some sort of sigma q squared, sigma r squared was always greater than or equal to 1 over 2i times the expectation of the commutator of operator q and operator r, all squared. That's our generalized uncertainty principle. This inequality, where did that inequality come from? Well, it came from two places. It came from the Schwarz inequality, which told you that the inner product of that vector we defined, f with itself, multiplied by the inner product of the vector g with itself, was always going to be greater than the squared modulus of the inner product of f and g. That was one source of the inequality. So if we're trying to make this into an equality, we have to not grant any space in between the result of these inner products and the inner product of the vectors with itself. How can we make the Schwarz inequality into an equality, in other words? And that's rather straightforward if you think about it. The vector g is just going to be some constant, say c, times the vector f. If this is true, then this is going to be c squared f squared, and this is going to be c squared f squared, and we're going to have an equality here overall. The second inequality we had was when we threw out the real part. We said the magnitude of that complex number, fg, in terms of its squared modulus, was always going to be greater than or equal to this 1 over 2i times fg minus gf. All of that squared. This statement, can we make this into an equality as well? Well, what we're looking at here is going to be an equality if we're throwing out the real part, and we're taking the squared magnitude of it. The squared magnitude is only ever not going to change when we throw out the real part if the real part is 0 to begin with. So we've got equality here if the real part of fg, that inner product, is equal to 0. And that's reasonably straightforward. We're looking at fg, but we know g can be expressed in terms of c, so we're talking about the real part of f times g expressed as cf gives me a c and another f. So the real part of c times this inner product of a function, or of a vector with itself, this inner product of a vector with itself is going to be a real number. No matter what you do, you're taking a complex conjugate, multiplying it by itself, essentially, you're going to get a real number. So this is only ever going to equal 0 if c is complex. C is, purely imaginary. C being purely imaginary, let's write it as the imaginary unit I times some real number, A. So given some C equals I times A, if we define our states, or if we define our operators and our states such that G is given by some complex unit times A times the state F, for some real A, then we've turned both of our inequalities into equalities. So what does that mean? What sort of implications does this have? Let's consider that in the context of position momentum uncertainty, just to make this a little more concrete. We have this notion that our vector G is imaginary unit times some real number times our vector F. Now, in the version, or in the language of position momentum uncertainty, then this vector G is going to be p hat minus expectation of p times our state. And we know what the position, or what the momentum operator is. This is going to be minus I h bar, partial derivative with respect to x, minus expectation value of p. I'll just leave it as expectation value of p here. This is just going to be a number, so there's no magic there. And this is going to be multiplied by psi of x. If I'm writing out my momentum operator in terms of partial derivatives, I better write my wave function in terms of x instead of just as some arbitrary state vector. Likewise, we've got our vector f, and this has to be expressed in terms of our position. So this is going to be x hat minus expectation of x, acting on our state. And likewise, in terms of wave functions, this is going to be x multiplication minus expectation value of x, the constant, multiplying our wave function psi of x. So our expression for g in terms of IA times f, with these particular definitions of g and f, we can plug these together, substitute these expressions here into this equation here, and you end up with, separating things out, minus I h bar partial psi partial x minus expectation value of momentum multiplying psi. And that has to be equal to I times A times our expression for f, which, I'll just expand that out. We've got I times A times x times psi of x minus I times A times expectation of x times psi of x. This right here is a differential equation for psi. And it turns out it's actually a pretty easy differential equation to solve. If you rearrange things a little bit, you can find out that this is going to give you a derivative of psi with respect to x as, in terms of, let's see, what have I got? I've got a, after I've divided through by minus I h bar, I'm going to have a minus a over h bar, let's say x psi, pulling the complicated term first, and then I'm going to have a plus a over h bar expectation of x psi, and a plus I expectation of p over h bar psi. Provided I've got all of my signs correct there, I haven't lost any terms. I've got the over h bars. Yeah, I think that looks right. This is a fairly straightforward ordinary differential equation to solve. Now I'll leave it as an exercise to you guys to actually go through and solve this, but the procedure for solving it I think is most easy to think about. Let me just guess that my wave function psi is equal to e to the some sort of function f of x. If you do that, you find a simplified differential equation just for f. This sort of initial guess where psi is going to be some sort of an exponential and you're trying to find the behavior of the exponent is a common technique for solving differential equations where your derivatives essentially give you the function back multiplied by various terms. Under these circumstances, you can figure out what your psi of x actually looks like. And your psi of x under these circumstances has to be e to the minus a over 2 h bar, let's see, x minus the expected value of x, quantity squared, e to the I expectation value of p over h bar times x. And then there's another constant floating around here, something like e to the a expectation value of x squared all over 2 h bar. This solution comes out of just a straightforward solve here. The only simplification I've made on the result is to complete the square in the exponent. Whenever you have a x squared sort of behavior, it's good to pull that off by itself. The reason I've separated these three terms out instead of writing them all as sums together in the exponent is it makes the structure a little bit more straightforward. This is some sort of a constant. This is something that looks like just something with a certain momentum, ikx. And this is a Gaussian. E to the minus something x squared. This Gaussian form is definitely a realizable wave function. We've actually met Gaussian wave functions before, for example, in the quantum harmonic oscillator ground state. Under those circumstances, you have met the uncertainty limit. You can meet the uncertainty principal limit, so the two messages there is that, first of all, the uncertainty limit is attainable, but it's difficult. You have to be in a very specific sort of mathematical state. This is not going to be true for anything that's non-Gaussian. The second take-home message from this is that the uncertainty principle is actually a fairly strict limit. That despite the fact that we made those seemingly a little bit fudgy simplifications when we were working through the derivation of the generalized uncertainty principle, applying the Schwarz inequality, and just assuming that the real part of the number could be neglected and the imaginary part was the only thing that mattered, we haven't actually ceded too much ground there. The uncertainty principle is a fairly strict limit that is actually attainable. It's not like we've made some ridiculous lower limit, or ridiculous lower limit on the uncertainty. Regardless, that's a mathematical discussion of the formal structure of the uncertainty principle in quantum mechanics, and subject to the generalized uncertainty principle, any two operators with a non-zero commutator are going to have some sort of uncertainty principle. And you could go through the same sort of derivation of what the minimum uncertainty behavior would look like for any two operators. It's relatively straightforward for the position momentum structure, and you get a Gaussian, but you could do it for other cases as well. I think that about sums it up, though. Generalized uncertainty in quantum mechanics is, like I said, a very powerful mathematical tool, so keep that one in your bag of tricks. Given the generalized uncertainty principle for any two quantum mechanical operators, something like sigma q squared sigma r squared is greater than or equal to 1 over 2i times the commutator of the operator q and the operator r, all squared, you might think that uncertainty principles have been pretty well settled. But that's actually not the case. While this does give a good and satisfying explanation of something like the classic sort of delta p delta x is greater than or equal to h bar over 2 sort of uncertainty relation, it doesn't cover the case delta e delta t is greater than or equal to h bar over 2. If you've seen this sort of uncertainty principle, it's also very useful in physics, but it is of a fundamentally different nature than position momentum uncertainty. And the fundamental reason for that is that there's something special about time. Time in quantum mechanics is a parameter that shows up in the arguments to your equations. It's not so much like momentum where there's a well-defined momentum operator. So how can we handle energy-time uncertainty? Well, the notion of time in a quantum mechanical system is a little bit squishy. If you're talking about the time evolution of something like e to the I e t over h bar, that solution to the time-dependent Schrodinger equation, or at least the time part thereof when you apply separation of variables, this thing just rotates around in complex number space. It doesn't actually change the fundamental nature of the solution unless you have some sort of a superposition of two states where they have different time dependences, two states of different energies, and the overall time dependence only ever depends on the energy difference. Now, that suggests that if we're talking about some sort of a change in a process, some sort of a change in expectation value of position, for instance, that as it results from a superposition of two stationary states with different energies, we ought to consider the notion of change. Time is only ever going to be relevant when we're considering things that change, because if nothing is changing, then what does time really mean? Well, if we're talking about change, we're talking about some sort of an operator, because we're talking about something that changes. We need to have an observable, so we need to have some operator, and as usual, I'll call that q hat, meaning the Hermitian operator that corresponds to some sort of quantity q. So let's consider time derivative of the expectation value of q. This gives us some sort of classical almost notion of how things change with time. Now, the expectation value in our generalized linear algebra formulation is a linear product of our state psi, our operator q hat acting on state psi. This inner product has three components to it. We've got a wave function on the left, an operator, which potentially has time dependence in it itself, and another wave function on the right, or another state on the right. And if you think about the inner product as written out in terms of an integral of wave functions, this is going to be a complicated integral, but it's got three things in it that are all going to potentially vary with time. So let me sweep some of the mathematical details under the rug here and rewrite this, more or less applying the product rule. So we've got a partial derivative of psi with respect to time, whatever that state may be, multiplying our inner product with q acting on psi. We have psi on the left, acting on a partial derivative of q hat with respect to time, whatever that may be, that operator acting on psi, and we have psi acting on, or inner product with q hat acting on partial psi, partial t. Now this is a very suggestive notation. It feels like it's only ever going to be relevant if we're talking about psi as functions of time. What on earth does this notation mean to begin with? Not much, to be quite frank with you. There's a lot of somewhat dicey mathematical things that have happened behind the scenes in applying the, quote, product rule, unquote, to this sort of expression. If we're really going to write these things out as integrals, then these are well-defined mathematical operations, and you can apply the product rule, and all of these sorts of things make sense. But if we're trying to do this in general, I've kind of swept a little bit too much under the rug. That said, I'm going to leave things in this general form. And the reason for that is it's a much more concise notation. So if you want a sort of behind-the-scenes idea of what's going on in each of these terms, try and translate it into an integral and figure out what exactly has happened in each of these steps. If you're willing to take me at my word that this is at least somewhat meaningful notation, we can write down, for instance, some of these terms with partial derivatives of psi in them can be simplified with the time-dependent Schrodinger equation. And the time-dependent Schrodinger equation tells us that I, h bar, partial psi, partial t, is given by the Hamiltonian operator acting on psi. So really I ought to say this is a state, and this is a state in my vector notation. But in this sort of context, you can simplify this sort of term and this sort of term. So let's do that. Let's substitute in for this and in for this. When you do that, these three sort of expectation value-like terms can be simplified a little bit. First of all, this partial psi partial t on the left, I've got a 1 over I h bar when I simplify to just get partial psi partial t by itself. So this is 1 over I h bar Hamiltonian applied to psi as our replacement for this overall state here on the left. And then I've got q hat psi on the right. This middle term here is just going to be the expectation value of partial q partial t. Now, what on earth is that? Can I take the partial time derivative of an operator? Yes, if the operator has explicit time dependence. If the operator doesn't have explicit time dependence, then it's not going to have any partial time derivative. This term is going to be 0, and we're about to say this term is equal to 0 in a few minutes anyway. To give you an example of a situation where this term would be non-zero, think about something like the potential energy in the harmonic oscillator, where the spring constant of the harmonic oscillator is gradually being tuned. The frequency of the oscillator is changing with time. Perhaps the spring is getting gradually weaker, or the temperature is changing, affecting the spring constant. Under those circumstances, this term would be non-zero. The operator for, say, the potential energy in that quantum harmonic oscillator would be a time-dependent operator, and taking the partial time derivative would give you something that's non-zero. This third term, we can also apply a simplification. We've got psi on the left. We're not going to touch that. And on the right-hand side, we've got, let's see, 1 over I h bar. We've got a q hat and an h, and a 1 over I h bar there, acting on psi. Now, the next step in the derivation here, in considering how we can possibly simplify this, is we've got a term with q hat, h hat, excuse me, on the right, and a term here, h hat and q hat. So let's see if we can simplify this by applying the notion of a Hermitian operator to each of these terms. If I use the fact that h hat is a Hermitian operator, I can simplify, or not simplify, I can move the h. I can, instead of having h act on the left, I can have h act on the right. So this will become an h hat q hat acting on psi, similar to my q hat h hat over here. Now the other thing that I have to do in order to simplify these terms is to figure out what to do with these constants. Multiplication by a constant on the right does nothing. I h bar in the denominator, I'm just going to move that outside. So that will become a 1 over I h bar outside this expression. Now the 1 over I h bar here cannot simply be moved outside, and the reason for that is it's inside this left-hand side of the equation. So if I move it outside, I have to think about taking complex conjugate. So if I'm going to move this guy outside, I have to stick a minus sign on it because I've got an I in it. I have to flip the sign on it. Now, if I do those two simplifications, first I have a minus 1 over I h bar. In this term, I have psi h hat q hat psi. This term, which I'm going to write next, is plus 1 over I h bar psi q hat h hat psi. And my remaining term over here is partial q hat partial t, expectation of that, whatever it may be. Now, this overall expression here can be simplified even further. Here I have a h hat q hat and a q hat h hat. If you're seeing a commutator on the horizon, you're thinking the right thought. Let's combine these two terms together, these two expectations together, essentially factoring out the psi on the left and the psi on the right. What we're going to be left with is something like minus 1 over I h bar psi, and then the operator here is going to be h hat q hat minus q hat h hat. Factored out a second minus from the q hat h hat term here. And I've got psi on the right. And as before, I've got my expectation of partial q hat partial t coming along for the ride. So this term, now I can write that as I over h bar. If I multiply and divide both of these things by I, basically move the I to the numerator, flips the sign. I have here the expectation of the commutator of h and q, plus the expectation of the partial derivative of the operator q hat with respect to time. So this is a somewhat general result. Any time derivative of an expectation value is going to be given by a commutator of that operator that gives you the expectation and the Hamiltonian, plus some sort of explicit time dependence. If there isn't any explicit time dependence in this, what this tells you is that if the operator and the Hamiltonian commute with each other, if the commutator is 0, in other words, if HQ is equal to QH, then there is potentially going to be no time dependence for your expectation value. Essentially, time evolution of system as given by the time-dependent Schrodinger equation, essentially ignores the expectation value of the operator that you're considering. It's some sort of a conserved quantity. That's a very useful sort of thing to be able to figure out. So if you've got commutator is 0, you're going to have a conserved quantity. Keep that in the back of your mind. Now, for the special case where the partial derivative of the Q operator itself is exactly 0, then what we're left with from the previous slide is that the time derivative of our expectation value of Q is equal to I over h bar times the expectation of our commutator h hat q hat. That was our general result. I just dropped the partial the expectation value of this sort of term. Now, back to the notion of uncertainty. If I have the Hamiltonian and my operator q as the two things that I'm considering, meaning I'm looking at an uncertainty in the Hamiltonian squared and the uncertainty in my operator q squared, this is going to be our energy uncertainty. What is it sigma q going to be? Well, given this expectation of a commutator, that's the sort of thing that appears on the right-hand side of our generalized uncertainty principle. We had a 1 over 2i expectation of a commutator applied to this particular operator pair is going to be h hat q hat inside the commutator, all squared. So expectation of a commutator, I can rewrite that in terms of the time derivative of the expectation. So my right-hand side here, I can rewrite in terms of this as I've got my 1 over 2i as before. I got to solve for the commutator by multiplying through by h and dividing by I. So I've got an h bar over I on the left-hand side and d dt of the expectation value of q. All of that's going to be squared. So simplifying this, I've got an I and an I, which is going to give you a minus 1 in the denominator, so I'm going to have a minus sign, but I'm squaring everything overall, so that's not going to change much. And what I've got for my right-hand side is h bar squared over, let's see. Let me write it as h bar over 2, quantity squared, and then I've got my d dt of the expectation value of q squared. So what this tells you is that sigma h, sigma q, taking the square root of both sides of this equation, is going to be greater than or equal to h bar over 2 times this weird thing, the time derivative of the expectation value of q. I'll put that in absolute magnitude sign to cover my bases in terms of square roots of squares. What this tells you is that the uncertainty in the value of an operator, the uncertainty in the operator itself, is going to be related to the time derivative of the expectation value of that operator. Essentially what that's telling you is that your uncertainty in the outcome of a measurement is going to depend on how quickly the quantity that you're trying to measure is changing. And that seems honestly rather logical. There is another factor here in terms of the uncertainty in the energy that helps bring things into focus further, though. So let's make a note of this result. It's nice and sort of qualitatively appealing, the notion that the uncertainty in an observable is related to how fast it changes, and the more quickly it's changing, the higher the time derivative of its expectation value, the larger the resulting uncertainty must be. But let's see if we can cast that in terms of that classic delta E, delta T uncertainty. If we're talking about delta E, that's essentially our sigma sub h. It's our uncertainty that results from a measurement of the energy, which is given by proxy in the notion of quantum mechanics, or the language of quantum mechanics, in terms of the Hamiltonian operator. And really we need some notion of delta t as well. What is delta t in this case? Well, let's define delta t to be something like the uncertainty in our observable q divided by the magnitude of the time derivative of the expectation value of q. This is sort of some characteristic size of change in q multiplied by the rate of change in q. So if this is some sort of delta q over dq dt, this would give me some sort of a notion of delta t. More by dimensional analysis than anything else. Really what this means is sigma q can be thought of in terms of the time derivative of the expectation value of q and delta t, if I just say multiply this out onto the left-hand side, which says that this characteristic time that I'm interested in is the amount of time it takes the system to change by one sort of standard deviation of the observable in question. So this is going to depend on the observables that you're working with in some sense, but it is a notion of the characteristic timescale of change in the system. Now under these circumstances, our sigma h, sigma q expression is going to look like h bar over 2, and then we had the time derivative of the expectation value of q. That is going to be converted into delta E, replacing sigma h, delta t, replacing sigma q, with this sort of expression. And then you can cancel out, essentially, this time derivative of q is going to appear both on the left-hand side and the right-hand side, thinking about it along those lines. And what we'll be left with is just that this is greater than equal to h bar over 2. So, there you have it. We have a derivation of the conventional energy-time uncertainty relation. What you should keep in mind here is that all of this was derived assuming a particular observable. So the potential results that you're going to get are going to depend on the quantity that you're interested in. If some quantity that you're interested in is changing very rapidly, then you're going to end up with a relevant delta t. This delta t is not just some time measurement uncertainty, it's a time scale of change of the quantity that you're interested in. So there has to be some sort of quantity in the back of your mind. You're not just saying delta t for the system, you're saying delta t for momentum, or delta t for position, or delta t for kinetic energy, or something like that. Regardless, the conclusions are the same. The system is evolving rapidly, meaning with respect to the variable that I'm concerned about, the time derivative of the expectation value is large. Then what that means is that delta t will be small, right? Large number in the denominator gives you a small number. And what that means is that the uncertainty in the energy will be large. Essentially what that means is if you have a system that is changing rapidly, it has to consist of a superposition of a wide range of different energies. You can only ever get a system to evolve rapidly with time if it contains a wide range in energies. And that gets back to the same sort of discussion we had earlier on in this lecture, where I said that the only way you ever got an expectation value to evolve was if you had a superposition of states with multiple energies. The wider the separation between those energies, the more rapidly the evolution would occur. That's reflected again in this energy-time sort of uncertainty relation. The flip side of this, if the system is relatively stable, what that means is that your system is evolving slowly with respect to the observable that you're interested in. So the time derivative of the expectation value of that observable is small. Then that means it will take a long time for the observable to change by one sort of standard deviation in the observable, which means our delta t is large. And consequently, our delta E can be small. We can have a small uncertainty in energy if we have a slowly varying system. If you have a system that's stable with time, nothing is changing very rapidly, then the energy uncertainty can be small. It can have a very precise energy. Keep in mind, these are all just inequalities, so you can have a very large energy uncertainty and a very rapidly evolving, and a very slowly evolving system. But at any rate, the last thing that I wanted to mention here is that all of this is really valid for any sort of Q. So this Q is representing any observable. What that means is that if anything is changing rapidly, then the energy uncertainty will be small. We can flip that statement around and say that the energy uncertainty will be large. We can flip that statement around and say if the energy uncertainty is very small, meaning we're dealing with sort of a determinate state, something with almost no energy uncertainty, then all time derivatives of expectations of any observable are going to be small. And we've said that before in the context of stationary states. Stationary states are the states that are eigenstates of the Hamiltonian operator. They evolve with time in a very simple way, and for a system that is in a single stationary state, the energy uncertainty is zero, therefore the delta t has to be a very, very large number, effectively infinity, in order for this inequality to hold, which means all changes in the system take place on a very, very, very long timescale. Everything is evolving very, very slowly. And in the sense of a true mathematical stationary state that is exactly stationary, nothing is allowed to change with time. Stationary states are truly stationary. So, that wraps up our discussion of energy-time uncertainty. This is fundamentally different than the notion of position-momentum uncertainty, where both position and momentum are operators. But it does have some nice general interpretations in terms of the rate of change of expectation values of operators. So keep all of this in the back of your mind. It will help you interpret the behavior of quantum mechanical systems in general as they evolve with time.
We started off this course by building a framework, talking about quantum mechanics in one dimension, where it is most simple and easiest to understand. Then we built up some formalism, talking about the mathematical structure of quantum mechanics. Now we're going to come back to where we started, except instead of talking about quantum mechanics in one dimension, we're going to talk about it in 3 dimensions. We live in 3 dimensions, so this is where the real-world examples start to enter quantum mechanics. First of all, how do we go from 1 dimension to 3 dimensions? If we're going to start off in 1 dimension, we ought to have counterparts for the concepts that we encountered in 1 dimension in 3 dimensions. In 1 dimension, we had a wave function, which was a function of position and time. In 3 dimensions, our wave function is going to be a function of position in 3 dimensions and time. Thankfully, it has not become a vector function. It is still only a scalar function, but it is now a function of 4 variables instead of only 1. Or instead of only 2 here. We will see shortly that when we were talking about the time-independent Schrodinger equation, as derived from this full time-dependent wave function, we ended up with the solution to the time-independent Schrodinger equation were simply a function of position times e to the minus I energy time over h bar. We're going to find out something very similar happens in 3-dimensional quantum mechanics. We'll get a function of position in 3 dimensions
multiplied by the same exponential factor, e to the minus I energy time over h bar. The operators that will appear in the Schrodinger equation, for instance, in one dimension, we had, for instance, the position operator x hat and the momentum operator p hat. X hat and p hat in 3 dimensions are going to be vector operators. So instead of just having x hat, I'll have x hat, y hat, and z hat in a vector, or px hat, py hat, and pz hat in a vector. And the definitions here are more or less what you would expect. For instance, let's just say px hat is going to be minus I h bar derivative with respect to x. I have to start being more careful about the difference between total derivatives and partial derivatives now, since we're talking about functions of multiple variables. But hopefully the notation will become reasonably clear shortly. The full momentum vector operator here is going to be written then in terms of partial derivatives of x, y, and z, and we have some notation for that. Minus I h bar times this upside down triangle with a vector hat on top of it. This is the gradient operator from vector calculus, and this is going to be read as del or grad, or the gradient of, depending on whatever it's acting on. And this gradient operator here, as before, let me move this out of the way a little bit so my notation is less confusing. This full vector. One of the key experiments that really got quantum mechanics started was spectroscopy. Bright line spectra of the elements. They couldn't really be explained in the context of what physics was known at the time, and we've finally gotten to the point now where we can use the quantum mechanics we've learned so far to explain these bright line spectra. At least some of them, perhaps. This is the spectrum of hydrogen, this is the spectrum of mercury, this is the spectrum of neon, and this is xenon. So, 4 gases, and we'll be able to explain successfully the most simple gas possible, hydrogen. Our discussion of the time-independent Schrodinger equation in 3D, separated in spherical coordinates as appropriate for the spherically symmetric potential of a charged particle orbiting a nucleus, gave us psi with 3 quantum numbers n, l, and m. I'm not going to reproduce the long, complicated expression for what these are, but you know the radial part is given by the associated Laguerre polynomials, and the angular part is given by the spherical harmonics. As we went through the solution of the time-independent Schrodinger equation, we introduced a variety of constants, and then requirements, in particular for periodicity in the phi solution, the convergence and well-behavedness of the angular solutions, and convergence and well-behavedness of the radial solutions, gave us quantization conditions that we used to construct these n, l, and m. The constants that we got, for instance, we defined a k squared that was given by a 2me over h bar squared. That should look familiar. We found out that that constant had to be given by 1 over some a squared, some radius squared, times an n squared quantum number. This a value, the Bohr radius, is about half an angstrom. And the energies that we got, after unwinding all of those definitions that we made, look something like this. You have the energy of the nth energy level, the nth stationary state, the stationary state with n as the quantum number, is given by this constant times 1 over n squared. And that constant should look familiar. It's minus 13.6, or it's 13.6 electron volts, with a minus sign out front, signifying that these are bound states. Their energy is less than the energy of a free particle. So minus 13.6 electron volts over n squared, those are the energy levels of our stationary states. Our stationary states are not going to be stationary in reality because atoms bump into each other and atoms interact in random ways that we haven't described the physics of yet. But suffice it to say, perhaps, that these energies are not going to remain forever fixed. If I prepare an atom in, say, the n equals 3, a quantum state with n equals 3, it's not going to stay there forever. After a while, it will lose that energy, and when it does, it will emit a photon. The changes in energy that take place are energy carried off by the photon. So we would say, for instance, that if we had, say,
n equals 3 goes to n equals 2, there's a change in energy here, and we would say the atom has emitted a photon. Correspondingly, if you have an atom in state n equals 2 and it's excited up to state n equals 3 by an electromagnetic field surrounding the atom, we would say this atom has absorbed a photon. This absorption and emission of photons, photon here is our shorthand term for a particle of light, or quanta of light, perhaps I should say quantum of light, is really the crux of the matter here. All of our experiments that motivated quantum mechanics had somehow to do with the interaction of light and matter. With our treatment of the hydrogen atom, we now have descriptions of how we can calculate changes in energy on the matter side. We haven't really said anything about the photon side, and unfortunately for that we'll need relativistic quantum mechanics, which is a topic for another course. But at any rate, you know that light is going to be emitted and absorbed in quanta, and the energies of those quanta are going to be given by the changes in energy of the thing that we can calculate, the thing that happens on the atomic side. So these stationary states are not going to be all that stationary, and by plugging in numbers for initial and final energy levels, you can calculate out what the energy of the photon would be, what the change in energy of the atom would be. These transitions have names, and this is a very standard visualization of what those energies might look like. The y-axis here is an energy scale, and it has 0 at the top. Anything with energies higher than 0 is not a bound state. The thick horizontal lines here represent the energies of the nth energy level. Here's n equals 1, the lowest energy level, n equals 2, 3, 4, 5, 6, 7, etc., up to infinity, where the bound state isn't really bound anymore. It has essentially 0 energy. The transitions that are possible, for instance, if we're looking at the emission of light by a hydrogen atom, the atom is going to start in a higher energy level and drop down to a lower energy level. When it does so from an energy level 2, 3, 4, 5, 6, etc. up to infinity, all the way down to the ground state, n equals 1, we call that a Lyman line. The emission in the spectroscopic context has a particular pattern of energies that were first examined by, well, Lyman, and the lines are named after him. Transitions that start with 3, 4, 5, 6, etc. go up to infinity and drop down to the second energy level are called Balmer lines. Likewise, end state lines with n equals 3 are Paschen lines. There are also bracket lines. You don't hear very much about them. Even less common are the Pfund lines and the Humphrey lines, which you can imagine have a final state of energy 5 and energy 6. So these transitions are the sorts of things that you would expect from the energy structure that we calculated as a result of the time-independent Schrodinger equation with a 1 over r potential. The transition wavelengths can be calculated pretty simply. What we have here is an energy that we can calculate, and we know the energy of the photon is going to be given by Planck's constant times the speed of light, let's say Planck's constant times the frequency, or alternatively, Planck's constant times the speed of light divided by the wavelength. Note that this is Planck's constant, not h bar, the version of the reduced Planck's constant that we've been using so far. So when you actually go out to calculate these things, you can calculate wavelengths easily by using the expression we had for the energy change by the atom, using that as the energy of the photon. The symbol for photon is gamma, typically, and solving for the wavelength. Doing so, you end up with this sort of thing, and this is a logarithmic scale now, 100 nanometer wavelength, 1000 nanometer wavelength, 10,000 nanometer wavelengths, and these things fall in very specific patterns. The Lyman series, which ended with n equals 1 as the final state, so this is a 2-to-1 transition, the longest wavelength Lyman line. This would be a 3-to-1, 4-to-1, 5-to-1, etc., all the way up to infinity to 1. Likewise for the Balmer lines, 3-to-2, 4-to-2, 5-to-2, 6-to-2, 7-to-2, etc., up to infinity to 2. Same for the Paschen series, and the Bracket series, and the Pfund series, and I forgot his name already, the Humphrey series. They all have these nice patterns, and they all overlap. And if what you're looking at is the visible spectrum of hydrogen, you're looking at the Balmer lines. There are probably other lines that are visible if you look at a, quote, hydrogen gas, unquote, source, being excited by a gas discharge, high voltage for instance, those are likely due to impurities. And if you think about the hydrogen atom, well, that's going to behave differently than the hydrogen molecule. It's going to behave differently than the singly ionized hydrogen molecule. And spectra like this, even with just a single atom, and this is just as predicted for the hydrogen atom with just a single electron, you already have very complicated behavior. So if I flip back to my motivating slide here, this is just looking at the visible portion of the hydrogen spectrum, and you can now identify this as the n equals 3 to 2 transition, this as the 4 to 2 transition, 5 to 2, 6 to 2, and if you continue into the UV, 7 to 2, 8 to 2, 9 to 2, 10 to 2, etc. These are the Balmer lines of hydrogen. When you work with more complicated atoms with more electrons, you have far more complicated behavior, and this is unfortunately something that quantum mechanics still really cannot predict well. To check your understanding of all of this, I have some simple calculations for you to do. First of all, figure out how the formulas that we gave for hydrogen would change for helium. You still have just singly ionized helium. So a single electron, instead of orbiting a single proton, orbiting an electron or orbiting an alpha particle, something with 2 protons. So the charge on the nucleus is going to double, and that will change the energies. Then make some calculations of energies, figure out whether they would be visible or not, and as finally, calculate the longest wavelength. Identify the transition for the longest wavelength in the Lyman series. These are conceptual sorts of questions that you need to understand the structure of the energy levels of hydrogen in order to answer, and there are also some simple calculations to do. But the fact that you are capable of making these calculations is really a triumph of quantum mechanics. We started with something that is essentially just an equation, hypothesized, almost entirely without justification. And it actually seems to work. You can do separation of variables, you can go through a lot of complicated mathematics, which from the physics perspective is more or less just turning the crank, trying to solve this equation. And the structure that you get, subject to all of this interpretation we did as far as the probabilistic interpretation of quantum mechanics requiring normalization of the wave function, and the overall structure of all of this leads to calculations of real measurable physical quantities. And for instance, the answer that you'll calculate for this is something that you can look up. If you look up helium spectrum in Google, you will get lots and lots of matches, and some of them will include data tables with hundreds, if not thousands, of observed and identified helium lines. And the energies that you calculate, the energy that you calculate will be in that list. And that's really quite astonishing if you think about it. It speaks to the overall power of quantum mechanics. We started this chapter by considering quantum mechanics in 3 dimensions. The first tool we used to solve problems, to solve the time-independent Schrodinger equation in 3 dimensions, in particular, was separation of variables. We used separation of variables back in 1 dimension as well to separate the time evolution of an equation from the spatial evolution. That was how we got the time-independent Schrodinger equation from the time-dependent Schrodinger equation. In the case of 3-dimensional space, we also use separation of variables to separate the dimensions of space from each other. X from Y from Z, or in the case of spherical coordinates, which are most convenient for spherically symmetric potentials like we have for the case of the hydrogen atom, R from theta from phi. Another major difference between 3-dimensional space and 1-dimensional space is that in 3-dimensional space we have angular momentum. Angular momentum is not something that's going to fit into a single dimension, of course. So let's think about how angular momentum might behave in quantum mechanics. The approach we're going to take in this lecture uses operator algebra, the same sort of cleverness that we used back when we were talking about the quantum harmonic oscillator in 1 dimension with raising and lowering operators. We're going to take a very similar approach here. Back to basics though, first let's consider angular momentum. Angular momentum is what you have when you have an object and it's rotating about some axis. In classical physics, you're used to thinking about this as something like r times m times v, the momentum and the radius, mvr. The best way of expressing this in classical physics is as L, which is a vector, is r vector cross with momentum vector, where r is the vector that goes from the axis to the object that's rotating, and p is the momentum, linear momentum, of the object that's rotating.
We can make an analogous expression in quantum mechanics simply by replacing the arrows with hats. I know that's not terribly instructive, and we'll talk about that in more detail. But let's define a momentum operator, L hat, that's equal to R hat cross P hat, where P hat is a vector momentum operator and R hat is a vector position operator. Essentially, X hat, Y hat, Z hat as a vector crossed with PX hat, PY hat, PZ hat, if I was writing things out in Cartesian coordinates. Now at this point, I'm going to save myself a lot of writing and drop the hats. I'll try and make it clear as I write these things down what's an operator and what's not an operator, but for the most part in this lecture, what I'm going to be working with are operators. This is an operator algebra lecture after all. So if you actually do the cross product between these x, y, and z operators, and these px, py, and pz operators, what you end up with is, well, you can do cross product, presumably. You end up with y hat pz, sorry, I was dropping the hats, wasn't I? Y pz minus z py, that's our x component. Z px minus x pz, that's our y component. And x py minus y px, that's our z component. Now these are all operators, and they're the same sort of thing that you're familiar with. Y, and I'll put the hat on in this case, is going to be y, the coordinate, multiplied by something. Whatever the operator is acting on, y hat acting on that is just going to be y, the coordinate, times whatever it's acting on, the function in this case. Likewise, for instance, py hat is minus I h bar partial derivative with respect to y of whatever the operator is acting on. So these are the usual operators. We're just combining them in a new way, in 3 dimensions. Now, as far as answering the question of how angular momentum behaves, one of the interesting questions is it quantized, for instance? How should we describe it? The approach that we're going to take here is motivated by, for instance, when we were talking about the position operator, we considered the eigenstates of the position operator. Those were the Dirac delta functions. Those were useful. If you consider eigenfunctions of the momentum operator in 1 dimension, you get plane wave states, states with definite momentum. And of course, if we're considering eigenstates of the Hamiltonian, those are the stationary states. Whatever the operator, if we consider the states, the eigenstates of that operator, we get states with a definite value of the observable associated with that operator. This is especially interesting to do in the case of angular momentum. So, I said this was an operator algebra question. How can we analyze the algebraic structure of the angular momentum operators? Well, I said angular momentum operators there, and there are going to be 3 of them. I'm going to break it down into Lx, Ly, and Lz in Cartesian coordinates, because those are the coordinates that are most easy to work with. The way to think about these things in the operator algebra context is to think about commutators. And you'll see a very good example later on of why commutators are useful. But in this case, for instance, consider calculating the commutator of Lx and Ly. Now, I know what the definitions of Lx and Ly are in terms of their Cartesian coordinates, so I can expand that out. Y pz minus z py, z px minus x pz, that's what I get for Lx, Ly, and from that I'm going to subtract z px minus x pz and y pz minus z py. So this is Lx, Ly minus Ly, Lx, just by the definition of the commutator. If I expand out each of these terms, for instance, you'll get, if I expand the term from the product of these 2 terms in the expansion, I've got a y, I've got a z, I've got a pz, and I've got a px. All of these coordinates are, in some sense, different, except for pz and z. Back when we were talking about quantum mechanics in 3 dimensions, at the very beginning of this chapter, we talked about the commutators of, for instance, pz and z being the same sort of commutator as you calculated in 1 dimension between, say, x and px. Y and pz, however, commute, as do y and px, z and py, etc. If the momentum and the position operators that you're considering are not the same coordinate. For instance, if I'm not talking about x and px, y and py, z and pz, the operators commute. So when I calculate the product here, y pz times z px, I have to keep the relative order of pz and z constant, but I can move the px and the y around wherever I want. What you end up getting for that, then, is something like this. I'll start at the left. This is going to be a kind of long and annoying expression. Apologies in advance. We're going to get a y, px, pz, z. So y, and I have to keep the pz and the z in order, and I'll put the px on the right, for instance. Actually, you know what? I'll save a simplification step here. I'm going to move the px to the left because I can do that. Px commutes with pz and z, and just write pz, z. And I'll put parentheses around them to signify that I have to keep them together in that order. The next term I get, multiplying across here, I have a y, I have a pz, I have an x, and I have a pz. So I have a pz and a pz, and pz, of course, commutes with itself. It doesn't even matter the order that I write pz and itself. So for this term, I'm going to get something like minus y, x, and I'll write pz, pz, just writing it down twice. If I keep expanding out these terms, minus z, py, px. It's hard to read my notes here, since my handwriting on my notes is even messier than my handwriting on the screen. X, py, z, pz, in parentheses again, from the contribution of this term. Comes in with the plus sign because we have two minuses. The z and the x commute as needed, as does the py and the pz, but I have to keep the z and the pz in order, so I've got z, pz, x and py being pulled out front. That's for the top two terms here. For the bottom two terms, everything is going to have a relative minus sign. So I'm going to get a minus and y, px, z, pz, plus z, py, px, plus x, y, pz, pz, minus x, py, and then pz, z. So these are all my operators that I get as a result of expanding this out, provided I've copied everything down correctly from my notes. Now, if I've done things right here, you notice I have a z, py, px here, and a minus z, py, px here. So these two terms cancel out. I have a x, y, pz, pz here, and a y, x, pz, pz here. But x and y commute, so these two terms are actually the same as well, and they also cancel out. Another thing to notice here is here I have y, px on the left. These two terms both have y, px on the left. And on the right, I have things that don't commute, pz, z, and z, pz. So this term here, I'll write it in black, I can combine these together. I'm going to have a y, px, and then a pzz minus z, pz. And you know what that is? That's the commutator of pz and z, the operators. I can make the same sort of simplification over here. I have an xpy on the left, and I have a commutator of pz and z over here on the right, plus xpy, z, pz commutator, coming from these two terms. Now you know what the commutator of pz and z is. The commutator of z and pz is ih bar. This is the reason we like commutators. Commutator-like expressions often appear in expressions like this and allow us to simplify things, in this case just down to a constant. So this guy is going to be ih bar, and this, which is the same commutator only with the order reversed, is going to be minus ih bar. You can easily verify for yourself that swapping the order of the arguments in a commutator gives you minus the original commutator. So what I'm going to get now, at the end of all this, is y, where'd it go? I have a minus ih bar and I have an ih bar here, so I'm going to factor that out, and I'm going to have a y px and an x py, which should start looking familiar. Y px and x py appears in LZ. So this overall expression is just going to be I h bar LZ. So we started out calculating the commutator of Lx and Ly, and we got I bar Lz. You can write down expressions for all of the commutators in this way. The commutator of Lx and Ly is I bar Lz. The commutator of Ly and Lz is I bar Lx. And the commutator of Lz and Lx is I bar Ly. Likewise, if you swap the orders, you get minus signs. These are the commutators that are going to be useful to us in considering the algebra of angular momentum. If you feel the need to memorize formulas like this, note that the order these expressions always come in is always sort of cyclic, always sort of alphabetical. X to y to z and back to x. Here I have x, y, z. Here I have y, z, x. Here I have z, x, y. Always going around in this sort of clockwise order. You see a lot of sort of cyclic or anti-cyclic sort of permutation type arguments associated with commutators like this. And this is the first time that this sort of thing has shown up. So one thing you notice right away is that Lx, L, and Ly don't commute. We didn't get 0 for the right-hand side here. What that means is that if you want to determine simultaneously Lx and Ly, you have to consider the uncertainty relation between Lx and Ly. If I want to simultaneously determine Lx and Ly, the generalized uncertainty principle from the last chapter tells me that the product of the uncertainties in Lx and Ly is going to be given by the commutator of Lx and Ly. And if you go back to the previous page and figure out what that expression actually looks like, you get h bar squared over 4 times the expected value of Lz squared. So if I have some angular momentum in the z direction, I cannot simultaneously determine Lx and Ly. What that means is that if I'm considering angular momentum, I shouldn't be thinking about the angular momentum in the x direction or the angular momentum in the y direction. They're not very convenient observables to work with. What is actually a convenient observable to work with is L squared, which is defined to be the sum Lx squared plus Ly squared plus Lz squared. Essentially, the squared magnitude of the angular momentum, if you wanted to think about this in the classical context. This is sort of like saying r squared is the total length of a vector. So the question then is, how does this L squared work? One thing you can do with this, L squared, since we're calculating commutators, is ask what's the commutator of L squared with, for example, Lz. Can I simultaneously determine one of my angular momentum direction coefficients with this total angular momentum squared sort of operator? What is this commutator equal to? Well, this L is going to be Lx squared plus Ly squared plus Lz squared, and we can separate out those commutators. Lx squared commutator with Lz plus commutator Ly squared commutator with Lz. And the third term is commutator of Lz squared with Lz. Now the commutator of Lz squared with Lz is just going to be 0. This term drops out. This is going to be Lz, Lz, Lz minus Lz, Lz, Lz. These two commutators we have to treat in a little more detail. So let's expand them out. This is going to be Lx, Lx, Lz minus Lz, Lx, Lx. And this is going to be Ly, Ly, Lz minus Lz, Ly, Ly. You can simplify this expression by adding and subtracting the sort of missing terms, if you think about this. Here I have two x's on the end and Lz. What about Lz in the middle? So let's add and subtract Lz in the middle here. I'll write this as minus Lx, Lz, Lx, plus Lx, Lz, Lx. So I haven't actually changed this expression any, I've just added and subtracted the same quantity. In the operator case, the addition and subtraction gets a little bit more difficult to understand, but this is essentially an identity. And I can do the same sort of thing here. I'll write minus Ly, Lz, Ly plus Ly Lz Ly. Now this we can actually work with. If you notice, here I have an Lx on the left, and then an Lx Lz minus Lz Lx. So if I was treating these two terms just by themselves, I could factor out an Lz on the left, and I would be left with a commutator of Lx and Lz. That would end up looking like this. So this is still an equality. Lx on the left, and then Lx commutator with Lz accounts for this term. This term is accounted for in much the same way, except I have to factor an Lx out to the right. So this is going to give me an Lx Lz commutator with an Lx on the right. I can make the same sort of simplifications over here for exactly the same reasons, and I end up with pulling the Ly out to the left, Ly commutator with Lz, and pulling the Ly off to the right, Ly commutator with Lz, Ly on the right. So, still equal to my original expression. I haven't really made very much progress, but I know what the commutators of Lx and Lz are, or Ly and Lz. Those were the commutators I calculated on the last page. So this does actually simplify things out. The commutator of Lx and Lz is minus IH bar Ly. So this whole thing is going to be Lx. I'll stop writing it in square brackets because it's not a commutator anymore. Minus IH bar Ly. What I get for this commutator is the same. It's going to be minus IH bar Ly Lx plus, over here I've got Ly on the left, and these commutators are in alphabetical order, so I'm just getting positive IH bar plus IH bar Ly. Now, oops, I forgot where to go. I forgot my operator. The commutator of Ly and Lz is not just IH bar, it's IH bar Lx plus IH bar Lx Ly. Now, if you notice here, here I have an Lx followed by an Ly. I have to keep these in the right order because they don't commute, but I have a minus IH bar Lx Ly. I can bring the minus IH bar out front. Here, I have an IH bar Lx Ly. So, minus IH bar Lx Ly plus IH bar Lx Ly. These two terms cancel out. These two terms, here I have an Ly Lx, here I have an Ly Lx. Here I have a minus IH bar, here I have a plus IH bar. These two terms commute, or cancel out as well. So essentially what we're left with here, since everything is canceled, is 0, which means that L squared does commute with Lz. L squared commutator with Lz is equal to 0. This is the result that we'd hoped for. It means that we don't have a generalized uncertainty relation between Lz and L squared, which means I can simultaneously determine both L squared and Lz. That means I can hope to find eigenstates states that are both eigenstates of L squared and Lz. And that's really what we want. When we're done with this, we want something that's easy to work with, and eigenstates are especially easy to work with. So, we've worked out the general algebraic properties of angular momentum operators. And we've settled on working with this combination L squared and Lz. Those are operators that we can hope to work with. And what we're hoping to find are eigenstates, things that we can, most easily work with. So, how are we going to proceed? The way we're going to proceed is ladder operators. This is the same approach that we took back when we were doing the one-dimensional quantum harmonic oscillator. It was difficult to explain then, and it's difficult to explain now. Fundamentally, if we're working with L squared and Lz as our operators of interest, consider this just a definition. L plus or minus is equal to L sub x plus or minus I L sub y. These should look a little bit familiar, and we're in the end going to make the same sort of cleverness arguments that we made back when we were doing the quantum harmonic oscillator. But for now, let's just consider the properties of these L plus or minuses. We're doing algebra with operators, and we were calculating commutators. So let me ask you the question, what is Lz commutator with L plus or minus? Well, you can substitute in the definitions of Lz, L plus, and L minus. And since the commutator is linear, I can just split this up into two separate commutators. Lz commutator with Lx, plus or minus I times Lz commutator with Ly. You know what both of these commutators are. We've already calculated them out. You get I h bar Ly plus or minus I times z and y here now are in the wrong order, so I'm actually going to get a minus I h bar Lx in this case. So this is our commutator, and if you simplify that down, you'll find that this is actually equal to plus or minus h bar L plus or minus. So calculating the commutator of Lz with L plus or minus gave me something relatively simple. It just gave me L plus or minus back. If I ask you the question, what is the commutator of L squared with L plus or minus? Again, you can expand out the definition of L plus or minus, L squared Lx plus or minus I times the commutator of L squared and Ly. But you know L squared commutes with Lx and L squared commutes with Ly. These are essentially the same as it commuted with Lz. So without even calculating anything here, we know the answer is 0. So this is the algebraic structure of these ladder operators. The key fact that I mentioned earlier is that what we're looking for are eigenstates of both of these operators simultaneously. Simultaneous eigenstates like that. Essentially, the question that we need to ask, then that we can use these ladder operators to answer, is if we have some state, and I'm just calling it f here, if L squared f is going to be given is an eigenvalue, if f is an eigenstate of L squared, it would have an eigenvalue lambda, for instance, and f is a simultaneous eigenstate of Lz, it would have an eigenvalue, for instance, mu. What about L plus or minus acting on f? Now the terminology here should be suggestive. I call these things ladder operators. Let's see what that actually gets us. First of all, consider L squared acting on this, L plus or minus f, acting on f. Well, you know that L plus or minus commutes with L squared. So I can write this as L plus or minus times L squared acting on f without changing anything. But L squared acting on f, I know what that is. It's just an eigenvalue multiplied by f. So this is L plus or minus times acting on lambda f. Lambda just being a constant can be pulled out front. So I've got lambda and then L plus or minus f. What this tells you is that L plus or minus f, if f is an eigenvalue, f is an eigenstate of L squared, L plus or minus f is also an eigenstate of L squared with the same eigenvalue. I can ask the same question of Lz. What does Lz do to this mysterious quantity L plus or minus acting on f? This is a little bit more complicated, and I can simplify it by rewriting it slightly. Let's say this is Lz, L plus or minus. Now I'll write this as minus L plus or minus Lz plus L plus or minus Lz. I've just added and subtracted the quantity, and you can see what I'm trying to do now. I'm trying to arrange things such that I get commutators, as well as things that I know, because this is all acting on f, and I know what Lz does to f. It just gives me an eigenvalue. So this is now going to be the commutator of Lz and L plus or minus acting on f, plus L plus or minus Lz acting on f. And I know what Lz does under these circumstances, since f is hypothetically an eigenstate of the Lz operator. It's just going to give me mu f back. This commutator, I also know how this behaves. This is Lz. In the last lecture, we were able to, purely by examination of the structure of the angular momentum operators, derive the quantization properties of angular momentum in quantum mechanics. We were able to examine the commutators, manipulate the operators, and essentially derive the eigenvalues associated with the operators L squared and L sub z. That's nice, and it's very useful. The eigenstates associated with Hermitian operators in the Hilbert space have nice properties, but we don't actually know what those eigenstates look like. In order to get something easier to visualize, let's consider what the eigenfunctions are. trying to express the angular momentum operators as partial differential equations that we can solve with the techniques that we've been applying earlier in this chapter. The angular momentum operators that we were working with in the last lecture are expressed in Cartesian coordinates. This was very nice because the Cartesian form has this nice symmetry to it and we could calculate commutators easily. Just by manipulating these, we were able to derive expressions like the eigenfunctions of L squared had this sort of form. H bar squared L plus 1 was our eigenvalue. Likewise, for L sub z, we ended up with eigenvalues of the form m times some constant h bar. The L's that we got had to be half integers, either 0 or 1/2 or 1 or 3/2, etc. And the constants m that we got here had to be between minus L and L, going up in steps of 1. So our eigenvalue structure here, as I mentioned, doesn't tell us anything about the actual form of f. When we were working with the one-dimensional quantum harmonic oscillator, we were able to derive, for instance, the ground state by knowing that the lowering operator acting on the ground state gave us 0. That was a differential equation that we could work with since we knew differential forms for the lowering operator. We can do the same thing with the angular momentum operators, but in this case, it's more worthwhile to think more generally. So suppose we just have some general psi of r, theta, and phi. This is our wave function expressed in general polar coordinates, and it would be nice to know how our angular momentum operators act on this general wave function. If we can express our angular momentum operators in spherical coordinates, we can write down this sort of eigenvalue equation. It will then be a partial differential equation that we can solve, in general, for any value of L or M. Unfortunately, in this lecture, we run into some thorny notational issues. I like to use hats to designate operators. Griffiths, your textbook author, likes to leave the hats off when it's not ambiguous. This is one of those cases where it is ambiguous and I would like to use the hats, but unfortunately hats are also significant in other ways. In particular, hats in this section of the textbook mean unit vectors. So I'm going to try and follow Griffith's notation, and I'm going to try and point out where things are operators and where things are unit vectors. But in this case, in this lecture, if I write something like Lx, I mean the operator. And if I write something like r hat, I mean the unit vector. Like I said, I'll try and be clear about what I mean in each case. At any rate, our goal here is to come up with spherical coordinates expressions for the operators that we were working with when we were considering angular momentum operator algebra, L squared and L sub z. So first of all, let's consider just L in spherical coordinates. There's going to be a lot of math in this lecture, and I'm going to go through it only conceptually. The level of grunge in this sort of coordinate transformation is above and beyond what I would expect you to be able to do for an exam. So, most important, I need you to understand the overall structure, the sorts of manipulations that are being done. Change of variables in the context of partial differential equations is tricky, so let's try and just understand overall how it works. First of all, what we're working with is angular momentum, L, which is given by r cross p. Now, I've left both vector hats and operator hats off of these, but this is the angular momentum operator, this is the position operator in spherical coordinates, and this is the momentum operator in spherical coordinates. The momentum operator in spherical coordinates is rather straightforward to write down. We can write it as minus I h bar times this gradient operator, del, which you know as, I'll write it in Cartesian coordinates, x hat times the partial derivative of x plus y hat times the partial derivative with respect to y plus z hat times the partial derivative with respect to z. You can apply this to an arbitrary function of x, y, and z, a scalar function, and it will give you a vector. So this is a vector, as is the momentum, so this is a sort of momentum vector operator. This gradient can be expressed in spherical coordinates as well, and expressed in spherical coordinates it has this partial derivative with respect to r, partial derivative with respect to theta, and with respect to phi. The partial derivatives with respect to theta and phi have to be rescaled, since, for instance, if you consider it in Cartesian coordinates, this is essentially a spatial rate of change. It's a vector that points in the direction that the function changes most quickly with respect to physical space. And a change with respect to theta is not a change with respect to physical space. R d theta is a motion in space, whereas r sine theta d phi is a motion in space. So these are our motions in space, and the rescaling necessary is taken care of by this 1 over r and this 1 over sine theta. This gradient gives us the momentum, which we can cross with the radius operator, the position operator in spherical coordinates, which is quite simply r hat. So this hat now designates a unit vector, and this designates a coordinate. And as usual, our position operator is multiplication by the coordinate in question of, well, the multiplication of this with whatever the operator is acting on, some function in this case. So our angular momentum then is going to be a cross product of something like, I don't know why I erased it, r hat. So I'm going to be taking the cross product of r hat, that's the vector part of my position operator, with this part of my momentum operator. I can pull my minus I h bar out, and this is what you end up with, simply taking cross products r cross theta, and r cross phi. Where here I had a 1 over r in my gradient, but it's been cancelled out by the r coordinate multiplication in my position operator. Likewise for phi. There was a 1 over r here as well. This can be simplified slightly. You know that r cross r is going to be 0. The cross product of any vector with itself is going to be 0, since the cross product depends on the angle between the vectors. They have to be pointing in different directions. R cross theta is going to give me phi hat, a unit vector pointing in the phi hat direction. And r cross phi is going to give me minus theta hat, a unit vector pointing in the minus theta direction. You can, therefore, you're only going to end up with 2 terms, and that will be our angular momentum operator. Since, however, what we were actually doing when we were working with L squared and Lz, we needed expressions, for instance, for things like L plus or minus. This L plus or minus was expressed in terms of Lx and Ly, so what we actually need to do is take the overall angular momentum operator in spherical coordinates and use it to find angular momentum operators in Cartesian coordinates expressed in spherical coordinates. Now this is a very strange way of saying things, but essentially what I want is the angular momentum about the x-axis, the x component of the angular momentum, but expressed still in spherical coordinates. The way to do that, and the way Griffiths uses at least, is to take this expression for the angular momentum operator, which has phi hat and theta hat in it, and express the phi hat and the theta hat in Cartesian coordinates. Those Cartesian coordinates values of theta hat and phi hat will depend on theta and phi, so we end up with this weird hybrid Cartesian spherical coordinate system. But doing so allows you to identify the x component of the angular momentum, y component, and z component. If you actually do that, substitute in phi hat in Cartesian coordinates, for instance. Phi hat in Cartesian coordinates, this weird Cartesian spherical coordinate system, is minus sine phi I hat plus cosine of theta j hat, where I hat and j hat now are Cartesian coordinate unit vectors. This would normally be written as x hat in a normal physics class, but of course we know x hat as the x component position operator, and we can't reuse that notation. You can see why I'm sort of glossing over the details of this. Actually doing it all out would require a fair number of slides and a good deal of your time. At any rate, substituting in this expression, for instance, for phi hat, and a similar expression for theta hat, you can identify the I hat component of L, the x component of the angular momentum. And when you do that, this is what you're left with. So the x component of the angular momentum has derivatives with respect to both theta and phi. Likewise for L sub y, the y component of the angular momentum. L sub z, however, only has derivatives with respect to phi, and this should make a fair amount of sense since z is special in spherical coordinates. Phi is the angle that rotates around the z-axis. So that's all well and good. We're starting to work our way towards expressions of the operators that we're actually interested in, L squared and L sub z. We have one for L sub z, but what about L squared? L squared, it turns out, is easy to express if you think about it in terms of the L plus or minus operators. This was the trick that we used back when we were doing operator algebra. L plus or minus, of course, is expressed in terms of Lx and Ly. But we have Lx and Ly now, so we're ready to go. L plus or minus being expressed in terms of Lx and Ly. Going back to your notes from the lecture on the algebraic structure of the angular momentum operators, we can express L squared rather simply in terms of L plus and L minus. L plus and L minus being expressed in terms of Lx and Ly, we can make combinations of Lx and Ly. Multiplying those out is simply an exercise in calculus, multivariable calculus, taking partial derivatives, applying chain rules, etc. When you do all of that, evaluating this expression that we got from the algebraic structure of L squared in terms of L plus, L minus, and Lz squared and Lz, you can go and look that up in your notes, you end up with an expression for L squared. This should start looking reasonably familiar. What I really want to do here is write this into an eigenvalue problem by adding some arbitrary function f. This whole operator, acting on some function f, is going to be equal to, we know what the answer is from our consideration of operator algebra. It's going to be h bar squared L plus 1 times f. It's going to give us our original function back. So this right here, this is our partial differential equation that we can solve for f, where f now is a function of r, theta, and phi, and is going to essentially give us our wave function. We only have angular components here, so there isn't going to be any radial part. That should make a good amount of sense. Radial motion doesn't contribute any angular momentum. We can do something very similar for L sub z. L sub z acting on some arbitrary function, and L sub z we already had an expression for. It was minus I h bar partial derivative with respect to phi of f. We know what that's going to give us already as well, because we know the eigenvalue structure of L sub z as well. It's going to give you m times h bar f. Both of these are going to be then partial differential equations that we can solve. This tells us something about the eigenstates of L sub z. This tells you something about the eigenstates of L squared. And if you look at these equations, they should be familiar. These are the angular equations that we had earlier. These essentially gave us the YLM of theta and phi as their solution. So what we've shown here is that the eigenfunctions associated with the L squared and L sub z operators are exactly the spherical harmonics. The spherical harmonics were what we got from a spherically symmetric potential expressing the time-independent Schrodinger equation in spherical coordinates. And this should make a certain amount of sense, since what we're talking about now is angular momentum, and L squared, for instance, angular momentum squared, has to do with the rotational kinetic energy. So it ought to play some role in the time-independent Schrodinger equation, which tells us the energy of the stationary states. So if we have an eigenvalue of L squared, simultaneous eigenstates of L squared and Lz are exactly the spherical harmonics. There is a slight difference here, and it comes down to the value of L. Essentially, we have two classes of solutions here. We have half-integer L and integer L. Our consideration of spherical harmonics gave us only integer L, whereas, our consideration of wave functions, the solutions to these partial differential equations, give us spherical harmonics, which are only meaningful for integer L, integer L. Half-integer L doesn't really make any sense in the context of spherical harmonics, which means if what we're talking about is angular momentum of something like a physical particle, orbital angular momentum, rotational kinetic energy, essentially, we can't have half-integer L. But we do have these half-integer L solutions. If I'm talking about wave functions, I have to have YLMs for my solution. That means I have to have L being 0, 1, 2, etc., and M being, minus L up to L. If what I'm just talking about, though, is the algebra of things, then I don't really know what the solutions look like. But I can have L is 0, or half, or 1, or 3/2. This is interesting. My M values are going to behave the same way, minus L, going up to L. But these half-integer values of L they're rather strange. They're going to behave in ways that are utterly unfamiliar if what you're used to thinking about are things that actually live in ordinary three-dimensional space. But these do actually happen to have physical reality, and it has to do not so much with orbital angular momentum, the motion of a particle around in an orbit, for instance, as they do with spin angular momentum, or at least that's the name quantum mechanists, I think? I don't think I should say quantum mechanic. Quantum mechanists say is associated with these half-integer values. They have physical meaning in the context of spin angular momentum. As an example of how these angular momentum structures can be useful, consider the rigid rotator. What I mean by that is, suppose I have two masses, both equal to mass m, separated by some distance a. And I put them on a rod of length a, and I spin them around. This is a, system that can in principle be treated with quantum mechanics. The only energy associated with this system is going to come from rotational kinetic energy, since the thing is not allowed to translate. I'm fixing it to rotate about the center here. So my Hamiltonian operator is going to essentially be the rotational kinetic energy, which is going to be L squared over 2 times the moment of inertia. This is the rotational analog of p squared over 2m. I have angular momentum squared divided by twice the moment of inertia, the rotational equivalent of the mass. Now, I suppose I should either erase the hat for my Hamiltonian operator or add a hat to my angular momentum operator. I said in this lecture I wasn't going to use hats to designate operators, so I'll erase it from the Hamiltonian. At any rate, you know how L squared behaves. The moment of inertia here, I, is going to be 2, since I have two masses, times mr squared, essentially, so the mass times the radius squared, which is going to be a over 2 squared. So this is going to be ma squared over 2 for my moment of inertia. The time-independent Schrodinger equation then becomes h times my wave function is e times my wave function. That's my original. When I substitute in the specific definition of the Hamiltonian here, I have L squared, my squared angular momentum operator, divided by twice my moment of inertia, which is just ma squared. I have an over 2 here, and I have a 2 here, and they cancel each other out. If this is going to be equal to L squared acting on psi is going to be equal to E times psi, ma squared here is a constant, I can rearrange this and write L squared psi is equal to ma squared E times psi. This now, this ma squared E, this is my eigenvalue of an eigenvalue problem with L squared in it. I know what those eigenvalues are. This is h bar squared L plus 1. That's my eigenvalue, the form of my eigenvalues of the L squared operator. So what that tells me is that ma squared E is equal to h bar squared L plus 1. And I can solve this for E easily. It tells me that E is equal to, an equal sign somewhere, h bar squared L plus 1 divided by ma squared. These are the allowed energies, the energies of the stationary states, for the rigid rotator. You can just as easily go through the same sorts of arguments and write down normalized wave functions for the rigid rotator. But essentially this is a very common structure that you're going to encounter in quantum mechanics. Angular momentum is, of course, a conserved quantity in classical physics, and it's a conserved quantity in quantum mechanics as well, which means it's interesting in a lot of respects. And the quantum mechanical structures you get, either if you're looking at something like a rigid rotator now, since we could actually write a real-world wave function for this, we're stuck with just spherical harmonics for the wave functions, integer values for L, and you're going to encounter this sort of expression a lot in quantum mechanics, especially if you go on to the upper levels. Think about for a moment what we've accomplished. Solely by messing with operators and solving partial differential equations as motivated by this original hypothesis of the time-dependent Schrodinger equation, we were able to determine conserved angular momentum structures. We're even able to predict that there's going to be something strange happening for half-integer values of L in these eigenvalue equations, and that's going to be the topic of the next section in the textbook, spin. The half-integers have a lot of strange properties associated with them. So that's where we are, and that's where we're going. The machinery of quantum mechanics is obviously very productive, and we're going to keep working our way through the results of it for the next couple of lectures.
We've spent the last couple of lectures talking about angular momentum. From the quantum mechanics perspective, we ended up talking about a total angular momentum operator L squared and a z component of angular momentum operator L sub z. These two operators gave us a certain algebraic structure, and we ended up with quantum numbers L and m. The allowed values of L were either integers or half integers. L could be 0, a half, 1, 3 halves, etc., going up to infinity in steps of a half, whereas m could only be in between minus L and L in steps of 1. These quantum numbers were interesting for a couple of perspectives. If we considered the motion of a particle, for instance, the electron orbiting the nucleus in the hydrogen atom, we only got integer values of L, 0, 1, 2, 3, etc. Whereas the algebraic structure of these operators allows for L equals a half or 3 halves, etc., going up in steps of a half. These half integer values are essentially valid solutions. And that brings us to the topic of spin in quantum mechanics. Essentially, these half integer values of L are perfectly valid physical solutions, and they have meaning. They're actually what we use to describe an intrinsic property of fundamental particles like electrons called their spin. Spin is essentially a property of the universe. That's just the way things are. I don't have a good answer for why does an electron have spin, but I can describe the spin of the electron, and I can describe it using the same language as we used when we were discussing angular momentum. So, angular momentum, we were working with equations like L squared F, and the eigenvalues we got for that were h bar squared L, L plus 1. Likewise, L sub z applied to F gave us eigenvalues of the form m h bar. Examining the algebraic structure of this gave us allowed values for the L quantum number of 0, or a half, or 1, or 3 halves, etc. These integer and half integer values had different interpretations. If I look at just the integer values, those describe orbital angular momentum, the angular momentum of a particle as it moves in a circle around a focus, for instance, around a center. So now we're talking about particle motion. And we can write a wave function, psi, of, say, x, y, and z, or perhaps more accurately, r, theta, and phi, that has this property of orbital angular momentum. You know what the answers for this are already. We've discussed it in previous lectures. The wave functions with specific values of L squared and L sub z, the eigenfunctions of the L squared and L sub z operators, are the spherical harmonics. We're also allowed to have spin, angular momentum, with integer values, but spin is really more interesting when we're talking about the half integers, 1 half, 3 halves, 5 halves, etc. I keep writing 3/3. I wonder why. Here, these half integer cases don't have any nice wave function that we can express. So we're really only talking about spin under these circumstances. So, what exactly is this spin thing? I can't give you a good argument or a good answer for this, other than saying this is essentially just a property of the universe. The name spin, at least, I can explain, and the name comes from a classical analogy. Suppose we have a positively charged nucleus and a negatively charged electron orbiting that nucleus. We are going to have orbital angular momentum associated with the motion of that electron, but there's also the possibility that the electron itself would be rotating. Spin.
We've built up, over the past few chapters, a fairly complete understanding of how single particles behave in quantum mechanics. We can describe them with wave functions, like psi of x, y, z, functions of position, which we can use to calculate expected values of, for instance, of what the x-coordinate will be. We know how to calculate the allowed set of energies for bound states, for instance, of the hydrogen atom, and we can predict the spectra. This is very nice and it's very useful, but it's of course not the end of the road for quantum mechanics. The next step that we're going to make is to talk about multiple particle systems, to start building things that are more complicated than a single particle in a single potential. The first step, then, is to expand on our formalism of wave functions to two-particle systems. If we're working with a one-particle wave function, psi, of x, y, and z, if we're working with two particles, we no longer have the position of just one particle, x, y, and z. We're working with two particles, so the wave function psi is going to be a function of 6 variables, x1, y1, z1, and x2, y2, and z2. This means if we construct, for instance, a probability density for finding the particle at a particular position, we're not finding the particle. There are two particles. There are two positions. And what we get is a joint probability distribution for the position of both particles. So this is if we're talking about two particles, and you can easily imagine what would happen if we had more particles. You would have simply more arguments. This is part of what makes quantum mechanics so difficult to compute with, since effectively representing functions of many variables in the computer is a very difficult proposition. If our wave functions are functions of multiple variables, you might expect that our Hamiltonians would get more complicated as well, and they do. The Hamiltonian operator, which we had before, was simply, in the single particle case, was a momentum operator and a potential operator. Now you'll have to deal with the momentum of each particle separately. So, for instance, the Hamiltonian for a particle might look like minus h bar squared over 2m times, and I'll write this as gradient squared with a subscript 1, minus h bar squared over 2m gradient squared with a subscript 2, where the gradient with a subscript 1 refers to partial derivatives with respect to x1, y1, and z1, and the subscript 2 refers to partial derivatives with respect to x2, y2, and z2. Essentially, this is the momentum of particle 1 in operator formalism with wave functions, and this is the momentum of particle 2. The potential energy now, of course, will also have to be a function of the positions of both of these particles, so we'll have to add on a potential term which is a function of both r1 vector and r2 vector. There are some simplifications that you can make. If the potential is only a function of the separation of the particles, for instance, you can do the same sort of thing as you can do in the case of the two-body problem in classical physics. Namely, instead of working with two independent bodies, work with the center of mass and the essentially angular orientation of the bodies about the center of mass. But that's a story for another day. The Hamiltonian we get here is now a partial differential equation in multiple variables, many more variables than we were working with originally. So it's much harder to work with. Our wave functions, of course, still have to be normalized, since we still have to represent, probability densities with them. But the normalizations we're going to work with are a little different. In particular, while the probability density that we're working with is still going to be psi star psi, we're going to have to integrate it over many, many dimensions. 6 dimensions in this case if I'm working with two particles in 3 dimensions, dx1, dy1, dz1, dx2, dy2, dz2. So if you're trying to normalize a wave function for two particles in 3 dimensions in Cartesian coordinates, you've got a lot of integrating to do. The time-independent Schrodinger equation is going to look very similar. Essentially, h psi equals e psi, same as before, where the Hamiltonian now as an operator h hat. The solutions you get to the time-independent Schrodinger equation are still going to behave the same way they behaved before, and this is the very comforting thing. When we derive the time-independent Schrodinger equation from the time-dependent Schrodinger equation, we still get the same sort of behavior. Our wave function now is a function of the positions of two particles, if I represent them as vectors r1 and r2, as the spatial part, the solution to the time-independent Schrodinger equation, and the time dependence looks very much the same, minus I e t over h bar, the same sort of expression as we got before. So adding multiple particles adds a great deal of complexity to the spatial part of the wave function, but if we have a stationary state, the temporal evolution is as simple as it was before. The subtle point of multiple particle wave functions comes from whether the particles are distinguishable or indistinguishable. Consider combining two one-dimensional systems. So the position of particle 1 is represented by x1, position of particle 2 represented by x2. So we have two particles in a one-dimensional system essentially, and the positions of those particles are independent.
This looks a lot like two independent variables. So you can think about this as, in 2 dimensions, an x1 axis and an x2 axis. If I measure the positions of these particles at the same time, I illuminate the system with high energy radiation and look for where the radiation has scattered off of the positions of the particles. I can represent the outcome of a measurement by a point in this 2-dimensional space. Suppose this point is 1, 0.3. I might also measure the particles to be here. Another possible outcome for this measurement is 0.3, 1. What I mean by whether the particles are indistinguishable or distinguishable is whether these two outcomes, 0.31 or 1, 0.3, are actually distinct. If I was measuring this in a 2-dimensional space, these points would, of course, be very distinct. But I don't actually have a 2-dimensional space. I have a 1-dimensional space with 2 particles in it. So if I measure, say, this outcome in 1-dimensional space, I'm measuring one particle at point 0.3 and another particle at position 1. So my wave function then essentially has a particle there and a particle there. If I measure this other outcome, 1, 0.3, one of my particles is at position 1, one of my particles is at position 0.3, so my wave function essentially looks like that. These guys are essentially the same. What does that mean? Well, if this is particle A and this is particle B, and this is particle A and this is particle B, then these two outcomes are different. But that requires the particles themselves to be distinguishable, and if the particles are not distinguishable, if this is an electron and this is an electron, there is no difference in principle between the electrons in these two peaks, then, well, electron-electron and electron-electron are actually the same outcome. And whether or not you count these as different is, well, one of the nuances of quantum mechanics. The essential fact that you have to keep in mind is that in quantum mechanics, the particles that we're working with, electrons, protons, photons, whatever they may be, are in principle indistinguishable. The wave function, quantum mechanics tells us, is all we can in principle know about these particles. So you can't paint one of them red or put a little piece of tape on it or do whatever you might do with other objects in order to keep track of whether or not they've exchanged places, for example. Particles are indistinguishable. Indistinguishable is a painfully long word, but essentially what this means is that we can't tell which particle is which. So let's consider what effect this has on quantum mechanics. If you had particles that were distinguishable, particle 1, its position being represented by the coordinate x1, could be in some wave function, in some state, psi sub a. And this would be quantum mechanically a complete description, all of the information necessary about particle 1. Likewise for particle 2, indexed by coordinate x2, in state psi sub b. The combined wave function for the overall state, then, is going to be psi as a function of x1 and x2. And we can write that down if particle 1 is in state psi a and particle 2 is in state psi b as simply the product psi a of x1 times psi b of x2. This gives us the sort of expression that you would expect to get for distinguishable particles. Namely, for instance, if I want to calculate the expected value of x1 for a particle in this state, this is the expected position of particle 1. My combined wave function here, calculating the expected value in this combined wave function, will require two integrals, one dx1 and one integral dx2. Both integrals are going to go from minus infinity to infinity. And the integrand, as before, is going to be psi star psi. If I expand that out, psi a star of x1, psi b star of x2, x1, and psi a x1, psi b of x2. This is the integrand you would get. Psi star and psi combined together with a multiplication means that's our probability density for position, and this is then, of course, the expected value of position formula that we're familiar with from single particle quantum mechanics. Looking at what's a function of what here, we can simplify things a little bit. I have functions of x1, and I have functions of x2. If I pull the terms that are not functions of x2 out of the x2 integral, essentially moving them over here, what I end up with is two integrals that you probably recognize. Integral from minus infinity to infinity dx1 of psi sub a star of x1, x1, psi sub a of x1. For my first integral, and the integral from minus infinity to infinity of, with respect to x2, of psi b star of x2 psi b of x2. So these integrals essentially separate out, and this is a normalization integral for psi sub b. If psi sub b is normalized, this is going to go to 1. And this expression on the left, the integral with respect to x1, is the single particle expectation value of the position x1 for a particle in the state A. So essentially, if I have distinguishable particles, my result looks pretty much as expected. These particles are clearly distinguishable because if the expected value of the position of the particle were different for state B as for state A, well, I got the expected value for state A, not some combination involving the expected value for state B. So these particles are clearly distinguishable, and there's nothing in principle wrong with writing wave functions like this, except for the fact that the fundamental particles we're working with are not distinguishable. So we have to somehow encode the indistinguishability of particles into our formulation of quantum mechanics. So how do we write a wave function for indistinguishable particles? The key fact is what happens if we exchange the particles. The wave function for particle 1, particle 2 versus the wave function for particle 2, particle 1. Exchanging the positions at which we evaluate coordinates is essentially, if you think back to that plot I was making earlier of x1 and x2, it's implying a degree of symmetry between this point and this point. That my wave function must be equal here and here, essentially being equal somehow across the axis. This sort of line here where x1 equals x2. That degree of symmetry implies some constraints on allowable forms of the wave function. We don't need just that the wave function itself doesn't change if I exchange x1 and x2. What we need is for the observables not to change. And furthermore, we need the observables not to change at all if we swap the particles back to where they were originally. So if we want the exchange of particles to not matter, let's define an exchange operator, p hat. Now don't worry, we're not going to be working with p hat in the context of it as a mathematical operator, but it's a useful notation to use. What we need, in order for the wave function essentially to not change the observables, is for p hat acting on psi, x1, x2, which is more or less defined to be psi of x2, x1. We need that to be equal to plus or minus psi of x1, x2. You know the way to not change the observables in quantum mechanics is to multiply by a complex phase. And this plus or minus essentially takes care of that complex phase. You could imagine any arbitrary e to the I phi being multiplied by psi, and that would not change the observables. But the fact that applying the exchange operator twice gets us back where we started means that the phase that we multiply by has to be either 0 or pi, meaning we have to either go from plus psi to minus psi or from plus psi to plus psi. Either we don't change the wave function at all by exchanging operands, or we flip the sign of the wave function by exchanging the particles. This is sort of a law of physics. The indistinguishability of particles requires this to hold. If I exchange the order of the arguments of a two-particle wave function, I must get my original wave function back with a plus or a minus sign. This symmetrization or anti-symmetrization under exchanging the arguments, symmetry referring to the plus sign, anti-symmetry referring to the minus sign, has some remarkable consequences, which we'll talk about over the next couple of lectures. One way, however, to write down these wave functions, since that's what we're going to want to do in the end, is if I have the two single particle states that I was working with in the past slide, psi A, psi B. My wave function, psi of x1, x2, started off as psi sub A of x1, psi sub B of x2. This was the distinguishable particle wave function, and it turns out that if I combine this with a permutation of x1 and x2, for instance, psi A of x2 instead of psi A of x1, and then psi B of x1 instead of x2, if I combine these two pieces with either a plus sign or a minus sign,
I get something that obeys the requirement that the particles are indistinguishable from the perspective of quantum mechanics. If I'm going to properly normalize this, I'll need a normalization constant out front. And for instance, you can check this fairly easily. If I wanted to know what psi of x2, x1 was here, well, it's going to be this expression on the right, exchanging 2's for 1's and 1's for 2's. So it's going to give me a psi a of x2, psi b of x1, plus or minus psi a of x1, psi b of x2. If you compare the expression I get after exchanging these particles with the expression I got before exchanging these particles, you can see here's psi a x1, psi b x2, a1, b2, whereas here's a2, b1, a2, b1. So these expressions are essentially the same, except the plus or minus sign is going to mess things up a little bit. If I use the plus sign, clearly these two expressions are the same. a1, b2 plus a2, b1 versus a2, b1 plus a1, b2. All I've done is exchange the order of these two terms. Since this is just multiplication, we're working with wave functions, there's nothing fancy about the order of the terms over addition. Everything commutes, that's fine. If I use the minus sign, I have a1, b2 and minus a1, b2 in my exchanged version, whereas minus a2, b1 becomes plus a2, b1 in my exchanged version. So I flip the signs in my wave function if I use the minus sign when I calculate my exchanged form. So this trick for making indistinguishable particle wave functions from distinguishable particle wave functions actually always works. You need to combine all of the different permutations of all of your particles with appropriate plus or minus signs such that you obey this overall anti-symmetry under exchange or symmetry under exchange requirement. Whether or not we have symmetry or anti-symmetry under exchange is a really interesting topic. And it gets us down to a distinction that I've mentioned earlier on in the context of fermions and bosons. Essentially, indistinguishability has a couple of consequences. First of all, if I have the plus version, the symmetry under exchange, essentially psi of x2, x1 equals psi of x1, x2. My exchanged version is equal to my original version. This is the case for bosons. And bosons were the particles that we talked about earlier that had spin, integer spin, 0, 1, or 2, etc. If you make the other choice, say psi of x2, x1 is equal to minus psi of x1, x2, that's the case for fermions. And fermions, we said earlier, were particles with half integer spin. Spin 1 half, 3 halves, 5 halves, etc. on up to infinity. There's actually quite a lot that you can do with this. For instance, the symmetry and anti-symmetry properties of these wave functions have, well, it has observable effects, and the behavior of fermions and bosons is crucially different in a lot of ways that have very important consequences. For instance, earlier on we talked a little bit about superfluid helium in the context of the domain of quantum mechanics and whether that was important or not. Helium atoms are bosons with integer spin, and they have very different behavior than other liquid gases, for instance. If you wanted to determine the quantum mechanical behavior of very cold liquid hydrogen, for instance, it would behave differently. Hydrogen behaves differently from helium in that context. The indistinguishability of particles is something of an axiom in quantum mechanics. The exchange can't affect anything. In particular, it doesn't affect the Hamiltonian. Exchanging two particles should not affect the energy of the state if the particles are completely indistinguishable. Put another way, the exchange operator and the Hamiltonian operator commute. The commutator of p hat and h hat is 0. What that means is that we can always write wave functions in these forms. x2, x1 after exchange equal to plus or minus psi of x1, x2. We can do that and still be able to come up with stationary states. We can come up with a simultaneous set of eigenstates, a set of simultaneous eigenstates of both this exchange operator and the Hamiltonian. So it's always possible to write our wave functions like this. This is similar to the reasoning we applied earlier when we were talking about functions, or about the time-independent Schrodinger equation in one dimension with an even potential. You could always write the solution as either even or odd if the potential was even in one dimension. You can make a similar argument, or this is a very similar argument. There is a symmetry property that we can exploit when we're looking for solutions of multiple particle wave functions. So bosons and fermions and exchange, these are fundamental properties of nature, and the connection between the spin of the particle and the symmetry or anti-symmetry of the wave function overall is a really interesting topic that we'll discuss a little more later on. One application that you guys have hopefully heard about from your chemistry class is the Pauli exclusion principle. The Pauli exclusion principle holds for fermions, and for fermions we know that the exchange operator acting on the wave function psi gives you minus the wave function psi. So suppose the wave function that we were working with was writable in the form that we were talking about earlier. Psi of x1, x2 is equal to some normalization constant times psi a, x1, psi b, x2. Now we're using the minus sign since we're talking about fermions. We're talking about exchange antisymmetric spatial wave functions. Psi a, x2, psi b, x1 for our second term as before. The Pauli exclusion principle determines what happens if the two particles are in the same state. If the two particles are in the same state, psi a is equal to psi b. What that means is that I can rewrite this as psi a and rewrite this as psi a. You can tell what we're left with now. We've got psi a x1, psi a x2 minus psi a x2, psi a x1. We've got essentially something minus itself. So if the particles are in the same state, then psi of x1, x2 equals 0 with this particular fermion antisymmetry under exchange. This is interesting, and I suppose I shouldn't use an exclamation point here because 0 factorial is 1, and that wouldn't be all that interesting. But what this means is that this is not possible. First of all, the wave function psi equals 0 is a perfectly valid solution to the Schrodinger equation, but it doesn't tell you anything, so this is not useful. It does not describe a normalizable state. What this means, and what the Pauli exclusion principle says, is that two fermions cannot occupy the same state. I'm not quite sure how I spelled occupy there, but I don't think it was right. Two fermions cannot occupy the same quantum mechanical state, and that comes from the fact that fermions are required to obey antisymmetry under exchange. And of course, if you have two particles in the same state, exchanging things doesn't do anything. It's not going to change your wave function. So if it's not going to change your wave function, and yet it is going to change your wave function by giving it a minus sign, you've got a problem. Two fermions cannot occupy the same quantum mechanical state as a result. And this comes just from the nature of indistinguishable particles. The antisymmetric combination to render two otherwise distinguishable particles indistinguishable means that those two particles cannot occupy the same state. For bosons, though, we use the plus sign, so that's no problem. If we use a plus sign here, we end up with psi a x1, psi a x2 plus psi a x2, psi a x1. So just twice psi a x1, psi b x2. Or sorry, psi a x2. So that's a perfectly valid wave function. Bosons, if we use the plus sign, make the symmetric instead of antisymmetric combination to render the particles indistinguishable. Those particles can occupy the same state right off the bat. This ability to occupy
put multiple particles into the same quantum mechanical state is the difference between the bizarre behavior of liquid helium and the behavior of liquid hydrogen. As an example, consider back to the very beginning. The very first quantum mechanical system we worked with was a particle in a box. What happens if we put two particles in a box? Well, two particles in a box, if we're going to write wave functions as symmetric or antisymmetric combinations of our distinguishable single particle wave functions, is a little bit of a lie. Because if these particles are anything that we know of realistically, those particles will interact, and the interaction in the Hamiltonian will affect the potential. So we won't be working with a simple v of x equals 0 inside the box and infinity outside the box potential. We'll be working with something more complicated, and accounting for that interaction will mean that our stationary states are not simply the stationary states of single particles. But suppose, for instance, vigorously waving my hands, though you can't really see it in a video lecture, suppose those particles didn't actually interact, then the potential would not be affected and the stationary states would indeed be the single particle stationary states. If I have distinguishable particles then, I can write down my states as, for instance, psi nm of x1, x2 as, well, the product of the state for n and the state for m. Psi sub n of x1, psi sub m of x2. The ground state, for instance, and I'm going to smush this down, give myself some space. The ground state then has n and m both equal to 1. In this case, looks like my normalization overall out front, 2 over a, different normalization since I've got the product of two separately normalized functions, times sine of pi x1 over a, sine of pi x2 over a. And it has energy, if I substitute 1 for the energy of one particle and 1 for the energy of the other particle, I'm just going to get k plus k. My total energy is 2k. The first excited state, and there are two ways I can do this. I could write psi 2,1 or psi 1,2, depending on which particle I bump up from the ground state, is going to be very similar. It's going to be 2 over a sine pi x1 over a sine 2 pi x2 over a, if, for instance, I use this combination. So there are actually two distinct ways to write the first excited state. One where I put the 2 with the x1, and the other where I put the 2 with the x2. That means this first excited state, for this distinguishable particles case, is doubly degenerate. There are two allowable states with the same energy. That's what we mean when we say degeneracy. Suppose instead of distinguishable particles, I had bosons. The states that I would work with then would look very similar. If I had psi 1,1, my ground state, well, there's nothing wrong with putting two quantum mechanical particles in the same quantum state with bosons. So I'd have to make the symmetric indistinguishabilization. Sure, why not? I'll make up a word. The symmetric form of this, sine of pi x1, sine of pi x2, plus sine of pi x2, sine of pi x1, but since they're the same, that's all just going to end up adding up. So your ground state is essentially going to be unchanged from your distinguishable particle case. If your distinguishable particles are in the same quantum state, are they really all that distinguishable? So psi 1,1 is unchanged. The first excited state, however, that looks a little different. Psi 1,2, for instance. Let me actually not write it as psi 1,2. Let me write it as psi first excited. And that's going to be a symmetric under exchange version of the distinguishable particle wave function here, such that the particles are rendered indistinguishable. What it ends up looking like is root 2 over a times sine of pi x1 over a sine 2 pi x2 over a plus sine 2 pi x1 over a sine pi x2 over a. So I've moved the 2 from the term with x2 to the term with x1. And if you calculate observables with this first excited state, you'll get a different result than if you had two distinguishable particles. For instance, if I calculate the expected position of particle 1 or particle 2, I'll get the same answer, which is a requirement if the particles are going to be distinguishable. One thing to notice about this is that if I try to swap which of x1 or x2 has the 2, it doesn't work. I get the same quantum mechanical state back. So this is non-degenerate. There is only one allowed quantum mechanical state for the first excited state for bosons. Degeneracy does have consequences in the physical world. So the fact that distinguishable particles and non-distinguishable particles have different degeneracies for the first excited state means that, well, it means we're onto something. There should be some observable consequences for this prediction. The last possibility, fermions. Well, what about the ground state, psi 1, 1? The Pauli exclusion principle tells us that no two fermions can occupy the same quantum mechanical state. And in fact, if you look at our psi 1, 1 state here and try to make an antisymmetric under interchange version of it by adding on essentially another term that looks exactly like this, or more accurately, subtracting off a term that looks exactly like this, you get 0. So the ground state doesn't exist. There's no psi 1, 1 under these circumstances. Our new ground state, then, is essentially our first excited state from before, but with a minus sign. And I'll indulge in a little copy pasting here, just to save myself the writing. The only difference here is that we have a minus sign to render the two states antisymmetric under exchange, and we're combining two terms such that the resulting state is a valid state for indistinguishable particles. So our ground state again, which corresponded to our first excited state before, is also non-degenerate. There's only one allowable state here for our ground state, only one quantum mechanical state. And, well, fermions, bosons, and distinguishable particles obviously behave very differently here. Fermions and bosons differ in the sense that the ground state is different. Indistinguishable particles and distinguishable particles differ in the sense of the degeneracy of whether or not of the states. So there's a lot of interesting phenomena here, and it all boils down to this fundamental fact that quantum mechanical particles are indistinguishable. There is no difference between two electrons. Any two electrons are essentially exactly the same. They obey the same laws of physics. There is no additional information here that would allow us to keep track of which electron is which. We can make quantum mechanics validate this approach, we make quantum mechanics fail to keep track of which particle is which by making these symmetric or antisymmetric combinations of what would otherwise be distinguishable particle wave functions. And lo and behold, the distinguishable particles, bosons and fermions, all behave differently. So there's a lot going on here. To check your understanding, just to drive home the complexity of multiparticle wave functions, I'd like you to write down the normalization integral for a 3-particle wave function in 3-dimensional space. Finally, reflect on what it means for two fermions to be non-interacting if they can't occupy the same quantum mechanical state. Those two particles in a box that I did on the last slide, for a fermion they couldn't exist in the same state, but I wrote down the ground state. I wrote down the stationary states from which I was constructing those antisymmetric and symmetric combinations by stating that the particles didn't interact. So what does it mean for two things that don't interact to exclude each other from doing something? And finally, what I've been talking about in the context of the particle in a box is just the spatial wave function. We're just talking about psi of x, for instance, or in the case of two particles, psi of x1, x2. How would that change if I included spin? Particle 1 and particle 2 will now have independent spins, which you can think of as extra arguments to your wave function. So how might the inclusion of spin affect this symmetrization or anti-symmetrization? These are things to reflect on. And if you've got these down,
I think you've got the basics of multi-particle quantum mechanics soundly in your mind. Quantum mechanical systems with many particles in them are very difficult to solve in principle. Imagine trying to write down the wave function for a system of 10 to the 23rd not quite independent particles. That would be very, very complicated. And under most circumstances, the best that we can hope for is to uncover the general structure of the solution. What sort of energies are going to be allowed, for example. What we're getting into now is the basics of the quantum mechanical structure of solids, which is of course an incredibly rich subject, being, as it is, essentially the basis for all of materials science, all of semiconductor physics. One aspect of the theory of solids that we can actually do reasonably accurately, at least from a qualitative perspective, is the behavior of free electrons in conductors, and that's the topic of this lecture. Free electrons in a conductor are something that we can work with reasonably well, because if we think about a chunk of material, for instance, as being the space over which some electron, a conduction electron, is free to wander, the particles are essentially free. The electrons, however, will never be found outside the box, or outside the material. It's very unlikely for an electron to wander off into the air surrounding a chunk of conductor. Conductors just don't do that. So the particles are not found outside the box. The electrons are confined. You can probably see what I'm getting at here. We have free particles that are never going to be found outside of some rectangular region. This is starting to look like the particle in a box. So maybe we can work with that. What about a particle in a box? Well, a single particle in a box, that's easy enough to handle. But what about multiple particles in a box? What if I have a second particle here that's also wandering around on its own? Well, provided I make the very, very inaccurate yet useful assumption that these particles don't interact much, I can actually work with that. Now I'll put a star on that, sort of a footnote, asterisk, because this is not a very good assumption that the electrons in a metal don't interact. Essentially what this assumption amounts to is that, on average, particles aren't going to interact much. Two randomly chosen electrons in a metal are unlikely to have just recently collided, for example, and that, on average, the vast sea of electrons that are not free to move about this equalize the charges to the degree that any two conduction electrons are unlikely to encounter the free charges of either the nucleus, free charges of the other electrons, or free charges of other conduction electrons. Those are some pretty stiff assumptions, and they're probably not correct. But if we make those assumptions, we can actually solve this problem and figure out what the quantum mechanical structure is. That's a very useful thing to do, so we're going to go ahead and do it. The starting point, though, is a single particle in a box. The single particle in a box in 3 dimensions is something that we've talked about, and the Hamiltonian that we're working with is essentially just given by the momentum squared, the kinetic energy, h bar squared over 2m times the gradient operator in 3 dimensions. We also have to multiply by a potential, which is now going to be a function of x, y, and z, where the potential we're working with, v of x, y, and z now, is equal to, well, 0 if we're inside the box, and that's going to happen for x, y, and z in between, let's say, L sub x, L sub y, and L sub z, and 0, respectively. So if x is between 0 and Lx, y is between 0 and Ly, and z is between 0 and Lz, the particle is officially in the box, and the potential energy function is 0. We say the potential energy is infinite outside the box to enforce the particle to always be inside the box. This is essentially identical to our one-dimensional particle in a box, we just have more dimensions to work with, and the solution procedure is very similar. The Schrodinger equation we're working with is, as usual, the time-independent Schrodinger equation, h psi equals E psi, and if we make our usual separation of variables assumption that psi is given by some function of x multiplied by some function of y multiplied by some function of z, what you end up with is 3 separate, independent, one-dimensional particles in a box. Infinite square well potentials, essentially. One in the x direction, one in the y direction, and one in the z direction. The overall energy of your combination after you've done separation of variables is given by essentially the energy contributed by the x, and the energy contributed by the y, and the energy contributed by the z, independent, one-dimensional particles in a box. The wave functions that you get, psi of x, y, and z, are products then of three one-dimensional particles in a box. The normalization you get is 8 divided by Lx, Ly, Lz in a square root sign, and then you have your sine functions as usual for the 1D particle in a box. Sine of nx pi x over Lx, where the quantum number that you get as a result of the boundary conditions, I'm calling nx for the x part, ny for the y part, and nz for the z part. Ny pi y over Ly, sine of nz pi z over Lz. That's your wave function for a single particle in a three-dimensional box. The general solution you get in separation of variables, as usual, has sine and cosine terms in it, but the boundary conditions not only fix our quantization, give us quantum numbers nx, ny, and nz, but also eliminate the cosine terms, just because the wave function must go to 0 at points where the potential diverges to infinity. The quantization also sets the allowed energies of the system, and the energy of this state is given by h bar squared pi squared over 2m, and then we have a combination involving these quantum numbers, nx squared over Lx squared plus ny squared over Ly squared plus nz squared over Lz squared. Now this looks like a sum of three things squared, and it's useful to make this look more like the magnitude of a vector in 3 dimensions. Essentially, I'm going to define a vector, or a scalar quantity, for instance, k squared, a k vector, such that this overall energy here is equal to h bar squared k squared over 2m, looking like the kinetic energy of a particle with wave vector k being essentially 2 pi divided by the wavelength. The k vector that we're working with then is, for instance, given by kx is equal to pi nx over Lx. Likewise, for ky equals pi ny over Ly, and kz is equal to pi nz over Lz, where the overall k squared is kx squared plus ky squared plus kz squared. If I make these definitions, the overall energy now starts to look like the squared magnitude of a vector in a three-dimensional space with three separate components, kx, ky, and kz. And this k-space, three-dimensional space, is the space that you want to think about in terms of the quantum mechanical structure of many particles in a 3D box, which is, of course, where we're going with this. So what happens when we have many particles in a box? Well, we know we're working with fermions here, and fermions obey the Pauli exclusion principle, which means we're not going to be able to put more than 2 fermions in exactly the same quantum state. So if I'm trying to occupy many states here, I'm going to need many states to be, well, I'm going to need to understand the structure of many states. So thinking about this in terms of the three-dimensional k vectors, say this is my kx direction, this is my ky direction, and this is my kz direction. The overall allowed values that I had for my energy were given by specific integers, essentially dividing these k axes up into specific points. Kx was defined by pi nx over Lx, for instance. So nx being 1, 2, 3, etc., like for our one-dimensional particle in a box, I essentially have a set of ticks along my x-axis here, my kx axis, that tell me what the allowed values of kx are. Likewise, I have a set of allowed values for ky, and a set of allowed values for kz. And it's going to be hard for me to draw this out in 3 dimensions, but if you think about the allowed values, where these things all intersect, when I have an allowed value of kx, an allowed value of ky, and an allowed value of kz, I have an intersection point there. That means I have an allowed quantum state here for nx is 1, ny is 1, and nz is 1. I, of course, also have an allowed quantum state out here, where nx is 2, ny is 1, and nz is 1. And I'm not doing a very good job drawing this, but you can see each intersection point here is associated with some cube between the intersection and the origin. And that cube signifies a certain volume. And the volumes in K-space are something that's very useful to think about. So this point now here would represent ky is 2, kz is 1, kx is 1. Each of these points is associated with a cube. And the volume of this cube, which is going to become important when we start talking about trying to fill as many of these states as possible, is given by, well, the length of each of these sides. I'm talking about the volume in K-space now. This, of course, being associated with nx equals 1, this is pi divided by Lx, is the length of this side in K-space. Likewise, this is going to be pi over Lz. The y, of course, is going to be pi divided by Ly. So if I wanted to know the volume of one of these cubes in K-space, it would be... You saw in the last lecture how just considering the electrons in a conductor to be free particles in a box, you could get a reasonable impression of the quantum mechanical behavior of those electrons, what the allowed energies look like, what the behavior of the metal was even, to some degree. We were able to calculate, for instance, the degeneracy pressure of the electrons in that state, and get an answer that was comparable to the measurable physical properties like the bulk modulus of the material. That free particle assumption seems very fishy, though, because those conduction electrons are going to interact with the atoms in some way. So what I'd like to talk about in this lecture is how we can include the atoms and the results, in particular the band structure of energy levels in solids. Including the atoms in the behavior of the free electrons in a material, for instance, is a rather complicated process. You might think about an electron coming in towards some atom, where we have electrons orbiting the nucleus of the atom, and how these particles might interact. Now, we know from quantum mechanics that this picture is just plain not correct, that we need to consider the electron as it approaches the atom as some sort of a wave packet. So I'll draw some wave fronts. And the atom itself as being composed of a nucleus, which has almost negligible wave nature compared to the wave nature of the electron, since the nucleus is so much heavier, surrounded by some cloud of electron. Describing the interaction of a wave packet like this and an atom with an electron cloud surrounding it is a very complicated process in principle. But whatever the interaction is, it's going to be encoded by some Hamiltonian, h hat, which is going to include the kinetic energies of the particles and then some potential that tells you how the energy of this interaction takes place. If the electron were very close to the atom, would there be an attractive force? Would there be a repulsive force? Would there be an increase in energy or a decrease of energy? Now, typically you can assume that the potentials like this are related just to the relative displacement between the atom and the electron, so some difference between the position of the electron and the position of the atom. Perhaps the potential even only depends on the absolute magnitude of that vector, only depending on the distance between the electron and the atom. Either way, these potentials can come in a variety of forms. But if you're trying to consider a material with many electrons and many atoms, what you're going to have to work with is actually going to be a sum over all the atoms of the material of the contribution of each atom to the energy of an electron. If we have multiple electrons, we'll have to have lots of different kinetic energy terms, and we'll have to have a sum over electrons here as well. So this is a very complicated Hamiltonian. We can't really hope to solve it analytically. We can, however, make some analytical progress if we make some simplifications. And I'm going to make 3 simplifications for this lecture. First of all, this potential, which is in principle a function of the distance between the electron, the position of the electron and the position of the atom, I'm going to pretend it only depends on the magnitude of the distance, and I'm going to make a very crude approximation to this potential, namely that if the electron is right on top of the atom, it experiences a very strong repulsive force. If the electron is displaced from the atom significantly, the atom overall looks neutral, and there is no energy associated with that reaction. The approximation I'm actually going to make then is that the potential contribution of a single atom
to an electron is given by a Dirac delta function. Some proportionality constant describing the strength of the delta function times the delta function itself as the distance between the electron and the atom. So this is the potential that we're going to work with. This is just for an interaction between a single electron and a single atom, however, and we're going to have to consider multiple atoms. And in order to make any mathematical progress, we're going to have to know the positions of all the atoms. In any realistic material, the atoms will be more or less randomly distributed, though there may be some overall structure dictated by the structure of the bonds between those atoms. I'm going to assume a very, very simple structure here. I'm going to assume that we're working with a crystal. So we're working with a regular array of atoms, for example. Furthermore, I don't really want to mess with trying to express this regular array of atoms in 3 dimensions. So I'm going to assume that we're only working with a one-dimensional system. Essentially a one-dimensional crystal, just looking at a slice through a potential 3-dimensional crystal. This is not the most relevant physical scenario, since a Dirac delta function in 1 dimension extrapolated to 3 dimensions is sort of a sheet delta function, not an array of point delta functions like a crystal. So this is not the most realistic scenario, but it does actually reproduce a lot of the observed behavior of, well, real electrons in real crystals. The potential we're talking about here, then, is going to be a one-dimensional array of delta functions. So our v of x is going to look something like this. It's going to be 0 whenever you're not on top of an atom, and it's going to spike up whenever you are on top of an atom. And this is going to continue, potentially infinitely, in both directions. This is called a Dirac comb, since I guess it kind of looks like a comb, and it's made of Dirac delta functions. So this is the potential we're going to work with. The nice feature of this potential is that if these atoms are, say, spaced by some distance a, this is a periodic potential, and there are theorems that help us deal with periodic potentials. One of these theorems is called Bloch's theorem, and what it states is that for a potential that's periodic, namely the potential evaluated at some displacement a from the current position is just equal to the potential at the current position, the solutions to the time-independent Schrodinger equation for that potential can be written as follows. Psi of x plus a, displacing the argument of psi, is essentially the psi at the current location multiplied by some complex constant with magnitude 1, e to the I k a, for some unknown constant k. Essentially what this means is that the observables don't change. You know, multiplying the wave function by some complex number isn't going to, some complex phase, e to the I k a, isn't going to change the answer. Well, essentially what this means is that for a completely periodic potential, the observables aren't going to change from one period to the next, and that's more or less a requirement. Periodic potentials should have periodic solutions to the Schrodinger equation. We don't know anything necessarily about this constant k, but essentially what we're talking about, if we apply this to our delta function potential, or our Dirac comb potential, is atoms spaced apart by some distance a, and Bloch's theorem tells us that the wave function here gives us the wave function here, gives us the wave function here, gives us the wave function here. So we don't need to worry about the entire space. We can only worry about a sub-portion of the space. This is very useful. One unfortunate consequence of Bloch's theorem is that it only works for completely periodic potentials. So if we're talking about a material, a chunk of silicon, say, there are edges. In the inside here, we definitely have a periodic potential. We have a silicon crystal, we have an array of atoms, that's fine. We're working with something periodic. But at the edges, we're going to have problems. Since at the edges, well, the periodicity obviously breaks down. Under these circumstances, then, Bloch's theorem isn't going to apply. So we need to find out some approximation, some simplification, or at least some plausibility argument for how we can still apply Bloch's theorem to these cases. Well, we've already made a lot of simplifying assumptions, so what's one more? Our potential v of x is this Dirac-Combe structure that potentially continues to infinity. If we're working with a realistic material, we're going to have something like 10 to the 23 atoms here. As such, the contribution of the atoms you would expect, if you had a free electron here, it's going to be much, much, much more sensitive to the atoms nearby than to the boundaries of the material. As such, you wouldn't expect the edge effects to be terribly significant. So, one way to fix Bloch's theorem, if we're willing to ignore the edge effects and deal just with electrons near the interior of the material, is to take our delta function potential and wrap it around. Essentially treat this edge of the material as connected somehow through a wormhole to this edge of the material, wrapping the material around in a circle, for instance, working with a donut of material instead of a block of material. What this periodicity means, that we're assuming the potential is periodic overall, not just periodic from one atom to the next, is that our wave function psi of n times a, essentially the wave function on the right edge of our material, has to be equal to the wave function on our left edge of the material. And let me rewrite this. I have my wave function as a function of x, and if I add n times a, where I have n atoms from one side of the material to the other side of the material, times the separation of the atoms, I've essentially wrapped all the way around and gotten back where I started. That has to give me my original wave function back. So that's my periodicity. And under these circumstances, Bloch's theorem, which tells me how to displace my wave function by a certain amount, tells me what I need to know. Bloch's theorem gives us that psi of x plus na is going to be equal to e to the I capital N capital Ka times my original wave function, psi of x. My periodicity then means this is going to be equal to psi of x, which I can just cancel out then from this periodicity equation, giving me e to the I n capital Ka equals 1. That tells me that this capital K constant I have can only take on specific values. And those specific values are given by what will make the exponential 1, essentially 2 pi times an integer divided by capital N-A. The argument here has to be 2 pi times an integer, and this is then the value of k that's going to give you 2 pi times an integer when you multiply it by n times a, essentially. So n now is going to be some integer, either 0, plus or minus 1, plus or minus 2, etc. Knowing something about this constant tells us how the wave function in one region relates to the wave function in the next region, and we have a variety of allowed values for this overall constant. So we have now what we need to solve the time-independent Schrodinger equation. The potential we're working with, and I'll just draw a chunk of it here, just with, say, 2 spikes. Let's say this is the spike at x equals 0, and this is the spike at x equals a. I'll add another spike here on the left at x equals minus a. We need to go through our usual machinery for solving the time-independent Schrodinger equation. We have our potential, and in regions, say, there, the potential v of x is equal to 0, which means our time-independent Schrodinger equation is just going to be the free particle equation, minus h bar squared over 2m times the second derivative of psi with respect to x is equal to e times psi. You know what the solution to this is. We've done the free particle case many, many times. Our general solution is that psi of x is equal to a times sine kx plus b cosine kx, where k squared is equal to 2me over h bar squared. This should all look familiar. It's solving a second-order differential equation, essentially the simplest second-order differential equation you can think of. The subtlety with solving the Schrodinger equation under these circumstances is that the general solution in one sub-region isn't enough. We have to find the solution in all regions, which means we're going to have to match boundary conditions.
So it's also useful to know then what the solution is at some other region so that I can match those two solutions together across the delta function. Bloch's theorem tells us that the solution in this region is going to be the solution in this region multiplied by some e to the ikx, e to the ika, excuse me. Since we're not shifting to the right, we're shifting to the left, it's actually e to the minus ika, but our solution in this region, psi of x, is equal to e to the minus I capital K A times our solution in this region, a sine k x, x plus a plus b cosine x plus a. So I'm writing now this x is referring to negative values, so I have to shift it over to make it correspond to the values in the other region, and I multiply by this overall constant to make sure everything matches up. So we have our solutions now in this region and in this region, and these are general solutions. We have this capital K in here, which we know a little bit about from the overall periodicity, but we also have this unknown K constant, which is given in terms of the energy. Now, typically, the solutions to the Schrodinger equation matching boundary conditions tells us something about the allowed energies, and that's going to be the case here as well. But these are our two general solutions, and let's figure out how boundary condition matching at this boundary works, since that's going to tell us something about the energy, something about these A's and B's, and so how that information all connects to these capital K's. So the boundary conditions we have are going to match these two solutions together. We have two boundary conditions, and just to recap, we have our delta function potential, x equals 0, and we have our solution in this region and our solution in this region, and we're matching them across the delta function at x equals 0. So the two boundary conditions we have for the wave function. First of all, the wave function has to be continuous. What that means is that psi of 0 plus has to be equal to psi of 0 minus. The solution just on this side has to be equal to the solution just on this side of our boundary. And if I plug these in, the solution for 0 plus, substituting 0 in for x, the sine term is going to drop out, since sine of 0 is 0, and the cosine term is going to go to 1, since the cosine of 0 is 1. So the b is all I'm going to get. That's all that's left here. This term's dropped out. This term is just equal to b. So my equation then is b is equal to whatever I get when I plug 0 in for the solution on this side. So substituting in 0 for x, the x's are going to drop out, and I'm just going to get cosine ka and sine ka, and my a and b, and my e to the minus I ka. E to the minus I capital Ka times a sine lowercase ka plus b cosine lowercase ka. So that's our continuity boundary condition. The other boundary condition that we have to work with is that typically the first derivative of the wave function is continuous. The exception to that typical boundary condition is when the potential goes to infinity, you can have a discontinuity in the first derivative. And the only case that we know of that we can solve so far in this course is the delta function potential. We talked about this when we were doing bound states for the delta function. So if you're fuzzy on how this actually works, I suggest you go back and refer to the lecture on bound state solutions to the delta function potential. Otherwise, the equation we need to tell us how d psi dx is discontinuous relates the size of the discontinuity to the strength of the delta function potential. The equation, and this is equation 2.125 in your textbook, is that the delta of d psi dx is equal to 2m alpha over h bar squared psi. So we need to calculate the first derivative of the wave function from the left and from the right, subtract those two, and that's then going to be related to the value of the wave function and these constants, where alpha here is the same constant that we used to describe the strength of the delta function potential when we first introduced the structure of the potential. So if you actually go through, calculate the derivative of this with respect to x, the derivative of this with respect to x, what you end up with is, well, the derivative for this, we're then evaluating our derivatives at x equals 0, and a lot of the terms drop out. The derivative of this term from the plus direction at x equals 0 is k times a.
This is a lowercase k now. The derivative from the left, derivative of this potential with respect to x, evaluated at x equals 0, is e to the minus I capital Ka times a lowercase k from the derivative, and then capital A cosine Ka minus capital B sine Ka. That's the left-hand side of our discontinuity equation here. Discontinuity in the first derivative then being equal to 2m alpha over h bar squared, and the value of psi at 0, well, I could use either the left-hand side of this equation or the right-hand side of this equation, but, well, left-hand side here is much simpler, so I'm just going to use capital B for the value of my equation. Now we have two equations, and we have a lot of unknowns to work with. We have capital A, capital B, capital K, and lowercase k. But it turns out we can come up with a useful relationship just by manipulating these equations to eliminate capital A and capital B. Essentially, what you want to do is you want to solve this equation for A sine Ka. Multiply this equation through by sine Ka so that we have an A sine Ka here and an A sine Ka here, and then use the result of solving this equation to eliminate capital A. So making that substitution, we're going to have a capital B from this equation. So you'll have a capital B in this term, capital B in this term, and then capital B in this term, as before, which means you can divide out your capital B's. So you've successfully eliminated both capital A and capital B from your equation. The subtle term, as far as simplification goes, is trying to get rid of this e to the minus I capital Ka. But if you make the appropriate simplifications, you can reduce this down not to completely eliminate capital K, but to at least get rid of the complex form of the exponential. You end up with a cosine e to the I capital Ka when you finish solving this. So, subject to a lot of algebra that I'm skipping, the end result here that we can actually work with can be expressed as cosine capital Ka is equal to cosine lowercase ka plus m alpha over h bar squared lowercase k sine lowercase ka. So this is an equation that relates lowercase k, which is related to our energy, to uppercase K, which is what we got out of Bloch's theorem, and the strength of the delta function, the mass of the particle. This is then going to tell us essentially the allowed energies. There were very few restrictions on the value of this capital K. That was just related to some integer. The equation then, just copying it over from the last page, can be expressed, well, this is just the previous equation. Capital K is related to some integer n, and lowercase k is related to the energy. So if I look at the left-hand side here, what do I actually have to work with? Well, my capital K, think about the set of allowed values for capital K. Cap K, just being related to an integer, which can be positive or negative, is going to have a lot of allowed values. Keep in mind now that capital N here is something of order 10 to the 23, so we have a very large number in the denominator, and we have potentially relatively smaller numbers in the numerator, so capital K is going to have very densely spaced allowed values, going, over the allowable values of n, which are essentially the integers, up to some very large number. So my allowed space of capital K values are densely packed, negative and positive. Keep in mind, however, that my capital K's are being substituted into a cosine. So no matter what I use for capital K, it gets multiplied by A. I'm going to have something between 0, or between minus 1 and 1 for the outcome here. The right-hand side of this equation depends on lowercase k, which depends on the energy. So you can think of lowercase k here as being essentially the energy of the state. So we have something that depends on the energy, and it looks like cosine of something related to the energy plus some constant times sine of something related to the energy divided by something related to the energy. You can simplify these a little bit. In particular, I'm going to redefine the variable z equal to lowercase k times a.
which means this is going to be cosine z plus some constant times sine z over z. So I'm going to define beta being equal to, where'd it go? It's going to be m alpha a over h bar squared, leaving me with a ka in the denominator. So my right-hand side now, which is what I'm plotting here, is going to be cosine z plus beta sine z over z. So if I plot my right-hand side for a particular value, in this case I'm using beta equals 10, beta just being a combination of the strength of the delta function, spacing of the potentials, mass of the particle, and Planck's constant, you end up with a function that looks sort of like this. It looks kind of like sine x over x. Well, it does. But this z parameter is now related to the energy. So essentially we have an x-axis here that tells us the energies. And we know we can have solutions whenever it's possible to solve this. Our capital K space, densely packed with allowable values of capital K being plugged into cosine, is going to give us very densely packed values of, well, essentially the y-axis here, whatever the y-coordinate is. Since there are so many allowable values of capital K, since capital N here is a very large number, you can think of these essentially as a continuum of allowable values on the y-axis. The places where I have a solution then are going to depend on, well, the right-hand side of my equation, which is only between -1 and 1 for certain values of the energy. So these shaded regions here, where the energy of the state is such that the right-hand side of this equation corresponds to values between -1 and 1, for which we can find a nearby allowable value of cosine capital Ka, these are the allowed energies. And they come in bands. There is no single isolated value of the ground state energy. There is sort of a continuum of allowable energies, subject to these approximations that capital N is very large, for instance. So if we're dealing with a macroscopic chunk of material, the allowed energy states for a free electron that's encountering these atoms are going to come in energy bands. This is actually a really, really nice result because it allows us to understand a lot of the properties of things like conductors, insulators, and semiconductors. If, for instance, we allowed bound states to exist as well, they would have negative energies. So our free electron states are going to appear in separate bands. Our bound states are also going to appear in bands as well, and you can verify that by going through the solution process using delta function wells instead of delta function barriers. But if we have no bound or no free electrons, if we just have bound electrons, if we just have states down here, essentially, we don't have enough free electrons, don't have enough electrons, period, in this state to occupy all of our possible bound states, then we have an insulator. If we have states populated, again, same as in the previous lecture, starting with the lowest energy and populating states as you go up, you'll have an insulator until all of these bound states are filled. Once you start filling states in this first sort of energy band of free electrons, you have a conductor. It's very easy for electrons in an energy state here to shift to another energy state of slightly higher or slightly lower energy that may be slightly displaced in the conductor. So it's possible for an electron to move from one side of the conductor by moving from one of these free particle states to another. If we have all of our bound states filled and the complete conduction band, or a complete band here, also filled, well, that's going to be an insulator again, because it's impossible for electrons to move from one state to the other if all of the available states are filled. The only way for an electron to effectively become free here is for it to jump up to the next energy band across this gap. So we have gaps between our bands. And that determines whether or not we've got a conductor or an insulator. A third case that you've probably heard of is if we have, well, all of our bound states filled and almost all, or perhaps just a few states in the next energy state filled. This we would call a semiconductor.
It can act like a conductor if you have these few extra electrons filling the lowest energy states in a mostly empty band. But if you lack these few electrons, then you've gone to the insulating state. So they're states that are sort of on the boundary between entirely filled and mostly empty. And if you add a few electrons, it acts like a conductor. If you subtract a few electrons, it acts like an insulator. And this transition between conductor and insulator is something that we can arrange chemically and electrically, and this is essentially the basis of all of semiconductor physics. We'll talk in the next lecture about how semiconductor devices like diodes and transistors actually work in the context of these allowed energy bands and what sort of chemical modifications happen as a result. Another note here is that the temperature affects the energies that are allowed here. The next section in your textbook after this talks about quantum statistical mechanics, which tells you about, as a function of the temperature of the material, how these energy states are likely to be populated. The approximation that we're making here by saying start filling the energy states from the lowest energy possible and continue until you run out of free electrons isn't entirely accurate. That's essentially assuming that everything is at absolute zero, that there is no additional energy available to these materials. Now, conductors, insulators, and semiconductors behave differently in the context of temperature. Because, for instance, consider a conductor, or consider an insulator. If I have an insulator like this, or an insulator like this, if I add energy to that insulator, I'm essentially going to be contributing some additional energy to some of these electrons, which would otherwise be filling the lowest possible energy state. So I would be kicking them up to higher energy states. And if I have an insulator like this that hasn't even filled all of its bound states, well, adding energy is going to kick them up to higher energy bound states. It's unlikely to make those electrons free. But if I have a conductor that has entirely filled a sort of free electron state, and I add energy, I may kick more and more and more electrons up to the next higher energy band, transitioning that insulator into a conductor. So if I have an insulating material and I increase the temperature, the conductivity of the material tends to increase. If I have a conductor, on the other hand, and I add energy to these states, well, I'm not actually making any more free conduction electrons. I'm more just rearranging existing conduction electrons. And that rearrangement actually happens to be unfavorable under most circumstances. The classical explanation that's usually given is that as you increase the temperature of a material, the orderedness of the material goes away. Essentially, that nice periodic array of delta function potentials becomes slightly disordered, and that disrupts the band structure and makes it more difficult for electrons to transition from one energy state to the next. Thinking about it classically, the electrons are more likely to collide into atoms that are vibrating rapidly than into atoms that are nice and stationary. So if I increase the temperature of an insulator, I make it more conducting. If I increase the temperature of a conductor, I make it less conducting. If I increase the temperature of semiconductors, you can actually do some math to figure out what's going on. I'm not going to ask you to do that, but if you increase the temperature of a semiconductor, typically you increase the conductivity. So we can understand a lot of the properties of how insulators and conductors, even semiconductors, behave just with this simple periodic array of delta functions, which describes that the result are going to have the resulting energy states that are available for a bound or free electron in this material are going to come in bands. And the relative population of those bands determines essentially the nature of the material. To check your understanding of this, here are a few questions, namely asking you to recall what that trick was to figure out the boundary condition in terms of the discontinuity in the first derivative of the wave function at a delta function. Finally, describe how you suspect the solutions would change if the delta function wells had been used instead of barriers. We used barriers, assuming that if the electron was right on top of the atom, it would be strongly repelled by essentially running into the atom. But maybe it's actually attracted. Maybe there are bound states as well. Finally, going back and looking at that equation that gave you the energy bands, how do the energy bands look? What is their spacing? How wide are they, etc., as the energy becomes very large? And finally, there's this essay that's intentionally humorous, Electron Band Structure in Germanium, My Ass. I'd like you to read through that. It's fun. I'm not actually asking you to do all that much here. And then explain qualitatively what the plot that he describes should have looked like.